Hello, very good morning, friends. So today I'm going to start this book. I have read only once. Now going to revise it. I will revise all the chapters from chapter 1 to chapter 21 of this book. It's very important book. Data structure algorithm made by Narasimha Karumanchi. All those who are learning data structure algorithm in depth and full basic, you want to from basic to depth, all things will be covered in this book. So I'm going to read all the chapters in one shot in one day. Okay. So I have already gone through this book one time. Now it's time to revise it. Okay, all the chapter by reading it. So I'm going to start from chapter 1, introduction, until chapter 21, miscellaneous concept. I will go through all the chapters. Okay, so let's start it. Introductions. Okay, what I can do, I can mute myself so there will be no disturbance from my side. Okay, I will mute myself. Okay. I will off this camera also, so you can focus on the text. You can read it, listen it properly without any distraction, and I can also focus it because this camera is there. So okay, let me deactivate it. Okay, now it's time to mute myself.
The objective of this chapter is to explain the importance of the analysis of algorithms, their notations, relationships, and solving as many problems as possible. Let us first focus on understanding the basic elements of algorithms, the importance of algorithm analysis, and then slowly move toward the other topics as mentioned above. After completing this chapter, you should be able to find the complexity of any given algorithm. 1.1 Variables. Before going to the definition of variables, let us relate them to old mathematical equations. All of us have solved many mathematical equations since childhood. As an example, consider the below equation. We don't have to worry about the use of this equation. The important thing that we need to understand is that the equation has names, which hold values. That means the names are placeholders for representing data. Similarly, in computer science programming, we need something for holding data, and variables is the way to do that. 1.2 Data types. In the above-mentioned equation, the variables x and y can take any values, such as integral numbers, real numbers, or just 0 and 1. To solve the equation, we need to relate them to the kind of values they can take, and data type is the name used in computer science programming for this purpose. A data type in a programming language is a set of data with predefined values. Examples of data types are integer, floating point, unit number, character, string, etc. Computer memory is all filled with zeros and ones. If we have a problem and we want to code it, it's very difficult to provide the solution in terms of zeros and ones. To help users, programming languages and compilers provide us with data types. For example, integer takes 2 bytes, float takes 4 bytes, etc. This says that in memory we are combining 2 bytes and calling it an integer. Similarly, combining 4 bytes and calling it a float. A data type reduces the coding effort. At the top level, there are 2 types of data types. User-defined data types. System-defined data types. System-defined data types. Data types that are defined by system are called primitive data types. The primitive data types provided by many programming languages are int, float, char, double, bool, etc. The number of bits allocated for each primitive data type depends on the programming languages, the compiler, and the operating system. For the same primitive data type, different languages may use different sizes. Depending on the size of the data types, the total available values will also change. For example, int may take 2 bytes or 4 bytes. If it takes 2 bytes, then the total possible values are minus 32,768 to plus 32,767. If it takes 4 bytes, then the possible values are between minus 2,147,483,648 and plus 2,147,400 and 447,647. The same is the case or not enough, then most programming languages allow the users to define their own data types called user-defined data types. Good examples of user-defined data types are structures in C, C++, and classes in Java. For example, in the snippet below, we are combining many system-defined data types and calling the user-defined data type by the name newtype. This gives more flexibility and comfort in dealing with computer memory. 1.3 Data structures. Based on the discussion above, once we have data in variables, we need some mechanism for manipulating that data to solve problems. Data structure is a particular way of storing and organizing data in a computer so that it can be used efficiently. A data structure is a special format for organizing and storing data. General data structure types include arrays, files, linked lists, stacks, queues, trees, graphs, and so on. Depending on the organization of the elements, data structures are classified into two types. 1. Linear data structures. Elements are accessed in a sequential order, but it is not compulsory to store all elements sequentially. Examples, linked lists, stacks, and queues. 2. Non-linear data structures. Elements of this data structure are stored accessed in a non-linear order. Examples, trees and graphs. 1.4 Abstract data types. Before defining abstract data types, let us consider the different view of system-defined data types. We all know that by default, all primitive data types support basic operations such as addition and subtraction. The system provides the implementations for the primitive data types. For user-defined data types, we also need to define operations. The implementation for these operations can be done when we want to actually use them. That means, in general, user-defined data types are defined along with their operations. To simplify the process of solving problems, we combine the data structures with their operations, and we call this abstract data types. An ADT consists of two parts. 1. Declaration of data. 2. Declaration of operations. Commonly used ADTs include linked lists, stacks, queues, priority queues, binary trees, dictionaries, disjoint sets, hash tables, graphs, and many others. For example, stack uses LIFO mechanism while storing the data in data structures. The last element inserted into the stack is the first element that gets deleted. Common operations of it are creating the stack, pushing an element onto the stack, popping an element from stack, finding the current top of the stack, finding number of elements in the stack, etc. While defining the ADs, do not worry about the implementation details. They come into the picture only when we want to use them. Different kinds of ADs are suited to different kinds of applications, and some are highly specialized to specific tasks. By the end of this book, we will go through many of them, and you will be in a position to relate the data structures to the kind of problems they solve. 1.5. What is an algorithm? Let us consider the problem of preparing an omelet. To prepare an omelet, we follow the steps given below. 1. Get the frying pan. 2. Get the oil. A. Do we have oil? I. If yes, put it in the pan. 2. If no, do we want to buy oil? 1. If yes, then go out and buy. 2. If no, we can terminate. 3. Turn on the stove, etc. What we are doing is, for a given problem, we are providing a step-by-step procedure for solving it. The formal definition of an algorithm can be stated as: an algorithm is the step-by-step, unambiguous instructions to solve a given problem. In the traditional study of algorithms, there are two main criteria for judging the merits of algorithms: correctness and efficiency does it take to execute the. Note, we do not have to prove each step of the algorithm. 1.6. Why the analysis of algorithms? To go from city A to city B, there can be many ways of accomplishing this: by flight, by bus, by train, and also by bicycle. Depending on the availability and convenience, we choose the one that suits us. Similarly, in computer science, multiple algorithms are available for solving the same problem. Algorithm analysis helps us to determine which algorithm is most efficient in terms of time and space consumed. 1.7 Goal of the analysis of algorithms. The goal of the analysis of algorithms is to compare algorithms mainly in terms of running time, but also in terms of other factors. 1.8. What is running time analysis? It is the process of determining how processing time increases as the size of the problem increases. Input size is the number of elements in the input, and depending on the problem type, the input may be of different types. The following are the common types of inputs: size of an array, polynomial degree, number of elements in a matrix, number of bits in the binary representation of the input, vertices and edges in a graph. 1.9 How to compare algorithms. To compare algorithms, let us define a few objective measures. Execution times. Not a good measure, as execution times are specific to a particular computer. Number of statements executed. Not a good measure, since the number of statements varies with the programming language as well as the style of the individual programmer. Ideal solution. Let us assume that we express the running time of a given algorithm as a function of the input size n, and compare these different functions corresponding to running times. This kind of comparison is independent of machine time, programming style, etc. 1.10. What is rate of growth? The rate at which the running time increases as a function of input is called rate of growth. Let us assume that you go to a shop to buy a car and a bicycle. If your friend sees you there and asks what you're buying, then in general you say buying a car. This is because the cost of the car is high compared to the cost of the bicycle. For the above-mentioned example, we can represent the cost of the car and the cost of the bicycle in terms of function. And for a given function, ignore the low-order terms that are relatively insignificant. As an example, in the case below, n2, n100, and 500 are the individual costs of some function and approximate to n, since n is the highest rate of growth. 1.11 Commonly used rates of growth. The diagram below shows the relationship between different rates of growth. Below is the list of growth rates you will come across in the following chapters. 1.12 Types of analysis. To analyze the given algorithm, we need to know with which inputs the algorithm takes less time and with which inputs the algorithm takes a long time. We have already seen that an algorithm can be represented in the form of an expression. That means we represent the algorithm with multiple expressions, one for the case where it takes less time and another for the case where it takes more time. In general, the first case is called the best case, and the second case is called the worst case for the algorithm. To analyze an algorithm, we need some kind of syntax, and that forms the base for asymptotic analysis notation. There are three types of analysis. Worst case defines the input for which the algorithm takes a long time. Input is the one for which the algorithm runs the slowest. Best case defines the input for which the algorithm takes the least time. Input is the one for which the algorithm runs the fastest. Average case provides a prediction about the running time of the algorithm. Run the algorithm many times using many different inputs that come from some distribution that generates these inputs, compute the total running time, and divide by the number of trials. Assumes that the input is random. Lower bound less than equal to average time less than equal to upper bound. For a given algorithm, we can represent the best, worst, and average cases in the form of expressions. As an example, let f be the function which represents the given algorithm. Similarly, for the average case, the expression defines the inputs with which the algorithm takes the average running time. 1.13 Asymptotic notation. Having the expressions for the best, average, and worst cases, for all three cases, we need to identify the upper and lower bounds. To represent these upper and lower bounds, we need some kind of syntax, and that is the subject of the following discussion. Let us assume that the given algorithm is represented in the form of function f. 1.14 Big O notation. This notation gives the tight upper bound of the given function. Generally, it is represented as f equal to O. That means, at larger values of n, the upper bound of f is g. For example, if f equal to n plus 100n plus 10n plus 50 is the given algorithm, then n is g. That means g gives the maximum rate of growth for f at larger values of n. Let us see the O notation with a little more detail. O notation defined as O equal to. G is an asymptotic tight upper bound for f. Our objective is to give the smallest rate of growth g, which is greater than or equal to the given algorithm's rate of growth slash. Generally, we discard lower values of n. That means the rate of growth at lower values of n is not important. In the figure, n is the point from which we need to consider the rate of growth for a given algorithm. Below n, the rate of growth could be different. N is called threshold for the given function. Big O visualization. O is the set of functions with smaller or the same order of growth as g. For example, O includes O, etc. Note, analyze the algorithms at larger values of n only. What this means is, below n, we do not care about the rate of growth. Big O examples. Example 1, find upper bound for f equal to 3n 8. Solution, 3n plus 8 less than or equal to 4n. For all n greater than or equal to 8, 3n plus 8 equal to O with c equal to 4 and n equal to 8. Example 2, find upper bound for f equal to n plus 1. Solution, n plus 1 less than or equal to 2, n for all n greater than or equal to 1. Example 3, find upper bound for f equal to n plus 100 n plus 50. Solution, n plus 100 n plus 50% less than or equal to 2n for all n greater than or equal to 11. Example 4, find upper bound for f2n to 2n. Solution, 2n to 2n less than or equal to 2n for all n greater than 1. Example 5, find upper bound for f equal to n. Solution, n less than or equal to n for all n greater than or equal to 1. Example 6, find upper bound for f equal to 410. Solution, 410 less than or equal to 410 for all n greater than 1. 410 equal to O with c equal to 1 and n equal to 1. No uniqueness. There is no unique set of values for n and c improving the asymptotic bounds. Let us consider 100n plus 5 equal to O. For this function, there are multiple n and c values possible. Solution, 100n plus 5 less than or equal to 100n plus n equal to 100 and 1n less than or equal to 101n for all n greater than or equal to 5, n equal to 5, and c equal to 101 is a solution. Solution, 100n plus 5 less than or equal to 100n plus 5n equal to 105n less than or equal to 105n for all n greater than 1, n equal to 1, and c equal to 105 equal to 105n notation. Similar to the O discussion, this notation gives the tighter lower bound of the given algorithm, and we represent it as f equal to ohm. That means, at larger values of n, the tighter lower bound of f is g. For example, if f equal to 100n plus 10n plus 50, g is ohm. The ohm notation can be defined as ohm equal to. G is an asymptotic tight lower bound for f. Our objective is to give the largest rate of growth g, which is less than or equal to the given algorithm's rate of growth f. Ohm examples. Example 1, find lower bound for f equal to 5n. Solution, c, n such that 0 less than or equal to cn less than or equal to 5n cn less than or equal to 5n c equal to 5 and n equal to 1. Example 2, prove f equal to 100n plus 5 not equal to ohm. Solution, c, n such that 0 less than or equal to cn less than or equal to 100n plus 5. 100n plus 5 less than or equal to 100n plus 5n equal to 105n. Cn less than or equal to 105 and n less than or equal to 105n, or tau 0. Contradiction. Contradiction n less than or equal to c. 1 smell when 1/6 theta theta notation. This notation decides whether the upper and lower bounds of a given function are the same. Is always between the lower bound and the upper bound. If the upper bound and lower bound give the same result, then the theta notation will also have the same rate of growth. As an example, let us assume that f equal to 10n plus n is the expression. Then, its tight upper bound g is O. The rate of growth in the best case is g equal to O. In this case, the rates of growth in the best case and worst case are the same. As a result, the average case will also be the same. For a given function, if the rates of growth for O and ohm are not the same, then the rate of growth for the theta case may not be the same. In this case, we need to consider all possible time complexities and take the average of those. Now consider the definition of theta notation. It is defined as theta equal to. G is an asymptotic tight bound for f. Theta is the set of functions with the same order of growth as g. Theta examples. Example 1, find r bound for f n2n equal to 2, 2. n2 n2 n solution, n2 for all, n greater than or equal to 5, 2, 2, n equal to O with c1 equal to 1/5, c2 equal to 1, and po equal to 2, 2. Example 2, prove n plus O. Solution, c1n, 2 less than or equal to n less than or equal to c2n2 equal to only holds for n less than or equal to 1, c1, c1. Z, example 3, prove 6 and 3. Solution, C1 and 2 less than or equal to 6 and 3 less than or equal to C2 n, 2 equal to only holds 4 and less than or equal to C2/6. Example 4, prove n plus O. N solution, C1 ln less than or equal to n less than or equal to C2 ln C2 greater than or equal to ln Vn greater than or equal to no impossible. 1.17 important notes. For analysis, we try to give the upper bound and lower bound and average running time. From the above examples, it should also be clear that, for a given function, getting the upper bound and lower bound and average running time may not always be possible. For example, if we are discussing the best case of an algorithm, we try to give the upper bound and lower bound and average running time. In the remaining chapters, we generally focus on the upper bound because knowing the lower bound of an algorithm is of no practical importance, and we use the notation if the upper bound and lower bound are the same. 1.18. Why is it called asymptotic analysis? From the discussion above, we can easily understand that in every case for a given function f, we are trying to find another function g, which approximates f at higher values of n. That means g is also a curve which approximates f at higher values of n. In mathematics, we call such a curve an asymptotic curve. In other terms, g is the asymptotic curve for f. For this reason, we call algorithm analysis asymptotic analysis. 1.19 Guidelines for asymptotic analysis. There are some general rules to help us determine the running time of an algorithm. 1. Loops. The running time of a loop is, at most, the running time of the statements inside the loop multiplied by the number of iterations. Executes n times for m equal to m plus 2. Constant time, c. Total time a constant cxn equal to cn equal to o. 2. Nested loops, analyzed from the inside out. Total running time is the end product of the sizes of all the loops. Outer loop executed n times for. Inner loop executes n times for k plus 1. Constant time. Total time equal to cxnxn equal to cn2 equal to o. 3. Consecutive statements. Add the time complexities of each statement. X equal to x plus 1. Constant time. Executes n times for mm plus 2. Constant time. Outer loop executes n times for. Inner loop executed n times for kk plus 1. Constant time. Total time equal to c plus c 1n plus c2 n2 equal to o. 4. If then else statements. Worst case running time, the test, plus either the then part or the else part. Test, constant if equal to 0, return false, then part, constant else part, n4, n plus plus, another if constant plus constant if equals, constant return false. Total time, co, plus c, 1 plus n equal to o. 5. Logarithmic complexity. An algorithm is o if it takes a constant time to cut the problem size by a fraction. As an example, let us consider the following program. For 1 equal to 1 times 2. If we observe carefully, the value of I is doubling every time. Initially, I equal to 1, in next step I equal to 2, and in subsequent steps I equal to 4, 8, and so on. Let us assume that the loop is executing some k times. At kth step 2 k equal to n, and at th step we come out of the loop. Taking logarithm on both sides gives total time equal to o, if we assume base minus 2. Note, similarly, for the case below, the worst case rate of growth is o. The same discussion holds good for the decreasing sequence as well, for I/2. Another example, binary search. Look at the center point in the dictionary. Is the word towards the left or right of center? Repeat the process with the left or right part of the dictionary until the word is found. 1.20 Simplifying properties of asymptotic notations. Transitivity, f equal to and g equal to copyright, equal to f equal to copyright, valid for O and as well. Reflexivity, f equal to, valid for O and second quarter. Symmetry, f equal to if and only if g equal to. Transpose symmetry, f equal to O, if and only if g equal to q. If f is an O for any constant k greater than 0, then f is an O. If phi is an O and f2 is an O, then is an O. If phi is an O and f2 is an O, then phi f2 is an OG1. 1.21 Commonly used logarithms and summations. Logarithms. Log xy equal to I log x. Arithmetic series. Geometric series. Harmonic series. Other important formulae. 1.2 Master theorem for divide and conquer recurrences. All divide and conquer algorithms divide the problem into subproblems, each of which is part of the original problem, and then perform some additional work to compute the final answer. As an example, a merge sort algorithm operates on 2 subproblems, each of which is half the size of the original, and then performs O additional work for merging. This gives the running time equation. The following theorem can be used to determine the running time of divide and conquer algorithms. For a given program, first we try to find the recurrence relation for the problem. If the recurrence is of the below form, then we can directly give the answer without fully solving it. If the recurrence is of the form t equal to at to the power of plus o, where a greater than or equal to 1, b greater than 1, k greater than or equal to 0, and p is a real number, then if a bk, then t equal to 1. 2, if a equal to bk. 3, if a bk, b, if p less than 0, then t equal to o. 1.23 Divide and conquer master theorem, problems and solutions. For each of the following recurrences, give an expression for the runtime t if the recurrence can be solved with the master theorem. Otherwise, indicate that the master theorem does not apply. Equal to problem 1 t3 trillions plus n2. Problem 2 t4 trillions plus n2. Solution t equal to 4 trillions plus n2 equal to t equal to. Problem minus 3 trillions equal to t plus n2. Solution t equal to t plus n2 equal to greater than. Problem minus 4 t equal to 2 t plus n. Solution t equal to 2 t plus n equal to does not apply. Problem minus 5 trillions equal to 16 trillions plus n. Problem minus 6 t equal to 2 t plus non. Solution t equal to 2 trillions plus non equal to t equal to o. Problem minus 7 trillions equal to 2 trillions plus n ln. Solution t equal to 2 trillions plus n ln equal to t equal to o. Problem minus 8 trillions 2 trillions plus n. Solution t equal to 2 trillions plus no 51 equal to t equal to problem minus 9. T equal to 0.5 t plus 1 n. Solution t equal to 0.5 t plus 1 n equal to does not apply. Problem minus 10 trillions 6 trillions plus n2 ln. Solution t equal to 6 trillions plus n2 ln equal to t equal to o. Problem minus 11 trillions equal to 64 trillions nilon. Solution t equal to 64 trillions n2 ln equal to does not apply. Equal to problem 12 t 7 trillions plus n2. Solution t equal to 7 trillions plus n2 equal to t equal to. Equal to problem 13 t 4 trillions plus ln. Solution t equal to 4 trillions plus ln equal to t equal to o. Problem minus 14. T equal to 16 trillions plus n. Solution, t equal to 16 trillions plus n equal to t equal to. Problem minus 19 trillions equal to 3 trillions plus ln solution. T equal to 3 trillions plus ln equal to t equal to O. Problem minus 15 trillions equal to 2 trillions plus ln solution. T equal to 2 trillions plus ln equal to t equal to. Problem 16t equal to 3 trillions plus n. Solution, t equal to 3 trillions plus n equal to t equal to copyright. Problem 17t equal to 3 trillions plus n solution. T equal to 3 trillions plus n equal to t equal to O. Problem minus 18 trillions equal to 4 trillions plus cn solution. T equal to 4 trillions plus cn equal to t equal to O. Problem minus 20 trillions 3 trillions plus equal to plus n slash 2 solution. T equal to 3 trillions plus n slash 2 equal to t equal to O. 1.2. Four-master theorem for subtract and conquer recurrences. Let t be a function defined on positive n and having the property. For some constants c, a greater than 0, b greater than or equal to 0, k greater than or equal to 0, and function f, if f is in O then. 1.25 variant of subtraction and conquer master theorem. The solution to the equation t equal to t plus t n plus ssn, where 0a less than 1% and ss greater than 0 are constants, is O. 1.26 method of guessing and confirming. Now let us discuss a method which can be used to solve any recurrence. The basic idea behind this method is guess the answer and then prove it correct by induction. In other words, it addresses the question, what if the given recurrence doesn't seem to match with any of these methods? If we guess a solution and then try to verify our guess inductively, usually either the proof will succeed or the proof will fail. As an example, consider the recurrence t equal to nt plus n. This doesn't fit into the form required by the master theorems. Carefully observing the recurrence gives us the impression that it is similar to the divide and conquer method. As we can see, the size of the subproblems at the first level of recursion is n. So let us guess that t equal to O and then try to prove that our guess is correct. Let's start by trying to prove an upper bound t ln. 1. The last inequality assumes only that 1 less than or equal to c ln. This is correct if n is sufficiently large and for any constant c, no matter how small. From the above proof, we can see that our guess is correct for the upper bound. Now, let us prove the lower bound for this recurrence. 1. 2. The last inequality assumes only that 1 greater than or equal to k ln. This is incorrect if n is sufficiently large and for any constant k. From the above proof, we can see that our guess is incorrect for the lower bound. From the above discussion, we understood that O is too big. How about O? The lower bound is easy to prove directly. Now, let us prove the upper bound for this O. From the above induction, we understood that O is too small and O is too big. So, we need something bigger than n and smaller than ln. How about n ln? Proving the upper bound for n ln. Proving the lower bound for n ln. The last step doesn't work, so O doesn't work. What else is between n and ln? How about nog ln? Proving upper bound for nog ln. Proving lower bound for nog ln. From the above proofs, we can see that t less than or equal to sen log ln, if c greater than or equal to 1, and t greater than or equal to con log ln, if k less than or equal to 1. Technically, we're still missing the base cases in both proofs, but we can be fairly confident at this point that t equal to O. 1.27 Amortized analysis. Amortized analysis refers to determining the time average running time for a sequence of operations. It is different from average case analysis because amortized analysis does not make any assumption about the distribution of the data values, whereas average case analysis assumes the data are not bad. That is, amortized analysis is a worst case analysis, but for a sequence of operations rather than for individual operations. The motivation for amortized analysis is to better understand the running time of certain techniques, where standard worst case analysis provides an overly pessimistic bound. Amortized analysis generally applies to a method that consists of a sequence of operations, where the vast majority of the operations are cheap, but some of the operations are expensive. If we can show that the expensive operations are particularly rare, we can change them to the cheap operations, and only bound the cheap operations. The general approach is to assign an artificial cost to each operation in the sequence, such that the total of the artificial costs for the sequence of operations bounds the total of the real costs for the sequence. This artificial cost is called the amortized cost of an operation. To analyze the running time, the amortized cost thus is a correct way of understanding the overall running time. But note that particular operations can still take longer, so it is not a way of bounding the running time of any individual operation in the sequence. When one event in a sequence affects the cost of later events, one particular task may be expensive, but it may leave data structure in a state that the next few operations become easier. Example, let us consider an array of elements from which we want to find the kth smallest element. We can solve this problem using sorting. After sorting the given array, we just need to return the kth element from it. The cost of performing the sort is O. If we perform n such selections, then the average cost of each selection is O equal to O. This clearly indicates that sorting once is reducing the complexity of subsequent operations. 1.28 Algorithms analysis, problems and solutions. Note, from the following problems, try to understand the cases which have different complexities, etc. Problem minus 21, find the complexity of the below recurrence. Solution, let us try solving this function with substitution. T equal to 3 trillions. This clearly shows that the complexity of this function is O. Note, we can use the subtraction and conquer master theorem for this problem. Problem minus 22. Find the complexity of the below recurrence. Solution, let us try solving this function with substitution. T equal to 2, 1. T equal to 2, 1, minus 1 equal to 2, do t 2 to 1. T equal to 2 to the power of 2, 2 to 1, minus 1 equal to 2, 2 to 1. T, 2 and 1, 2, 2, 3, 2 to the power. T, 2 and 1 equal to 2, 2 equal to 2. Time complexity is O. Note that while the recurrence relation looks exponential, the solution to the recurrence relation here gives a different result. Problem 23. What is the running time of the following function? Void function. Solution, consider the comments in the below function. Void function, int I equal to 1, s equal to 1. S is increasing not at rate 1, but I while itt. S equal to s plus I, print tf. We can define the s terms according to the relation s equal to s1 plus I. The value oft increases by 1 for each iteration. The value contained in s at the eth iteration is the sum of the first positive integers. If k is the total number of iterations taken by the program, then the while loop terminates if. Problem 24, find the complexity of the function given below. Solution, void function, int I, count equal to 0 for count plus plus. In the above mentioned function, the loop will end if I2n equal to t equal to O. This is similar to problem 23. Problem, minus 25, what is the complexity of the program given below? Void function, int I, jk, count equal to 0 for 4 for count plus plus. Solution, consider the comments in the following function. Void function, int I, jk, count equal to 0, Outer loop execute n slash 2 times 4. Middle loop executes n slash 2 times 4. Inner loop execute long times for count plus plus. The complexity of the above function is O. Problem 26. What is the complexity of the program given below? Void function int I j k count equal to 0 for 4 for count plus plus. Solution. Consider the comments in the following function. Void function int I j k count equal to 0. Outer loop execute n slash 2 times 4. Middle loop executes long times 4. Inner loop execute long times for count plus plus. The complexity of the above function is O. Problem minus 27. Find the complexity of the program below. Function. Solution. Consider the comments in the function below. Function. Constant time if return. Outer loop execute n times 4. Inner loop executes only time due to break statement. 4. Print ef break. The complexity of the above function is O. Even though the inner loop is bounded by n due to break statement, it is executing only once. The problem 28. Write a recursive function for the running time t of the function given below. Prove using the iterative method that t equal to O. Function if return for printf function. Solution. Consider the comments in the function below. Function. Constant time if return. Outer loop execute n times 4. Inner loop executes n times 4. Constant time print f function. The recurrence for this code is clearly t equal to t plus cn2 for some constant c greater than 0, since each call prints out n2 asterisks and calls itself recursively on n3. Using the iterative method, we get t equal to t plus cn2. Using the subtraction and conquer master theorem, we get t equal to. Determine bounds for the recurrence relation, t problem minus 29. Solution. Using divide and conquer master theorem, we get O equal to 2 trillions plus ln. The recurrence equation, we get nt less than or equal to c plus c plus c plus cn less than or equal to kn, where k is a constant. This clearly 248 says O. Solution. Substituting in. Problem minus 31. Determine bounds for the recurrence relation, t equal to t plus 7. Solution. Using master theorem, we get. Problem 32. Prove that the running time of the code below is 2. Solution. The while loop will terminate once the value of k is greater than or equal to the value of n. In each iteration, the value of k is multiplied by 3. If I is the number of iterations, then k has the value of 3 to the power of 2 after I iterations. The loop is terminated upon reaching I iterations when 3 to the power of 1 greater than or equal to n. T I greater than or equal to log, which shows that I equal to q. Problem 33. Solve the following recurrence. Solution by iteration. Note, we can use the subtraction and conquer master theorem for this problem. Problem 34. Consider the following program. Else return fib plus fib n minus 2. Solution. The recurrence relation for the running time of this program is t equal to t plus tc. Note t has 2 recurrence calls indicating a binary tree. Each step recursively calls the program for n reduced by 1 and 2, so the depth of the recurrence tree is O. The number of leaves at depth n is 2, since this is a full binary tree, and each leaf takes at least O computations for the constant factor. Running time is clearly exponential in n, and it is O. Problem 35. Running time of following program. Function. For printf. Solution. Consider the comments in the function below. Function. This loop executes n times for, this loop executes j times with j increased by the rate of I for printf. In the above code, inner loop executes ni times for each value of I. Its running time is nx equal to O. Problem minus 36. What is the complexity of log I? Solution. Using the logarithmic property, log c equal to log x plus log e, we can see that this problem is equivalent to. This shows that the time complexity equal to O. Problem minus 37. What is the running time of the following recursive function? First write the recurrence formula, and then find its complexity. Solution. Consider the comments in the below function. Function. Constant time if return. This loop executes with recursive loop of value 4. We can assume that for asymptotical analysis k equal to for every integer k greater than or equal to 1. The recurrence for this code is t equal to 3 trillions plus. Using master theorem, we get t equal to. Problem minus 38. What is the running time of the following recursive function? First write a recurrence formula and show its solution using induction. Function if return. Solution. Consider the comments in the function below. Function. Constant time if return. This loop executes 3 times with recursive call of n1 value for function. The if statement requires constant time. With the for loop, we neglect the loop overhead and only count 3 times that the function is called recursively. This implies a time complexity recurrence. Using the subtraction and conquer master theorem, we get t equal to. Problem minus 39 is below. Write a recursion formula for the running time t of the function whose code. Function if return for printf function. Solution. Consider the comments in the function below. Function less than equal to if return. Constant time. This loop executes n times with constant time loop for printf. Recursive call with coin in function. The recurrence for this piece of code is t equal to t plus O equal to t plus O 4/5 trillion plus O. Applying master theorem, we get t equal to O. Problem 40. Find the complexity of the recurrence. T equal to 2 trillions plus ln. Solution. The given recurrence is not in the master theorem format. Let us try to convert this to the master theorem format by assuming n equal to 2 meters. Applying the logarithm on both sides gives ln log L equal to m equal to ln. Now, the given function becomes equal to. To make it m, simple s equal to ts equal to t equal to s equal to 2 seconds equal to plus m. Applying the master theorem format would result in s equal to O if we substitute m equal to ln back, t equal to s equal to O log ln. Problem minus 41. We find the complexity of the recurrence t equal to pi plus 1. Assume. Solution. Applying the logic of problem minus 40 gives s equal to s plus 1. Applying the master theorem would result in s equal to O. Substituting m equal to ln gives to equal to s equal to. Problem minus 42. Find the complexity of the recurrence t equal to 2 pi plus 1, 2 seconds plus 1. Using the master solution, applying the logic of problem 40 gives s. Problem minus 43. Find the complexity of the below function. Solution. Consider the comments in the function below. In t function, if return 1, constant time else, executes n plus 1 times return plus 1. For the above code, the recurrence function can be given as t equal to t plus 1. This is same as that of problem 41. Problem minus 44n. Analyze the running time of the following recursive pseudocode as a function of void function if return, else counter equal to 0% for I equal to 1 to 82 function. Solution. Consider the comments in below pseudocode and call running time of function as t. Void function. If return, constant time. Else counter equal to 0. Function. This loop executes n 3 times with constant time loop. For I, 1 to n3 do. T can be defined as follows. Using the master theorem gives T equal to O equal to problem minus 45, find the complexity of the below pseudocode equal to temp 1 repeat. For I equal to 1 to n temp equal to temp plus 1, n equal to n2 until n less than equal to 1. Solution. Consider the comments in the pseudocode below. Temp equal to 1. Const time repeat for I equal to 1 to n. This loops executes n times temp equal to temp plus 1. Recursive call with value until n less than equal to 1. The recurrence for this function is t equal to t plus n. Using master theorem, we get t equal to O. Problem minus 46 running time of the following program. Function. Solution. Consider the comments in the below function. Function 4. This loops executes n times. This loops executes ln times from our logarithms guideline for printf. Complexity of above program is O. Problem minus 47 running time of the following program. Function. Solution. Consider the comments in the below function. Function. This loops executes n/3 times for this loops executes n/4 times for printf. The time complexity of this program is O. Problem minus 48. Find the complexity of the below function. Void function. Solution. Consider the comments in the below function. Void function if return. Constant time if. Constant time printf. Recursion with n/2 value function. Recursion with n/2 value function. Plus 1. Using master theorem, we get t equal to the recurrence for this function is t equal to 2 trillions. O. Problem minus 49. Find the complexity of the below function. Function I. Solution. Function I equal to 2I. Lone times. Time complexity O equal to O. Problem minus 50. Zisks and O, where O stands for order n is 0000. Solution. Sigma is less than or equal to no. Equal to O sigma is less than or equal to 1 equal to O minus 51. Which of the following three claims are correct? Problem I equal to, where k and m are constants 2, 2n plus 1 equal to 0, 3, 22, n plus 1 equal to O, and 2i and 3, 2, and 3i, 2 and third solution equal to n, 2 plus c, nk minus 1 plus km equal to copyright, and 2n plus 1 equal to 2, 2n equal to O. Problem minus 52, consider the following functions, f equal to 2 and g equal to n. Equal to 2, consider the following statements about the asymptotic behavior of f, g, and h is true. F equal to O, G equal to O, F equal to Q, G equal to O. Solution. According to the rate of growth, HFG is asymptotically greater than F, and F is asymptotically greater than H. We can easily see the above order by taking logarithms of the given three functions, log ln, n log. Note that log equal to O. Problem 53. Consider the following segment of C code. The number of comparisons made in the execution of the loop for any n greater than 0 is seal plus 1, n seal, floor plus 1. Solution. Let us assume that the loop executes k times. After kth step, the value of j is 2k. Taking logarithms on both sides gives k equal to log. Since we are doing one more comparison for exiting from the loop, the answer is seal plus 1. Problem 54. Consider the following C code segment. Let t denote the number of times the for loop is executed by the program on input n. Which of the following is true? Int is prime. Return 1, t on and t equal to q. Return 0, t equal to O and t equal to q. T equal to O and t equal to none of the above. Solution. Big O notation describes the tight upper bound, and big omega notation describes the tight lower bound for an algorithm. The for loop in the question is run maximum n times and minimum 1 time. Therefore, t equal to O and t equal to q. Problem minus 55 in the following C function. Let n greater than or equal to m. How many recursive calls are made by this function? int gcd if n equal to n%m. Return gcd. O omega. O solution. No option is correct. Big O notation describes the tight upper bound, and big omega notation describes the tight lower bound for an algorithm. For m equal to 2 and for all n equal to 21, the running time is O, which contradicts every option. Problem 56, suppose t equal to 2 trillions plus n, t equal to 1. Which one of the following is false? T equal to O, t equal to O, t equal to q, t equal to O. Solution. Big O notation describes the tight upper bound, and big omega notation describes the tight lower bound for an algorithm. Based on master theorem, we get t equal to O. This indicates the tight lower bound and tight upper bound are the same. That means O and q are correct for given recurrence. So option is wrong. Problem minus 57, find the complexity of the below function. Function. Solution. Function for 4. Executes n times. Executes n times. If for printf. Executes j times. Equal to times. Time complexity. O. Problem minus 58 to calculate 9. Give an algorithm and discuss its complexity. Solution. Start with 1 and multiply by 9 until reaching 9. Time complexity. There are n1 multiplications and each takes constant time giving O algorithm. Problem minus 59 for problem 58. Can we improve the time complexity? Solution. Refer to the divide and conquer chapter. Problem 60. Find the time complexity of recurrence d equal to te2 plus te2 plus te2 plus n. Solution. Let us solve this problem by method of guessing. The total size on each level of the recurrence tree is less than n, so we guess that f equal to n will dominate. Assume for all I n that c1 and tc2n. Then, n if c1 greater than or equal to 8k and c2 less than or equal to 8k, then c1n equal to t equal to c2n. So, t equal to O. In general, if you have multiple recursive calls, the sum of the arguments to those calls is less than n, and f is reasonably large. A good guess is t equal to. Problem minus 61. Solve the following recurrence relation using the recursion tree method, t equal to t plus n. 2n. Solution. How much work do we do in each level of the recursion tree? In level 0, we take n 2 time. At level 1, the 2 subproblems take time, 1n at level 2. The 4 subproblems are of size, subproblems take time, 2 meters, 1, 2n, 2, 2n, and 22. 32 feet, 2 inches, 3, 33, respectively. These two. Similarly, the amount of work at level k is at most n2. 25 let alpha equal to the total runtime is then 36. That is, the first level provides a constant fraction of the total runtime. Problem 62 plus 20n, rank the following functions by order of growth. N, 4n, n times 3, 3 plus n2, and plus 200, 20n plus 500, 1gn, and 2, 4n. The complexity of the below function. Function for sum equal to sum minus 1. Solution, consider the worst case. Function int sum equal to 0, 4. Executes n times if sum equal to sum plus 1. Executes n times else, 4. Executes n times sum equal to sum minus 1. Time complexity O. Problem minus 64. Can we say 3n equal to O? 3n1 solution, yes, because 30, 7, 5. Can we say 23n equal to O? Problem 65. Solution, no, because 23n equal to n equal to 8, not less than 2n. 2.1 Introduction. In this chapter, we will look at one of the important topics, recursion, which will be used in almost every chapter, and also its relative backtracking. 2.2 What is recursion? Any function which calls itself is called recursive. A recursive method solves a problem by calling a copy of itself to work on a smaller problem. This is called the recursion step. The recursion step can result in many more such recursive calls. It is important to ensure that the recursion terminates each time the function calls itself with a slightly simpler version of the original problem. The sequence of smaller problems must eventually converge on the base case. 2.3 Why recursion? Recursion is a useful technique borrowed from mathematics. Recursive code is generally shorter and easier to write than iterative code. Generally, loops are turned into recursive functions when they are compiled or interpreted. Recursion is most useful for tasks that can be defined in terms of similar subtasks. For example, sort, search, and traversal problems often have simple recursive solutions. 2.4 Format of a recursive function. A recursive function performs a task in part by calling itself to perform the subtasks. At some point, the function encounters a subtask that it can perform without calling itself. This case, where the function does not recur, is called the base case. The former, where the function calls itself to perform a subtask, is referred to as the accursive case. We can write all recursive functions using the format. As an example, consider the factorial function n is the product of all integers between n and 1. The definition of recursive factorial looks like, this definition can easily be converted to recursive implementation. Here, the problem is determining the value of n, and the subproblem is determining the value of. In the recursive case, when n is greater than 1, the function calls itself to determine the value of, and multiplies that with n in. The base case, when n is 0 or 1, the function simply returns 1. This looks like the following. Or calculates factorial of a positive integer in fact, if base case is fact of or 1 is 1, return 1. Else, if return 1. Else, recursive case, multiply n by factorial, return n fact. 2.5 Recursion in memory. Each recursive call makes a new copy of that method in memory. Once a method ends, the copy of that returning method is removed from memory. The recursive solutions look simple, but visualization and tracing takes time. For better understanding, let us consider the following example. Print numbers 1 to n backward in tprint if this is the terminating base case, return 0, else printf, return print, recursive call to itself again. For this example, if we call the print function with n equal to 4, visually our memory assignments may look like. Now, let us consider our factorial function. The visualization of factorial function with n equal to 4 will look like 2.6 Recursion versus iteration. While discussing recursion, the basic question that comes to mind is, which way is better? Iteration or recursion? The answer to this question depends on what we are trying to do. A recursive approach mirrors the problem that we are trying to solve. A recursive approach makes it simpler to solve a problem that may not have the most obvious of answers. But recursion adds overhead for each recursive call. Recursion terminates when a base case is reached. Each recursive call requires extra space on the stack frame. If we get infinite recursion, the program may run out of memory and result in stack overflow. Solutions to some problems are easier to formulate recursively. Iteration terminates when a condition is proven to be false. Each iteration does not require extra space. An infinite loop could loop forever since there is no extra memory being created. Iterative solutions to a problem may not always be as obvious as a recursive solution. 2.7 Notes on recursion. Recursive algorithms have two types of cases, recursive cases and base cases. Every recursive function case must terminate at a base case. Generally, iterative solutions are more efficient than recursive solutions. A recursive algorithm can be implemented without recursive function calls using a stack, but it's usually more trouble than it's worth. That means any problem that can be solved recursively can also be solved iteratively. For some problems, there are no obvious iterative algorithms. Some problems are best suited for recursive solutions, while others are not. 2.8 Example algorithms of recursion. Fibonacci series, factorial finding, merge sort, quicksort, binary search, tree traversals, and many tree problems, in order, pre-order, post-order. Graph traversals, DFS and BFS. Dynamic programming examples, divide and conquer algorithms, towers of Hanoi, backtracking algorithms. 2.9 Recursion, problems and solutions. In this chapter, we cover a few problems with recursion, and we will discuss the rest in other chapters. By the time you complete reading the entire book, you will encounter many recursion problems. Problem -1 discuss Towers of Hanoi puzzle. Solution, the Towers of Hanoi is a mathematical puzzle. It consists of 3 rods and a number of disks of different sizes which can slide onto any rod. The puzzle starts with the disks on one rod in ascending order of size, the smallest at the top, thus making a conical shape. The objective of the puzzle is to move the entire stack to another rod, satisfying the following rules. Only one disk may be moved at a time. Each move consists of taking the upper disk from one of the rods and sliding it onto another rod, on top of the other disks that may already be present on that rod. No disk may be placed on top of a smaller disk. Algorithm. Move the top N1 disks from source to auxiliary tower. Move the nth disk from source to destination tower. Move the N1 disks from auxiliary tower to destination tower. Transferring the top N1 disks from source to auxiliary tower can again be thought of as a fresh problem and can be solved in the same manner. Once we solve Towers of Hanoi with 3 disks, we can solve it with any number of disks with the above algorithm. Void, Towers of Hanoi if, printf, return. Move top N1 disks from A to B, using C as auxiliary. Towers of Hanoi. Move remaining disks from A to C. Printf, move N1 disks from B to C using A as auxiliary. Towers of Hanoi. Problem -2 solution. Given an array, check whether the array is in sorted order with recursion. Int is array in sorted order. Int n, if return 1, return A. 0, isarray in sorted order. Time complexity, O, space complexity, O for recursive stack space. 2.10, what is backtracking? Backtracking is an improvement of the brute force approach. It systematically searches for a solution to a problem among all available options. In backtracking, we start with one possible option out of many available options and try to solve the problem. If we are able to solve the problem with the selected move, then we will print the solution, else we will backtrack and select some other option and try to solve it. If none, if the options work out, we will claim that there is no solution for the problem. Backtracking is a form of recursion. The usual scenario is that you are faced with a number of options and you must choose one of these. After you make your choice, you will get a new set of options. Just what set of options you get depends on what choice you made. This procedure is repeated over and over until you reach a final state. If you made a good sequence of choices, your final state is a goal state. If you didn't, it isn't. Backtracking can be thought of as a selective tree graph traversal method. The tree is a way of representing some initial starting position and a final goal state. Backtracking allows us to deal with situations in which a raw brute force approach would explode into an impossible number of options to consider. Backtracking is a sort of refined brute force. At each node, we eliminate choices that are obviously not possible and proceed to recursively check only those that have potential. What's interesting about backtracking is that we back up only as far as needed to reach a previous decision point with an as yet unexplored alternative. In general, that will be at the most recent decision point. Eventually, more and more of these decision points will have been fully explored, and we will have to backtrack further and further. If we backtrack all the way to our initial state and have explored all alternatives from there, we can conclude the particular problem is unsolvable. In such a case, we will have done all the work of the exhaustive recursion and known that there is no viable solution possible. Sometimes the best algorithm for a problem is to try all possibilities. This is always slow, but there are standard tools that can be used to help. Tools, algorithms for generating basic objects, such as binary strings, permutations, combinations. Backtracking speeds the exhaustive search by pruning. 2.11 example algorithms of backtracking. Binary strings, generating all binary strings, generating k, array strings. N queens problem. The knapsack problem, generalized strings, Hamiltonian cycles, graph coloring problem, 2.12 backtracking problems and solutions. Problem -3, generate all the strings of n bits. Assume A is an array of size n. Solution, void binary, if print E. Assume array A is a global variable else, A equal to 0 binary, A equal to 1 binary. Let T be the running time of binary. Assume function printf takes time O. If n less than 0 trillions equal to 2 trillions plus D otherwise. Using subtraction and conquer master theorem, we get T equal to O. This means the algorithm for generating bit strings is optimal. Problem 4, generate all the strings of length n drawn from 0, k, 1. Solution. Let us assume we keep current k array string in an array A. Call function k string, void k string, process all k array strings of length m if printf, else, for A equal to j, k string. Assume array A is a global variable. Let T be the running time of k string. Then, using subtraction and conquer master theorem, we get T equal to O. Note, for more problems, refer to string algorithms chapter. Problem -5. Finding the length of connected cells of 1 second in a matrix of OS in 1 second, given a matrix, each of which may be 1 or 0. The filled cells that are connected form a region. Two cells are said to be connected if they are adjacent to each other horizontally, vertically, or diagonally. There may be several regions in the matrix. How do you find the largest region in the matrix? Solution. The simplest idea is for each location traverse in all 8 directions, and in each of those directions keep track of maximum region found. In getVal, in I, in j, in L, and h, for int nui equal to r plus direction, int nu gc plus direction, int val getVal, if equal to false, return max size. Sample call, int zar equal to count. Number of maximum 1 second are get max zones endl. Problem 6, solve the recurrence t equal to 2 trillions plus 2n. Solution. At each level of the recurrence tree, the number of problems is double from the previous level, while the amount of work being done in each problem is half from the previous level. Formally, the ith level has 2 problems, each requiring 2 I work, thus the h level requires exactly 2 work. The depth of this tree is n, because at the ith level the originating call will be t. Thus the total complexity for t is t. 3.1. What is a linked list? A linked list is a data structure used for storing collections of data. A linked list has the following properties. Successive elements are connected by pointers, the last element points to null. Can grow or shrink in size during execution of a program. Can be made just as long as required. Does not waste memory space. It allocates memory as list grows. Head. 3.2 Linked list ADT. The following operations make linked lists and ADT. Main linked list operations. Insert inserts an element into the list. Delete removes and returns the specified position element from the list. Auxiliary linked list operations. Delete list removes all elements of the list. Count returns the number of elements in the list. Find nth node from the end of the list. 3.3 Why linked lists? There are many other data structures that do the same thing as linked lists. Before discussing linked lists, it is important to understand the difference between linked lists and arrays. Both linked lists and arrays are used to store collections of data, and since both are used for the same purpose, we need to differentiate their usage. That means in which cases arrays are suitable, and in which cases linked lists are suitable. 3.4 Arrays overview. One memory block is allocated for the entire array to hold the elements of the array. The array elements can be accessed in constant time by using the index of the particular element as the subscript. Why constant time for accessing array elements? To access an array element, the address of an element is computed as an offset from the base address of the array, and one multiplication is needed to compute what is supposed to be added to the base address to get the memory address of the element. First, the size of an element of that data type is calculated, and then it is multiplied with the index of the element to get the value to be added to the base address. This process takes one multiplication and one addition. Since these two operations take constant time, we can say the array access can be performed in constant time. Advantages of arrays: simple and easy to use. Faster access to the elements. Disadvantages of arrays: pre-allocates all needed memory up front and wastes memory space for indices in the array that are empty. Fixed size: the size of the array is static. One block allocation to allocate the array itself at the beginning. Sometimes it may not be possible to get the memory for the complete array. Complex position-based insertion: to insert an element at a given position, we may need to shift the existing elements. This will create a position for us to insert the new element at the desired position. If the position at which we want to add an element is at the beginning, then the shifting operation is more expensive. Dynamic arrays. Dynamic array is a random access, variable size list data structure that allows elements to be added or removed. One simple way of implementing dynamic arrays is to initially start with some fixed size array. As soon as that array becomes full, create the new array double the size of the original array. Similarly, reduce the array size to half if the elements in the array are less than half. Note, we will see the implementation for dynamic arrays in the stacks, queues, and hashing chapters. Advantages of linked lists. Linked lists have both advantages and disadvantages. The advantage of linked lists is that they can be expanded in constant time. To create an array, we must allocate memory for a certain number of elements. To add more elements to the array when full, we must create a new array and copy the old array into the new array. This can take a lot of time. We can prevent this by allocating lots of space initially, but then we might allocate more than we need and waste memory. With a linked list, we can start with space for just one allocated element and add on new elements easily without the need to do any copying and reallocating. Issues with linked lists. There are a number of issues with linked lists. The main disadvantage of linked lists is access time to individual elements. Array is random access, which means it takes O to access any element in the array. Linked lists take O for access to an element in the list in the worst case. Another advantage of arrays in access time is spatial locality and memory. Arrays are defined as contiguous blocks of memory, and so any array element will be physically near its neighbors. This greatly benefits from modern CPU caching methods. Although the dynamic allocation of storage is a great advantage, the overhead with storing and retrieving data can make a big difference. Sometimes linked lists are hard to manipulate. If the last item is deleted, the last but one must then have its pointer changed to hold a null reference. This requires that the list is traversed to find the last but one link, and its pointer set to a null reference. Finally, linked lists waste memory in terms of extra reference points. 3.5 Comparison of linked lists with arrays and dynamic arrays. 3.6 Singly linked lists. Generally, linked list means a singly linked list. This list consists of a number of nodes in which each node has a next pointer to the following element. The link of the last node in the list is null, which indicates the end of the list. Head. Following is a type declaration for a linked list of integers, struct list node. Basic operations on a list, traversing the list, inserting an item in the list, deleting an item from the list, traversing the linked list. Let us assume that the head points to the first node of the list. To traverse the list, we do the following. Follow the pointers, display the contents of the nodes as they are traversed. Stop when the next pointer points to null. Head. The list length function takes a linked list as input and counts the number of nodes in the list. The function given below can be used for printing the list data with extra print function. In T list length, struct list node current equal to head, in count equal to 0, while count plus plus current, next return count. Time complexity O for scanning the list of size n. Space complexity O for creating a temporary variable. Singly linked list insertion. Insertion into a singly linked list has 3 cases. Inserting a new node before the head. Inserting a new node after the tail. Inserting a new node at the middle of the list. Note, to insert an element in the linked list at some position P, assume that after inserting the element, the position of this new node is P. Inserting a node in singly linked list at the beginning. In this case, a new node is inserted before the current head node. Only one next pointer needs to be modified, and it can be done in 2 steps. Update the next pointer of new node to point to the current head, new node. Update head pointer to point to the new node, head. Inserting a node in singly linked list at the ending. In this case, we need to modify 2 next pointers. New node's next pointer points to null, head. Inserting a node in singly linked list at the middle. Let us assume that we are given a position where we want to insert the new node. In this case also, we need to modify 2 next pointers. If we want to add an element at position 3, then we stop at position 2. That means we traverse 2 nodes and insert the new node. For simplicity, let us assume that the second node is called position node. The new node points to the next node of the position where we want to add this node. New node. Let us write the code for all 3 cases. We must update the first element pointer in the calling function, not just in the called function. For this reason, we need to send a double pointer. The following code inserts a node in the singly linked list. Void insert in linked list. Traverse the list until the position where we want to insert while indent. Note, we can implement the 3 variations of the insert operation separately. Time complexity O, since in the worst case, we may need to insert the node at the end of the list. Space complexity O for creating one temporary variable. Singly linked list deletion. Similar to insertion, here we also have 3 cases. Deleting the first node, deleting the last node, deleting an intermediate node, deleting the first node in singly linked list. First node is removed from the list. It can be done in 2 steps. Create a temporary node which will point to the same node as that of head. Head temp. Now, move the head node's pointer to the next node and dispose of the temporary node. Deleting the last node in singly linked list. In this case, the last node is removed from the list. This operation is a bit trickier than removing the first node because the algorithm should find a node which is previous to the tail. It can be done in 3 steps. Traverse the list and while traversing, maintain the previous node address also. By the time we reach the end of the list, we will have 2 pointers, one pointing to the tail node and the other pointing to the node before the tail node. Deleting an intermediate node in singly linked list. In this case, the node to be removed is always located between 2 nodes. Head and tail links not updated in this case. Such a removal can be done in 2 steps. R. Similar to the previous case, maintain the previous node while traversing the list. Once we find the node to be deleted, change the previous node's next pointer to the next pointer of the node to be deleted. Void delete node from linked list. Int k equal to 1, struct list node p, q if, printf return, p equal to head. From the beginning, if head equal to next, free, return else. Traverse the list until arriving at the position from which we want to delete while and, k plus plus, q equal to pp, equal to p. Next if, at the end, from the middle, printf, else, q, equal to p next, free. Time complexity, O. In the worst case, we may need to delete the node at the end of the list. Space complexity, O for one temporary variable. Deleting singly linked list. This works by storing the current node in some temporary variable and freeing the current node. After freeing the current node, go to the next node with a temporary variable and repeat this process for all nodes. Void delete linked list, struct list node auxiliary node, iterator equal to head, while auxiliary node iterator, next free, iterator equal to auxiliary node, head equal to null, to affect the real head back in the caller. Time complexity, O for scanning the complete list of size n. Space complexity, O for creating one temporary variable. 3.7 doubly linked lists. The advantage of a doubly linked list is that given a node in the list, we can navigate in both directions. A node in a singly linked list cannot be removed unless we have the pointer to its predecessor. But in a doubly linked list, we can delete a node even if we don't have the previous node's address. The primary disadvantages of doubly linked lists are, each node requires an extra pointer, requiring more space. The insertion or deletion of a node takes a bit longer. Similar to a singly linked list, let us implement the operations of a doubly linked list. If you understand the singly linked list operations, then doubly linked list operations are obvious. Following is a type declaration for a doubly linked list of integers. Struct dl node, int data, struct dl node next, struct dl node prev. Doubly linked list insertion. Insertion into a doubly linked list has 3 cases. Inserting a new node before the head. Inserting a new node after the tail. Inserting a new node at the middle of the list. Inserting a node in doubly linked list at the beginning. In this case, new node is inserted before the head node. Previous and next pointers need to be modified, and it can be done in 2 steps. Update the right pointer of the new node to point to the current head node, and also make left pointer of new node as null. Update head node's left pointer to point to the new node and make new node as head. Head. Inserting a node in doubly linked list at the ending. In this case, traverse the list till the end and insert the new node. New node right pointer points to null and left pointer points to the end of the list. Inserting a node in doubly linked list at the middle. As discussed in singly linked lists, traverse the list to the position node and insert the new node. New node right pointer points to the next node of the position node where we want to insert the new node. Also, new node left pointer points to the position node. Position node right pointer points to the new node, and the next node of position node left pointer points to new node. Now, let us write the code for all of these three cases. We must update the first element pointer in the calling function, not just in the called function. For this reason, we need to send a double pointer. The following code inserts a node in the doubly linked list. Void DL insert print if new node next temp next new node prev equal to temp if temp next prev new node temp next equal to new node return. Time complexity O. In the worst case, we may need to insert the node at the end of the list. Space complexity O for creating one temporary variable. Doubly linked list deletion. Similar to singly linked list deletion, here we have three cases: deleting the first node, deleting the last node, deleting an intermediate node, deleting the first node in doubly linked list. In this case, the first node is removed from the list. It can be done in two steps. Create a temporary node which will point to the same node as that of head. Null head temp null. Now move the head node's pointer to the next node and change the head's left pointer to null. Then dispose of the temporary node, deleting the last node in doubly linked list. This operation is a bit trickier than removing the first node, because the algorithm should find a node, which is previous to the tail first. This can be done in three steps. Traverse the list, and while traversing, maintain the previous node address also. By the time we reach the end of the list, we will have two pointers, one pointing to the tail and the other pointing to the node before the tail. Dispose the tail node, deleting an intermediate node in doubly linked list. In this case, the node to be removed is always located between two nodes, and the head and tail links are not updated. The removal can be done in two steps. Similar to the previous case, maintain the previous node while also traversing the list. Upon locating the node to be deleted, change the previous node's next pointer to the next node of the node to be deleted. Void DL delete if printf return if head equal to next if prev equal to null free return while and then temp next equal to null temp equal to temp next k plus plus if printf temp prev temp next if deletion from intermediate node temp next prev equal to temp free return. Time complexity O for scanning the complete list of size n. Space complexity O for creating one temporary variable. 3.8 circular linked lists. In singly linked lists and doubly linked lists, the end of lists are indicated with null value. But circular linked lists do not have ends. While traversing the circular linked lists, we should be careful, otherwise we will be traversing the list infinitely. In circular linked lists, each node has a successor. Note that unlike singly linked lists, there is no node with null pointer in a circularly linked list. In some situations, circular linked lists are useful. For example, when several processes are using the same computer resource for the same amount of time, we have to assure that no process accesses the resource before all other processes do. The following is a type declaration for a circular linked list of integers. In a circular linked list, we access the elements using the head node. Counting nodes in a circular linked list. Head. The circular list is accessible through the node marked head. To count the nodes, the list has to be traversed from the node marked head with the help of a dummy node current and stop the counting when current reaches the starting node head. If the list is empty, head will be null, and in that case, set count equal to 0. Otherwise, set the current pointer to the first node and keep on counting till the current pointer reaches the starting node. In circular list length while, return count. Time complexity O for scanning the complete list of size n. Space complexity O for creating one temporary variable. Printing the contents of a circular linked list. We assume here that the list is being accessed by its head node. Since all the nodes are arranged in a circular fashion, the tail node of the list will be the node previous to the head node. Let us assume we want to print the contents of the node starting with the head node, print its contents, move to the next node, and continue printing till we reach the head node again. Head. Void print circular list data while. Time complexity O for scanning the complete list of size n. Space complexity O for temporary variable. Inserting a node at the end of a circular linked list. Let us add a node containing data at the end of a list headed by head. The new node will be placed just after the tail node, which means it will have to be inserted in between the tail node and the first node. Create a new node and initially keep its next pointer pointing to itself. Node. Update the next pointer of the new node with the head node and also traverse the list to the tail. That means in a circular list, we should stop at the node whose next node is head. Update the next pointer of the previous node to point to the new node, and we get the list as shown below. Void insert at end in CLL if printf return new node data equal to data while current equal to current next new node next equal to new node if head equal to new node else new node next head current next equal to new node. Time complexity O for scanning the complete list of size n. Space complexity O for temporary variable. Inserting a node at the front of a circular linked list. The only difference between inserting a node at the beginning and at the end is that after inserting the new node, we just need to update the pointer. The steps for doing this are given below. Create a new node and initially keep its next pointer pointing to itself. Update the next pointer of the new node with the head node and also traverse the list until the tail. That means in a circular list, we should stop at the node which is its previous node in the list. New node. Update the previous head node in the list to point to the new node. Make the new node as the head. Data 1540 to 41 head. Void insert at begin in CL if printf return new node. Data equal to data. While current next new node if head equal to new node. Else new node next head. Current next equal to new node. Head equal to new node. Return. Time complexity O for scanning the complete list of size n. Space complexity O for temporary variable. Deleting the last node in a circular linked list. The list has to be traversed to reach the last but one node. This has to be named as the tail node. Its next field has to point to the first node. Consider the following list. And to delete the last node 40, the list has to be traversed till you reach 7. The next field of 7 has to be changed to point to 60, and this node must be renamed ptail. Traverse the list and find the tail node and its previous node. Update the next pointer of tail node's previous node to point to head. Dispose of the tail node. Void delete last node from CLL. Struct CLL node temp equal to head, current equal to head if printf return. While temp equal to current, next, temp next current, next, free, return. Time complexity O for scanning the complete list of size n. Space complexity O for a temporary variable. Deleting the first node in a circular list. The first node can be deleted by simply replacing the next field of the tail node with the next field of the first node. Find the tail node of a linked list by traversing the list. Tail node is the previous node to the head node which we want to delete. Create a temporary node which will point to the head. Also, update the tail node's next pointer to point to next node of head. Now, move the head pointer to next node. Create a temporary node which will point to head. Also, update the tail node's next pointer to point to next node of head. Void delete front node from CLL. Struct CLL node temp equal to head. Struct CLL node current equal to head if printf return. While current next equal to current next head equal to head, next free, return. Time complexity O for scanning the complete list of size n. Space complexity O for a temporary variable. Applications of circular list. Circular linked lists are used in managing the computing resources of a computer. We can use circular lists for implementing stacks and queues. 3.9, a memory-efficient, doubly linked list. In conventional implementation, we need to keep a forward pointer to the next item on the list and a backward pointer to the previous item. That means elements in doubly linked list implementations consist of data, a pointer to the next node, and a pointer to the previous node in the list as shown below. Conventional node definition. Recently, a journal presented an alternative implementation of the doubly linked list ADT with insertion, traversal, and deletion operations. This implementation is based on pointer difference. Each node uses only one pointer field to traverse the list back and forth. New node definition. The PTR diff pointer field contains the difference between the pointer to the next node and the pointer to the previous node. The pointer difference is calculated by using exclusive or operation. The PTR diff of the start node is the of null and next node. Similarly, the PTR diff of end node is the of previous node and null. As an example, consider the following linked list. In the example above, the next pointer of A is null B. The next pointer of B is AC. The next pointer of C is B, D. The next pointer of D is C, null. Why does it work? To find the answer to this question, let us consider the properties of x plus x equal to 0, x plus 0 equal to x equal to xy, yax z equal to x plus. For the example above, let us assume that we are at C node and want to move to B. We know that C's PTR diff is defined as BD. If we want to move to B, performing on C's PTR diff with D would give B. This is due to the fact that, similarly, if we want to move to D, then we have to apply to C's PTR diff with B to give D. From the above discussion, we can see that just by using a single pointer, we can move back and forth. A memory-efficient implementation of a doubly linked list is possible with minimal compromising of timing efficiency. 3.10 Unrolled linked lists. One of the biggest advantages of linked lists over arrays is that inserting an element at any location takes only O time. However, it takes O to search for an element in a linked list. There is a simple variation of the singly linked list called unrolled linked lists. An unrolled linked list stores multiple elements in each node. In each block, a circular linked list is used to connect all nodes. 10 list head block head, 36. Assume that there will be no more than n elements in the unrolled linked list at any time. To simplify this problem, all blocks except the last one should contain exactly elements. Thus, there will be no more than blocks at any time. Searching for an element in unrolled linked lists. In unrolled linked lists, we can find the KTH element in O. K1. Traverse the list of blocks to the one that contains the KTH node, that is the MCH block. It takes O since we may find it by going through no more than n blocks. 2. Find since there are no more than nodes in a single block. List head. Inserting an element in unrolled linked lists. List head. When inserting a node, we have to rearrange the nodes in the unrolled linked list to maintain the properties previously mentioned, that each block contains nodes. Suppose that we insert a node X after the ITH node, and X should be placed in the GTH block. Nodes in the GTH block and in the blocks after the GTH block have to be shifted toward the tail of the list so that each of them still have nodes. In addition, a new block needs to be added to the tail if the last block of the list is out of space, that is, it has more than nodes. Performing shift operation. Note that each shift operation, which includes removing a node from the tail of the circular linked list in a block and inserting a node to the head of the circular linked list in the block after, takes only O. The total time complexity of an insertion operation for unrolled linked lists is therefore O. There are at most O blocks and therefore at most O shift operations. 1. A temporary pointer is needed to store the tail of A. 2. In block A, move the next pointer of the head node to point to the second to last node so that the tail node of A can be removed. 3. Let the next pointer of the node which will be shifted point to the tail node of BA. 4. Let the next pointer of the head node of B point to the node temp points to. 5. Finally, set the head pointer of B to point to the node temp points to. Now the node temp points to becomes the new head node of B, 70. 6. Temp pointer can be thrown away. We have completed the shift operation to move the original tail node of A to become the new head node of B, performance. With unrolled linked lists, there are a couple of advantages, one in speed and one in space. First, if the number of elements in each block is appropriately sized, we get noticeably better cache performance from the improved memory locality. Second, since we have O-links, where n is the number of elements in the unrolled linked list and m is the number of elements we can store in any block, we can also save an appreciable amount of space, which is particularly noticeable if each element is small. Comparing linked lists and unrolled linked lists. To compare the overhead for an unrolled list, elements in doubly linked list implementations consist of data, a pointer to the next node, and a pointer to the previous node in the list, as shown below. Assuming we have 4 byte pointers, each node is going to take 8 bytes, but the allocation overhead for the node could be anywhere between 8 and 16 bytes. Let's go with the best case and assume it will be 8 bytes. So, if we want to store IK items in this list, we're going to have 16 kilobytes of overhead. Now let's think about an unrolled linked list node. It will look something like this. Therefore, allocating a single node with an array of 100 elements will now cost 428 bytes, or 4.28 bytes per element. Thinking about our IK items from above, it would take about 4.2 kilobytes of overhead, which is close to 4 times better than our original list. Even if the list becomes severely fragmented and the item arrays are only 1/2 full on average, this is still an improvement. Also, note that we can tune the array size to whatever gets us the best overhead for our application. Implementation. Hashtag include stdio.h. Hashtag include string.h. Hashtag include stdlib.h. Hashtag include math.h. Hashtag include time.h. Int block size. Max number of nodes in a block. Struct list node. Struct linked block. 1 struct linked block next. Struct list node head. In node count. Struct linked block block head. Create an empty block struct linked block new linked block. Struct linked block block malloc. Next null. Block head null. Block node count equal to 0. Return block. Create a node 1 struct list node new list node. pp. Next. F linked block equal to p. Find the node struct list node qp head. kk. Percent block size. If k block size kept node count plus 1. K well else ba minus next. Temp a minus head. Next a minus head. Next a minus head. Next. Temp next b head. Next b head. Next temp b minus head temp a minus node count. B minus node count plus AB, voided element else if, special case for K0. P blockhead head, QP next, P next new list node. Next equal to Q, blockhead head, P next, blockhead. Node count plus, shift blockhead, gels, circ element, QP, while QQ next, Q next new list node, Q next P, R node count plus, shift 1. Int circ element, struct list node P, struct link block Q, circ element, return P value. 1, int test unrolled linked list, int dt clock, int m, I, k, x, char cmd10 scam% d, and m block size plus 1. For scanf, fstrum 0 scanf, add element, else if 0 scanf, print %dn, crc element, gels, free printf 1, return 0. Return 0, crc element, true for representing abstract data types such as dictionaries and ordered lists. They work well when the elements are inserted in a random order. Some sequences of operations, such as inserting the elements in order, produce degenerate data structures that give very poor performance. If it were possible to randomly permute the list of items to be inserted, trees would work well with high probability for any input sequence. In most cases, queries must be answered online, so randomly permuting the input is impractical. Balanced tree algorithms rearrange the tree as operations are performed to maintain certain balance conditions and assure good performance. Skip lists are a probabilistic alternative to balanced trees. Skip list is a data structure that can be used as an alternative to balanced binary trees. As compared to a binary tree, skip lists allow quick search, insertion, and deletion of elements. This is achieved by using probabilistic balancing rather than strictly enforced balancing. It is basically a linked list with additional pointers such that intermediate nodes can be skipped. It uses a random number generator to make some decisions. In an ordinary sorted linked list, search, insert, and delete are a no, because the list must be scanned node by node from the head to find the relevant node. If somehow we could scan down the list in bigger steps, we would reduce the cost of scanning. This is the fundamental idea behind skip lists. Skip list with 1 level, skip list with 2 levels, skip list with 3 levels. Performance. In a simple linked list that consists of n elements, to perform a search, n comparisons are required in the worst case. N pointer pointing 2 nodes ahead is added to every node. The number of comparisons goes down to n2 plus 1 in the worst case. Adding one more pointer to every 4th node and making them point to the 4th node ahead reduces the number of comparisons to plus 2. If this strategy is continued, so that every node with I pointers points to 2i, 1 nodes ahead, O performance is obtained and the number of pointers is only doubled. The find, insert, and remove operations on ordinary binary search trees are efficient, O, when the input data is random, but less efficient, O, when the input data is ordered. Skip list performance for these same operations and for any dataset is about as good as that of randomly built binary search trees, namely O, comparing skip lists and unrolled linked lists. In simple terms, skip lists are sorted linked lists with 2 differences. The nodes in an ordinary list have 1 next reference. The nodes in a skip list have many next references. The number of forward references for a given node is determined probabilistically. We speak of a skip list node having levels, 1 level per forward reference. The number of levels in a node is called the size of the node. In an ordinary sorted list, insert, remove, and find operations require sequential traversal of the list. This results in O performance per operation. Skip lists allow intermediate nodes in the list to be skipped during a traversal, resulting in an expected performance of O per operation. Implementation. Hashtag include stdio.h. Hashtag include stdlib.h greater than hashtag define max skip level 5, struct list, node 1 for update list.header, list, less level, new level. Make new node if plus new level size off, 0, while list, header, and then temp, next data, temp, temp next, update daily, temp, temp, temp next, if return. Adjust next pointers for if next, temp, break, update, fill next till temp next. 1 free. Adjust header level while and equal to list.header, list.list level. Find node containing data struct list node find element if 0, insert element, for find element, for return 0. 1. 3.12 linked lists, problems and solutions. Problem -1 implement stack using linked list. Solution, refer to stacks chapter. Problem 2, find nth node from the end of a linked list. Solution, brute force method. Start with the first node and count the number of nodes present after that node. If the number of nodes is n1, then return saying fewer number of nodes in the list. If the number of nodes is n1, then go to next node. Continue this until the numbers of nodes after current node are n1. Time complexity O for scanning the remaining list for each node. Space complexity O. Problem -3. Can we improve the complexity of problem 2? Solution, yes, using hash table. As an example, consider the following list. Head. In this approach, create a hash table whose entries are position of node, node address. That means key is the position of the node in the list and value is the address of that node. By the time we traverse the complete list, we can find the list length. Let us say the list length is m. To find n from the end of linked list, we can convert this to mn plus first from the beginning. Since we already know the length of the list, it is just a matter of returning mn plus first key value from the hash table. Time complexity, time for creating the hash table, t equal to O. Space complexity, since we need to create a hash table of size mo. Problem -4. Can we use the problem 3 approach for solving problem 2 without creating the hash table? Solution, yes. If we observe the problem 3 solution, what we are actually doing is finding the size of the linked list. That means we are using the hash table to find the size of the linked list. We can find the length of the linked list just by starting at the head node and traversing the list. So we can find the length of the list without creating the hash table. After finding the length, compute mn plus 1, and with one more scan, we can get the mn plus first node from the beginning. This solution needs 2 scans, one for finding the length of the list and the other for finding mn plus first node from the beginning. Time complexity, time for finding the length plus time for finding the mn plus first node from the beginning. Therefore, t equal to O plus O approximately equal to O. Space complexity, O, hence no need to create the hash table. Problem -5. Can we solve problem 2 in one scan? Solution, yes. Efficient approach, use 2 pointers pnth node and ptemp. Initially, both point to head node of the list. Pnth node starts moving only after ptemp has made n moves. From there, both move forward until ptemp reaches the end of the list. As a result, pnth node points to nth node from the end of the linked list. Note, at any point of time, both move one node at a time. Struct list node, nth node from end, while if pnth node equal to head, else pnth node equal to pnth node, next ptemp equal to ptemp, next, if return pnth node, return null. Time complexity, O. Space complexity, O. Problem 6. Check whether the given linked list is either null terminated or ends in a cycle. Solution, brute force approach. As an example, consider the following linked list which has a loop in it. The difference between this list and the regular list is that in this list there are 2 nodes whose next pointers are the same. In regular singly linked lists, each node's next pointer is unique. That means the repetition of next pointers indicates the existence of a loop. One simple and brute force way of solving this is, start with the first node and see whether there is any node whose next pointer is the current node's address. If there is a node with the same address, then that indicates that some other node is pointing to the current node, and we can say a loop exists. Continue this process for all the nodes of the linked list. Does this method work? As per the algorithm, we are checking for the next pointer addresses, but how do we find the end of the linked list? Note, if we start with a node in a loop, this method may work depending on the size of the loop. Problem -7. Can we use the hashing technique for solving problem 6? Solution, yes. Using hash tables, we can solve this problem. Algorithm, traverse the linked list nodes one by one. Check if the address of the node is available in the hash table or not. If it is already available in the hash table, that indicates that we are visiting the node that was already visited. This is possible only if the given linked list has a loop in it. If the address of the node is not available in the hash table, insert that node's address into the hash table. Continue this process until we reach the end of the linked list or we find the loop. Time complexity, O for scanning the linked list. Note that we are doing a scan of only the input. Space complexity, O for hash table. Problem -8, can we solve problem 6 using the sorting technique? Solution, no. Consider the following algorithm, which is based on sorting. Then we see why this algorithm fails. Algorithm. Traverse the linked list nodes one by one and take all the next pointer values into an array. Sort the array that has the next node pointers. If there is a loop in the linked list, definitely two next node pointers will be pointing to the same node. After sorting, if there is a loop in the list, the nodes whose next pointers are the same will end up adjacent in the sorted list. If any such pair exists in the sorted list, then we say the linked list has a loop in it. Time complexity, O for sorting the next pointers array. Space complexity, O for the next pointers array. Problem with the above algorithm works only if we can find the length of the list. But if the list has a loop, then we may end up in an infinite loop. Due to this reason, the algorithm fails. Problem -9, can we solve the problem 6 in O? Solution, yes. Efficient approach. This problem was solved by Floyd. The solution is named the Floyd cycle finding algorithm. It uses two pointers moving at different speeds to walk the linked list. Once they enter the loop, they are expected to meet, which denotes that there is a loop. This works because a faster moving pointer would point to the same location as a slower moving pointer is if somehow the entire list or part of it is circular. Think of a tortoise and a hare running on a track. The faster running hare will catch up with the tortoise if they are running in a loop. As an example, consider the following example and trace out the Floyd algorithm. From the diagrams below, we can see that after the final step, they are meeting at some point in the loop, which may not be the starting point of the loop. Note, slope TR moves one pointer at a time, and fast PTR moves two pointers at a time. ENT does linked list has loop. Struct list node, slope TR equal to head, fast PTR equal to head, while slope TR sloped are next, fast PTR next, equal to if return 1, return 0. Time complexity, O, space complexity O. Problem -10 are given a pointer to the first element of a linked list, L. There are two possibilities for L. It either ends or its last element points back to one of the earlier elements in the list. Give an algorithm that tests whether a given list L is a snake or a snail. Solution, it is the same as problem -6. Problem 11, check whether the given linked list is null terminated or not. If there is a cycle, find the start node of the loop. Solution, the solution is an extension to the solution in problem 9. After finding the loop in the linked list, we initialize the slope PTR to the head of the linked list. From that point onwards, both slope TOR and fast PTR move only one node at a time. The point at which they meet is the start of the loop. Generally, we use this method for removing the loops. In find begin off loop, struct list node slope TR equal to head, fast PTR equal to head, int loop exists equal to 0, while equal to slope TR next, fast PTR next, if loop exists equal to 1, break if slope TR equal to head, while fast PTR next, slope TR next, return slope TR, return null. Time complexity, O, space complexity, O, problem -12. From the previous discussion and problems, we understand that the meeting of tortoise and hare concludes the existence of the loop, but how does moving the tortoise to the beginning of the linked list while keeping the hare at the meeting place, followed by moving both one step at a time, make them meet at the starting point of the cycle? Solution, this problem is at the heart of number theory. In the Floyd cycle finding algorithm, notice that the tortoise and the hare will meet when they are n times L, where L is the loop length. Furthermore, the tortoise is at the midpoint between the hare and the beginning of the sequence because of the way they move. Therefore, the tortoise is n times L away from the beginning of the sequence as well. If we move both one step at a time from the position of the tortoise and from the start of the sequence, we know that they will meet as soon as both are in the loop, since they are n times L, a multiple of the loop length, apart. One of them is already in the loop, so we just move the other one in single step until it enters the loop, keeping the other nxl away from it at all times. Problem -13, in the Floyd cycle finding algorithm, does it work if we use steps 2 and 3 instead of 1 and 2? Solution, yes, but the complexity might be high. Trace out an example. Problem -14, check whether the given linked list is null terminated. If there is a cycle, find the length of the loop. Solution, the solution is also an extension of the basic cycle detection problem. After finding the loop in the linked list, keep the slope TR as it is. The fast PTR keeps on moving until it again comes back to slope TR. While moving fast PTR, use a counter variable which increments at the rate of 1. In find loop length, fast PTR equal to fast per next counter plus plus, return counter, return 0, if no loops exists. Time complexity, O, space complexity. O, problem 15, insert a node in a sorted linked list. Solution, traverse the list and find a position for the element and insert it. Struct list node, inserting sorted list. Struct list node current equal to head, temp, if return new node. Traverse the list until you find item bigger, the new node value, while temp equal to current, current. Next, insert the new node before the big item new node. Next equal to current, temp next new node, return head. Time complexity, O, space complexity. O, problem -16 solution, reverse a singly linked list. Iterative version struct list node reverse list, struct list node temp equal to null. Next node equal to null, while next node equal to head next equal to temp equal to head equal to next node, return temp. Time complexity, O, space complexity. O, recursive version, we will find it easier to start from the bottom up by asking and answering tiny questions. What is the reverse of null? Null. What is the reverse of a one element list? The element itself. What is the reverse of an n element list? The reverse of the second element followed by the first element. Struct list node recursive reverse if return null. If return list, struct list node second lm equal to head. Next, need to unlink list from the rest or you will get a cycle head. Next equal to null. Reverse everything from the second element on struct list node reverse rest equal to recursive reverse. Then we join the two lists, second lm next. Head, return, reverse rest. Time complexity, O, space complexity, O for recursive stack. Problem -17. Suppose there are two singly linked lists, both of which intersect at some point and become a single linked list. The head or start pointers of both the lists are known, but the intersecting node is not known. Also, the number of nodes in each of the lists before they intersect is unknown and may be different in each list. List may have n nodes before it reaches the intersection point, and list might have m nodes before it reaches the intersection point, where m and n may be m equal to n, mn, or mn. Give an algorithm for finding the merging point. Solution, brute force approach. One easy solution is to compare every node pointer in the first list with every other node pointer in the second list, by which the matching node pointers will lead us to the intersecting node. But the time complexity in this case will be O, which will be high. Time complexity, O, space complexity, O. Problem 18, can we solve problem 17 using the sorting technique? Solution, no. Consider the following algorithm, which is based on sorting, and see why this algorithm fails. Algorithm. Take first list node pointers and keep them in some array and sort them. Take second list node pointers and keep them in some array and sort them. After sorting, use two indexes, one for the first sorted array and the other for the second sorted array. Start comparing values at the indexes and increment the index according to whichever has the lower value. At any point, if we are able to find two indexes whose values are the same, then that indicates that those two nodes are pointing to the same node, and we return that node. Time complexity, time for sorting lists plus time for scanning. Equal to O plus O plus O, we need to consider the one that gives the maximum value. Space complexity, O. Any problem with the above algorithm? Yes, in the algorithm, we are storing all the node pointers of both the lists and sorting, but we are forgetting the fact that there can be many repeated elements. This is because after the merging point, all node pointers are the same for both the lists. The algorithm works fine only in one case, and it is when both lists have the ending node at their merge point. Problem 19, can we solve problem 17 using hash tables? Solution, yes. Algorithm, select a list which has less number of nodes. Now, traverse the other list, and for each node pointer of this list, check whether the same node pointer exists in the hash table. If there is a merge point for the given lists, then we will definitely encounter the node pointer in the hash table. Time complexity, time for creating the hash table plus time for scanning the second list equal to O plus O plus O, depending on which list we select for creating the hash table, but in both cases the time complexity is the same. Space complexity, O or O. Problem 20, can we use stacks for solving the problem? 17, solution, yes, algorithm. Create two stacks, one for the first list and one for the second list. Traverse the first list and push all the node addresses onto the first stack. Traverse the second list and push all the node addresses onto the second stack. Now both stacks contain the node address of the corresponding lists. Now compare the top node address of both stacks. If they are the same, take the top elements from both the stacks and keep them in some temporary variable. Continue this process until the top node addresses of the stacks are not the same. This point is the one where the lists merge into a single list. Return the value of the temporary variable. Time complexity, O for scanning both the lists. Space complexity, O for creating two stacks for both the lists. Problem minus 21. Is there any other way of solving problem 17? Solution, yes. Using finding the first repeating number approach in an array. Algorithm, create an array A and keep all the next pointers of both the lists in the array. In the array, find the first repeating element. The first repeating number indicates the merging point of both the lists. Time complexity, O. Space complexity, O. Problem 22. Can we still think of finding an alternative solution for problem 17? Solution, yes. By combining sorting and search techniques, we can reduce the complexity. Algorithm, create an array A and keep all the next pointers of the first list in the array. Sort these array elements. Then, for each of the second list elements, search in the sorted array, let us assume that we are using binary search, which gives O. Since we are scanning the second list one by one, the first repeating element that appears in the array is nothing but the merging point. Time complexity, time for sorting plus time for searching equal to O. Space complexity, O. Problem minus 23. Can we improve the complexity for problem 17? Solution, yes. Efficient approach. Find lengths of both lists, O plus O equal to O. Take the difference D of the lengths, O. Make D steps in longer list, O. Step in both lists in parallel until links to next node match, O. Total time complexity equal to O. Space complexity equal to O. Struct list node find intersecting node while else, head list head equal to list diff, L1, L2. For head headle next, while if return headle, data, head headle next. Head next, return null. Problem minus 24. How will you find the middle of the linked list? Solution, brute force approach. For each of the node, count how many nodes are there in the, and see whether it is the middle node of the list. List. Time complexity, O. Space complexity, O. Problem minus 25. Can we improve the complexity of problem 24? Solution, yes. Algorithm. Traverse the list and find the length of the list. After finding the length, again scan the list and locate n/2 node from the beginning. Time complexity, time for finding the length of the list plus time for locating middle node equal to O plus O approximately equal to O. Space complexity, O. Problem 26. Can we use the hash table for solving problem 24? Solution, yes. The reasoning is the same as that of problem 3. Time complexity, time for creating the hash table. Therefore, T equal to O. Space complexity, O. Since we need to create a hash table of size n. Problem minus 27. Can we solve problem 24 just in one scan? Solution, efficient approach. Use two pointers. Move one pointer twice the speed of the second. When the first pointer reaches the end of the list, the second pointer will be pointing to the middle node. Note, if the list has an even number of nodes, the middle node will be of. Struct list node, find middle if return PTR. Now return the PTR, which points to the middle node. Time complexity, O. Space complexity, O. Problem 28. How will you display a linked list from the end? Solution, traverse recursively till the end of the linked list. While coming back, start printing the elements. This function will print the linked list from end void print list from end. If return, print list from end, printf. Time complexity, O. Space complexity, O for stack. Problem minus 29. Check whether the given linked list length is even or odd. Solution, use a 2 times pointer. Take a pointer that moves it 2 times. At the end, if the length is even, then the pointer will be null, otherwise it will point to the last node. Int is linked list length, even, while list head next. Next, if return 0, return 1. Time complexity O approximately equal to O. Space complexity, O. Problem minus 30. Linked list is pointing to kth element, then how will you get the elements before kth element? Solution, use memory efficient linked lists. Problem minus 31 order, given 2 sorted linked lists, how to merge them into the third list in sorted. Solution, assume the sizes of lists are m and n. Recursive, struct list node merge sorted list, struct list node result equal to null, if return b, if return a, if, result equal to a, result. Next merge sorted list, else, result equal to b, result, next equal to merge sorted list, return result. Time complexity, O, where n and m are lengths of 2 lists. Iterative, struct list node merge sorted list iterative, struct list node temp, new node equal to new node, next equal to null, temp equal to new node, while else, temp equal to temp, next, head equal to headle, next, temp, next equal to head temp equal to temp, next, head next, if temp next equal to head else temp, next equal to head temp equal to new node, next, free, return temp. Time complexity, O, where n and m are lengths of 2 lists. Problem minus 32, reverse the linked list in pairs. If you have a linked list that holds 1, 2, 3, 4x, then after the function has been called, the linked list would hold 2, 1, 4, 3, 10 solution, recursive. Struct list node reverse pair recursive, struct list node temp, if else return. Base case for empty or one element list. Reverse first pair temp equal to head next, temp next equal to head equal to temp. Call the method recursively for the rest of the list. Head next next equal to reverse pair recursive, return head. Iterative, struct list node reverse pair iterative temple next next, current next, temple equal to current next next, temple dot next equal to current if temp equal to temp current. Next, return temp. Time complexity, O. Space complexity, O. Problem -33 given a binary tree, convert it to doubly linked list. Solution, refer trees chapter. Problem 34. How do we sort the linked lists? Solution, refer sorting chapter. Problem 35. Split a circular linked list into 2 equal parts. If the number of nodes in the list are odd, then make first list 1 node extra than second list. Solution, algorithm. Store the mid and last pointers of the circular linked list using Floyd cycle finding algorithm. Make the second half circular, make the first half circular. Set head pointers of the 2 linked lists. As an example, consider the following circular list. Head. After the split, the above list will look like headle. Structure for a node struct list node, B int data, struct list node next, void split list, 1 struct list node slope tr equal to head, struct list node fast ptr equal to head if return. If there are odd nodes in the circular list, then fast ptr next becomes head, and for even nodes, fast ptr next becomes head. While fast ptr next equal to slope tr next. If there are even elements in list, then move fast ptr if fast ptr next. Set the head pointer of first half head equal to head. Set the head pointer of second half if head equal to slope tr next. Make second half circular. Fast ptr next slope tr next. Make first half circular slope tr next equal to head. Time complexity, O. Space complexity, O. Problem 36. If we want to concatenate 2 linked lists, which of the following gives O complexity? 1. Singly linked lists. 2. Doubly linked lists. 3. Circular doubly linked lists. Solution, circular doubly linked lists. This is because for singly and doubly linked lists, we need to traverse the first list till the end and append the second list. But in the case of circular, doubly linked lists, we don't have to traverse the lists. Problem, -37. How will you check if the linked list is palindrome or not? Solution, algorithm. 1. Get the middle of the linked list. 2. Reverse the second half of the linked list. 3. Compare the first half and second half. 4. Construct the original linked list by reversing the second half again and attaching it back to the first half. Time complexity, O. Space complexity, O. Problem -38 for a given k value, reverse blocks of k nodes in a list. Example. Input, 12,345,678,910. Output for different k values. For k equal to 2, 21,436,587,109. Equal to for k3, 321,654,987.10. For k4, 432,187,387.10. Solution of swapping nodes in a linked list. 1. Check if remaining list has k nodes. B. If yes, get the pointer of k plus first node. 2. Reverse first k nodes. 3. Set next of last node to k plus first node. 4. Move to k plus first node. 5. Go to step 1. 6. K. First node of first k nodes becomes the new head if available. Otherwise, we can return the head. Else return. Struct list node get k plus node, struct list node kth int I equal to 0 if return head. 4. I plus plus kth. Next, if return kth, return head. Next, int has nodes, int I equal to 0, equal to 4 I plus plus head. Next, if return 1, return 0. Struct list node reverse block of k nodes in linked list. Struct list node cur head. Temp. Next, new head, int I if return head. If, else new head get k plus 1 to node. New head equal to head, while temp equal to get k plus 1 to node. I equal to 0, while next cur. Next equal to temp equal to cur equal to next I plus plus, return new head. Problem -39. Is it possible to get O access time for linked lists? Solution, yes. Create a linked list and at the same time keep it in a hash table. For n elements, we have to keep all the elements in a hash table, which gives a preprocessing time of O. To read any element, we require only constant time O, and to read n elements, we require n 1 unit of time equal to n units. Hence, by using amortized analysis, we can say that element access can be performed within O time. Time complexity, O. Space complexity, O for hash table. Problem -40, Josephus circle. N people have decided to elect a leader by arranging themselves in a circle and eliminating every MTH person around the circle, closing ranks as each person drops out. Find which person will be the last one remaining. Solution. Assume the input is a circular linked list with n nodes and each node has a number associated with it. The head node has number 1 as data. Struct list node get Josephus position p next equal to q. Eliminate every mth player as long as more than one player remains. 4 for p equal to p next. Next, remove the eliminated player from the circular linked list. Print tf is %d n p data. Problem -41 given a linked list consists of data, a next pointer, and also a random pointer which points to a random node of the list. Give an algorithm for cloning the list. Solution. We can use a hash table to associate newly created nodes with the instances of node in the given list. Algorithm. Scan the original list, and for each node x, create a new node y with data of x, then store the pair in hash table using x as a key. Note that during the scan set y next and y, random to null, and we will fix them in the next scan. Now for each node x in the original list, we have a copy y stored in our hash table. We scan the original list again and set the pointers building the new list. Struct list node clone, while y malloc, y data equal to x data, y next equal to null, y random equal to null, hd.insert, x equal to x next, x equal to head, while get the node y corresponding to x from the hash table, y equal to ht.get, y next equal to ht.get, y to random ht.get, x next, return the head of the new list, that is the node y return ht.get. Time complexity, O. Space complexity, O. Problem -42. Can we solve problem 41 without any extra space? Solution, yes. Void clone while temp equal to malloc, temp data, temp random equal to temp equal to temp next. Step setting temp next is the old copy of the node that temp should point to, so temp next random is the new copy. Temp equal to head, while temp equal to temp random, temp next random, temp equal to temp next. Step repair damage to old list and fill in next pointer in new list. Temp equal to head, while temp equal to temp random, temp next, temp next, random, temp equal to temp next. Time complexity, O approximately equal to O. Space complexity, O. Problem -43. We are given a pointer to a node in a singly linked list. Delete that node from the linked list. Solution: to delete a node, we have to adjust the next pointer of the previous node to point to the next node instead of the current one. Since we don't have a pointer to the previous node, we can't redirect its next pointer. So what do? We can easily get away by moving the data from the next node into the current node and then deleting the next node. Void delete anodyne linked list. Struct list node temp equal to node next node data equal to node next data node next equal to temp next free. Time complexity O. Space complexity O. Problem -44. Given a linked list with even and odd numbers, create an algorithm for making changes to the list in such a way that all even numbers appear at the beginning. Solution: to solve this problem, we can use the splitting logic. While traversing the list, split the linked list into two. One contains all even nodes and the other contains all odd nodes. Now, to get the final list, we can simply append the odd node linked list after the even node linked list. To split the linked list, traverse the original linked list and move all odd nodes to a separate linked list of all odd nodes. At the end of the loop, the original list will have all the even nodes and the odd node list will have all the odd nodes. To keep the ordering of all nodes the same, we must insert all the odd nodes at the end of the odd node list. Time complexity O. Space complexity O. Problem -45. In a linked list with n nodes, the time taken to insert an element after an element pointed by some pointer is O. Solution: A. Problem -46. Find modular node given a singly linked list. Write a function to find the last element from the beginning whose n%k equal to 0, where n is the number of elements in the list and k is an integer constant. For example, if n equal to 19 and k equal to 3, then we should return 18th node. Solution: for this problem, the value of n is not known in advance. Struct list node modular double from Bagan ITT. Return modular node. Time complexity O. Space complexity O. Problem -47. Find modular node from the end given a singly linked list. Write a function to find the first from the end whose n%k equal to 0, where n is the number of elements in the list and k is an integer constant. If n equal to 19 and k equal to 3, then we should return 16th node. Solution: for this problem, the value of n is not known in advance, and it is the same as finding the kth element from the end of the linked list. Struct list node modular node friend return null for if else head next, return null, while modular node next head equal to head, next return modular node. Time complexity O. Space complexity O. Problem 48. Nk. Find fractional node given a singly linked list. Write a function to find the th element, where n is the number of elements in the list. Solution: for this problem, the value of n is not known in advance. Struct list node fractional nodes return null for if ITT, if fractional node equal to head, else fractional node equal to fractional node next return fractional node, int I equal to 0 if return null, for if I plus plus, fractional node equal to head, else fractional node equal to fractional node. Next return fractional node. Time complexity O. Space complexity O. Problem -49. Fifth, find node given a singly linked list. Write a function to find the n element, where n is the number of elements in the list. Assume the value of n is not known in advance. Solution: for this problem, the value of n is not known in advance. Struct list node sqrt node else sqrtn equal to sqrtn. Next j++ I++ return sqrtn. Time complexity O. Space complexity O. Problem 50. Given two lists, list 1 equal to with data in ascending order. Merge them into the third list in ascending order so that the merged list will be if n greater than equal to m, if m greater than equal to n. Solution: struct list node alternate merge. Struct list node new node equal to struct list node temp, new node next null temp equal to new node, while temp next equal to list temp equal to temp, next list equal to list next, temp next equal to list equal to list next, temp equal to temp next, if temp next equal to list else temp, next equal to list temp equal to new node, next free return temp. Time complexity. The while loop takes O time as it will run for min times. The other steps run in O. Therefore, the total time complexity is O. Space complexity O. Problem -51. Median in an infinite series of integers. Solution: median is the middle number in a sorted list of numbers. If we have an even number of elements, the median is the average of two middle numbers in a sorted list of numbers. We can solve this problem with linked lists. First, let us try with an unsorted linked list. In an unsorted linked list, we can insert the element either at the head or at the tail. The disadvantage with this approach is that finding the median takes O. Also, the insertion operation takes O. Now, let us try with a sorted linked list. We can find the median in O time if we keep track of the middle elements. Insertion to a particular location is also O in any linked list, but finding the right location to insert is not O as in a sorted array. It is instead O because we can't perform binary search in a linked list even if it is sorted. So, using a sorted linked list isn't worth the effort as insertion is O and finding median is O, the same as the sorted array. In the sorted array, the insertion is linear due to shifting, but here it's linear because we can't do a binary search in a linked list. Note: for an efficient algorithm, refer to the priority queues in Heaps chapter. Problem -52. Given a linked list, how do you modify it such that all the even numbers appear before all the odd numbers in the modified linked list? Solution: struct list node exchange even odd list else. Inserting the node at the end of linked list even list end, next equal to ITR, even list end equal to ITR, else if first odd node odd list end equal to ITR else. Inserting the node at the end of linked list odd list end, next equal to ITR, odd list end equal to ITR, one iterator, next even list end, next equal to odd list return head. Time complexity O. Space complexity O. Problem -53. Given two linked lists, each list node with one integer digit, add these two linked lists. The result should be stored in the third linked list. Also note that the head node contains the most significant digit of the number. Solution: since the integer addition starts from the least significant digit, we first need to visit the last node of both lists and add them up, create a new node to store the result, take care of the carry if any, and link the resulting node to the node which will be added to the second least significant node and continue. First of all, we need to take into account the difference in the number of digits in the two numbers. So before starting recursion, we need to do some calculation and move the longer list pointer to the appropriate place so that we need the last node of both lists at the same time. The other thing we need to take care of is carry. If two digits add up to more than 10, we need to forward the carry to the next node and add it. If the most significant digit addition results in a carry, we need to create an extra node to store the carry. The function below is actually a wrapper function, which does all the housekeeping like calculating lengths of lists, calling recursive implementation, creating an extra node for the carry in the most significant digit, and adding any remaining nodes left in the longer list. Void add list numbers wrapper, int list length 0, list 0, diff 0, 1, struct list node current, list while, sum equal to list, data plus list plus, store carry sum, 10. Sum %10, temp data equal to sum, temp next, result temp, return, void add remaining numbers, in sum equal to 0, if or a diff equal to 0, return, Add remaining numbers, struct list node temp equal to malloc, sum list 1 data plus, carry sum, 10, sum %10, temp data equal to sum temp next, result equal to temp, return. Time complexity, O, space complexity O for recursive stack. Note, it can also be solved using stacks. Problem -54, which sorting algorithm is easily adaptable to singly linked lists? Solution, simple insertion sort is easily adaptable to singly linked lists. To insert an element, the linked list is traversed until the proper position is found, or until the end of the list is reached. It is inserted into the list by merely adjusting the pointers without shifting any elements, unlike in the array. This reduces the time required for insertion, but not the time required for searching for the proper position. Problem 55, given a list equal to without using any extra space, n1, and with data reorder it to a 1. Solution, find the middle of the linked list. We can do it by slow and fast pointer approach. After finding the middle node, we reverse the right halfle, then we do a in-place merge of the two halves of the linked list. Problem 56, given two sorted linked lists, given an algorithm for the printing common elements of them. Solution, the solution is based on merge sort logic. Assume the given two linked lists are list and list. Since the elements are in sorted order, we run a loop till we reach the end of either of the list. We compare the values of list and list. If the values are equal, we add it to the common list. We move list, both nodes ahead to the next pointer if the values pointed by list was less more, equal to the value pointed by list. Time complexity O, where m is the length of list and n is the length of list. Space complexity O, struct list node common element, else if else. List data list equal to list next, 1 return temp next. 4.1. What is a stack? A stack is a simple data structure used for storing data. In a stack, the order in which the data arrives is important. A pile of plates in a cafeteria is a good example of a stack. The plates are added to the stack as they are cleaned, and they're placed on the top. When a plate is required, it is taken from the top of the stack. The first plate placed on the stack is the last one to be used. Definition: a stack is an ordered list in which insertion and deletion are done at one end, called top. The last element inserted is the first one to be deleted. Hence, it is called the last in, first out, or first in, last out list. Special names are given to the two changes that can be made to a stack. When an element is inserted in a stack, the concept is called push, and when an element is removed from the stack, the concept is called pop. Trying to pop out an empty stack is called underflow, and trying to push an element in a full stack is called overflow. Generally, we treat them as exceptions. As an example, consider the snapshots of the stack. 4.2, how stacks are used. Consider a working day in the office. Let us assume a developer is working on a long-term project. The manager then gives the developer a new task, which is more important. The developer puts the long-term project aside and begins work on the new task. The phone rings, and this is the highest priority as it must be answered immediately. The developer pushes the present task into the pending tray and answers the phone. When the call is complete, the task that was abandoned to answer, the phone is retrieved from the pending tray and work progresses. To take another call, it may have to be handled in the same manner, but eventually the new task will be finished, and the developer can draw the long-term project from the pending tray and continue with that. 4.3 Stack ADT. The following operations make a stack an ADT. For simplicity, assume the data is an integer type. Main stack operations: push, inserts data onto stack. Int pop, removes and returns the last inserted element from the stack. Auxiliary stack operations: int top, returns the last inserted element without removing it. Int size, returns the number of elements stored in the stack. Int is empty stack, indicates whether any elements are stored in the stack or not. Int is full stack, indicates whether the stack is full or not. Exceptions. Attempting the execution of an operation may sometimes cause an error condition, called an exception. Exceptions are said to be thrown by an operation that cannot be executed. In the stack ADT, operations pop and top cannot be performed if the stack is empty. Attempting the execution of pop on an empty stack throws an exception. Trying to push an element in a full stack throws an exception. 4.4 Applications. Following are some of the applications in which stacks play an important role. Direct applications: balancing of symbols, infix to postfix conversion, evaluation of postfix expression, implementing function calls, finding of spans, page visited history in a web browser, undo sequence in a text editor, matching tags in HTML and XML, indirect applications, auxiliary data structure for other algorithms, component of other data structures. 4.5 Implementation. There are many ways of implementing stack ADT. Below are the commonly used methods: simple array-based implementation, dynamic array-based implementation, linked lists implementation, simple array implementation. This implementation of stack ADT uses an array. In the array, we add elements from left to right and use a variable to keep track of the index of the top element. S. The array storing the stack elements may become full. A push operation will then throw a full stack exception. Similarly, if we try deleting an element from an empty stack, it will throw stack empty exception. 1 struct array stack if free. Hashtag define max size 10. Performance and limitations. Performance, let n be the number of elements in the stack. The complexities of stack operations with this representation can be given as limitations. The maximum size of the stack must first be defined, and it cannot be changed. Trying to push a new element into a full stack causes an implementation-specific exception. Dynamic array implementation. First, let's consider how we implemented a simple array-based stack. We took one index variable top, which points to the index of the most recently inserted element in the stack. To insert an element, we increment top index and then place the new element at that index. Similarly, to delete an element, we take the element at top index and then decrement the top index. We represent an empty queue with top value equal to -1. The issue that still needs to be resolved is what we do when all the slots in the fixed size array stack are occupied. First try, what if we increment the size of the array by 1 every time the stack is full? Push, increase size of s by 1. Pop, decrease size of s by 1. Problems with this approach? This way of incrementing the array size is too expensive. Let us see the reason for this. For example, at n equal to 1. To push an element, create a new array of size 2 and copy all the old array elements to the new array, and at the end add the new element. At n equal to 2, to push an element, create a new array of size 3 and copy all the old array elements to the new array, and at the end add the new element. Similarly, at n equal to n1, if we want to push an element, create a new array of size n and copy all the old array elements to the new array, and at the end add the new element. After n push operations, the total time t is proportional to 1 plus 2 plus and approximately equal to O. Alternative approach: repeated doubling. Let us improve the complexity by using the array doubling technique. If the array is full, create a new array of twice the size and copy the items. With this approach, pushing n items takes time proportional to n. For simplicity, let us assume that initially we started with n equal to 1 and moved up to n equal to 32. That means we do the doubling at 124,816. The other way of analyzing the same approach is, at n equal to 1, if we want to add an element, double the current size of the array and copy all the elements of the old array to the new array. At n equal to 1, we do 1 copy operation. At n equal to 2, we do 2 copy operations. And at n equal to 4, we do 4 copy operations, and so on. By the time we reach n equal to 32, the total number of copy operations is 1 plus 2 plus 4 plus 8 plus 16 equal to 31, which is approximately equal to 2n value. If we observe carefully, we are doing the doubling operation ln times. Now, let us generalize the discussion. For n push operations, we double the array size ln times. That means we will have ln terms in the expression below. The total time t of a series of n push operations is proportional to t is O, and the amortized time of a push operation is O. Struct dyn array stack 1 int top int capacity int array struct dyn array stack create stack struct dyn array stack s equal to malloc if return null, s capacity equal to 1, s top equal to -1, s array malloc, allocate an array of size 1 initially if return null, return s int is full stack if return int min, return s array, void delete stack if free. Performance, let n be the number of elements in the stack. The complexities for operations with this representation can be given as, note, too many doublings may cause memory overflow exception. Top, linked list implementation. The other way of implementing stacks is by using linked lists. Push operation is implemented by inserting element at the beginning of the list. Pop operation is implemented by deleting the node from the beginning. 1111 in data struct list node next, struct stack create stack free, struct list node, performance. Let n be the number of elements in the stack. The complexities for operations with this representation can be given as 4.6% comparison of implementations, comparing incremental strategy and doubling strategy. We compare the incremental strategy and doubling strategy by analyzing the total time t needed to perform a series of n push operations. We start with an empty stack represented by an array of size 1. We call amortized time of a push operation is the average time taken by a push over the series of operations, that is tn. Incremental strategy. The amortized time of a push operation is O. Doubling strategy. In this method, the amortized time of a push operation is O. Note, for analysis, refer to the implementation section. Comparing array implementation and linked list implementation. Array implementation. Operations take constant time. Expensive doubling operation every once in a while. Any sequence of n operations amortized bound takes time proportional to n. Linked list implementation. Grows and shrinks gracefully. Every operation takes constant time O. Every operation uses extra space and time to deal with references. 4.7 Stacks, problems and solutions. Problem -1, discuss how stacks can be used for checking balancing of symbols. Solution, stacks can be used to check whether the given expression has balanced symbols. This algorithm is very useful in compilers. Each time the parser reads one character at a time. If the character is an opening delimiter, such as the stack is popped, the opening and closing delimiters are then compared. If they match, the parsing of the string continues. If they do not match, the parser indicates that there is an error on the line. A linear time O algorithm based on stack can be given as algorithm. A, create a stack. While 1, if the character read is not a symbol to be balanced, ignore it. 2, if the character is an opening symbol like push it onto the stack. 3, if it is a closing symbol like, then if the stack is empty, report an error. Otherwise, pop the stack. 4, if the symbol popped is not the corresponding opening symbol, report an error. C, at end of input, if the stack is not empty, report an error. Examples. For tracing the algorithm, let us assume that the input is time complexity, O. Since we are scanning the input only once. Space complexity, O. Problem -2, discuss infix to postfix conversion algorithm using stack. Solution, before discussing the algorithm, first let us see the definitions of infix, prefix, and postfix expressions. Infix, an infix expression is a single letter, or an operator, preceded by one infix string and followed by another infix string. Prefix, a prefix expression is a single letter, or an operator, followed by two prefix strings. Every prefix string longer than a single variable contains an operator, first operand and second operand. Postfix, a postfix expression is a single letter or an operator, preceded by two postfix strings. Every postfix string longer than a single variable contains first and second operands followed by an operator, AB plus AB plus CD plus. Prefix and postfix notions are methods of writing mathematical expressions without parenthesis. Time to evaluate a postfix and prefix expression is O, where n is the number of elements in the array. Unless we use parentheses. Therefore, for the infix to postfix conversion algorithm, we have to define the operator precedence inside the algorithm. The table shows the precedence and their associativity among operators. Important properties. Let us consider the infix expression 2 plus 3 times 4 and its postfix equivalent 234 plus. Notice that between infix and postfix, the order of the numbers is unchanged. It is 234 in both cases, but the order of the operators and plus is affected in the two expressions. Only one stack is enough to convert an infix expression to postfix expression. The stack that we use in the algorithm will be used to change the order of operators from infix to postfix. The stack we use will only contain operators and the open parentheses symbol. Postfix expressions do not contain parentheses. We shall not output the parentheses in the postfix output. Algorithm. A, create a stack. B, for each character T in the input stream. If, output T, else if, pop and output tokens until left parenthesis is popped. Else, T is an operator or left parenthesis. Pop and output tokens until one of lower priority than T is encountered or a left parenthesis is encountered or the stack is empty. Push TC, pop and output tokens until the stack is empty. For better understanding, let us trace out an example. A B minus plus E. Problem -3, discuss postfix evaluation using stacks. Solution, algorithm. 1, scan the postfix string from left to right. 2, initialize an empty stack. 3, repeat steps 4 and 5 till all the characters are scanned. 4, if the scanned character is an operand, push it onto the stack. 5, if the scanned character is an operator, and if the operator is a unary operator, then pop an element from the stack. If the operator is a binary operator, then pop 2 elements from the stack. After popping the elements, apply the operator to those popped elements. Let the result of this operation be retvol onto the stack. 6, after all characters are scanned, we will have only one element in the stack. 7, return top of the stack as result. Example, let us see how the above-mentioned algorithm works using an example. Assume that the postfix string is 123 plus 5. Initially, the stack is empty. Now, the first 3 characters scanned are 1, 2, and 3, which are operands. They will be pushed into the stack in that order. Expression, stack. The next character scanned is, which is an operator. Thus, we pop the top 2 elements from the stack and perform the operation with the 2 operands. The second operand will be the first element that is popped. 2 times 3 equal to 6 expression. Stack. The value of the expression that has been evaluated is pushed into the stack. Expression, stack. The next character scanned is plus, which is an operator. Thus, we pop the top 2 elements from the stack and perform the plus operation with the 2 operands. The second operand will be the first element that is popped. 1 plus 6 equal to 7 expression. Stack. The value of the expression that has been evaluated is pushed into the stack expression. The next character scanned is 5, which is added to the stack expression. The next character scanned is, which is an operator. Thus, we pop the top 2 elements from the stack and perform the operation with the 2 operands. The second operand will be the first element that is popped. Expression, stack. The value of the expression that has been evaluated is pushed into the stack expression. Now, since all the characters are scanned, the remaining element in the stack will be returned. End result, postfix string 123 plus 5, result 2. Problem -4. Can we evaluate the infix expression with stacks in one pass? Solution, using 2 stacks, we can evaluate an infix expression in one pass without converting to postfix. Algorithm, 1. Create an empty operator stack. 2. Create an empty operand stack. 3. For each token in the input string, A. Get the next token in the infix string. B. If next token is an operand, place it on the operand stack. C. If next token is an operator. I. Evaluate the operator. 4. While operator stack is not empty, pop operator and operands, evaluate left operator right, and push result onto operand stack. 5. Pop result from operator stack. Problem -5. How to design a stack such that get minimum should be O. Solution, take an auxiliary stack that maintains the minimum of all values in the stack. Also, assume that each element of the stack is less than its below elements. For simplicity, let us call the auxiliary stack min stack. When we pop the main stack, pop the min stack too. When we push the main stack, push either the new element or the current minimum, whichever is lower. At any point, if we want to get the minimum, then we just need to return the top element from the min stack. Let us take an example and trace it out. Initially, let us assume that we have pushed 2, 6, 4, 1, and 5. Based on the above-mentioned algorithm, the min stack will look like. After popping twice, we get. Based on the discussion above, now let us code the push, pop, and get minimum operations. Struct advanced stack in temp if return -1, temp pop pop, return temp, int get minimum, return top, struct advanced stack create advanced stack, struct advanced stack s equal to malloc if return null, s element stack, create stack equal to s min stack create stack, return s. Time complexity, O, space complexity, O. This algorithm has much better space usage if we rarely get a new minimum or equal. Problem -6 for problem 5. Is it possible to improve the space complexity? Solution, yes. The main problem of the previous approach is, for each push operation, we are pushing the element onto min stack also. That means we are pushing the duplicate minimum elements onto the stack. Now, let us change the algorithm to improve the space complexity. We still have the min stack, but we only pop from it when the value we pop from the main stack is equal to the one on the min stack. We only push to the min stack when the value being pushed onto the main stack is less than or equal to the current min value. In this modified algorithm also, if we want to get the minimum, then we just need to return the top element from the min stack. For example, taking the original version and pushing 1 again, we get popping from the above pops from both stacks because 1 equal to 1, leaving. Popping again only pops from the main stack because 5 greater than 1. Popping again pops both stacks because 1 equal to 1. Note, the difference is only in push and pop operations. Struct advanced stack in temp if return -1 equal to temp top if pop pop return temp, in get minimum return top, struct advanced stack, struct advanced stack s equal to malloc if return null, s element stack create stack, s min stack create stack, return s. Time complexity, O, space complexity, O. But this algorithm has much better space usage if we rarely get a new minimum or equal. Problem -7 for a given array with n symbols. How many stack permutations are possible? Solution, the number of stack permutations with n symbols is represented by Catalan number, and we will discuss this in the dynamic programming chapter. Problem -8, given an array of characters formed with A's and B's. The string is marked with special character X, which represents the middle of the list. Check whether the string is palindrome. Solution, this is one of the simplest algorithms. What we do is start 2 indexes, one at the beginning of the string and the other at the end of the string. Each time compare whether the values at both the indexes are the same or not. If the values are not the same, then we say that the given string is not a palindrome. If the values are the same, then increment the left index and decrement the right index. Continue this process until both the indexes meet at the middle, or if the string is not palindrome. Int is palindrome. 1 int I equal to 0, j equal to strlen -1, while equal to a, I plus plus, j if printf return 0, else printf return 1. Time complexity, O. Space complexity, O. Problem -9 for problem 8. If the input is in singly linked list, then how do we check whether the list elements form a palindrome? Solution, refer linked list chapter. Problem 10, can we solve? Problem 8 using stacks? Solution, yes. Algorithm. Traverse the list till we encounter X as input element. During the traversal, push all the elements onto the stack. For the second half of the list, compare each element's content with top of the stack. If they are the same, then pop the stack and go to the next element in the input list. If they are not the same, then the given string is not a palindrome. Continue this process until the stack is empty or the string is not a palindrome. Int is palindrome return is empty stack. Time complexity, O. Space complexity, O approximately equal to O. Problem 11. Given a stack, how to reverse the elements of the stack using only stack operations. Solution. Algorithm. First, pop all the elements of the stack till it becomes empty. For each upward step in recursion, insert the element at the bottom of the stack. Void reverse stack int data if return data equal to pop reverse stack insert at bottom void insert at bottom int temp if push return temp equal to pop insert at bottom push. Time complexity, O. Space complexity, O for recursive stack. Problem 12. Show how to implement one queue efficiently using 2 stacks. Analyze the running time of the queue operations. Solution. Refer queues chapter. Problem -13. Show how to implement one stack efficiently using 2 queues. Analyze the running time of the stack operations. Solution. Refer queues chapter. Problem 14. How do we implement 2 stacks using only one array? Our stack routines should not indicate an exception unless every slot in the array is used. Solution. Algorithm. Start 2 indexes, one at the left end and the other at the right end. The left index simulates the first stack and the right index simulates the second stack. If we want to push an element into the first stack, then put the element at the left index. Similarly, if we want to push an element into the second stack, then put the element at the right index. The first stack grows towards the right and the second stack grows towards the left. Time complexity of push and pop for both stacks is O. Space complexity is O. Problem -15. 3 stacks in one array. How to implement 3 stacks in one array. Solution. For this problem, there could be other ways of solving it. Given below is one possibility and it works as long as there is an empty space in the array. To implement 3 stacks, we keep the following information. The index of the first stack, this indicates the size of the first stack. The index of the second stack, this indicates the size of the second stack. Starting index of the third stack, top index of the third stack. Now, let us define the push and pop operations for this implementation. Pushing. For pushing onto the first stack, we need to see if adding a new element causes it to bump into the third stack. If so, try to shift the third stack upwards. Insert the new element at. For pushing to the second stack, we need to see if adding a new element causes it to bump into the third stack. If so, try to shift the third stack downward. Insert the new element at. When pushing to the third stack, see if it bumps into the second stack. If so, try to shift the third stack downward and try pushing again. Insert the new element at. Time complexity O. Since we may need to adjust the third stack, space complexity O. Popping for popping, we don't need to shift, just decrement the size of the appropriate stack. Time complexity O. Space complexity O. Problem -16 for problem 15. Is there any other way implementing the middle stack? Solution, yes. When either the left stack or the right stack bumps into the middle stack, we need to shift the entire middle stack to make room. The same happens if a push on the middle stack causes it to bump into the right stack. To solve the above-mentioned problem, what we can do is alternating pushes can be added at alternating sides of the middle list. This would keep the middle stack balanced in the center of the array, but it would still need to be shifted when it bumps into the left or right stack, whether by growing on its own or by the growth of a neighboring stack. We can optimize the initial locations of the three stacks if they grow shrink at different rates and if they have different average sizes. For example, suppose one stack doesn't change much. If we put it at the left, then the middle stack will eventually get pushed against it and leave a gap between the middle and right stacks, which grow toward each other. If they collide, then it's likely we've run out of space in the array. There is no change in the time complexity, but the average number of shifts will get reduced. Problem -17 multiple stacks in one array, similar to problem 15. What if we want to implement m stacks in one array? Solution. Let us assume that array indexes are from 1 to n. Similar to the discussion in problem to implement m stacks in one array, we divide the array into m parts. The size of each part is nm. From the above representation, we can see that first stack is starting at index 1, starting index is stored in base, second stack is starting at index, third 2 and an m stack is starting at index, and so on. Similar to base array, m let us assume that top array stores the top indexes for each of the stack. Consider the following terminology for the discussion. Top for 1 less than or equal to less than or equal tom will point to the topmost element of the stack. If base equal to top, then we can say the stack I is empty. I. If top equal to base, then we can say the stack I is full. N initially base equal to top or equal to for 1 less than or equal to I less than or equal tom. M. The ith stack grows from base plus 1 to base. Pushing on to ith stack 1. For pushing on to the ith stack, we check whether the top of ith stack is pointing to base. That means we need to see if adding a new element causes it to bump into the I plus first stack. If so, try to shift the stacks from I plus first stack to mth stack toward the right. Insert the new element at plus top. 2. If right shifting is not possible, then try shifting the stacks from 1 to I, first stack toward the left. 3. If both of them are not possible, then we can say that all stacks are full. Void push. If equal to base, print ith stack is full and does the necessary action, top equal to top plus 1, A equal to data. Time complexity, O. Since we may need to adjust the stacks, space complexity, O. Popping from I each stack. For popping, we don't need to shift, just decrement the size of the appropriate stack. The only case to check is stack empty case. Int pop, if equal to base, print if stack is empty, return A. Time complexity, O. Space complexity, O. Problem -18. Consider an empty stack of integers. Let the numbers 1, 2, 3, 4, 5, 6 be pushed onto this stack in the order they appear from left to right. Let 5 indicate a push and x indicate a pop operation. Can they be permuted into the order 325,641st and order 154,643rd? Solution, SSSXXXXXX outputs 325,641. 154,623 cannot be output, as 2 is pushed much before 1,641. Problem 19. Earlier in this chapter, we discussed that for dynamic array implementation of stacks, the repeated doubling approach is used. For the same problem, what is the complexity if we create a new array whose size is n plus if instead of doubling? Solution, let us assume that the initial stack size is 0. For simplicity, let us assume that k equal to 10. For inserting the element, we create a new array whose size is 0 plus 10 equal to 10. Similarly, after 10 elements, we again create a new array whose size is 10 plus 10 equal to 20, and this process continues at values 30,040. That means, for a given n value, we are creating the new arrays at the total number of copy operations is n 10 2030 40. n 10 n plus 1 2030 n equal to 1 equal to ln equal to 10 1 2 3 10. If we are performing n push operations, the cost per operation is O. Problem -20, given a string containing ns's and nx's where 5 indicates a push operation, and x indicates a pop operation, and with a stack initially empty, formulate a rule to check whether a given string 5% of operations is admissible or not. Solution. Given a string of length 2n, we wish to check whether the given string of operations is permissible or not with respect to its functioning on a stack. The only restricted operation is pop, whose prior requirement is that the stack should not be empty. So while traversing the string from left to right, prior to any pop, the stack shouldn't be empty, which means the number of s's is always greater than or equal to that of x's. Hence, the condition is at any stage of processing of the string, the number of push operations should be greater than the number of pop operations. Problem 21. Suppose there are two singly linked lists which intersect at some point and become a single linked list. The head or start pointers of both the lists are known, but the intersecting node is not known. Also, the number of nodes in each of the lists before they intersect are unknown, and both lists may have a different number. List may have n nodes before it reaches the intersection point, and list may have m nodes before it reaches the intersection point, where m and n may be m equal to n, m, n, or mn. Can we find the merging point using stacks? Solution, yes. For algorithm, refer to linked lists chapter. Problem -22, finding spans. Given an array A, the span S of A is the maximum number of consecutive elements A immediately preceding A, and such that A. Other way of asking, given an array A of integers, find the maximum of J. I subjected to the constraint of A. Solution. This is a very common problem in stock markets to find the peaks. Spans are used in financial analysis. The span of a stock price on a certain day, I, is the maximum number of consecutive days the price of the stock has been less than or equal to its price on I. As an example, let us consider the table and the corresponding spans diagram. In the figure, the arrows indicate the length of the spans. Now, let us concentrate on the algorithm for finding the spans. One simple way is each day check how many contiguous days have a stock price that is less than the current price. Algorithm finding spans in n, return s, executes n times n1 plus 2 plus 1 plus 2 plus n1. Time complexity, O. Space complexity, O. Problem 23. Can we improve the complexity of problem 22? Solution. From the example above, we can see that span S on day I can be easily calculated if we know the closest day preceding I, such that the price is greater on that day than the price on day I. Let us call such a day as P. If such a day exists, then the span is now defined as S equal to I. P. Algorithm. Finding spans int n. Struct stack D equal to create stack in TP for 1 while and A. Pop. If P minus 1 return S, else P equal to top. S equal to IP. Push. Time complexity. Each index of the array is pushed into the stack exactly once and also popped from the stack at most once. The statements in the while loop are executed at most n times. Even though the algorithm has nested loops, the complexity is O as the inner loop is executing only n times during the course of the algorithm. Space complexity. O. Problem minus 24 largest rectangle under histogram. A histogram is a polygon composed of a sequence of rectangles aligned at a common baseline. For simplicity, assume that the rectangles have equal widths but may have different heights. For example, the figure on the left shows a histogram that consists of rectangles with the heights 3, 2, 5, 6, 1, 4, 4, measured in units where 1 is the width of the rectangles. Here our problem is, given an array with heights of rectangles, we need to find the largest rectangle possible. For the given example, the largest rectangle is the shared part. Solution. A straightforward answer is to go to each bar in the histogram and find the maximum possible area in the histogram for it. Finally, find the maximum of these values. This will require O. Problem 25. For problem 24, can we improve the time complexity? Solution. Linear search. Using a stack of incomplete subproblems, there are many ways of solving this problem. Judge has given a nice algorithm for this problem which is based on stack. Process the elements in left to right order and maintain a stack of information about started but yet unfinished subhistograms. If the stack is empty, open a new subproblem by pushing the element onto the stack. Otherwise, compare it to the element on top of the stack. If the new one is greater, we again push it. If the new one is equal, we skip it. In all these cases, we continue with the next new element. If the new one is less, we finish the topmost subproblem by updating the maximum area with respect to the element at the top of the stack. Then, we discard the element at the top and repeat the procedure keeping the current new element. This way, all subproblems are finished when the stack becomes empty, or its top element is less than or equal to the new element, leading to the actions described above. If all elements have been processed and the stack is not yet empty, we finish the remaining subproblems by updating the maximum area with respect to the elements at the top. Struct stack item if plus top s height equal to a s index equal to I, return max area. At the first impression, this solution seems to be having O complexity. But if we look carefully, every element is pushed and popped at most once, and in every step of the function at least one element is pushed or popped. Since the amount of work for the decisions and the update is constant, the complexity of the algorithm is O by amortized analysis. Space complexity, O. Problem minus 26 on a given machine. How do you check whether the stack goes up or down? Solution, try noting down the address of a local variable. Call another function with a local variable declared in it and check the address of that local variable and compare. In t-test stack growth, in t-temporary, stack growth, exit, void stack growth, in temp printf, printef, if else printf, printef. Time complexity, O. Space complexity, O. Problem minus 27. Given a stack of integers, how do you check whether each successive pair of numbers in the stack is consecutive or not? The pairs can be increasing or decreasing, and if the stack has an odd number of elements, the element at the top is left out of a pair. For example, if the stack of elements are, then the output should be true because each of the pairs, and consists of consecutive numbers. Solution, refer to Q's chapter. Problem 28, recursively remove all adjacent duplicates. Given a string of characters, recursively remove adjacent duplicate characters from string. The output string should not have any adjacent duplicates. Solution. This solution runs with the concept of in-place stack. When element on stack doesn't match the current character, we add it to stack. When it matches to stack top, we skip characters until the element matches the top of stack and remove the element from stack. Void remove adjacent duplicates else, while equal to str, I++, sdkptr, str equal to 0. Time complexity, O. Space complexity, O as the stack simulation is done in place. Problem 29. Given an array of elements, replace every element with nearest greater element on the right of that element. Solution. One simple approach would involve scanning the array elements, and for each of the elements, scan the remaining elements and find the nearest greater element. Void, replace with nearest greater element. Int n, int next nearest greater equal to int min, int I equal to 0, j equal to 0, 4, equal to next nearest greater int min, for if a, equal to next nearest greater a, break, printf, next nearest greater. Time complexity, O. Space complexity, O. Problem minus 30 for problem 29. Can we improve the complexity? Solution. The approach is pretty much similar to problem 22. Create a stack and push the first element. For the rest of the elements, mark the current element as next nearest greater. If stack is not empty, then pop an element from stack and compare it with next nearest greater. If next nearest greater is greater than the popped element, then next nearest greater is the next greater element for the popped element. Keep popping from the stack while the popped element is smaller than next nearest greater. Next nearest greater becomes the next greater element for all such popped elements. If next nearest greater is smaller than the popped element, then push the popped element back. Void replace with nearest greater element, int n, int I equal to 0. Struct stack s equal to create stack, int t element, next nearest greater, push, 4, equal to next nearest greater a, if, element equal to pop, while, printf, next nearest greater, if, break, element equal to pop, if push, push while, element equal to pop, equal to next nearest greater, int min, printf, next nearest greater. Time complexity, O. Space complexity, O. Problem minus 31. How to implement a stack which will support following operations in O time complexity. Push which adds an element to the top of stack. Pop which removes an element from top of stack. Find middle which will return middle element of the stack. Delete middle which will delete the middle element. Solution. We can use a linked list data structure with an extra pointer to the middle element. Also, we need another variable to store whether the linked list has an even or odd number of elements. Push. Add the element to the head of the linked list. Update the pointer to the middle element according to variable. Pop. Remove the head of the linked list. Update the pointer to the middle element according to variable. Find middle which will return middle element of the stack. Delete middle which will delete the middle element. Use the logic of problem minus 43 from linked lists chapter. 5.1. What is a queue? A queue is a data structure used for storing data. In queue, the order in which data arrives is important. In general, a queue is a line of people or things waiting to be served in sequential order starting at the beginning of the line or sequence. Definition. A queue is an ordered list in which insertions are done at one end and deletions are done at other end. The first element to be inserted is the first one to be deleted. Hence, it is called first in, first out, or last in, last out list. Similar to stacks, special names are given to the two changes that can be made to a queue. When an element is inserted in a queue, the concept is called onQueue, and when an element is removed from the queue, the concept is called dequeue. Dequeuing an empty queue is called underflow, and enqueuing an element in a full queue is called overflow. Generally, we treat them as exceptions. As an example, consider the snapshot of the queue. 5.2. How are queues used? The concept of a queue can be explained by observing a line at a reservation counter. When we enter the line, we stand en el de line, et la personne qui sert de frontière de ligne is that one qui will serve accent. He will exit the queue, I be servi. As this happens, the next person will come at the head of the line, will exit the queue, and will be served. As each person at the head of the line keeps exiting the queue, we move towards the head of the line. Finally, we will reach the head of the line and we will exit the queue and be served. This behavior is very useful in cases where there is a need to maintain the order of arrival. 5.3 Queue ADT. The following operations make a queue an ADT. Insertions and deletions in the queue must follow the FIFO scheme. For simplicity, we assume the elements are integers. Main queue operations. En queue. Inserts an element at the end of the queue. Into queue. Removes and returns the element at the front of the queue. Auxiliary queue operations. In front. Returns the element at the front without removing it. Into queue size. Returns the number of elements stored in the queue. Int is empty QQ indicates whether no elements are stored in the queue or not. In 6.4 exceptions. Similar to other ADTs, executing DQ on an empty queue throws an empty queue exception, and executing on queue on a full queue throws full queue exception. 5.5 Applications. Following are some of the applications that use queues. Direct applications. Operating systems schedule jobs in the order of arrival. Simulation of real-world queues such as lines at a ticket counter or any other first-come, first-served scenario requires a queue. Multi-programming. Asynchronous data transfer. Waiting times of customers at call center. Determining number of cashiers to have at a supermarket. Indirect applications. Auxiliary data structure for algorithms. Component of other data structures. 5.6% implementation. There are many ways of implementing queue operations, and some of the commonly used methods are listed below. Simple circular array-based implementation. Dynamic circular array-based implementation. Linked list implementation. Why circular arrays? First, let us see whether we can use simple arrays for implementing queues as we have done for stacks. We know that in queues, the insertions are performed at one end and deletions are performed at the other end. After performing some insertions and deletions, the process becomes easy to understand. In the example shown below, it can be seen clearly that the initial slots of the array are getting wasted. So simple array implementation for queue is not efficient. To solve this problem, we assume the arrays as circular arrays. That means we treat the last element and the first array elements as contiguous. With this representation, if there are any free slots at the beginning, the rear pointer can easily go to its next free slot. Note, the simple circular array and dynamic circular array implementations are very similar to stack array implementations. Refer to Stack's chapter for analysis of these implementations. Simple circular array implementation. This simple implementation of QADT uses an array. In the array, we add elements circularly and use two variables to keep track of the start element and end element. Generally, front is used to indicate the start element and rear is used to indicate the end element in the queue. The array storing the queue elements may become full. An end queue operation will then throw a full queue exception. Similarly, if we try deleting an element from an empty queue, it will throw empty queue exception. Note, initially, both front and rear points to -1, which indicates that the queue is empty. Struct array queue in front, rear, int capacity, int array, struct array queue, if return null, queue capacity size, queue front, queue rear, 1, queue array malloc, if return null, return queue, int is empty queue, int is full queue when 1 int data equal to 0, or element which does not exist in queue, if. Else, printf, return 0, data queue array, if queue front, queue rear equal to -1. Else queue front percent queue capacity, return data, void delete queue, if queue array, free QL. Performance and limitations. Performance, let n be the number of elements in the queue. Limitations, the maximum size of the queue must be defined as prior and cannot be changed. Trying to enqueue a new element into a full queue causes an implementation-specific exception. Dynamic circular array implementation. Struct din array queue, struct dyn array queue equal to malloc return null, queue capacity equal to 1, queue front, queue rear equal to -1, car array malloc, if return null, return queue, int is empty queue 1. If the condition is true, then I is returned, else 0 is returned, return, int is full queue. If the condition is true, then 1 is returned, else 0 is returned, return percent queue capacity queue front, int queue size printf, return, I fic front, queue rear, in queue, if free. Performance. Let n be the number of elements in the queue. Linked list implementation. Another way of implementing queues is by using linked lists. Enqueue operation is implemented by inserting an element at the end of the list. Dequeue operation is implemented by deleting an element from the beginning of the list. 1 struct queue, create queue, struct list node, new node malloc, if return null, new node, data equal to data, new node next, null, equal to if queue rear next new node, queue rear new node, if queue front null, queue front queue rear, into queue int data equal to 0, or element which does not exist in queue struct list node temp, if it's empty queue, printf, return 0, else temp queue front data, queue front next, free, return data, void delete queue, struct list node temp, while temp, queue next free. 1. Free. Performance. Let n be the number of elements in the queue then. Comparison of implementations. Note, comparison is very similar to stack implementations and Stack's chapter. 5.7 queues, problems and solutions. Problem -1, give an algorithm for reversing a queue. To access the queue, we are only allowed to use the methods of QADT. Solution. Time complexity. Problem 2. How can you implement a queue using 2 stacks? Solution. Let Sci and S2 be the 2 stacks to be used in the implementation of queue. All we have to do is to define the onQueue and DQ operations for the queue. Struct queue, struct stack S1, for enqueue struct stack S2, for DQ. Enqueue algorithm. Just push on to stack S1. Void on queue, push, time complexity. DQ algorithm. If stack S2 is not empty, then pop from S2 and return that element. If stack is empty, then transfer all elements from Si to S2 and pop the top element from S2 and return the popped element. If stack S1 is also empty, then throw error. Into queue, if else, return pop, while push, return pop. Time complexity from the algorithm. If the stack S2 is not empty, then the complexity is O. If the stack S2 is empty, then we need to transfer the elements from Si to S2. But if we carefully observe, the number of transferred elements and the number of popped elements from S2 are equal. Due to this, the average complexity of pop operation in this case is O. The amortized complexity of pop operation is O. Problem -3, show how you can efficiently implement one stack using 2 queues. Analyze the running time of the stack operations. Solution. Yes, it is possible to implement the stack ADT using 2 implementations of the queue ADT. One of the queues will be used to store the elements, and the other to hold them temporarily during the pop and top methods. The push method would enqueue the given element onto the storage queue. The top method would transfer all but the last element from the storage queue onto the temporary queue, save the front element of the storage queue to be returned, transfer the last element to the temporary queue, then transfer all elements back to the storage queue. The pop method would do the same as top, except instead of transferring the last element onto the temporary queue after saving it for return, that last element would be discarded. Let first quarter and Q2 be the two queues to be used in the implementation of stack. All we have to do is to define the push and pop operations for the stack. Struct stack, struct queue first quarter, struct queue second quarter. In the algorithms below, we make sure that one queue is always empty. Push operation algorithm, insert the element in whichever queue is not empty. Check whether queue first quarter is empty or not. If first quarter is empty, then enqueue the element into second quarter. Otherwise, onqueue the element into first quarter. Push, if, onqueue, else onqueue. Time complexity, O. Pop operation algorithm. Transfer N1 elements to the other queue and delete last from queue for performing pop operation. If queue first quarter is not empty, then transfer N1 elements from first quarter to second quarter, and then dequeue the last element of first quarter and return it. If queue second quarter is not empty, then transfer N1 elements from second quarter to first quarter, and then dequeue the last element of second quarter and return it. Int pop, int I, size if, size equal to size, I equal to 0. One while, on queue, I plus plus, return dequeue, else size equal to size, while on queue, I plus plus, return dequeue. Time. Complexity running time of pop operation is O. As each time pop is called, we are transferring all the elements from one queue to the other. Problem -4 maximum sum in sliding window, given array A with sliding window of size W, which is moving from the very left of the array to the very right. Assume that we can only see the W numbers in the window. Each time, the sliding window moves rightwards by one position. For example, the array is, and W is 3. Input, along array A, and a window with W output, and array B. B is the maximum value from A to A. Requirement, find a good optimal way to get B. Solution, this problem can be solved with doubly ended queue. Refer priority queues chapter for algorithms. Problem -5, given a queue containing n elements, transfer these items onto a stack S so that front element of queue appears at the top of the stack and the order of all other items is preserved. Using NQ and DQ operations for the queue and push and pop operations for the stack, outline an efficient O algorithm to accomplish the above task, using only a constant amount of additional storage. Solution, assume the elements of QQ are a1 dots alpha 2, alpha. Dequeuing all elements and pushing them onto the stack will result in a stack with alpha at the top and a 1 at the bottom. This is done in O time as DQ, and each push require constant time per operation. The queue is now empty. By popping all elements and pushing them on the queue, we will get a 1 at the top of the stack. This is done again in O time. As in big O arithmetic, we can ignore constant factors. The process is carried out in O time. The amount of additional storage needed here has to be big enough to temporarily hold one item. Problem 6, a queue is set up in a circular array A with front and rear defined as usual. Assume that n1 locations in the array are available for storing the elements. Give a formula for the number of elements in the queue in terms of rear, front, and n. Solution, consider the following figure to get a clear idea of the queue. Rear of the queue is somewhere clockwise from the front. To enqueue an element, we move rear 1 position clockwise and write the element in that position. To dequeue, we simply move front 1 position clockwise. Queue migrates in a clockwise direction as we enqueue and dequeue. Emptiness and fullness to be checked carefully. Analyze the possible situations. We will get this. Number of elements equal to rear front plus 1 if rear equal to rear front plus n front otherwise. Problem 7 order. What is the most appropriate data structure to print elements of queue in reverse? Solution stack. Problem -8 implement doubly ended queues. A double-ended queue is an abstract data structure that implements a queue for which elements can only be added to or removed from the front or back. It is also often called a head-tail linked list. Solution. Void pushback deck equal to new node prev new node next head prev next equal to new node prev new node. Void push front deck pushback deck. Head prev in pop back deck in data equal to if prev equal to head. Data equal to data free. Head equal to null. Else struct list node new tail equal to prev data. New tail next equal to head free prev new tail return data. Int pop front in data. Head next equal to data pop back deck return data. Problem 9, given a stack of integers, how do you check whether each successive pair of numbers in the stack is consecutive or not? The pairs can be increasing or decreasing, and if the stack has an odd number of elements, the element at the top is left out of a pair. For example, if the stack of elements are, then the output should be true because each of the pairs, and consists of consecutive numbers. Solution. Int check stack pairwise order. Struct q equal to create q, int pairwise ordered equal to 1, while on q, while push while, int n equal to pop in q if, int m equal to pop in q if equal to 1, pairwise ordered equal to 0, while push, return, pairwise ordered. Time complexity, O. Space complexity, O. Problem -10, given a queue of integers, rearrange the elements by interleaving the first half of the list with the second half of the list. For example, suppose a queue stores the following sequence of values. Consider the two halves of this list, first half, second half. These are combined in an alternating fashion to form a sequence of interleaved pairs, the first values from each half, then the second values from each half, then the third values from each half, and so on. In each pair, the value from the first half appears before the value from the second half. Thus, after the call, the queue stores the following values. Solution. Void interleaving queue if %2 equal to 0, return, struct stack s create stack, int half size equal to size, 2 for push, while on q for push, while and q, on q. Time complexity, O. Space complexity, O. Problem 11. Given an integer k and a queue of integers, how do you reverse the order of the first k elements of the queue, leaving the other elements in the same relative order? For example, if k equal to 4 and q has the elements, the output should be. Solution. Void reverse a queue first element struct stack s create stack for push while on q for k I++, wrap around rest of elements on q. Time complexity, O. Space complexity, O. What is a tree? A tree is a data structure similar to a linked list, but instead of each node pointing simply to the next node in a linear fashion, each node points to a number of nodes. Tree is an example of a non-linear data structure. A tree structure is a way of representing the hierarchical nature of a structure in a graphical form. In trees ADT, the order of the elements is not important. If we need ordering information, linear data structures like linked lists, stacks, queues, etc. can be used. 6.2 Glossary. The root of a tree is the node with no parents. There can be at most one root node in a tree. An edge refers to the link from parent to child. A node with no children is called leaf node. Children of same parent are called siblings. A node P is an ancestor of node Q if there exists a path from root to Q and P appears on the path. The node Q is called a descendant of P. For example, A, C, and G are the ancestors of if. The set of all nodes at a given depth is called the level of the tree. The root node is at level 0. The depth of a node is the length of the path from the root to the node. The height of a node is the length of the path from that node to the deepest node. The height of a tree is the length of the path from the root to the deepest node in the tree. A tree with only one node has a height of 0. In the previous example, the height of B is 2. Height of the tree is the maximum height among all the nodes in the tree, and depth of the tree is the maximum depth among all the nodes in the tree. For a given tree, depth and height returns the same value. But for individual nodes, we may get different results. The size of a node is the number of descendants it has, including itself. If every node in a tree has only one child, then we call such trees skew trees. If every node has only left child, then we call them left skew trees. Similarly, if every node has only right child, then we call them right skew trees. 6.3 Binary trees. A tree is called binary tree if each node has 0 child, 1 child, or 2 children. Empty tree is also a valid binary tree. We can visualize a binary tree as consisting of a root and 2 disjoint binary trees, called the left and right subtrees of the root. Generic binary tree. 6.4 Types of binary trees. Strict binary tree. A binary tree is called strict binary tree if each node has exactly 2 children or no children. Full binary tree. A binary tree is called full binary tree if each node has exactly 2 children and all leaf nodes are at the same level. Complete binary tree. Before defining the complete binary tree, let us assume that the height of the binary tree is h. In complete binary trees, if we give numbering for the nodes by starting at the root, then we get a complete sequence from 1 to the number of nodes in the tree. While traversing, we should give numbering for null pointers also. A binary tree is called complete binary tree if all leaf nodes are at height h or h1, and also without any missing number in the sequence. 6.5 Properties of binary trees. 4. The following properties let us assume that the height of the tree is h. Also assume that root node is at height 0. Height number of nodes at level h equal to 0, 2, o equal to 1, h equal to 121 equal to 2, h equal to 2, 2 to the power of 2 equal to 4. From the diagram, we can infer the following properties. The number of nodes n in a full binary tree is 2 hours plus 1 to 1. Since there are h levels, we need to add all nodes at each level. The number of nodes n in a complete binary tree is between 2 hours and 2 hours 1 to 1. For more information on this, refer to priority queues chapter. The number of leaf nodes in a full binary tree is 2 hours. The number of null links in a complete binary tree of n nodes is n plus 1. Structure of binary trees. Now let us define structure of the binary tree. For simplicity, assume that the data of the nodes are integers. One way to represent a node is to have 2 links which point to left and right children along with data fields as shown below. Note, in trees, the default flow is from parent to children, and it is not mandatory to show directed branches. For our discussion, we assume both the representations shown below are the same. Operations on binary trees, basic operations, inserting an element into a tree, deleting an element from a tree, searching for an element, traversing the tree, auxiliary operations, finding the size of the tree, finding the height of the tree, finding the level which has maximum sum, finding the least common ancestor for a given pair of nodes, and many more. Applications of binary trees. Following are some of the applications where binary trees play an important role. Expression trees are used in compilers, Huffman coding trees that are used in data compression algorithms, binary search tree, which supports search, insertion, and deletion on a collection of items in O, priority queue, which supports search and deletion of minimum on a collection of items in logarithmic time. 6.6 Binary tree traversals. In order to process trees, we need a mechanism for traversing them, and that forms the subject of this section. The process of visiting all nodes of a tree is called tree traversal. Each node is processed only once, but it may be visited more than once. As we have already seen in linear data structures, the elements are visited in sequential order. But in tree structures, there are many different ways. Tree traversal is like searching the tree, except that in traversal, the goal is to move through the tree in a particular order. In addition, all nodes are processed in the traversal, but searching stops when the required node is found. Traversal possibilities. Starting at the root of a binary tree, there are 3 main steps that can be performed, and the order in which they are performed defines the traversal type. These steps are performing an action on the current node, traversing to the left child node, and traversing to the right child node. This process can be easily described through recursion. Based on the above definition, there are 6 possibilities. 1, 2, LRD, process left subtree, process right subtree, and then process the current node data. 3, DLR, process the current node data, process left subtree, and then process right subtree. 4, DRL, process the current node data, process right subtree, and then process left subtree. 5, RDL, process right subtree, process the current node data, and then process left subtree. 6, RLD, process right subtree, process left subtree, and then process the current node data. LDR, process left subtree, process the current node data, and then process right subtree. Classifying the traversals. The sequence in which these entities are processed defines a particular traversal method. The classification is based on the order in which current node is processed. That means if we are classifying based on current node, and if D comes in the middle, then it does not matter whether L is on left side of D or R is on left side of D. Similarly, it does not matter whether L is on right side of D or R is on right side of D. Due to this, the total 6 possibilities are reduced to 3, and these are pre-order traversal, in-order traversal, post-order traversal. There is another traversal method which does not depend on the above orders, and it is level order traversal. This method is inspired from breadth first traversal. Let us use the diagram below for the remaining discussion. Pre-order traversal. In pre-order traversal, each node is processed before either of its subtrees. This is the simplest traversal to understand. However, even though each node is processed before the subtrees, it still requires that some information must be maintained while moving down the tree. In the example above, one is processed first, then the left subtree, and this is followed by the right subtree. Therefore, processing must return to the right subtree after finishing the processing of the left subtree. To move to the right subtree after processing the left subtree, we must maintain the root. Information. The obvious ADT for such information is a stack. Because of its LIFO structure, it is possible to get the information about the right subtrees back in the reverse order. Pre-order traversal is defined as follows. Visit the root. Traverse the left subtree in pre-order. Traverse the right subtree in pre-order. The nodes of tree would be visited in the order 1,245,300 in the order. Void pre-order. Time complexity, O. Space complexity, O. Non-recursive pre-order traversal. In the recursive version, a stack is required as we need to remember the current node so that after completing the left subtree, we can go to the right subtree. To simulate the same, first we process the current node, and before going to the left subtree, we store the current node on stack. After completing the left subtree processing, pop the element and go to its right subtree. Continue this process until stack is non-empty. Void pre-order non-recursive, struct stack s equal to create stack, while, process current node print, push. If left subtree exists, add to stack equal to root left, if break root equal to pop, indicates completion of left subtree and current node. Now go to right subtree root equal to root right, delete stack. Time complexity, O. Space complexity, O. In-order traversal. In in-order traversal, the root is visited between the subtrees. In-order traversal is defined as follows. Traverse the left subtree in order. Visit the root. Traverse the right subtree in order. The nodes of tree would be visited in the order 4,251,637. Void in order. If in order. Print in order. Time complexity, O. Space complexity, O. Non-recursive in-order traversal. The non-recursive version of in-order traversal is similar to pre-order. The only change is, instead of processing the node before going to left subtree, process it after popping. Void in order non-recursive if break root equal to pop printf after popping process the current node. Indicates completion of left subtree and current node. Now go to right subtree root equal to root right, delete stack. Time complexity, O. Space complexity, O. Post-order traversal. In post-order traversal, the root is visited after both subtrees. Post-order traversal is defined as follows. Traverse the left subtree in post-order. Traverse the right subtree in post-order. Visit the root. The nodes of the tree will be visited in the order 4,526,731. Void post-order if post-order print f. Time complexity, O. Space complexity, O. Non-recursive post-order traversal. In pre-order and in-order traversals, after popping the stack element, we do not need to visit the same vertex again. But in post-order traversal, each node is visited twice. That means after processing the left subtree, we will visit the current node, and after processing the right subtree, we will visit the same current node. But we should be processing the node during the second visit. Here the problem is how to differentiate whether we are returning from the left subtree or the right subtree. We use a previous variable to keep track of the earlier traversed node. Let's assume current is the current node that is on top of the stack. When previous is current's parent, we are traversing down the tree. In this case, we try to traverse the current's left child if available. If it is not available, we look at current's right child. If both left and right child do not exist, we print current's value and pop it off the stack. If prev is current's left child, we are traversing up the tree from the left. We look at current's right child. If it is available, then traverse down the right child. Otherwise, print current's value and pop it off the stack. If previous is current's right child, we are traversing up the tree from the right. In this case, we print current's value and pop it off the stack. Void post-order non-recursive, else root, right, while. Time complexity, O. Space complexity, O. Level order traversal. Level order traversal is defined as follows. Visit the root. While traversing level, keep all the elements at level plus 1 in. Q. Go to the next level and visit all the nodes at that level. Repeat this until all levels are completed. The nodes of the tree are visited in the order 1,234,567. Void level order, struct binary tree node temp, struct q equal to create q, if return on q, while temp equal to dq. Process current node b print if and q, delete q. Time complexity, O. Space complexity, O. Since in the worst case, all the nodes on the entire last level could be in the queue simultaneously. Binary trees, problems, and solutions. Problem -1, give an algorithm for finding maximum element in binary tree. Solution, one simple way of solving this problem is, find the maximum element in left subtree, find the maximum element in right subtree, compare them with root data, and select the one which is giving the maximum value. This approach can be easily implemented with recursion. In find max in root underscore val left right max equal to int min, if root underscore val equal to root data, left equal to find max equal to right find max, find the largest of the three values, if max equal to left, else max equal to right, if max equal to root underscore val, return max. Time complexity, O. Space complexity, O. Problem 2, give an algorithm for finding the maximum element in binary tree without recursion. Solution, using level order traversal, just observe the element's data while deleting. Int, find max using level order, largest of the three values if max equal to temp data, if on q, delete q, return max. Time complexity, O. Space complexity, O. Problem -3, give an algorithm for searching an element in binary tree. Solution, given a binary tree, return true if a node with data is found in the tree. Recurse down the tree, choose the left or right branch by comparing data with each node's data. In find in binary tree using recursion. Int temp equal to base case empty tree. In that case, the data is not found, so return false if return 0, else. See if found here, if return 1, else. Otherwise, recur down the correct subtree equal to temp find in binary tree using recursion if return temp, else return 0. Time complexity, O. Space complexity, O. Problem -4, give an algorithm for searching an element in binary tree without recursion. Solution, we can use level order traversal for solving this problem. The only change required in level order traversal is, instead of printing the data, we just need to check whether the root data is equal to the element we want to search. In T, search using level order, struct binary tree node temp, struct qq, if return -1, q equal to create q, on q, while temp equal to dq. See if found here if return 1, if on q, delete q, return 0. Time complexity, O. Space complexity, O. Problem -5, give an algorithm for inserting an element into binary tree. Solution, since the given tree is a binary tree, we can insert the element wherever we want. To insert an element, we can use the level order traversal and insert the element wherever we find the node whose left or right child is null. Void insert in binary tree q equal to create q, on q, while temp equal to dq, if in q, else. Temp left new node, delete q, return if else, on q, temp right new node, delete q, return, delete q. Time complexity, O. Space complexity, O. Problem -6, give an algorithm for finding the size of binary tree. Solution, calculate the size of left and right subtrees recursively, add 1 and return its parent. 2. Compute the number of nodes in a tree. In size of binary tree, if return 0, else return +1 plus size of binary tree. Time complexity, O. Space complexity, O. Problem -7, can we solve problem 6 without recursion? Solution, yes, using level order traversal. In size of BT using level order, struct binary tree node temp, struct qq, in count equal to 0, if return 0, q equal to create q, on q, while temp equal to count plus dq, if on q, delete q, return count. Time complexity, O. Space complexity, O. Problem -8, give an algorithm for printing the level order data in reverse order. For example, the output for the below tree should be 4,567,231. Solution, void level order traversal, reverse, struct qq, equal to struct stack s create stack, struct binary tree node temp, if return, q equal to create q, on q, while temp equal to dq, if on q, push, while printf data. Time complexity, O. Space complexity, O. Problem -9, give an algorithm for deleting the tree. Solution. To delete a tree, we must traverse all the nodes of the tree and delete them one by one. So which traversal should we use? In order, pre-order, post-order, or level-order traversal? Before deleting the parent node, we should delete its children nodes first. We can use post-order traversal as it does the work without storing anything. We can delete tree with other traversals also with extra space complexity. For the following, tree nodes are deleted in order. 4, 5, 2, 3, 1. Void delete binary tree, if return. First delete both subtrees. Delete binary tree, delete binary tree. Delete current node only after deleting subtrees free. Time complexity, O. Space complexity, O. Problem -10, give an algorithm for finding the height of the binary tree. Solution, recursively calculate height of left and right subtrees of a node and assign height to the node as max of the heights of two children plus 1. This is similar to pre-order tree traversal. Int height of binary tree, int left height, right height, if else return 0. Compute the depth of each subtree. Left height of binary tree, right height of binary tree, if else return. Time complexity, O. Space complexity, O. Problem 11, can we solve problem 10 without recursion? Solution, yes, using level order traversal. This is similar to BFS of graph algorithms. End of level is identified with null. Int find height of binary tree, int level equal to 0, struct QQ if return 0, Q equal to create Q on Q. End of first level on Q, while root to Q, completion of current level. If, put another marker for next level. If NQ, level plus plus, else, if NQ, if on Q, return level. Time complexity, O. Space complexity, O. Problem 12. Give an algorithm for finding the deepest node of the binary tree. Solution. Struct binary tree node deepest node in binary tree. 1. Struct binary tree node temp. Struct QQ, if return null, Q equal to create Q on Q, while temp equal to DQ. If in Q, delete Q, return temp. Time complexity, O. Space complexity, O. Problem -13 tree. Give an algorithm for deleting an element from binary. Solution. The deletion of a node in binary tree can be implemented as: starting at root, find the node which we want to delete. Find the deepest node in the tree. Replace the deepest node's data with node to be deleted. Then delete the deepest node. Problem 14. Give an algorithm for finding the number of leaves in the binary tree without using recursion. Solution. The set of nodes whose both left and right children are null are called leaf nodes. Int number of leaves in B2 using level order, struct binary tree node temp, struct QQ, int count equal to 0, if return 0, Q equal to create Q, and Q, while temp equal to DQ, if count plus plus, else, if NQ, if delete Q, return count on Q. Time complexity, O. Space complexity, O. Problem 15. Give an algorithm for finding the number of full nodes in the binary tree without using recursion. Solution. The set of all nodes with both left and right children are called full nodes. Int number of full nodes in B2 using level order, struct binary tree node temp, struct QQ, int count equal to 0, if return 0, Q equal to create Q, on Q, while temp equal to DQ, if count plus plus, if on Q, if on Q, delete Q, return count. Time complexity, O. Space complexity, O. Problem 16. Give an algorithm for finding the number of half nodes in the binary tree without using recursion. Solution. The set of all nodes with either left or right child are called half nodes. Int number of half nodes in B2 using level order, struct binary tree node temp, struct QQ, int count equal to 0 if return 0, Q equal to create Q, on Q, while temp equal to DQ, lambda. We can use this condition also instead of 2 temp left to the power of temp right, if count plus plus, if in Q, delete Q, return count. Time complexity, O. Space complexity, O. Problem 17. Given two binary trees, return true if they are structurally identical. Solution. Algorithm. If both trees are null, then return true. If both trees are not null, then compare data and recursively check left and right subtree structures. Return true if they are structurally identical. In T are structurally same trees, both empty, 1 if return 1. If return 0, both non-empty, compare them, return and end are structurally same trees. Time complexity, O. Space complexity, O, for recursive stack. Problem -18. Give an algorithm for finding the diameter of the binary tree. The diameter of a tree is the number of nodes on the longest path between two leaves in the tree. Solution. To find the diameter of a tree, first calculate the diameter of left subtree and right subtrees recursively. Among these two values, we need to send maximum value along with current level. Int diameter of tree, int left right if return 0, left diameter of tree equal to right diameter of tree. If PTR equal to left plus right, return max plus 1. Alternative coding static int diameter if return 0 equal to int height equal to int r height, int e diameter, int r diameter, return max. The function compute the height of a tree. Height is the number of the longest path from the root node down to the farthest leaf node. Static int height if return 1 plus max height of nodes along. There is another solution, and the complexity is O. The main idea of this approach is that the node stores its left child and right child's maximum diameter if the node's child is the root. Therefore, there is no need to recursively call the height method. The drawback is we need to add 2 extra variables in the node structure. Int find maxlen, int n maxlen equal to 0. If return 0, if root.n max left equal to 0. If root max right equal to 0. If find maxlen, if int n temp maxlen equal to 0, and temp maxlen equal to root.left.n max left, root.left.n max right, root.max left equal to n temp maxlen plus 1. If int and temp maxlen equal to 0, equal to n temp maxlen, root right.n max left, root.right.n max right, root.n max right, n temp maxlen plus 1. If n maxlen root.n max left plus root.n max right, return n maxlen. Time complexity, O. Space complexity, O. Problem -19 tree. Give an algorithm for finding the level that has the maximum sum in the binary. Solution. The logic is very much similar to finding the number of levels. The only change is we need to keep track of the sums as well. In find level with max sum, else current sum equal to temp data. If on Q, 1 return max level. Time complexity, O. Space complexity, O. Problem 20. Given a binary tree, print out all its root to leaf paths. Solution. Refer to comments and functions. Void print paths recur. Int pathlen if return. Append this node to the path array path root data, pathlen plus plus. It's a leaf, so print the path that led to here if print array else. Otherwise, try both subtrees print paths recur, function that prints out an array on a line. Void print array int len for printf. Time complexity, O. Space complexity, O, for recursive stack. Problem minus 21. Give an algorithm for checking the existence of path with given sum. That means, given a sum, check whether there exists a path from root to any of the nodes. Solution. For this problem, the strategy is, subtract the node value from the sum before calling it, children recursively, and check to see if the sum is 0 when we run out of tree. Void print paths recur. In pathlen if return, append this node to the path array path root data, pathlen plus plus equal to, it's a leaf, so print the path that led to here if print array, else. Otherwise try both subtrees print paths recur, function that prints out an array on a line. Void print array, int len. For print df, if or, return or has path sum, else if else return has path sum, return has path sum. Time complexity, O. Space complexity, O. Problem 22, give an algorithm for finding the sum of all elements in binary tree. Solution, recursively, call left subtree sum, right subtree sum, and add their values to current nodes data. Nt add if return 0, else return plus ed. Time complexity, O. Space complexity, O. Problem 23. Can we solve problem 22 without recursion? Solution, we can use level order traversal with simple change. Every time after deleting an element from Q, add the node's data value to some variable. Int sum of b2 using level order, struct binary tree node temp, struct QQ, in sum equal to 0, if return 0, Q equal to create Q, on Q, while temp equal to DQ. Sum plus equal to temp data, if in Q, delete Q, return sum. Time complexity, O. Space complexity, O. Problem 24. Give an algorithm for converting a tree to its mirror. Mirror of a tree is another tree with left and right children of all non-leaf nodes interchanged. The trees below are mirrors to each other. Root SL3. Solution. Struct binary tree node mirror of binary tree, struct binary tree node temp, if mirror of binary tree, mirror of binary tree. Swap the pointers in this node. Temp equal to root left equal to root right equal to temp, return root. Time complexity, O. Space complexity, O. Problem 25, given two trees. Give an algorithm for checking whether they are mirrors of each other. Solution. In T are mirrors. If equal to return 0. Null and root equal to null or root equal to null if return 0, else return are mirrors and are mirrors. Time complexity, O. Space complexity, O. Problem 26, give an algorithm for finding LCA of two nodes in a binary tree. Solution. Struct binary tree node LCA return root if return root, left LCA, right LCA if return root, else return. Time complexity, O. Space complexity, O for recursion. Problem minus 27, give an algorithm for constructing binary tree from given in-order and pre-order traversals. Solution. Let us consider the traversals below. In order sequence, DBAFC pre-order sequence, abdec. In a pre-order sequence, leftmost element denotes the root of the tree, so we know A is the root for given sequences. By searching A in in-order sequence, we can find out all elements on the left side of A, which come under the left subtree, and elements on the right side of A, which come under the right subtree. So we get the structure as seen below. We recursively follow the above steps and get the following tree. Algorithm, build tree. 1. Select an element from pre-order. Increment a pre-order index variable to pick next element in next recursive call. 2. 3. Find the selected element's index in order. Let the index be in-order index. 4. Call build binary tree for elements before in-order index and make the build tree as left subtree of new node. 5. Call build binary tree for elements after in-order index and make the build tree as right subtree of new node. Create a new tree node from heap with the data as selected element. 6. Return new node. Struct binary tree node, build binary tree, int pre-order, int in order start, in static int pre-order index equal to 0, struct binary tree node new node, if in order start in order end, return null, new node malloc, if print ef return null, or select current node from pre-order traversal using pre-order index new node data pre-order index plus plus, if in order start in order end, return new node. Find the index of this node in order traversal int in order index search. Fill the left and right subtrees using index in order traversal equal to new node. Left build binary tree equal to new node. Right build binary tree, return new node. In order end. Time complexity, O. Space complexity, O. Problem minus 28. If we are given two traversal sequences, can we construct the binary tree uniquely? Solution. It depends on what traversals are given. If one of the traversal methods is in order, then the tree can be constructed uniquely, otherwise not. Therefore, the following combinations can uniquely identify a tree. In order and pre-order, in order and post-order, in order and level order. The following combinations do not uniquely identify a tree. Post-order and pre-order and level order. Post-order and level order. For example, pre-order, level order, and post-order traversals are the same for the above trees. So, even if 3 of them are given, the tree cannot be constructed uniquely. Problem 29, give an algorithm for printing all the ancestors of a node in a binary tree. For the tree below, for 7, the ancestors are 137. Solution. Apart from the depth first search of this tree, we can use the following recursive way to print the ancestors. Int print all ancestors, if return 0, if or print f, return 1, 1 return 0, print all ancestors. Time complexity, O. Space complexity, O for recursion. Problem 30, zigzag tree traversal. Give an algorithm to traverse a binary tree in zigzag order. For example, the output for the tree below should be 1,324,567. Solution. This problem can be solved easily using 2 stacks. Assume the 2 stacks are current level and next level. We would also need a variable to keep track of the current level order. We pop from current level stack and print the node's value. Whenever the current level order is from left to right, push the node's left child, then its right child to stack next level. Since a stack is a last in first out structure, the next time that nodes are popped off next level, it will be in the reverse order. On the other hand, when the current level order is from right to left, we would push the node's right child first, then its left child. Finally, don't forget to swap those 2 stacks at the end of each level. Void zigzag traversal else if push, if left to right, one left to right swap. Time complexity, O. Space complexity, space for 2 stacks equal to O plus O equal to O. Problem minus 31, give an algorithm for finding the vertical sum of a binary tree. For example, the tree has 5 vertical lines. Vertical own, nodes minus 4 equal to vertical sum is 4 vertical 2, nodes 2 equal to vertical sum is 2 vertical 3, nodes 1, 5, 6 equal to vertical sum is 1 plus 5 plus 6 equal to 12 vertical minus 4, nodes 3 equal to vertical sum is 3 vertical 5, nodes 7 equal to vertical sum is 7 we need to output, 42, 12, 37. Solution, we can do an in-order traversal and hash the column. We call vertical sum on binary tree fruit 0, which means the root is at column 0. While doing the traversal, hash the column and increase its value by root data. Void vertical sum in binary tree if return, vertical sum in binary tree, refer hashing chapter for implementation of hash table hash column, plus root data, vertical sum in binary tree, vertical sum in binary tree, print hash. Problem 32, how many different binary trees are possible with n nodes? Solution, for example, consider a tree with 3 nodes. It will have the maximum combination of 5 different trees. In general, if there are n nodes, there exist 2n different trees. Problem minus 33, given a tree with a special property where leaves are represented with L, an internal node with I. Also, assume that each node has either 0 or 2 children. Given pre-order traversal of this tree, construct the tree. Example, given pre-order string equal to allele. Solution, first we should see how pre-order traversal is arranged. Pre-order traversal means first put root node, then pre-order traversal of left subtree, and then pre-order traversal of right subtree. In a normal scenario, it's not possible to detect where left subtree ends and right subtree starts using only pre-order traversal. Since every node has either 2 children or no child, we can surely say that if a node exists, then its sibling also exists. So every time when we are computing a subtree, we need to compute its sibling subtree as well. Secondly, whenever we get L in the input string, that is a leaf, and we can stop for a particular subtree at that point. After this L node, its sibling starts. If L node is right child of its parent, then we need to go up in the hierarchy to find the next subtree to compute. Keeping the above invariant in mind, we can easily determine when a subtree ends and the next one starts. It means that we can give any start node to our method, and it can easily complete the subtree it generates going outside of its nodes. We just need to take care of passing the correct start nodes to different subtrees. Struct binary tree node build tree from pre-order if equal to L. On reaching leaf node, return new node, +1. Populate left subtree equal to +1. New node left build tree from pre-order equal to new node right build tree from pre-order. Return new node. Populate right subtree. Time complexity. O. Problem minus 34. Given a binary tree with 3 pointers, give an algorithm for filling the next sibling pointers assuming they are null initially. Solution. We can use simple Q. Let us assume that the structure of binary tree is struct binary tree node left, struct binary tree node right, struct binary tree node next sibling, int fill next siblings else, temp next sibling Q front, equal to if in Q. Time complexity. O. Space complexity. O. Problem minus 35. Is there any other way of solving problem 34? Solution. The trick is to reuse the populated next sibling pointers. As mentioned earlier, we just need one more step for it to work. Before we pass the left and right to the recursion function itself, we connect the right child's next sibling to the current node's next sibling left child. In order for this to work, the current node next sibling pointer must be populated, which is true in this case. Void fill next siblings if return. If root left next sibling equal to root right. If root right next sibling equal to root next sibling left. Null fill next siblings. Time complexity. O. 6.7 generic trees. In the previous section, we discussed binary trees where each node can have a maximum of 2 children, and these are represented easily with 2 pointers. But suppose if we have a tree with many children at every node, and also if we do not know how many children a node can have, how do we represent them? For example, consider the tree shown below. How do we represent the tree? In the above tree, there are nodes with 6 children, with 3 children, with 2 children, with 1 child, and with 0 children. To present this tree, we have to consider the worst case and allocate that many child pointers for each node. Based on this, the node representation can be given as struct tree node int data, struct tree node first child, struct tree node second child, struct tree node third child, struct tree node fourth child, struct tree node fifth child, struct tree node sixth child. Since we are not using all the pointers in all the cases, there is a lot of memory wastage. Another problem is that we do not know the number of children for each node in advance. In order to solve this problem, we need a representation that minimizes the wastage and also accepts nodes with any number of children. Representation of generic trees. Since our objective is to reach all nodes of the tree, a possible solution to this is as follows. At each node, link children of same parent from left to right. Remove the links from parent to all children except the first child. What these above statements say is if we have a link between children, then we do not need extra links from parent to all children. This is because we can traverse all the elements by starting at the first child of the parent. So if we have a link between parent and first child and also links between all children of same parent, then it solves our problem. This representation is sometimes called first child next sibling representation. First child next sibling representation of the generic tree is shown above. The actual representation for this tree is, based on this discussion, the tree node declaration for general tree can be given as struct tree node int data, struct tree node first child, struct tree node next sibling. Note, since we are able to convert any generic tree to binary representation, in practice we use binary trees. We can treat all generic trees with a first child next sibling representation as binary trees. Generic trees, problems and solutions. Problem 36, given a tree, give an algorithm for finding the sum of all the elements of the tree. Solution. The solution is similar to what we have done for simple binary trees. That means traverse the complete list and keep on adding the values. We can either use level order traversal or simple recursion. In find sum, if return 0, return root data plus find sum. Time complexity. O. Space complexity. O. Otherwise O. Note, all problems which we have discussed for binary trees are applicable for generic trees also. Instead of left and right pointers, we just need to use first child and next sibling. Problem minus 37 for a 4-array tree. What is the maximum possible height with 100 nodes? Assume height of a single node is 0. Solution. In 4-array tree, each node can contain 0 to 4 children, and to get maximum height, we need to keep only 1 child for each parent. With 100 nodes, the maximum possible height we can get is 99%. If we have a restriction that at least one node has 4 children, then we keep one node with 4 children and the remaining nodes with 1 child. In this case, the maximum possible height is 96. Similarly, with n nodes, the maximum possible height is n4. Problem minus 38 for a 4-array tree. What is the minimum possible height with n nodes? Solution. Similar to the above discussion. If we want to get minimum height, then we need to fill all nodes with maximum children. Now let's see the following table, which indicates the maximum number of nodes for a given height. H plus 1 for a given height. The maximum possible nodes are, to get minimum height, take logarithm on both sides. Problem minus 39, given a parent array P, where P indicates the parent of th node in the tree. Give an algorithm for finding the height or depth of the tree. Solution. For example, if the P is, its corresponding tree is, from the problem definition, the given array represents the parent array. That means we need to consider the tree for that array and find the depth of the tree. The depth of this given tree is 4. If we carefully observe, we just need to start at every node and keep going to its parent until we reach -1, and also keep track of the maximum depth among all nodes. int find depth in generic tree, int n, current depth equal to 0, j equal to I, while, equal to -1, current depth plus, j equal to p. If max depth, current depth, return max depth. Time complexity, O. For skew trees, we will be recalculating the same values. Space complexity, O. Note, we can optimize the code by storing the previous calculated node's depth in some hash table or other array. This reduces the time complexity but uses extra space. Problem -40, given a node in the generic tree, give an algorithm for counting the number of siblings for that node. Solution, since tree is represented with a first child next sibling method, the tree structure can be given as struct tree node, int data, struct tree node first child, struct tree node next sibling. For a given node in the tree, we just need to traverse all its next siblings. In siblings count, int count equal to 0, while count plus current equal to current next sibling return count. Time complexity, O. Space complexity, O. Problem 41. Given a node in the generic tree, give an algorithm for counting the number of children for that node. Solution, since the tree is represented as first child next sibling method, the tree structure can be given as struct tree node, int data, struct tree node first child, struct tree node next sibling. For a given node in the tree, we just need to point to its first child and keep traversing all its next siblings. In child count, int count equal to 0, current first child, while count plus current next sibling return count. Time complexity, O. Space complexity, O. Problem -42. Given two trees. How do we check whether the trees are isomorphic to each other or not? Solution. Two binary trees, root and root, are isomorphic if they have the same structure. The values of the nodes does not affect whether two trees are isomorphic or not. In the diagram below, the tree in the middle is not isomorphic to the other trees, but the tree on the right is isomorphic to the tree on the left. Int isomorphic end. Root, return 1 if and root or end. Root, return 0, return and isomorphic. Time complexity, O. Space complexity, O. Problem -43. Given two trees. How do we check whether they are quasi-isomorphic to each other or not? Solution. Two trees, root and root, are quasi-isomorphic if root can be transformed into root by swapping the left and right children of some of the nodes of root. Data in the nodes are not important in determining quasi-isomorphism, only the shape is important. The trees below are quasi-isomorphic because if the children of the nodes on the left are swapped, the tree on the right is obtained. Int quasi-isomorphic if or return 0, return and quasi-isomorphic or quasi-isomorphic and quasi-isomorphic. Time complexity, O. Space complexity, O. Problem -44. A full k-array tree is a tree where each node has either 0 or k children. Given an array which contains the pre-ordered traversal of full k-array tree, give an algorithm for constructing the full k-array tree. Solution. In k-array tree, for a node at the ith position, its children will be at ki plus 1 to ki plus k. For example, the example below is for full 3-array tree. As we have seen, in pre-order traversal, first left subtree is processed, then followed by root node and right subtree. Because of this, to construct a full k-array, we just need to keep on creating the nodes without bothering about the previous constructed nodes. We can use this trick to build the tree recursively by using one global index. The declaration for k-mars array tree can be given as struct k-array tree node, struct k-array tree node child, int equal to 0, struct k-array tree node build k-array tree, int n int k equal to new node child build k-array tree, else new node child equal to null, return new node. Time complexity, O, where n is the size of the pre-order array. This is because we are moving sequentially and not visiting the already constructed nodes. 6.8 threaded binary tree traversals. In earlier sections, we have seen that pre-order, in-order, and post-order binary tree traversals use stacks and level order traversals use queues as an auxiliary data structure. In this section, we will discuss new traversal algorithms which do not need both stacks and queues. Such traversal algorithms are called threaded binary tree traversals or stack queue, less traversals. Issues with regular binary tree traversals. The storage space required for the stack and queue is large. The majority of pointers in any binary tree are null. For example, a binary tree with n nodes has n plus 1 null pointers and these were wasted. It is difficult to find successor node for a given node. Motivation for threaded binary trees. To solve these problems, one idea is to store some useful information in null pointers. If we observe the previous traversals carefully, stack queue is required because we have to record the current position in order to move to the right subtree after processing the left subtree. If we store the useful information in null pointers, then we don't have to store such information in stack queue. The binary trees which store such information in null pointers are called threaded binary trees. From the above discussion, let us assume that we want to store some useful information in null pointers. The next question is what to store. The common convention is to put predecessor-successor information. That means if we are dealing with pre-order traversals, then for a given node, null left pointer will contain pre-order predecessor information, and null right pointer will contain pre-order successor information. These special pointers are called threads. Classifying threaded binary trees. The classification is based on whether we are storing useful information in both null pointers or only in one of them. If we store predecessor information in null left pointers only, then we can call such binary trees left-threaded binary trees. If we store successor information in null right pointers only, then we can call such binary trees right-threaded binary trees. If we store predecessor information in null left pointers and successor information in null right pointers, then we can call such binary trees fully threaded binary trees or simply threaded binary trees. Note, for the remaining discussion, we consider only threaded binary trees. Types of threaded binary trees. Based on above discussion, we get 3 representations for threaded binary trees. Pre-order threaded binary trees, null left pointer will contain pre-order predecessor information, and null right pointer will contain pre-order successor information. In-order threaded binary trees, null left pointer will contain in-order predecessor information, and null right pointer will contain in-order successor information. Post-order threaded binary trees. Null left pointer will contain post-order predecessor information, and null right pointer will contain post-order successor information. Note, as the representations are similar, for the remaining discussion we will use in-order threaded binary trees, threaded binary tree structure. Any program examining the tree must be able to differentiate between a regular left-right pointer and a thread. To do this, we use 2 additional fields in each node, giving us, for threaded trees, nodes of the following form. Difference between binary tree and threaded binary tree structures. Note, similarly, we can define pre-order post-order differences as well. As an example, let us try representing a tree in in-order threaded binary tree form. The tree below shows what an in-order threaded binary tree will look like. The dotted arrows indicate the threads. If we observe the left pointer of leftmost node and right pointer of rightmost node are hanging, what should leftmost and rightmost pointers point to? In the representation of a threaded binary tree, it is convenient to use a special node dummy, which is always present even for an empty tree. Note that right tag of dummy node is 1, and its right child points to itself. With this convention, the above tree can be represented as dummy node. Finding an order successor in an order threaded binary tree. To find an order successor of a given node without using a stack, assume that the node for which we want to find the in-order successor is P. Strategy: if P has a no-right subtree, then return the right child of P. If P has right subtree, then return the left of the nearest node whose left subtree contains P. Struct threaded binary tree node in-order successor. Struct threaded binary tree node position if return P. Right, else equal to position P right. While position left, return position. Time complexity, O. Space complexity, O. In-order traversal in in-order threaded binary tree. We can start with dummy node and call in-order successor to visit each node until we reach dummy node. Void, in-order traversal, struct threaded binary tree node P equal to in-order successor, while P in-order successor, print EF. Alternative coding, void in-order traversal, struct threaded binary tree node P equal to root, while P in-order successor, if return, print F. Time complexity, O. Space complexity, O. Finding pre-order successor in in-order threaded binary tree. Strategy: if P has a left subtree, then return the left child of P. If P has no left subtree, then return the right child of the nearest node whose right subtree contains P. Struct threaded binary tree node pre-order successor, struct threaded binary tree node position, if else, return P left, position equal to P, while position equal to position right, return position right. Time complexity, O. Space complexity, O. Pre-order traversal of in-order threaded binary tree. As in in-order traversal, start with dummy node and call pre-order successor to visit each node until we get dummy node again. Void pre-order traversal, struct threaded binary tree node P equal to P pre-order successor, while P equal to pre-order successor, print EF. Alternative coding. Void pre-order traversal, struct threaded binary tree node P equal to root, while P equal to pre-order successor, if return, print F. Time complexity, O. Space complexity, O. Note: from the above discussion, it should be clear that in-order and pre-order successor finding is easy with threaded binary trees, but finding post-order successor is very difficult if we do not use stack. Insertion of nodes in in-order threaded binary trees. For simplicity, let us assume that there are two nodes P and Q, and we want to attach Q to right of P. For this, we will have two cases. Node P does not have right child. In this case, we just need to attach Q to P and change its left and right pointers. Node P has right child. In this case, we need to traverse R's left subtree and find the leftmost node, and then update the left and right pointer of that node. Void insert right in order, DBT, temp equal to Q right, while temp equal to temp left equal to Q, case 2. Time complexity, O. Space complexity, O. Threaded binary trees, problems and solutions. Problem 45 for a given binary tree. How do we find the pre-order successor? Solution: for solving this problem, we need to use an auxiliary stack S. On the first call, the parameter node is a pointer to the head of the tree, and thereafter its value is null. Since we are simply asking for the successor of the node we got the last time we called the function, it is necessary that the contents of the stack S and the pointer P to the last node visited are preserved from one call of the function to the next. They are defined as static variables. Or pre-order successor for an unthreaded binary tree, struct binary tree node pre-order successor, else, while P equal to pop, P equal to P right, return P. Problem -46 for a given binary tree. How do we find the in-order successor? Solution: similar to the above discussion, we can find the in-order successor of a node as in-order successor for an unthreaded binary tree, struct binary tree node in-order successor, static struct binary tree node P, static stack S equal to if P equal to node, create stack, if else, P equal to pop, P equal to P right, while push, P equal to P left, return P. 6.9 Expression trees. A tree representing an expression is called an expression tree. In expression trees, leaf nodes are operands and non-leaf nodes are operators. That means an expression tree is a binary tree where internal nodes are operators and leaves are operands. An expression tree consists of binary expression, but for a unary operator, one subtree will be empty. The figure below shows a simple expression tree for D. Algorithm for building expression tree from postfix expression. Struct binary tree node build XPR tree. In size, struct binary tree node new node equal to malloc. If else, new node data equal to postfix XPR. New node left equal to T1. New node right equal to T2. Push return S. Example: assume that one symbol is read at a time. If the symbol is an operand, we create a tree node and push a pointer to it onto a stack. If the symbol is an operator, pop pointers to two trees T1 and T2 from the stack and form a new tree whose root is the operator and whose left and right children point to T2 and T1 respectively. A pointer to this new tree is then pushed onto the stack. As an example, assume the input is ABC plus D. The first three symbols are operands, so create tree nodes and push pointers to them onto a stack as shown below. Next, an operator is read, so two pointers to trees are popped. A new tree is formed and a pointer to it is pushed onto the stack. Next, an operator plus is read, so two pointers to trees are popped. A new tree is formed and a pointer to it is pushed onto the stack. Next, an operand D is read. A one-node tree is created and a pointer to the corresponding tree is pushed onto the stack. Finally, the last symbol is read. Two trees are merged and a pointer to the final tree is left on the stack. 6.10 XOR trees. This concept is similar to memory-efficient doubly linked lists of linked lists chapter. Also, like threaded binary trees, this representation does not need stacks or queues for traversing the trees. This representation is used for traversing back and forth using operation. To represent the same in XOR trees, for each node below are the rules used for representation. Each node's left will have the of its parent and its left children. Each node's right will have the of its parent and its right children. The root node's parent is null, and also leaf node's children are null nodes. Based on the above rules and discussion, the tree can be represented as. The major objective of this presentation is the ability to move the parent as well to children. Now, let us see how to use this representation for traversing the tree. For example, if we are at node B and want to move to its parent node A, then we just need to perform on its left content with its left child address. Similarly, if we want to move to its child, then we have to perform on its left content with its parent node address. One important point that we need to understand about this representation is, when we are at node B, how do we know the address of its children D? Since the traversal starts at node root node, we can apply on root's left content with null. As a result, we get its left child B. When we are at B, we can apply on its left content with A address. 6.1 binary search trees. Why binary search trees? In previous sections, we have discussed different tree representations, and in all of them, we did not impose any restriction on the node's data. As a result, to search for an element, we need to check both in left subtree and in right subtree. Due to this, the worst case complexity of search operation is O. In this section, we will discuss another variant of binary trees, binary search trees. As the name suggests, the main use of this representation is for searching. In this representation, we impose restriction on the kind of data a node can contain. As a result, it reduces the worst case average search operation to O binary search tree property. In binary search trees, all the left subtree elements should be less than root data, and all the right subtree elements should be greater than root data. This is called binary search tree property. Note that this property should be satisfied at every node in the tree. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search trees. Example, the left tree is a binary search tree, and the right tree is not a binary search tree. Binary search tree declaration. There is no difference between regular binary tree declaration and binary search tree declaration. The difference is only in data but not in structure, but for our convenience we change the structure name as operations on binary search trees. Main. Operations following are the main operations that are supported by binary search trees. Find minimum, find maximum element in binary search trees, inserting an element in binary search trees, deleting an element from binary search trees, auxiliary operations checking whether the given tree is a binary search tree or not, finding kth smallest element in tree, sorting the elements of binary search tree, and many more. Important notes on binary search trees. Since root data is always between left subtree data and right subtree data, performing in-order traversal on binary search tree produces a sorted list. While solving problems on binary search trees, first we process left subtree, then root data, and finally, we process right subtree. This means, depending on the problem, only the intermediate step changes, and we do not touch the first and third steps. If we are searching for an element, and if the left subtree root data is less than the element we want to search, then skip it. The same is the case with the right subtree. Because of this, binary search trees take less time for searching an element than regular binary trees. In other words, the binary search trees consider either left or right subtrees for searching an element, but not both. The basic operations that can be performed on binary search tree are insertion of element, deletion of element, and searching for an element. While performing these operations on BST, the height of the tree gets changed each time. Hence, there exists variations in time complexities of best case, average case, and worst case. The basic operations on a binary search tree take time proportional to the height of the tree. For a complete binary tree with node n, such operations runs in O worst case time. If the tree is a linear chain of n nodes, however, the same operations takes O worst case time. Finding an element in binary search trees. Find operation is straightforward in a BST. Start with the root and keep moving left or right using the BST property. If the data we are searching is same as node's data, then we return current node. If the data we are searching is less than node's data, then search left subtree of current node, otherwise search right subtree of current node. If the data is not present, we end up in a null. Link, struct binary search tree node find, if return null, if return find, else if return root. Time complexity O in worst case. Space complexity O for recursive stack. Non-recursive version of the above algorithm can be given as struct binary search tree node find return null, while if return root, else if root equal to root right, else root equal to root left, one return null. Time complexity O, space complexity O. Finding minimum element in binary search trees. In BSTs, the minimum element is the leftmost node, which does not has left child. In the BST below, the minimum element is 4. Struct binary search tree node find min, if return null, else if else return root, return find min. Time complexity O in worst case. Space complexity O for recursive stack. Non-recursive version of the above algorithm can be given as struct binary search tree node find min, if return null, while root equal to root left, return root. Time complexity O, space complexity O. Finding maximum element in binary search trees. In BSTs, the maximum element is the rightmost node, which does not have right child. In the BST below, the maximum element is 16. Struct binary search tree node find max, if return null, else if return root, else return find max. Time complexity O in worst case. Space complexity O for recursive stack. Struct binary search tree node find max, if return null, while root equal to root right, return root. Time complexity O, space complexity O. Where is in order predecessor and successor? Where is the in-order predecessor and successor of node X in a binary search tree, assuming all keys are distinct? If X has 2 children, then its in-order predecessor is the maximum value in its left subtree, and its in-order successor the minimum value in its right subtree. Predecessor. If it does not have a left child, then a node's in-order predecessor is its first left ancestor, inserting an element from binary search tree. To insert data into binary search tree, first we need to find the location for that element. We can find the location of insertion by following the same mechanism as that of find operation. While finding the location, if the data is already there, then we can simply neglect and come out. Otherwise, insert data at the last location on the path traversed. As an example, let us consider the following tree. The dotted node indicates the element to be inserted. To insert 5, traverse the tree using find function. At node with key 4, we need to go right, but there is no subtree, so 5 is not in the tree, and this is the correct location for insertion. Struct binary search tree node insert return root. Note, in the above code, after inserting an element in subtrees, the tree is returned to its parent. As a result, the complete tree will get updated. Time complexity O. Space complexity O for recursive stack. For iterative version, space complexity is O. Deleting an element from binary search tree. The delete operation is more complicated than other operations. This is because the element to be deleted may not be the leaf node. In this operation also, first we need to find the location of the element which we want to delete. Once we have found the node to be deleted, consider the following cases. If the element to be deleted is a leaf node, return null to its parent. That means make the corresponding child pointer null. In the tree below, to delete 5, set null to its parent node 2. If the element to be deleted has one child, in this case, we just need to send the current node's child to its parent. In the tree below, to delete 4 left subtree is set to its parent node 2. If the element to be deleted has both children, the general strategy is to replace the key of this node with the largest element of the left subtree and recursively delete that node. The largest node in the left subtree cannot have a right child, so the second delete is an easy one. As an example, let us consider the following tree. In the tree below, to delete 8, it is the right child of the root. The key value is 8. It is replaced with the largest key in its left subtree, and then that node is deleted as before. Note, we can replace with minimum element in right subtree also. Struct binary search tree node delete. Found element if return root. Time complexity O. Space complexity O for recursive stack. For iterative version, space complexity is O. Binary search trees, problems and solutions. Note, for ordering related problems with binary search trees and balanced binary search trees, in-order traversal has advantages over others as it gives the sorted order. Problem -47 given pointers to 2 nodes in a binary search tree. Find the lowest common ancestor. Assume that both values already exist in the tree. Solution. The main idea of the solution is, while traversing BST from root to bottom, the first node we encounter with value between A and SS, that is a node data less than SS, is the least common ancestor of A and SS. So just traverse the BST in pre-order, and if we find a node with value in between A and SS, then that node is the LCA. If its value is greater than both A and SS, then the LCA lies on the left side of the node, and if its value is smaller than both A and SS, then the LCA lies on the right side. Struct binary search tree node find LCA. While if or a return root, if root root left equal to else root equal to root right, A data root data, and in B data root data all. Time complexity, O. Space complexity, O for skew trees. Problem -48 give an algorithm for finding the shortest path between two nodes in a BST. Solution, it's nothing but finding the LCA of two nodes in BST. Problem -49 give an algorithm for counting the number of BSTs possible with n nodes. Solution, this is a DP problem. Refer to chapter on dynamic programming for the algorithm. Give an algorithm to check whether the given binary tree is a BST or not. Problem -50% solution. Consider the following simple program. For each node, check if the node on its left is smaller, and check if the node on its right is greater. This approach is wrong as this will return true for binary tree below. Checking only a current node is not enough. In TSBST, if return 1. False if left is then root if return 0. False if right is then root if return 0. Or false if, recursively, the left or right is not a BST if or SBST, return 0. Passing all that, it's a BST, return 1. Problem 51, can we think of getting the correct algorithm? Solution, for each node, check if max value in left subtree is smaller than the current node data and min value in right subtree greater than the node data. It is assumed that we have helper functions find min and find max that return the min or max integer value from a non-empty tree. Returns true if a binary tree is a binary search tree. Int ISBST, if return 1. False if the max of the left is then root. If root data, return 0. False if the min of the right is less than equal to than root. If root data, return 0. False if recursively, the left or right is not a BST. If or ISBST, return 0. Passing all that, it's a BST. Return 1. Time complexity, O. Space complexity, O. Problem 52. Can we improve the complexity of problem 51? Solution, yes. A better solution is to look at each node only once. The trick is to write a utility helper function isBestUtil that traverses down the tree keeping track of the narrowing min and max allowed values as it goes, looking at each node only once. The initial values for min and max should be int min and int max. They narrow from there. Initial call ISBST, int ISBST if return 1, return and end ISBST util. Time complexity, O. Space complexity, O for stack space. Problem -53. Can we further improve the complexity of problem 51? Solution, yes, by using in-order traversal. The idea behind the solution is that in-order traversal of BST produces sorted lists. While traversing the BST in order, at each node check the condition that its key value should be greater than the key value of its previous visited node. Also, we need to initialize the prev with possible minimum integer value. Int prev equal to int min, int ISBST, if return 1, if return 0, if return 0, prev equal to root data, return ISBST. Time complexity, O. Space complexity, O for stack space. Problem 54, give an algorithm for converting BST, the circular DLL with space complexity, O. Solution, convert left and right subtrees to DLS and maintain end of those lists. Then, adjust the pointers. Struct binary search tree node BST2DLL. Struct binary search tree node, left, itail, right, rtail, if itail equal to null, return null, left BST2DLL, equal to right BST2DLL, root left equal to itail, root right equal to right, if else, itail equal to root, right left equal to root, itail equal to rtail, if return root, else, itail right equal to root, return left. Time complexity, O. Problem 55 for problem 54, is there any other way of solving it? Solution, yes. There is an alternative solution based on the divide and conquer method, which is quite neat. Struct binary search tree, node append return B, if return A last, A left, blast B left, A last, right equal to B, B left equal to A last, blast right equal to A left equal to blast, return A, struct binary search tree node tree to list, struct binary search tree node alist, B list, if return null, A list tree to list, equal to B list tree to list, root left equal to root right equal to root, equal to A list append, return. Tree node B. Time complexity, O. Problem 56. Given a sorted doubly linked list, give an algorithm for converting it into balanced binary search tree. Solution, find the middle node and adjust the pointers. Struct DL node DLLTO balanced BST. Struct DL node temp, P, Q, if return head, temp equal to find middle node, P equal to head, while P equal to P next equal to null, Q equal to temp next equal to null, temp prev equal to DLLTO balanced BST, temp next equal to DLLTO balanced BST, return temp. Time complexity, 2 trillions plus O equal to O. Note, for find middle node function, refer linked lists chapter. Problem 57, given a sorted array, give an algorithm for converting the array to BST. Solution, if we have to choose an array element to be the root of a balanced BST, which element should we pick? The root of a balanced BST should be the middle element from the sorted array. We would pick the middle element from the sorted array in each iteration. We then create a node in the tree initialized with this element. After the element is chosen, what is left? Could you identify the sub-problems within the problem? There are 2 arrays left, the one on its left and the one on its right. These 2 arrays are the sub-problems of the original problem since both of them are sorted. Furthermore, they are subtrees of the current node's left and right child. The code below creates a balanced BST from the sorted array in O time. Compare how similar the code is to a binary search algorithm. Both are using the divide and conquer methodology. Struct binary tree node build BST, int left, int right, struct binary tree node new node, int mid, if return null, new node malloc, if printf, return if, new node data equal to A, new node left, new node right equal to null, else mid left plus 2, new node data equal to A, new node left build BST equal to new node right build BST, return new node. Time complexity, O. Space complexity, O for stack space. Problem 58, given a singly linked list where elements are sorted in ascending order, convert it to a height balanced BST. Solution. A naive way is to apply the problem 56% solution directly. In each recursive call, we would have to traverse half of the list's length to find the middle element. The runtime complexity is clearly O, where n is the total number of elements in the list. This is because each level of recursive call requires a total of n/2 traversal steps in the list, and there are a total of ln number of levels. Problem 59 for problem 58, can we improve the complexity? Solution, hint, how about inserting nodes following the list order? If we can achieve this, we no longer need to find the middle element as we are able to traverse the list while inserting nodes to the tree. Best solution. As usual, the best solution requires us to think from another perspective. In other words, we no longer create nodes in the tree using the top-down approach. Create nodes bottom-up and assign them to their parents. The bottom-up approach enables us to access the list in its order while creating nodes. Isn't the bottom-up approach precise? Anytime we are stuck with the top-down approach, we can give bottom-up a try. Although the bottom-up approach is not the most natural way we think, it is helpful in some cases. However, we should prefer top-down instead of bottom-up in general, since the latter is more difficult to verify. Below is the code for converting a singly linked list to a balanced BST. Please note that the algorithm requires the list length to be passed in as the function parameters. The list length can be found in O time by traversing the entire list once. The recursive calls traverse the list and create tree nodes by the list order, which also takes O time. Therefore, the overall runtime complexity is still O. Struct binary tree node sorted list to BST if return null, same as /2, avoids overflow into mid-start plus. 2. Struct binary tree node left child sorted list to BST, struct binary tree node parent malloc if printf return parent data list data parent left equal to left child list next equal to parent right sorted list to BST, return parent struct binary tree node sorted list to BST, return sorted list to BST. Problem 60, give an algorithm for finding the kth smallest element in BST. Solution. The idea behind this solution is that in order traversal of BST produces sorted lists. While traversing the BST in order, keep track of the number of elements visited. Struct binary search tree node cast smallest in BST if return null, struct binary search tree node left equal to cast smallest in BST if return left, if return root, return kth smallest in BST. Oh, space complexity. Oh, problem -61 floor and ceiling. If a given key is less than the key at the root of a BST, then the floor of the key must be in the left subtree. If the key is greater than the key at the root, then the floor of the key could be in the right subtree, but only if there is a key smaller than or equal to the key in the right subtree. If not, then the key at the root is the floor of the key. Finding the ceiling is similar with interchanging right and left. For example, if the sorted with input array is, then for x equal to 0, floor doesn't exist in array, ceil equal to 1, for x equal to 1, floor equal to 1, ceil equal to 1 for x equal to 5, floor equal to 2, ceil equal to 8, for x equal to 20, floor equal to 19, ceil doesn't exist in array. Solution. The idea behind this solution is that in order traversal of BST produces sorted lists. While traversing the BST in order, keep track of the values being visited. If the root's data is greater than the given value, then return the previous value which we have maintained during traversal. If the root's data is equal to the given data, then return root data. Struct binary tree node floor in BST, struct binary tree node prev equal to null. Return floor in BST util, struct binary tree node floor in BST util return null, struct binary tree node prev in data, if return 0, if return root, if return prev equal to root, return floor in BST util. Time complexity, O. Space complexity, O for stack space. For ceiling, we just need to call the right subtree first, followed by left subtree. Struct binary tree node ceiling in BST, struct binary tree node prev equal to null, return ceiling in BST util, struct binary tree node ceiling in BST util, struct binary tree node prev into data, return null, if return 0, if return root, if return prev equal to root, return ceiling in BST util. Time complexity, O. Space complexity, O for stack space. Problem 62. Give an algorithm for finding the union and intersection of BSTs. Assume parent pointers are available. Also, assume the lengths of two BSTs are m and n respectively. Solution. If parent pointers are available, then the problem is same as merging of two sorted lists. This is because if we call in order successor each time we get the next highest element, it's just a matter of which in order successor to call. Time complexity, O. Space complexity, O. Problem 63 for problem 62. What if parent pointers are not available? Solution. If parent pointers are not available, the BSTs can be converted to linked lists and then merged. 1. Convert both the BSTs into sorted doubly linked lists in O time. This produces two sorted lists. 2. Merge the two double linked lists into one and also maintain the count of total elements in O time. 3. Convert the sorted doubly linked list into height balanced tree in O time. Problem 64. For problem 62, is there any alternative way of solving the problem? Solution. Yes, by using in-order traversal. Perform in-order traversal on one of the BSTs. While performing the traversal, store them in table. After completion of the traversal of first BST, start traversal of second BST, and compare them with hash table contents. Time complexity, O. Space complexity, O. Problem -65. Given a BST and two numbers K1 and K2, give an algorithm for printing all the elements of BST in the range K1 and K2. Solution. Void range printer if return, if range printer, if printf, if range printer. Time complexity, O. Space complexity, O for stack space. Problem 66 for problem 65. Is there any alternative way of solving the problem? Solution. We can use level order traversal while adding the elements to Q check for the range. Void range seach level order, struct binary search tree node temp, struct Q create Q if return null, Q equal to on Q, while temp to Q if printf, if in Q delete Q, return null. Time complexity, O. Space complexity, O for Q. Problem -67 for problem 65. Can we still think of an alternative way to solve the problem? Solution. First locate K1 with normal binary search and after that use in order successor until we encounter K2. For algorithm, refer to problem section of threaded binary trees. Problem 68, given root of a binary search tree, trim the tree so that all elements returned in the new tree are between the inputs A and B. Solution. It's just another way of asking problem 65. Problem -69, given two BSTs, check whether the elements of them are the same or not. For example, two BSTs with data 105 2015 30 and 10 20 15 35 should return true, and the dataset with 105 21,500 data, and the dataset with return true. Note, BN 30 205 15 32 and its data in hash table. And 10 50 step perform in order traversal on second tree and check whether that data is already there in hash table or not. During the traversal of second tree, if we find any mismatch, return false. After traversal of second tree, check whether it has all -1 second in the hash table or not. Time complexity, O, where m and n are the number of elements in first and second BST. Space complexity, O. This depends on the size of the first tree. Problem -70 for problem -69. Can we reduce the time complexity? Solution. Instead of performing the traversals one after the other, we can perform in-order traversal of both the trees in parallel. Since the in-order traversal gives the sorted list, we can check whether both the trees are generating the same sequence or not. Time complexity, O. Complexity, O. This depends on the size of the first tree. Problem 71 for the key values. 1. N. How many structurally unique BSTs are possible that store those keys? Solution, strategy, consider that each value could be the root. Recursively find the size of the left and right subtrees. In count trees, if return 1, else, there will be one value at the root, with whatever remains on the left and right, each forming their own subtrees. Iterate through all the values that could be the root. Int sum equal to 0, int left, right, root, for left count trees equal to right count trees. Number of possible trees with this root equal to left, right sum, plus equal to left, right, return. Problem 72 given a BST of size n, in which each node R has an additional field R size, the number of the keys in the subtree rooted at R, given O algorithm greater than constant to find the number of keys that are strictly greater than K. Solution. Int greater than constant if return keys count. The suggested algorithm works well if the key is a unique value for each node. Otherwise, when reaching K equal to R data, we should start a process of moving to the right until reaching a node Y with a key that is bigger than K, and then we should return keys count plus Y, size. Time complexity, O where H equal to O in the worst case and O in the average case. 6.12 balanced binary search trees. In earlier sections, we have seen different trees whose worst case complexity is O, where n is the number of nodes in the tree. This happens when the trees are skew trees. In this section, we will try to reduce this worst case complexity to O by imposing restrictions on the heights. In general, the height balanced trees are represented with HB, where K is the difference between left subtree height and right subtree height. Sometimes K is called balance factor. Full balanced binary search trees. In HB, if K equal to 0, then we call such binary search trees as full balanced binary search trees. That means in HB binary search tree, the difference between left subtree height and right subtree height should be at most 0. This ensures that the tree is a full binary tree. For example, note, for constructing HB tree, refer to problem section. 6.13 AVL trees. In HB, if K equal to 1, such a binary search tree is called an AVL tree. That means an AVL tree is a binary search tree with a balanced condition. The difference between left subtree height and right subtree height is at most 1. Properties of AVL trees. A binary tree is said to be an AVL tree if it is a binary search tree, and for any node X, the height of left subtree of X and height of right subtree of X differ by at most 1. As an example, among the above binary search trees, the left one is not an AVL tree, whereas the right binary search tree is an AVL tree. Minimum, maximum number of nodes in AVL tree. For simplicity, let us assume that the height of an AVL tree is H, and N indicates the number of nodes in AVL tree with height H. To get the minimum number of nodes with height H, we should fill the tree with the minimum number of nodes possible. That means if we fill the left subtree with height H1, then we should fill the right subtree with height H2. As a result, the minimum number of nodes with height H is, in the above equation, N indicates the minimum number of nodes with height H1. N indicates the minimum number of nodes with height H2. In the above expression, 1 indicates the current node. We can give N either for left subtree or right subtree. Solving the above recurrence gives, where N is the number of nodes in AVL tree. Also, the above derivation says that the maximum height in AVL trees is O. Similarly, to get maximum number of nodes, we need to fill both left and right subtrees with height H1. As a result, we get, the above expression defines the case of full binary tree. Solving the recurrence, we get, in both the cases, AVL tree property is ensuring that the height of an AVL tree with n nodes is O. AVL tree declaration. Since AVL tree is a BST, the declaration of AVL is similar to that of BST. But just to simplify the operations, we also include the height as part of the declaration. Struct AVL tree node, struct AVL tree node left, int data, struct AVL tree node right, int height, finding the height of an AVL tree. Int height, if else return -1, return root, height. Time complexity, O, rotations. When the tree structure changes, we need to modify the tree to restore the AVL tree property. This can be done using single rotations or double rotations. Since an insertion deletion involves deleting a single node, this can only decrease the height of a subtree by 1. So if the AVL tree property is violated at a node X, it means that the heights of left and right differ by exactly 2%. This is because if we balance the AVL tree every time, then at any point, the difference in heights of left and right differ by exactly 2. Rotations is the technique used for restoring the AVL tree property. This means we need to apply the rotations for the node 10th observation. One important observation is that after an insertion, only nodes that are on the path from the insertion point to the root might have their balances altered, because only those nodes have their subtrees altered. To restore the AVL tree property, we start at the insertion point and keep going to the root of the tree. While moving to the root, we need to consider the first node that is not satisfying the AVL property. From that node onwards, every node on the path to the root will have the issue. Also, if we fix the issue for that first node, then all other nodes on the path to the root will automatically satisfy the AVL tree property. That means we always need to care for the first node that is not satisfying the AVL property on the path from the insertion point to the root and fix it. Types of violations. Let us assume the node that must be rebalanced is 10th, since any node has at most 2 children, and a height imbalance requires that X's 2 subtree heights differ by 2. We can observe that a violation might occur in 4 cases. 1. An insertion into the left subtree of the left child of 10th 2. An insertion into the right subtree of the left child of 10th 3. An insertion into the left subtree of the right child of 10th 4. An insertion into the right subtree of the right child of 10th cases 1 and 4 are symmetric and easily solved with single rotations. Similarly, cases 2 and 3 are also symmetric and can be solved with double rotations. Single rotations. Left-left rotation. In the case below, node X is not satisfying the AVL tree property. As discussed earlier, the rotation does not have to be done at the root of a tree. In general, we start at the node inserted and travel up the tree, updating the balance information at every node on the path. For example, in the figure above, after the insertion of 7 in the original AVL tree on the left, node 9 becomes unbalanced. So, we do a single left-left rotation at 9. As a result, we get the tree on the right. Struct AVL tree node single rotate left, struct AVL tree node W equal to X left equal to W right equal to X height equal to max, height plus 1, W height equal to max, X height plus 1, return W, new root. O, space complexity. O, right rotation. In this case, node X is not satisfying the AVL tree property. For example, in the figure, after the insertion of 29 in the original AVL tree on the left, node 15 becomes unbalanced. So, we do a single right rotation at 15. As a result, we get the tree on the right. Struct AVL tree node single rotate right, struct AVL tree node X equal to W right equal to X left equal to W height equal to max, height plus 1, X height max, W height plus 1, return X. O, space complexity. O, double rotations. Left-right rotation. For case 2 and case 3 single rotation does not fix the problem. We need to perform 2 rotations. As an example, let us consider the following tree. The insertion of 7 is creating the case 2 scenario, and the right side tree is the one after the double rotation. Code for left-right double rotation can be given as struct AVL tree node double rotate with left, z left single rotate right, return single rotate left. Right-left rotation, similar to case 2, we need to perform 2 rotations to fix this scenario. As an example, let us consider the following tree. The insertion of 6 is creating the case 3 scenario, and the right side tree is the one after the double rotation. Insertion into an AVL tree. Insertion into an AVL tree is similar to a BST insertion. After inserting the element, we just need to check whether there is any height imbalance. If there is an imbalance, call the appropriate rotation functions. Struct AVL tree node insert, root malloc, if 1 printf, return null, else root data equal to data. Root height equal to 0, root left, root right equal to null, else if root left insert, if height equal to 2, if else equal to root single rotate left, root double rotate left, else if root right insert, if height equal to 2, if equal to root single rotate right, else root double rotate right, else data is in the tree already. We'll do nothing. Root height max, height, plus 1, return root complexity, space complexity, int data, time. AVL trees, problems and solutions, problem 73. Given a height h, give an algorithm for generating the HB. Solution, as we have discussed, HB is nothing but generating full binary tree. In full binary tree, the number of nodes with height h is 2 hours 1 to 1. As a result, the nodes can be numbered as 1 to 2 hours plus 1 to 1. Struct binary search tree node build HBO return null equal to temp malloc equal to temp left build HB0 equal to temp data count plus plus. Assume count is a global variable temp right build HB0 return temp equal to. Time complexity, O. Space complexity, O, where lone indicates the maximum stack size, which is equal to height of tree. Problem minus 74. Is there any alternative way of solving problem 73? Solution, yes, we can solve it following merge sort logic. That means, instead of working with height, we can take the range. With this approach, we do not need any global counter to be maintained. Struct binary search tree node build HB0 return null, temp malloc, temp data equal to mid, temp left build the HB0 equal to temp right build HB0 return temp. The initial call to the build HBO function could be build the HB0. 1h does the shift operation for calculating the 2 hours plus 1 to 1. Time complexity, O. Space complexity, O, where lone indicates maximum stack size, which is equal to the height of the tree. Problem 75 construct minimal AVL trees of height 0, 1, 2, 3, 4, and 5. What is the number of nodes in a minimal AVL tree of height 6? Solution, let n be the number of nodes in a minimal AVL tree with height h. N equal to 2, n equal to 1n plus n equal to 1n plus n equal to 1 plus 2 plus 1 equal to 4, n equal to 1 plus n 1 plus 4 plus 2 equal to 7, n 1n plus n equal to 1 plus 7 plus 4 equal to 12, 0, n equal to 1n plus n equal to 1 plus 12 plus 7 equal to 20. Problem 76 for problem 73. How many different shapes can there be of a minimal AVL tree? Of height h? Solution. Let ns be the number of different shapes of a minimal AVL tree of height h. ns equal to 2. ns equal to 2 nanoseconds. ns equal to 2 times 2, 1 equal to 4. 0. ns 2 nanoseconds. ns equal to 2, 4, 1 equal to 8. Ans equal to 2 nanoseconds. ns. Problem 77. Given a binary search tree, check whether it is an AVL tree or not. Solution. Let us assume that eCivil is the function which checks whether the given binary search tree is an AVL tree or not. isAVL returns -1 if the tree is not an AVL tree. During the checks, each node sends its height to its parent. int is AVL, int left right if return 0, left equal to eCivil, if return left equal to right is AVL, if return right if 1, return -1, return max plus 1. O. Space complexity. O. Problem 78. Given a height h, give an algorithm to generate an AVL tree with minimum number of nodes. Solution. To get minimum number of nodes, fill one level with h1 and the other with h2. Struct AVL tree node generate AVL tree return null, temp malloc equal to temp left generate AVL tree equal to temp data count plus plus. Assume count is a global variable equal to temp right generate AVL tree, temp left height plus 1, or temp height equal to h, return temp. Problem minus 79. Given an AVL tree with n integer items and 2 integers a and b, where a and b can be any integers with a less than equal to b. Implement an algorithm to count the number of nodes in the range. Solution. The idea is to make use of the recursive property of binary search trees. There are 3 cases to consider, whether the current node is in the range, on the left side of the range, or on the right side of the range. Only subtrees that possibly contain the nodes will be processed under each of the 3 cases. Int range count if return 0, else if return range count, else if return range count, else if return range count plus 1. The complexity is similar to in order traversal of the tree, but skipping left or right subtrees when they do not contain any answers. So in the worst case, if the range covers all the nodes in the tree, we need to traverse all the n nodes to get the answer. The worst time complexity is therefore O. If the range is small, which only covers a few elements in a small subtree at the bottom of the tree, the time complexity will be O equal to O, where h is the height of the tree. This is because only a single path is traversed to reach the small subtree at the bottom, and many higher level subtrees have been pruned along the way. Note, refer similar problem in BST. Problem minus 80 given a BST, where each node contains 2 data elements as shown below. Convert the tree to another BST by replacing the second data element with previous node data in order traversal. Note that each node is merged with in-order previous node data. Also make sure that conversion happens in place. Solution, the simplest way is to use level order traversal. If the number of elements in the left subtree is greater than the number of elements in the right subtree, find the maximum element in the left subtree and replace the current node's second data element with it. Similarly, if the number of elements in the left subtree is less than the number of elements in the right subtree, find the minimum element in the right subtree and replace the current node's second data element with it. Struct BST tree compression, struct BST temp struct Q equal to create Q if return on Q. While temp equal to DQ, if temp equal to find max, else temp find min, temp data temp. Process current node, remember to delete this node. Delete node in BST, if in Q, delete Q. Time complexity, O on average, since BST takes O on average to find the maximum or minimum element. Space complexity, O, since in the worst case, all the nodes on the entire last level could be in the queue simultaneously. Problem minus 81. Can we reduce time complexity for the previous problem? Solution. Let us try using an approach that is similar to what we followed in problem 60. The idea behind the solution is that in order traversal of BST produces sorted lists. While traversing the BST in order, keep track of the elements visited and merge them. Struct binary search tree node tree compression return null into previous node data equal to previous node data equal to int min return tree compression. Time complexity O space complexity O. Note that we are still having recursive stack space for in-order traversal. Problem -82 key. Given a BST and a key, find the element in the BST which is closest to the given. Solution. As a simple solution, we can use level order traversal and for every element compute the difference between the given key and the element's value. If that difference is less than the previous maintained difference, then update the difference with this new minimum value. With this approach, at the end of the traversal, we will get the element which is closest to the given key. Int closest in BST, difference abs, element equal to temp, 1 if and q, delete q, return element, data. Time complexity, O, space complexity, O. Problem 83 for problem 82, can we solve it using the recursive approach? Solution, the approach is similar to problem 18. Following is a simple algorithm for finding the closest value in BST. 1. If the root is null, then the closest value is 0. 2. If the root's data matches the given key, then the closest is the root. 3. Else, consider the root as the closest and do the following. A. If the key is smaller than the root data, find the closest on the left side tree of the root recursively and call it temp. 4. B. If the key is larger than the root data, find the closest on the right side tree of the root recursively and call it temp. Return the root or temp depending on whichever is nearer to the given key. Struct binary tree node closest in BSD. Else, if return root, temp equal to closest in BST, return abs, root, temp, return null. Time complexity, O in worst case, and in average case it is O. Space complexity, O in worst case, and in average case it is O. Problem -84 median in an infinite series of integers. Solution, median is the middle number in a sorted list of numbers. If we have even number of elements, median is the average of two middle numbers in a sorted list of numbers. For solving this problem, we can use a binary search tree with additional information at each node, and the number of children on the left and right subtrees. We also keep the number of total nodes in the tree. Using this additional information, we can find the median in no time, taking the appropriate branch in the tree based on the number of children on the left and right of the current node. But the insertion complexity is O, because a standard binary search tree can degenerate into a linked list if we happen to receive the numbers in sorted order. So, let's use a balanced binary search tree to avoid worst-case behavior of standard binary search trees. For this problem, the balance factor is the number of nodes in the left subtree minus the number of nodes in the right subtree, and only the nodes with a balance factor of +1 or 0 are considered to be balanced. So, the number of nodes on the left subtree is either equal to or 1 more than the number of nodes on the right subtree, but not less. If we ensure this balance factor on every node in the tree, then the root of the tree is the median if the number of elements is odd. In the number of elements is even, the median is the average of the root and its in-order successor, which is the leftmost descendant of its right subtree. So, the complexity of insertion maintaining a balance condition is O, and finding a median operation is O assuming we calculate the in-order successor of the root at every insertion, if the number of nodes is even. Insertion and balancing is very similar to AVL trees. Instead of updating the heights, we update the number of nodes information. Balanced binary search trees seem to be the most optimal solution. Insertion is O, and find median is O. Note, for an efficient algorithm, refer to the priority queues in Heaps chapter. Problem 85, given a binary tree, how do you remove all the half nodes? Note that we should not touch leaves. Solution, by using post-order traversal, we can solve this problem efficiently. We first process the left children, then the right children, and finally the node itself. So we form the new tree bottom up, starting from the leaves towards the root. By the time we process the current node, both its left and right subtrees have already been processed. Struct binary tree node remove half nodes if return null, root left remove half nodes, root right remove half nodes, if return root right, if return root left, return root. Time complexity, O, problem -86. Given a binary tree, how do you remove its leaves? Solution, by using post-order traversal, we can solve this problem. Struct binary tree node remove leaves else equal to root left remove leaves, root right remove leaves, return root. Time complexity, O, problem 87. Given a BST and two integers as parameters, how do you remove elements that are not within that range? 2, 5, 25. Solution, observation. Since we need to check each and every element in the tree, and the subtree changes should be reflected in the parent, we can think about using post-order traversal. So we process the node starting from the leaves towards the root. As a result, while processing the node itself, both its left and right subtrees are valid pruned BSTs. At each node, we will return a pointer based on its value, which will then be assigned to its parent's left or right child pointer, depending on whether the current node is the left or right child of the parent. If the current node's value is between A and B, then no action needs to be taken, so we return the reference to the node itself. If the current node's value is less than A, then we return the reference to its right subtree and discard the left subtree, because if a node's value is less than A, then its left children are definitely less than A, since this is a binary search tree. But its right children may or may not be less than A, we can't be sure, so we return the reference to it. Since we're performing bottom-up post-order traversal, its right subtree is already a trimmed valid binary search tree, and its left subtree is definitely null because those nodes were surely less than A and they were eliminated during the post-order traversal. A similar situation occurs when the node's value is greater than B, so we now return the reference to its left subtree. Because if A node's value is greater than B, then its right children are definitely greater than B. But its left children may or may not be greater than B, so we discard the right subtree and return the reference to the already valid left subtree. Struct binary search tree node prune BST, if return null, root left prune BST, root right prune BST, if return root right, if return root left. Time complexity, O in worst case and in average case it is O. Note, if the given BST is an AVL tree, then O is the average time complexity. Problem -88, given a binary tree, how do you connect all the adjacent nodes at the same level? Assume that given binary tree has next pointer along with left and right pointers as shown below. Struct binary tree node, int data, struct binary tree node left, struct binary tree node right, struct binary tree node next. Solution, one simple approach is to use level order traversal and keep updating the next pointers. While traversing, we will link the nodes on the next level. If the node has left and right node, we will link left to right. If node has next node, then link rightmost child of current node, the leftmost child of next node. Void linking node of same level, struct QQ equal to create Q, struct binary tree node prev, pointer to the previous node of the current level struct binary tree node temp, and current level node account. Next level node account if return, on Q, current level node account equal to 1, next level node account equal to 0, prev equal to null, while temp equal to DQ if on Q, next level node account plus plus if on Q, next level node account plus plus, link the previous node of the current level to this node if prev next equal to temp, set the previous node to the current prev equal to temp, current level node account. If this is the last node of the current level node account equal to next level node account equal to 0, prev equal to null. Time complexity, O. Space complexity, O. Problem minus 89. Can we improve space complexity for problem 88? Solution. We can process the tree level by level, but without a queue. The logical part is that when we process the nodes of the next level, we make sure that the current level has already been linked. Void linking node self, FAMA level, if return, struct binary tree node rightmost node equal to null, next head equal to null, temp equal to root. Connect next level of current root node level, while if rightmost node temp left, next head temp left, else rightmost node, next equal to temp, left rightmost node equal to rightmost node, next if rightmost node temp right, next head temp right, else rightmost node. Next, temp right, rightmost node equal to rightmost node, next temp next, linking nodes off same level. Time complexity, O. Space complexity, O for stack space. Problem 90. Assume that a set S of n numbers are stored in some form of balanced binary search tree, that is the depth of the tree is O. In addition to the key value and the pointers to children, assume that every node contains the number of nodes in its subtree. Specify a reason why a balanced binary tree can be a better option than a complete binary tree for storing the set S. Solution. Implementation of a balanced binary tree requires less RAM space as we do not need to keep the complete tree in RAM. Problem 91 for the problem 90. Specify a reason why a complete binary tree can be a better option than a balanced binary tree for storing the set S. Solution. A complete binary tree is more space efficient as we do not need any extra flags. A balanced binary tree usually takes more space since we need to store some flags. For example, in a red-black tree, we need to store a bit for the color. Also, a complete binary tree can be stored in a RAM as an array without using pointers. Problem 92. Given a binary tree, find the maximum path sum. The path may start and end at any node in the tree. Solution. Int max path sum. If return 0, int left sum equal to max path sumrec, int right sum max path sumrec. If max value equal to max, return root data. If max value equal to max value up equal to max plus root data, max value equal to max, return max value up. Problem minus 93. Let T be a proper binary tree with root R. Consider the following algorithm. Algorithm tree traversal. If return 1, else A equal to tree traversal, B equal to tree traversal, return A plus B. 1. B, it computes the number of nodes in the tree. C, it computes the depth of the nodes. D, it computes the height of the tree. E, it computes the number of leaves in the tree. Solution, E. 6.1 for other variations on trees. In this section, let us enumerate the other possible representations of trees. In the earlier sections, we have looked at AVL trees, which is a binary search tree with balancing property. Now, let us look at a few more balanced binary search trees, red-black trees, and splay trees. 6.14.1 red-black trees. In red-black trees, each node is associated with an extra attribute, the color, which is either red or black. To get logarithmic complexity, we impose the following restrictions. Definition, a red-black tree is a binary search tree that satisfies the following properties. Root property, the root is black. External property, every leaf is black. Internal property, the children of a red node are black. Depth property, all the leaves have the same black. Similar to AVL trees, if the red-black tree becomes imbalanced, then we perform rotations to reinforce the balancing property. With red-black trees, we can perform the following operations in O in worst case, where n is the number of nodes in the trees. Insertion, deletion, finding predecessor, successor, finding minimum, maximum. 6.14.2 splay trees. Splay trees are BSTs with a self-adjusting property. Another interesting property of splay trees is, starting with an empty tree, any sequence of k operations with maximum of n nodes takes O time complexity in worst case. Splay trees are easier to program and also ensure faster access to recently accessed items. Similar to AVL and red-black trees, at any point that the splay tree becomes imbalanced, we can perform rotations to reinforce the balancing property. Splay trees cannot guarantee the O complexity in worst case, but it gives amortized O complexity. Even though individual operations can be expensive, any sequence of operations gets the complexity of logarithmic behavior. One operation may take more time, A. Single operation may take O time, but the subsequent operations may not take worst case complexity, and on the average per operation complexity is O, lone. 6.14.3 billions trees. B tree is like other self-balancing trees such as AVL and red-black tree, such that it maintains its balance of nodes, while operations are performed against it. B tree has the following properties. Minimum degree pound, where except root node, all other nodes must have no less than T1 keys. Each node with n keys has n plus 1 children. Keys in each node are lined up where K1K, Kn. Each node cannot have more than 2 T1 keys, thus 2 trillions children. Root node at least must contain 1 key. There is no root node if the tree is empty. Tree grows in depth only when root node is split. Unlike a binary tree, each node of a B tree may have a variable number of keys and children. The keys are stored in non-decreasing order. Each key has an associated child that is the root of a subtree containing all nodes with keys less than or equal to the key, but greater than the preceding key. A node also has an additional rightmost child that is the root for a subtree containing all keys greater than any keys in the node. A B tree has a minimum number of allowable children for each node known as the minimization factor. If T is this minimization factor, every node must have at least T1 keys. Under certain circumstances, the root node is allowed to violate this property by having fewer than T1 keys. Every node may have at most 2 T1 keys or equivalently 2 trillions children. Since each node tends to have a large branching factor, it is typically necessary to traverse relatively few nodes before locating the desired key. If access to each node requires a disk access, then a B tree will minimize the number of disk accesses required. The minimization factor is usually chosen so that the total size of each node corresponds to a multiple of the block size of the underlying storage device. This choice simplifies and optimizes disk access. Consequently, a B tree is an ideal data structure for situations where all data cannot reside in primary storage and accesses to secondary storage are comparatively expensive. To search the tree, it is similar to binary tree except that the key is compared multiple times in a given node, because the node contains more than 1 key. If the key is found in the node, the search terminates. Otherwise, it moves down where a child pointed by CI, where key KK. Key insertions of a B tree happens from the bottom phasian. This means that it walked down the tree from root to the target child node first. If the child is not full, the key is simply inserted. If it is full, the child node is split in the middle, the median key moves up to the parent, then the new key is inserted. When inserting and walking down the tree, if the root node is found to be full, it's split first and we have a new root node. Then the normal insertion operation is performed. Key deletion is more complicated as it needs to maintain the number of keys in each node to meet the constraint. If a key is found in leaf node and deleting it still keeps the number of keys in the nodes not too low, it's simply done right away. If it's done to the inner node, the predecessor of the key in the corresponding child node is moved to replace the key in the inner node. If moving the predecessor will cause the child node to violate the node count constraint, the sibling child nodes are combined, and the key in the inner node is deleted. 6.14.4 Augmented trees. In earlier sections, we have seen various problems like finding the KTH, smallest element in the tree, and other similar ones. Of all the problems, the worst complexity is O, where n is the number of nodes in the tree. To perform such operations in O, augmented trees are useful. In these trees, extra information is added to each node, and that extra data depends on the problem we are trying to solve. For example, to find the KTH element in a binary search tree, let us see how augmented trees solve the problem. Let us assume that we are using red-black trees as balanced BST, and augmenting the size information in the node's data. For a given node X in red-black tree with a field size equal to the number of nodes in the subtree and can be calculated as KTH smallest operation can be defined as struct binary circ tree node KTH smallest int r equal to size plus 1 if return X, if return KTH smallest, if return KTH smallest. Time complexity, O. Space complexity, O. Example, with the extra size information, the augmented tree will look like 6.14.5 interval trees. We often face questions that involve queries made in an array based on range. For example, for a given array of integers, what is the maximum number in the range A to SS, where A and SS are of course within array limits? To iterate over those entries with intervals containing a particular value, we can use a simple array. But if we need more efficient access, we need a more sophisticated data structure. An array-based storage scheme and a brute force search through the entire array is acceptable only if a single search is to be performed, or if the number of elements is small. For example, if you know all the array values of interest in advance, you need to make only one pass through the array. However, if you can interactively specify different search operations at different times, the brute force search becomes impractical, because every element in the array must be examined during each search operation. If you sort the array in ascending order of the array values, you can terminate the sequential search when you reach the object whose low value is greater than the element we are searching. Unfortunately, this technique becomes increasingly ineffective as the low value increases, because fewer search operations are eliminated. That means, what if we have to answer a large number of queries like this? Is brute force still a good option? Another example is when we need to return a sum in a given range. We can brute force this too, but the problem for a large number of queries still remains. So, what can we do? With a bit of thinking, we can come up with an approach like maintaining a separate array of n elements, where n is the size of the original array, where each index stores the sum of all elements from 0 to that index. So essentially we have, with a bit of pre-processing, brought down the query time from a worst case O to O. Now this is great as far as static arrays are concerned, but what if we are required to perform updates on the array too? The first approach gives us an O query time, but an O update time. The second approach, on the other hand, gives us O query time, but an O update time. So, which one do we choose? Interval trees are also binary search trees, and they store interval information in the node structure. That means we maintain a set of n intervals such that one of the intervals containing a query point Q can be found efficiently. Interval trees are used for performing range queries efficiently. A segment tree is a heap-like data structure that can be used for making update query operations upon array intervals in logarithmical time. We define the segment tree for the interval in the following recursive manner. The root node will hold the information for the interval. If I, the left and right children will hold the information for the intervals. Segment trees is a cool data structure, primarily used for range queries. It is a height-balanced binary tree with a static structure. The nodes of a segment tree correspond to various intervals, and can be augmented with appropriate information pertaining to those intervals. It is somewhat less powerful than a balanced binary tree because of its static structure, but due to the recursive nature of operations on the seg tree, it is incredibly easy to think about in code. We can use segment trees to solve range minimum maximum query problems. The time complexity is T, where O is the time required to build a tree, and each query takes O time. Example, given a set of intervals, S equal 2, a query with Q equal to 9 returns, or a query with Q equal to 23 returns. Construction of interval trees, let us assume that we are given a set S of n intervals. These n intervals will have two n endpoints. Now, let us see how to construct the interval tree. Algorithm. Recursively build tree on interval set 5 as follows. Sort the two n endpoints. Let x mid be the median point. Time complexity for building interval trees O. Since we are choosing the median, interval trees will be approximately balanced. This ensures that we split the set of endpoints up in half each time. The depth of the tree is O. To simplify the search process, generally x my d is stored with each node. Intervals that are completely to the left of x my d in n left. 6.14.6 Scapegoat trees. Scapegoat tree is a self-balancing binary search tree discovered by Arne Anderson. It provides worst-case O search time and O amortized insertion and deletion time. AVL trees rebalance whenever the height of two sibling subtrees differ by more than 1. Scapegoat trees rebalance whenever the size of a child exceeds a certain ratio of its parents, a ratio known as A. After inserting the element, we traverse back up the tree. If we find an imbalance where a child's size exceeds the parent size times alpha, we must rebuild the subtree at the parent, the scapegoat. There might be more than one possible scapegoat, but we only have to pick one. The most optimal scapegoat is actually determined by height balance. When removing it, we see if the total size of the tree is less than alpha of the largest size since the last rebuilding of the tree. If so, we rebuild the entire tree. The alpha for a scapegoat tree can be any number between 0.5 and 1. The value 0.5 will force perfect balance, while 1 will cause rebalancing to never occur, effectively turning it into a BST. Chapter Priority Queue 7 and Heaps. What is a point 1? What is a priority queue? In some situations, we may need to find a minimum maximum element among a collection of elements. We can do this with the help of priority queue ADT. A priority queue ADT is a data structure that supports the operations insert and delete min or delete max. These operations are equivalent to 1Q and DQ operations of a queue. The difference is that in priority queues, the order in which the elements enter the queue may not be the same in which you are processed. An example application of a priority queue is job scheduling, which is prioritized instead of serving in first come first serve. A priority queue is called an ascending priority queue if the item with the smallest key has the highest priority. Similarly, a priority queue is said to be a descending priority queue if the item with the largest key has the highest priority. Since these two types are symmetric, we will be concentrating on one of them, ascending priority queue. 7.2 Priority queue, ADT. The following operations make priority queues and ADT. Main priority queues operations. A priority queue is a container of elements, each having an associated key. Insert inserts data with key to the priority queue. Elements are ordered based on key. Delete min, delete max, remove and return the element with the smallest largest key. Get minimum, get maximum, return the element with the smallest largest key without deleting it. Auxiliary priority queues operations. KTH smallest KTH largest returns the KTH smallest KTH. Largest key in priority queue. Size returns number of elements in priority queue. Heap sorts the elements in the priority queue based on priority. 7.3 Priority queue applications. Priority queues have many applications. A few of them are listed below. Data compression, Huffman coding algorithm, shortest path algorithms, Dijkstra's algorithm, minimum spanning tree algorithms, Prim's algorithm, event-driven simulation, customers in a line, selection problem, finding KTH smallest element. 7.4 Priority queue implementations. Before discussing the actual implementation, let us enumerate the possible options. Unordered array implementation. Elements are inserted into the array without bothering about the order. Deletions are performed by searching the key and then deleting. Insertions complexity, O delete min complexity, O unordered list implementation. It is very similar to array implementation, but instead of using arrays, linked lists are used. Insertions complexity, O delete min complexity, O ordered array implementation. Elements are inserted into the array in sorted order based on key field. Deletions are performed at only one end. Insertions complexity, O delete min complexity, O ordered list implementation. Elements are inserted into the list in sorted order based on key field. Deletions are performed at only one end, hence preserving the status of the priority queue. All other functionalities associated with a linked list ADT are performed without modification. Insertions complexity, O, delete min complexity, O, binary search trees implementation. Both insertions and deletions take O on average if insertions are random. Balanced binary search trees implementation. Both insertions and deletion take O in the worst case. Binary heap implementation. In subsequent sections, we will discuss this in full detail. For now, assume that binary heap implementation gives O complexity for search, insertions, and deletions, and O for finding the maximum or minimum element. Comparing implementations. 7.5 Heaps and binary heaps. What is a heap? A heap is a tree with some special properties. The basic requirement of a heap is that the value of a node must be greater than or equal to than the values of its children. This is called heap property. A heap also has the additional property that all leaves should be at h or h, 1 levels for some h greater than 0. That means heap should form a complete binary tree. In the examples below, the left tree is a heap and the right tree is not a heap. Types of heaps. Based on the property of a heap, we can classify heaps into two types. Min heap, the value of a node must be less than or equal to the values of its children. Max heap, the value of a node must be greater than or equal to the values of its children. 7.6 Binary heaps. In binary heap, each node may have up to 2 children. In practice, binary heaps are enough, and we concentrate on binary min heaps and binary max heaps for the remaining discussion. Representing heaps. Before looking at heap operations, let us see how heaps can be represented. One possibility is using arrays. Since heaps are forming complete binary trees, there will not be any wastage of locations. For the discussion below, let us assume that elements are stored in arrays which starts at index 0. The previous max heap can be represented as declaration of heap, creating heap, struct heap, create heap, printf, return, h heap underscore type, h count equal to 0, h capacity equal to capacity, h array malloc h capacity, if printf, return h. Time complexity, O, parent of a node. 2, for a node at IT location, its parent is at 1-to-1 location. In the previous example, the element 6 is at second location and its parent is at 0th location. int parent, if return -1, return I 1/2. Time complexity, O, children of a node. Similar to the above discussion, for a node at ith location, its children are at 2i plus 1 and 2i plus 2 locations. For example, in the above tree, the element 6 is at second location and its children 2 and 5 are at 5 and 6 locations. int left child, int left equal to 2 plus 1, if return -1, return left. Time complexity, O. Int right child, int right equal to 2 times 1 plus 2, if return -1, return right. Time complexity, O, getting the maximum element. Since the maximum element in max heap is always at root, it will be stored at h array. Int get maximum, if return -1, return h array. Time complexity, O, heapifying an element. After inserting an element into heap, it may not satisfy the heap property. In that case, we need to adjust the locations of the heap to make it heap again. This process is called heapifying. In max heap, to heapify an element, we have to find the maximum of its children and swap it with the current element and continue this process until the heap property is satisfied at every node. Observation. One important property of heap is that if an element is not satisfying the heap property, then all the elements from that element to the root will have the same problem. In the example below, element 1 is not satisfying the heap property, and its parent 31 is also having the issue. Similarly, if we heapify an element, then all the elements from that element to the root will also satisfy the heap property automatically. Let us go through an example. In the above heap, the element 1 is not satisfying the heap property. Let us try heapifying this element. To heapify 1, find the maximum of its children and swap with that. We need to continue this process until the element satisfies the heap properties. Now swap 1 with 8. Now the tree is satisfying the heap property. In the above heapifying process, since we are moving from top to bottom, this process is sometimes called percolate down. Similarly, if we start heapifying from any other node to root, we can that process percolate up as move from bottom to top. Heapifying the element at location on. Void percolate down 1 equal to left child, r equal to right child, if h array, else max equal to 1, max equal to I, if h array, max equal to r, if. Swap h array and h array, temp equal to h array, harry h array equal to temp, percolate down. Time complexity, O. Heap is a complete binary tree, and in the worst case, we start at the root and come down to the leaf. This is equal to the height of the complete binary tree. Space complexity, O. Deleting an element. To delete an element from heap, we just need to delete the element from the root. This is the only operation supported by standard heap. After deleting the root element, copy the last element of the heap and delete that last element. After replacing the last element, the tree may not satisfy the heap property. To make it heap again, the percolate down function. Call. Copy the first element into some variable. Copy the last element into first element location, percolate down the first element. Int delete max, int data, if return -1, data equal to h array, h count. Reducing the heap size, percolate down, return data. Note, deleting an element uses percolate down, and inserting an element uses percolate up. Time complexity, same as heapify function, and it is O. Inserting an element. Insertion of an element is similar to the heapify and deletion process. Increase the heap size, keep the new element at the end of the heap tree. Heapify the element from bottom to top. Before going through code, let us look at an example. We have inserted the element 19 at the end of the heap, and this is not satisfying the heap property. In order to heapify this element, we need to compare it with its parent and adjust them. Swapping 19 and 14 gives. Now the tree is satisfying the heap property. Since we are following the bottom-up approach, we sometimes call this process percolate up. Insert int array underscore old equal to h array malloc h capacity 2, if printf return, for h array equal to array underscore old, h capacity equal to 2, free. Time complexity, O. The explanation is the same as that of the heapify function. Destroying heap. Void destroy heap if return free h equal to null. Heapifying the array. One simple approach for building a heap is take n input items and place them into an empty heap. This can be done with n successive inserts and takes O in the worst case. This is due to the fact that each insert operation takes O. To finish our discussion of binary heaps, we will look at a method to build an entire heap from a list of keys. The first method you might think of may be like the following. Given a list of keys, you could easily build a heap by inserting each key one at a time. Since you are starting with a list of one item, the list is sorted, and you could use binary search to find the right position to insert the next key at a cost of approximately O operations. However, remember that inserting an item in the middle of the list may require O operations to shift the rest of the list over to make room for the new key. Therefore, to insert n keys into the heap would require a total of O operations. However, if we start with an entire list, then we can build the whole heap in O operations. Observation. Leaf nodes always satisfy the heap property and do not need to care for them. The leaf elements are always at the end, and to heapify the given array, it should be enough if we heapify the non-leaf nodes. Now let us concentrate on finding the first non-leaf node. The last element of the heap is at location h, count 1, and to find the first non-leaf node, it is enough to find the parent of the last element. Void build heap, int n, if return, while resize heap, for h array equal to a, h count equal to n, for /2, I greater than equal to 0, I, percolate down. Time complexity. The linear time bound of building heap can be shown by computing the sum of the heights of all the nodes. For a complete binary tree of height h containing n equal to 2 hours plus 1 nodes, the sum of the heights of the nodes is n h, 1 equal to n lone 1. That means building the heap operation can be done in linear time by applying a percolate down function to the nodes in reverse level order. 7.7 Heap sort. One main application of heap ADT is sorting. The heap sort algorithm inserts all elements into a heap, then removes them from the root of a heap until the heap is empty. Note that heap sort can be done in place with the array to be sorted. Instead of deleting an element, exchange the first element with the last element and reduce the heap size. Then, we heapify the first element. Continue this process until the number of remaining elements is 1. Void heap sort in n, struct heap h equal to create heap int old underscore size I temp build heap old underscore size equal to h count 4. H array is the largest element temp equal to h array h array h array. H array equal to temp h count. Percolate down h count equal to old underscore size. Time complexity. As we remove the elements from the heap, the values become sorted. Since the time complexity of both the insertion algorithm and deletion algorithm is O, the time complexity of the heap sort algorithm is O. 7.8 Priority queues. Problems and solutions. Problem -1. What are the minimum and maximum number of elements in a heap of height? H. Solution. Since heap is a complete binary tree, it has at most 2 hours plus 1 elements. This is because, to get maximum nodes, we need to fill all the h levels completely, and the maximum number of nodes is nothing but the sum of all nodes at all h levels. To get minimum nodes, we should fill the h1 levels fully and the last level with only 1 element. As a result, the minimum number of nodes is nothing but the sum of all nodes from h1 levels plus 1, and we get 2 to 1 plus 1 equal to 2 hours elements. Problem 2 is there a min heap with 7 distinct elements so that the preorder traversal of it gives the elements in sorted order. Solution, yes. For the tree below, preorder traversal produces ascending order. Problem -3 is there a max heap with 7 distinct elements so that the preorder traversal of it gives the elements in sorted order. Solution, yes. For the tree below, preorder traversal produces descending order. Problem -4. Is there a min heap max heap with 7 distinct elements so that the in-order traversal of it gives the elements in sorted order? Solution, no. Since a heap must be either a min heap or a max heap, the root will hold the smallest element or the largest. An in-order traversal will visit the root of the tree as its second step, which is not the appropriate place if the tree's root contains the smallest or largest element. Problem 5 is there a min heap max heap with 7 distinct elements so that the post-order traversal of it gives the elements in sorted order? Solution, yes, if the tree is a max heap and we want descending order, or if the tree is a min heap and we want ascending order. Show that the height of a heap with n elements is lone. Problem -6. Solution, a heap is a complete binary tree. All the levels except the lowest are completely full. A heap has at least 2 hours elements and at most elements 2 hours less than or equal to n less than or equal to 2 hours plus 1 to 1. This implies h lone h plus 1. Since h is an integer, h equal to lone. Problem -7 given a min heap, give an algorithm for finding the maximum element. Solution, for a given min heap, the maximum element will always be at leaf only. Now, the next question is how to find the leaf nodes in the tree. If we carefully observe, the next node of the last element's parent is the first leaf node. Since the last element is always at the h count, first location, the next node of its parent, parent at, can be calculated as h count, 1 location 2. Now, the only step remaining is scanning the leaf nodes and finding the maximum among them. In find max in min heap, int max equal to -1 for /2, ih, count, I++ if max, max equal to h array. Time complexity, O approximately equal to O. Problem -8, give an algorithm for deleting an arbitrary element from min heap. Solution, to delete an element, first we need to search for an element. Let us assume that we are using level order traversal for finding the element. After finding the element, we need to follow the delete min process. Time complexity equal to time for finding the element plus time for deleting an element equal to O plus O approximately equal to O. Time for searching dominated. Problem -9, give an algorithm for deleting the ith index element in a given min heap. Solution is int delete return key equal to h array, h array, h array, h count. Percolate down, return key. Time complexity equal to O. Problem -10, prove that for a complete binary tree of height h, the sum of the height of all nodes is O. Solution, a complete binary tree has 2 to the power of 1 nodes on level. Also, a node on level has depth y and height hi. Let us assume that s denotes the sum of the heights of all these nodes, and s can be calculated as, multiplying with 2 on both sides gives, 2 seconds equal to 2 hours plus 4 plus 8 plus -2 hours 1. Now, subtract s from 2 seconds, s equal to, h plus 2 plus 4 plus -2 hours s equal to, but we already know that the total number of nodes n in a complete binary tree with height h is n equal to 2 hours plus 1 to 1. This gives us h equal to log. Finally, replacing 2 hours plus 1 to 1 with n gives s equal to n equal to o equal to o. Problem -11, give an algorithm to find all elements less than some value of k in a binary heap. Solution, start from the root of the heap. If the value of the root is smaller than k, then print its value and call recursively once for its left child and once for its right child. If the value of a node is greater or equal than k, then the function stops without printing that value. The complexity of this algorithm is O, where n is the total number of nodes in the heap. This bound takes place in the worst case, where the value of every node in the heap will be smaller than k, so the function has to call each node of the heap. Problem minus 12. Give an algorithm for merging two binary max heaps. Let us assume that the size of the first heap is m plus n, and the size of the second heap is n. Solution. One simple way of solving this problem is, assume that the elements of the first array are at the beginning. That means first m cells are filled and remaining n cells are empty. Without changing the first heap, just append the second heap and heapify the array. Since the total number of elements in the new array is m plus n, each heapify operation takes O. The complexity of this algorithm is O log. Problem minus 13. Can we improve the complexity of problem 12? Solution. Instead of heapifying all the elements of the m plus n array, we can use the technique of building heap with an array of elements. We can start with non-leaf nodes and heapify them. The algorithm can be given as, without changing the first heap, just append the second heap. Assume that the elements of the first array are at the beginning. That means the first m cells are filled and the remaining n cells are empty. Now, find the first non-leaf node and start heapifying from that element. In the theory section, we have already seen that building a heap with n elements takes O complexity. The complexity of merging with this technique is O. Problem minus 14. Is there an efficient algorithm for merging two max heaps? Assume both arrays have n elements. Solution. The alternative solution for this problem depends on what type of heap it is. If it's a standard heap where every node has up to two children and which gets filled up so that the leaves are on a maximum of two different rows, we cannot get better than O for the merge. There is an O algorithm for merging two binary heaps with sizes m and n. For m equal to n, this algorithm takes O time complexity. We will be skipping it due to its difficulty and scope. For better merging performance, we can use another variant of binary heap, like a Fibonacci heap, which can merge in O on average. Problem minus 15. Give an algorithm for finding the kth smallest element in min heap. Solution. One simple solution to this problem is, perform deletion k times from min heap. Return pq.min, just delete first k1 elements and return the kth element. For delete min, return delete min. Time complexity O. Since we are performing deletion operation k times, and each deletion takes O. Problem minus 16 for problem 15. Can we improve the time complexity? Solution. Assume that the original min heap is called horig, and the auxiliary min heap is named hos. Initially, the element at the top of horig, the minimum one, is inserted into hos. Here we don't do the operation of delete min with horig. Heap horig, heap ho, and find kth largest L else. Insert the left and right children in ho into the ha-ho insert hos at insert. Every while loop iteration gives the kth smallest element, and we need k loops to get the kth smallest elements. Because the size of the auxiliary heap is always less than k, every while loop iteration the size of the auxiliary heap increases by 1, and the original heap horig has no operation during the finding. The running time is O. Note, the above algorithm is useful if the k value is too small compared to n. If the k value is approximately equal to n, then we can simply sort the array and return kth smallest element from the sorted array. This gives O solution. Problem minus 17. Find k max elements from max heap. Solution. One simple solution to this problem is, build max heap and perform deletion k times. Problem 18 for problem 17. Is there any alternative solution? Solution. We can use the problem 16 solution. At the end, the auxiliary heap contains the largest elements. Without deleting the elements, we should keep on adding elements to ho. Problem minus 19. How do we implement stack using heap? Solution. To implement a stack using a priority queue PQ, let us assume that we are using one extra integer variable c. Also, assume that c is initialized equal to any known value. The implementation of the stack ADT is given below. Here c is used as the priority while deleting the elements from PQ. Void push 1 int pop in size int is empty, return PQ.I as empty. We could also increment c back when popping. Observation, we could use the negative of the current system time instead of c. The implementation based on this can be given as void push PQ.insert element. Problem 20. How do we implement queue using heap? Solution. To implement a queue using a priority queue PQ, as similar to stack simulation, let us assume that we are using one extra integer variable, c. Also, assume that c is initialized equal to any known value. The implementation of the queue ADT is given below. Here the c is used as the priority while deleting the elements from PQ. One void push c++ in pop return pq.delete min in t top return pq.min in size return pq.size in t is empty return pq.is empty. No, we could also decrement c when popping. Observation, we could use just the negative of the current system time instead of c. The implementation based on this can be given as void push pq.insert element. Note, the only change is that we need to take a positive c value instead of negative. Problem 21. Given a big file containing billions of numbers, how can you find the 10 maximum numbers from that file? Solution. Always remember that when you need to find max n elements, the best data structure to use is priority queues. One solution for this problem is to divide the data in sets of 1,000 elements and make a heap of them, and then take 10 elements from each heap one by one. Finally, heap sort all the sets of 10 elements and take the top 10 among those. But the problem in this approach is where to store 10 elements from each heap. That may require a large amount of memory as we have billions of numbers. Reusing the top 10 elements and subsequent elements can solve this problem. That means take the first block of 1,000 elements and subsequent blocks of 990 elements each. Initially, heap sort the first set of 1,000 numbers, take max 10 elements, and mix them with 990 elements of the second set. Again, heap sort these 1,000 numbers, take 10 max elements, and mix them with 990 elements of the third set. Repeat to the last set of 990 elements, and take max 10 elements from the final heap. These 10 elements will be your answer. Time complexity, O equal to n. 1,000 times since complexity of heap sorting 1,000 elements will be a constant, so the O equal to n that is linear complexity. Problem minus 22. Merge k-sorted lists with total of n elements. We are given k-sorted lists with total n inputs in all the lists. Give an algorithm to merge them into one single sorted list. Solution. Since there are k equal size lists with a total of n elements, the size of each list is, or one simple way of solving this problem is, take the first list and merge it with the second list. Since the size of each list is h, this step produces a sorted list with size. This is similar to merge sort logic. The 2n time complexity of this step is 2 nkk. This is because we need to scan all the elements of both the lists. Then, merge the second list output with the third list. As a result, this step produces a sorted list with size. The time complexity of this step is, this is because we 3nk2 need to scan all the elements of both lists. Continue this process until all the lists are merged to one list. Total. Space complexity, O. Complexity. Problem 23 for problem 22. Can we improve the time complexity? Solution. 1. Divide the lists into pairs and merge them. That means first take 2 lists at a time and merge them so that the total elements parsed for all lists is O. This operation gives k 2 lists. 2 repeat step minus 1 until the number of lists becomes 1. Time complexity, step 1 executes lock times, and each operation parses all n elements in all the lists for making k2 lists. For example, if we have 8 lists, then the first pass would make 4 lists by parsing all n elements. The second pass would make two lists by again parsing n elements, and the third pass would give one list by again parsing n elements. As a result, the total time complexity is O, space complexity, O. Problem 24 for problem 23, can we improve the space complexity? Solution, let us use heaps for reducing the space complexity. 1. Build the max heap with all the first elements from each list in O. 2. In each step, extract the maximum element of the heap and add it at the end of the output. 3. Add the next element from the list of the one extracted. That means we need to select the next element of the list which contains the extracted element of the previous step. 4. Repeat step 2 and step -3 until all the elements are completed from all the lists. Time complexity equal to O. At a time, we have k elements max heap, and for all n elements, we have to read just the heap in lock time, so total time equal to O. Space complexity, O. Problem 25, given two arrays A and B each with n elements. Given algorithm for finding largest n pairs, B. Solution, algorithm, heapify A and B. This step takes O approximately equal to O. Then keep on deleting the elements from both the heaps. Each step takes O. Total time complexity, O. Problem 26, min max heap. Give an algorithm that supports min and max in O time. Insert delete min and delete max in O time. That means design a data structure which supports the following operations. Solution, this problem can be solved using two heaps. Let us say two heaps are minimum heap hmin and maximum heap hmax. Also, assume that elements in both the arrays have mutual pointers. That means an element in hmn will have a pointer to the same element in hmax, and an element in hmax will have a pointer to the same element in hmn. Problem 27, median. Dynamic median finding. Design a heap data structure that supports finding the solution. In a set of n elements, median is the middle element, such that the number of elements lesser than the median is equal to the number of elements larger than the median. If n is odd, we can find the median by sorting the set and taking the middle element. If n is even, the median is usually defined as the average of the two middle elements. This algorithm works even when some of the elements in the list are equal. For example, the median of the multiset is 2, and the median of the multiset is 2.5. Median heaps are the variant of heaps that give access to the median element. A median heap can be implemented using two heaps, each containing half the elements. One is a max heap containing the smallest elements, the other is a min heap containing the largest elements. The size of the max heap may be equal to the size of the min heap if the total number of elements is even. In this case, the median is the average of the maximum element of the max heap and the minimum element of the min heap. If there is an odd number of elements, a max heap will contain one more element of the min heap. The median is simply the maximum element of the max heap. Problem 28, maximum sum in sliding window. Given array A with sliding window of size W, which is moving from the very left of the array to the very right. Assume that we can only see the W numbers in the window each time the sliding window moves rightwards by one position. For example, the array is, and W is 3. Input along array A and a window width W. Output, an array B. B is the maximum value from A to A. Requirement, find a good optimal way to get B. Solution, brute force solution is, every time the window is moved, we can search for a total of W elements in the window. Time complexity, O. Problem -29. For problem 28, can we reduce the complexity? Solution, yes, we can use heap data structure. This reduces the time complexity to O. Insert operation takes O time, where W is the size of the heap. However, getting the maximum value is cheap. It merely takes constant time as the maximum value is always kept in the root of the heap. As the window slides to the right, some elements in the heap might not be valid anymore. How should we remove them? We would need to be somewhat careful here. Since we only remove elements that are out of the window's range, we would need to keep track of the elements indices too. Problem 30 for problem 28. Can we further reduce the complexity? Solution, yes. The double-ended queue is the perfect data structure for this problem. It supports insertion deletion from the front and back. The trick is to find a way such that the largest element in the window would always appear in the front of the queue. How would you maintain this requirement as you push and pop elements in and out of the queue? Besides, you will notice that there are some redundant elements in the queue that we shouldn't even consider. For example, if the current queue has the elements, and a new element in the window has the element 11. Now, we could have emptied the queue without considering elements 10, 5, and 3, and insert only element 11 into the queue. Typically, most people try to maintain the queue size the same as the window's size. Try to break away from this thought and think out of the box. Removing redundant elements and storing only elements that need to be considered in the queue is the key to achieving the efficient O solution below. This is because each element in the list is being inserted and removed at most once. Therefore, the total number of insert plus delete operations is 2n. Void max sliding window, int n, int w, int b, struct double end q equal to create double end q. 4, while and a greater than equal to a, pop back, push back for b equal to a, while and a greater than equal to a, pop back, while and q front less than equal to iw, pop front, push back b equal to a. Problem -31. A priority queue is a list of items in which each item has associated with it a priority. Items are withdrawn from a priority queue in order of their priorities, starting with the highest priority item first. If the maximum priority item is required, then a heap is constructed such that the priority of every node is greater than the priority of its children. Design such a heap where the item with the middle priority is withdrawn first. If there are n items in the heap, then the number of items with a priority smaller than the middle priority is if n is odd, else equal to +1 and 2 and 2. Explain how withdraw and insert operations work, calculate their complexity, and how the data structure is constructed. Solution, we can use one min heap and one max heap such that root of the min heap is larger than the root of the max heap. The size of the min heap should be equal or one less than the size of the max heap. So the middle element is always the root of the max heap. For the insert operation, if the new item is less than the root of max heap, then insert it into the max heap, else insert it into the min heap. After the withdraw or insert operation, if the size of heaps are not as specified above, then transfer the root element of the max heap to min heap or vice versa. With this implementation, insert and withdraw operation will be in O time. Problem 32, given two heaps, how do you merge them? Solution, binary heap supports various operations quickly. Find min, insert, decrease key. If we have two min heaps, H1 and H2, there is no efficient way to combine them into a single min heap. For solving this problem efficiently, we can use mergeable heaps. Mergeable heaps support efficient union operation. It is a data structure that supports the following operations. Create heap creates an empty heap. Insert an item X with key K into a heap H. Find min, return item with min key. Delete min, return and remove. Union merge heaps H1 and H2. Examples of mergeable heaps are binomial heaps, Fibonacci heaps. Both heaps also support decrease key. Assign item Y with a smaller key K. Delete remove item 10th binomial heaps. Unlike binary heap which consists of a single tree, a binomial heap consists of a small set of component trees and no need to rebuild everything when union is performed. Each component tree is in a special format called a binomial tree. A binomial tree of order k denoted by bk is defined recursively as follows. Bo is a tree with a single node. For k greater than or equal to 1, bk is formed by joining 2b minus 1 such that the root of one tree becomes the leftmost child of the root of the other. Example, Fibonacci heaps. Fibonacci heap is another example of mergeable heap. It has no good worst case guarantee for any operation. Fibonacci heaps have excellent amortized cost to perform each operation. Like binomial heap, Fibonacci heap consists of a set of min-heap ordered component trees. However, unlike binomial heap, it has no limit on number of trees and no limit on height of a tree. Also, find min, delete min, union, decrease key, delete all have worst case O running time. However, in the amortized sense, each operation performs very quickly. Problem minus 33 median in an infinite series of integers. Solution, median is the middle number in a sorted list of numbers. If we have even number of elements, median is the average of two middle numbers in a sorted list of numbers. We can solve this problem efficiently by using two heaps, one max heap and one min heap. 1. Max heap contains the smallest half of the received integers. 2. Min heap contains the largest half of the received integers. The integers in max heap are always less than or equal to the integers in min heap. Also, the number of elements in max heap is either equal to or one more than the number of elements in the min heap. In the stream, if we get two n elements, max heap and min heap will both contain equal number of elements. Otherwise, if we have received two n plus 1 elements, max heap will contain n plus 1 and min heap n. Let us find the median. If we have two n plus 1 elements, the median of received elements will be the largest element in the max heap. Otherwise, the median of received elements will be the average of largest element in the max heap and smallest element in the min heap. This can be calculated in O. Inserting an element into heap can be done in O. Note that any heap containing n plus 1 elements might need one delete operation as well. Example, insert 1, insert to max heap. Max heap, min heap, insert 9, insert to min heap. Since 9 is greater than 1 and min heap maintains the maximum elements. Max heap, min heap, insert 2, insert min heap. Since 2 is less than all elements in min heap. Max heap, min heap, insert 0. Since max heap already has more than half, we have to drop the max element from max heap and insert it to min heap. So we have to remove 2 and insert into min heap. With that, it becomes max heap, min heap. Now, insert 0 to max heap. Total time complexity? Oh, problem minus 34. Suppose the elements 7, 2, 10, and 4 are inserted, in that order, into the valid 3 array max heap found in the above question. Which one of the following is the sequence of items in the array representing the resultant heap? 10, 7, 9, 8, 3, 1, 5, 2, 6, 4, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 10, 9, 4, 5, 7, 6, 8, 2, 1, 3. 10, 9, 8, 7, 4, 10, 9 max heap with elements 9, 7, after insertion of 7, after insertion of 2, after insertion of 10, after insertion of. Problem 35. The binary min heap is made by including each integer in exactly once. The depth of a node in the heap is the length of the path from the root of the heap to that node. Thus, the root is at depth 0. The maximum depth at which integer 9 can appear is. Solution, as shown in the figure below, for a given number 1, we can fix the element I at each level and arrange the numbers 1 to I, 1 to the levels above. Since the root is at depth 0, the maximum depth of the ith element in a min heap is I1. Hence, the maximum depth at which integer 9 can appear is 8. Problem minus 36. A d-array heap is like a binary heap, but instead of 2 children, nodes have d children. How would you represent a d-array heap with n elements in an array? What are the expressions for determining the parent of a given element, parent, and a jth child of a given element, child, where 1 less than or equal to j less than or equal to odd? Solution, the following expressions determine the parent and jth child of element 1. Child equal to .d plus j plus 1. Disjoint sets ADT, Chapter 8. 8.1 Introduction. In this chapter, we will represent an important mathematics concept, sets. This means how to represent a group of elements which do not need any order. The disjoint sets ADT is the one used for this purpose. It is used for solving the equivalence problem. It is very simple to implement. A simple array can be used for the implementation, and each function takes only a few lines of code. Disjoint sets ADT acts as an auxiliary data structure for many other algorithms. Before starting our discussion on disjoint sets ADT, let us look at some basic properties of sets. 8.2 Equivalence relations and equivalence classes. For the discussion below, let us assume that 5 is a set containing the elements and a relation R is defined on it. That means for every pair of elements in A, B, 5 euros, A, R, B is either true or false. If A, R, B is true, then we say A is related to B, otherwise A is not related to B. A relation R is called an equivalence relation if it satisfies the following properties. Reflexive, for every element A euro SRA is true. Symmetric, for any two elements A, B, IES, if a rubidium is true, then B radium is true. Transitive, for any three elements A, B, C, IES, if a rubidium and BRC are true, then A, RC is true. As an example, relations in greater than or equal to on a set of integers are not equivalence relations. They are reflexive and transitive but not symmetric. Similarly, rail connectivity is an equivalence relation. This relation is reflexive because any location is connected to itself. If there is connectivity from city A to city B, then city B also has connectivity to city A, so the relation is symmetric. Finally, if city A is connected to city B, and city B is connected to city C, then city A is also connected to city C. The equivalence class of an element AIES is a subset of S that contains all the elements that are related to A. Equivalence classes create a partition of S. Every member of S appears in exactly one equivalence class. To decide if A are B, we just need to check whether A and B are in the same equivalence class or not. In the above example, two cities will be in same equivalence class if they have rail connectivity. If they do not have connectivity, then they will be part of different equivalence classes. Since the intersection of any two equivalence classes is empty, the equivalence classes are sometimes called disjoint sets. In the subsequent sections, we will try to see the operations that can be performed on equivalence classes. The possible operations are creating an equivalence class, finding the equivalence class name, combining the equivalence classes. 8.3 Disjoint sets ADT. To manipulate the set elements, we need basic operations defined on sets. In this chapter, we concentrate on the following set operations. Make set creates a new set containing a single element, 10th union. Creates a new set containing the elements x and y in their union, and deletes the sets containing the elements x and y. Find returns the name of the set containing the element 10th 8.4 applications. Disjoint sets ADT have many applications, and a few of them are to represent network connectivity, image processing, define least common ancestor, to define equivalence of finite state automata. Driscoll's minimum spanning tree algorithm in game algorithms, 8.5 trade-offs in implementing disjoint sets ADT. Let us see the possibilities for implementing disjoint set operations. Initially, assume the input elements are a collection of n sets, each with one element. That means initial representation assumes all relations are false. Each set has a different element so that S and S equal to O. This makes the sets disjoint. To add the relation A, R, B, we first need to check whether A and B are already related or not. This can be verified by performing finds on both A and B and checking whether they are in the same equivalence class or not. If they are not, then we apply union. This operation merges the two equivalence classes containing A and B into a new equivalence class by creating a new set SK equal to S, US, and deletes silicon and S. Basically, there are two ways to implement the above find union operations. Fast find implementation. Fast union operation implementation. 8.6 fast find implementation. In this method, we use an array. As an example, in the representation below the array contains the set name for each element. For simplicity, let us assume that all the elements are numbered sequentially from 0 to n1. In the example below, element 0 has the set name 3, element 1 has the set name 5, and so on. With this representation, find takes only O, since for any element we can find the set name by accessing its array location in constant time. In this representation, to perform union, we need to scan the complete array and change all i's to j. This takes O. A sequence of n1 unions take O time in the worst case. If there are O find operations, this performance is fine, as the average time complexity is O for each union or find operation. If there are fewer finds, this complexity is not acceptable. 8.7 Fast union implementation. In this and subsequent sections, we will discuss the faster union implementations and its variants. There are different ways of implementing this approach, and the following is a list of a few of them. Fast union implementations. Fast union implementations. Fast union implementations with path compression. 8.8 Fast union implementation. As we have discussed, find operation returns the same answer if and only if they are in the same set. In representing disjoint sets, our main objective is to give a different set name for each group. In general, we do not care about the name of the set. One possibility for implementing the set is tree, as each element has only one root, and we can use it as the set name. How are these represented? One possibility is using an array. For each element, keep the root as its set name. But with this representation, we will have the same problem as that of find array implementation. To solve this problem, instead of storing the root, we can keep the parent of the element. Therefore, using an array which stores the parent of each element solves our problem. To differentiate the root node, let us assume its parent is the same as that of the element in the array. Based on this representation, make set, find, union operations can be defined as creates a new set containing a single element x, and in the array update the parent of x as 10th, that means root of x is 10th union, replaces the two sets containing x and y by their union, and in the array updates the parent of x as y. Find returns the name of the set containing the element 10th. We keep on searching for x's set name until we come to the root of the tree. For the elements 0 to n1, the initial representation is 0, 1. Parent array 1 to 2 n minus 1 n minus 2 n minus 1. To perform a union on two sets, we merge the two trees by making the root of one tree point to the root of the other. Initial configuration for the elements 0 to 6. After union, parent array, parent array. One important thing to observe here is union operation is changing the root's parent only, but not for all the elements in the sets. Due to this, the time complexity of union operation is O. A find on element x is performed by returning the root of the tree containing 10th. The time to perform this operation is proportional to the depth of the node representing 10th. Using this method, it is possible to create a tree of depth n1. The worst case running time of a find is O, and m consecutive find operations take O time in the worst case. Make set. Void make set in size for s equal to I, find, in size int x, if return -1, if equal to x, return x, else return find, union. Void union, in size, int root 1, int root, if find, return, if greater than equal to 0 and root size, and, return, s equal to root. 8.9 Fast union implementations. The main problem with the previous approach is that, in the worst case, we are getting the skew trees, and as a result, the find operation is taking O time complexity. There are two ways to improve it. Union by size, make the smaller tree a subtree of the larger tree. Union by height, make the tree with less height a subtree of the tree with more height. Union by size. In the earlier representation, for each element I, we have stored I for the root element, and for other elements, we have stored the parent of I. But in this approach, we store negative of the size of the tree. For the previous example, the new representation will look like parent array. Assume that the size of one element set is 1 and store 1. Other than this, there is no change. Make set. Void make set in size for s equal to -1. Find in size int x. If return -1, if equal to or equal to -1, return x, else return find. Union by size. Void union by size in size int root, else s equal to rootle, s plus equal to s. Note, there is no change in find operation implementation. Union by height. Parent array. As in union by size, in this method we store negative of height of the tree. We assume the height of a tree with one element set is 1. For the previous example, the new representation will look like union by height, parent array, void union by height, in size, in root. Note, for find operation there is no change in the implementation. Comparing union by size and union by height. With union by size, the depth of any node is never more than lone. This is because a node is initially at depth 0. When its depth increases as a result of a union, it is placed in a tree that is at least twice as large as before. That means its depth can be increased at most lon times. This means that the running time for a find operation is O, and a sequence of m operations takes O. Similarly, with union by height, if we take the union of two trees of the same height, the height of the union is 1 larger than the common height, and otherwise equal to the max of the two heights. This will keep the height of tree of n nodes from growing past O. A sequence of m unions and finds can then still cost O. Path compression. Find operation traverses a list of nodes on the way to the root. We can make later find operations efficient by making each of these vertices point directly to the root. This process is called path compression. For example, in the find operation, we travel from x to the root of the tree. The effect of path compression is that every node on the path from x to the root has its parent change to the root. With path compression, the only change to the find function is that s is made equal to the value returned by find. That means, after the root of the set is found recursively, x is made to point directly to it. This happened recursively to every node on the path to the root. Find with path compression. In find in size int x, if return if less than equal to 0, return x, equal to else return find. Note, path compression is compatible with union by size, but not with union by height a's. There is no efficient way to change the height of the tree. 8.10 Summary. Performing m union find operations on a set of n objects. 8.1 Disjoint sets, problems, and solutions. Problem -1. Consider a list of cities cone C2, C. Assume that we have a relation R such that for any I, J, R1, if cities C and C are in the same state, and 0 otherwise. If R is stored as a table, how much space does it require? Solution. R must have an entry for every pair of cities. There are of these. Problem -2 for problem 1. Using a disjoint sets ADT, give an algorithm that puts each city in a set such that C and C are in the same set if and only if they are in the same state. Solution. Problem -3 for problem 1. When the cities are stored in the disjoint sets ADT, if we are given two cities C and CJ, how do we check if they are in the same state? Solution. Cities C and C are in the same state if and only if find equal to find. Problem 4 for problem 1. If we use linked lists with union by size to implement the union find ADT, how much space do we use to store the cities? Solution. There is one node per city, so the space is O. Problem -5 for problem 1. If we use trees with union by rank, what is the worst case running time of the algorithm from problem 2? Solution. Whenever we do a union in the algorithm from problem 2, the second argument is a tree of size 1. Therefore, all trees have height 1, so each union takes time O. The worst case running time is then. Problem 6. If we use trees without union by rank, what is the worst case running time of the algorithm from problem 2? Are there more worst case scenarios than problem 5? Solution. Because of the special case of the unions, union by rank does not make a difference for our algorithm. Hence, everything is the same as in problem 5. Problem -7. With a quick union algorithm, we know that a sequence of n operations can take slightly more than linear time in the worst case. Explain why, if all the finds are done before all the unions, a sequence of n operations is guaranteed to take O time. Solution. If the find operations are performed first, then the find operations take O time each because every item is the root of its own tree. No item has a parent, so finding the set an item is in takes a fixed number of operations. Union operations always take O time. Hence, a sequence of n operations with all the finds before the unions takes O time. Problem -8 with reference to problem 7, explain why, if all the unions are done before all the finds, a sequence of n operations is guaranteed to take O time. Solution. This problem requires amortized analysis. Find operations can be expensive, but this expensive find operation is balanced out by lots of cheap union operations. The accounting is as follows. Union operations always take O time, so let's say they have an actual cost of 21. Assign each union operation an amortized cost of 22, so every union operation puts 21 in the account. Each union operation creates a new child. When all the union operations are done, there is $1 in the account for every child, or in other words, for every node with a depth of 1 or greater. Let's say that a find operation costs 21 if you use a root. For any other node, the find operation costs an additional 21 for each parent pointer the find operation traverses. So the actual cost is 2, where D is the depth of U. Assign each find operation an amortized cost of 22. This covers the case where U is a root or a child of a root. For each additional parent pointer traversed, 21 is withdrawn from the account to pay for it. Fortunately, path compression changes the parent pointers of all the nodes we pay 21 to traverse, so these nodes become children of the root. All of the traversed nodes whose depths are 2 or greater move up, so their depths are now 1. We will never have to pay to traverse these nodes again. Say that a node is a grandchild if its depth is 2 or greater. Every time find visits a grandchild, 21 is withdrawn from the account, but the grandchild is no longer a grandchild. So the maximum number of dollars that can ever be withdrawn from the account is the number of grandchildren. But we initially put $1 in the bank for every child, and every grandchild is a child, so the bank balance will never drop below 0. Therefore, the amortization works out. Union and find operations both have amortized costs of 22%. Sequence of n operations where all the unions are done first takes O time. 9.1 Introduction. In the real world, many problems are represented in terms of objects and connections between them. For example, in an airline route map, we might be interested in questions like, what's the fastest way to go from Hyderabad to New York? Or, what is the cheapest way to go from Hyderabad to New York? To answer these questions, we need information about connections between objects. Graphs are data structures used for solving these kinds of problems. 9.2 Glossary. Graph. A graph is a pair, where 5 is a set of nodes, called vertices, and pound is a collection of pairs of vertices, called edges. Vertices and edges are positions and store elements. Definitions that we use. OOO. Directed edge. Ordered pair of vertices. First vertex U is the origin. Second vertex 5 is the destination. Example, one-way road traffic. Undirected edge. Unordered pair of vertices. Example, railway lines. Directed graph. All the edges are directed. Example, route network. Undirected graph. All the edges are undirected. Example, flight network. When an edge connects two vertices, the vertices are said to be adjacent to each other, and the edge is incident on both vertices. A graph with no cycles is called a tree. A tree is an acyclic connected graph. A self-loop is an edge that connects a vertex to itself. Two edges are parallel if they connect the same pair of vertices. The degree of a vertex is the number of edges incident on it. A subgraph is a subset of a graph's edges that form a graph. A path in a graph is a sequence of adjacent vertices. Simple path is a path with no repeated vertices. In the graph below, the dotted lines represent a path from G to E. A cycle is a path where the first and last vertices are the same. A simple cycle is a cycle with no repeated vertices or edges. We say that one vertex is connected to another if there is a path that contains both of them. A graph is connected if there is a path from every vertex to every other vertex. If a graph is not connected, then it consists of a set of connected components. A directed acyclic graph is a directed graph with no cycles. A forest is a disjoint set of trees. A spanning tree of a connected graph is a subgraph that contains all of that graph's vertices and is a single tree. A spanning forest of a graph is the union of spanning trees of its connected components. A bipartite graph is a graph whose vertices can be divided into two sets, such that all edges connect a vertex in one set with a vertex in the other set. In weighted graphs, integers are assigned to each edge to represent. Graphs with all edges present are called complete graphs. Graphs with relatively few edges are called sparse graphs. Graphs with relatively few of the possible edges missing are called dense. Directed weighted graphs are sometimes called network. We will denote the number of vertices in a given graph by, and the number of edges by, or E, or note that E can range anywhere from 0 to or 5 or /2. This is because each node can connect to every other node. 9.3 Applications of graphs. Representing relationships between components in electronic circuits. Transportation networks, highway network, flight network, computer networks, local area network, internet, web, databases for representing ER diagrams in databases, for representing dependency of tables in databases. 9.4 Graph representation. As in other ADTs, to manipulate graphs, we need to represent them in some useful form. Basically, are 3 ways of doing this. There, adjacency matrix, adjacency list, adjacency set, adjacency matrix. Graph declaration for adjacency matrix. First, let us look at the components of the graph data structure. To represent graphs, we need the number of vertices, the number of edges, and also their interconnections. So the graph can be declared as struct graph int t5 int e int age, since we need two-dimensional matrix. Description. In this method, we use a matrix with size 5/5 if the values of matrix are Boolean. Let us assume the matrix is ADG. The value edge is set to 1 if there is an edge from vertex U to vertex V and 0 otherwise. In the matrix, each edge is represented by 2 bits for undirected graphs. That means an edge from U to V is represented by one value in both edge and edge. To save time, we can process only half of the symmetric matrix. Also, we can assume that there is an edge from each vertex to itself. So, edge is set to 1 for all vertices. If the graph is a directed graph, then we need to mark only one entry in the adjacency matrix. As an example, consider the directed graph below. The adjacency matrix for this graph can be given as. Now, let us concentrate on the implementation. To read a graph, one way is to first read the vertex names and then read pairs of vertex names. The code below reads an undirected graph. This code creates a graph with adj matrix representation, struct graph, adj matrix of graph, int I uv, struct graph g equal to malloc, if printf return scanf equal to g adj malloc, for g adj equal to 0, for read and edge scanf. For undirected graph, set both the bits g, adj equal to 1, g, adj equal to 1, return g. The adjacency matrix representation is good if the graphs are dense. The matrix requires O bits of storage and O time for initialization. If the number of edges is proportional to V2, then there is no problem because V2 steps are required to read the edges. If the graph is sparse, the initialization of the matrix dominates the running time of the algorithm, as it takes O, adjacency list. Graph declaration for adjacency list. In this representation, all the vertices connected to a vertex 5 are listed on an adjacency list for that vertex 5. This can be easily implemented with linked lists. That means, for each vertex 5, we use a linked list, and list nodes represents the connections between V and other vertices to which V has an edge. The total number of linked lists is equal to the number of vertices in the graph. The graph ADT can be declared as struct graph int t5 int e int adj, head pointers to linked list. Description. Considering the same example as that of the adjacency matrix, the adjacency list representation can be given as. Since vertex A has an edge for B and D, we have added them in the adjacency list for A. The same is the case with other vertices as well. One struct list node int I, xy, struct list node temp, struct graph G equal to malloc if retutin G. Nodes of the linked list. For this representation, the order of edges in the input is important. This is because they determine the order of the vertices on the adjacency lists. The same graph can be represented in many different ways in an adjacency list. The order in which edges appear on the adjacency list affects the order in which edges are processed by algorithms. Disadvantages of adjacency lists. Using adjacency list representation, we cannot perform some operations efficiently. As an example, consider the case of deleting a node. In adjacency list representation, it is not NU if we simply delete a node from the list representation. If we delete a node from the adjacency list, then that is enough. For each node on the adjacency list of that node specifies another vertex. We need to search other nodes linked list also for deleting it. This problem can be solved by linking the two list nodes that correspond to a particular edge and making the adjacency lists doubly linked. But all these extra links are risky to process. Adjacency set. It is very much similar to adjacency list, but instead of using linked lists, disjoint sets are used. For more details, refer to the disjoint sets ADT chapter. Comparison of graph representations. Directed and undirected graphs are represented with the same structures. For directed graphs, everything is the same, except that each edge is represented just once. An edge from X to Y is represented by a one value in AGJ in the adjacency matrix or by adding Y on X's adjacency list. For weighted graphs, everything is the same, except fill the adjacency matrix with weights instead of Boolean values. 9.5 Graph traversals. To solve problems on graphs, we need a mechanism for traversing the graphs. Graph traversal algorithms are also called graph search algorithms. Like trees traversal algorithms, graph search algorithms can be thought of as starting at some source vertex in a graph and searching the graph by going through the edges and marking the vertices. Now, we will discuss two such algorithms for traversing the graphs: depth first search, breadth first search, depth first search. DFS algorithm works in a manner similar to pre-order traversal of the trees. Like pre-order traversal internally, this algorithm also uses stack. Let us consider the following example. Suppose a person is trapped inside a maze. To come out from that maze, the person visits each path in each intersection. Let us say the person uses two colors of paint to mark the intersections already passed. When discovering a new intersection, it is marked gray, and he continues to go deeper. After reaching a dead end, the person knows that there is no more unexplored path from the gray intersection, which now is completed, and he marks it with black. This dead end is either an intersection which has already been marked gray or black, or simply a path that does not lead to an intersection. The intersections of the maze are the vertices, and the paths between the intersections are the edges of the graph. The process of returning from the dead end is called backtracking. We are trying to go away from the starting vertex into the graph as deep as possible, until we have to backtrack to the preceding gray vertex. In DFS algorithm, we encounter the following types of edges. For most algorithms, Boolean classification, unvisited, visited is enough. That means for some problems we need to use 3 colors, but for our discussion, 2 colors are enough. False true vertex is unvisited, vertex is visited. Initially, all vertices are marked unvisited. The DFS algorithm starts at a vertex U in the graph. By starting at vertex U, it considers the edges from U to other vertices. If the edge leads to an already visited vertex, then backtrack to current vertex U. If an edge leads to an unvisited vertex, then go to that vertex and start processing from that vertex. That means the new vertex becomes the current vertex. Follow this process until we reach the dead end. At this point, start backtracking. The process terminates when backtracking leads back to the start vertex. The algorithm based on mechanism is given below. Assume visited is a global array. This, int visited, void DFS visited equal to 1, for example, if the adjacency matrix is used for representing the graph, then the condition to be used for finding unvisited adjacent vertex of U is if and g age. For each unvisited adjacent node V of U, DFS, void DFS traversal for visited equal to 0. This loop is required if the graph has more than one component for if DFS. As an example, consider the following graph. We can see that sometimes an edge leads to an already discovered vertex. These edges are called back edges, and the other edges are called tree edges because deleting the back edges from the graph generates a tree. The final generated tree is called the DFS tree, and the order in which the vertices are processed is called DFS numbers of the vertices. In the graph below, the gray color indicates that the vertex is visited. We need to see when the visited table is updated. A. 11,110,000 billions HCE DFA, visited table, 11,111,000 billions HGCE, visited table, 11,110 billions HCE. Visited table 11,100 grams. Recursive call of DFS. Backtrack from F vertex F is visited. DF visited table A BHCE DF 11,111,100 in table 11,111,000 C DF visited table 11,110 grams. Backtrack from GA 11,111,111 billions HEA 11,111,110 grams. Backtrack from GA. Visited table 11,111,111 billions HCE. Visited table. Visited F. Visited 111 billions H. Visited table A 11,111,011 billions. 111 billion t. From the above diagrams, it can be seen that the DFS traversal creates a tree, and we call such tree a DFS tree. The above algorithm works even if the given graph has connected components. The time complexity of DFS is O if we use adjacency lists for representing the graphs. This is because we are starting at a vertex and processing the adjacent nodes only if they are not visited. Similarly, if an adjacency matrix is used for a graph representation, then all edges adjacent to a vertex can't be found efficiently, and this gives O complexity. Applications of DFS: topological sorting, finding connected components, finding articulation points of the graph, finding strongly connected components, solving puzzles such as mazes. For algorithms, refer to problem section. Breadth first search. The BFS algorithm works similar to level order traversal of the trees. Like level order traversal, BFS also uses queues. In fact, level order traversal got inspired from BFS. BFS works level by level. Initially, BFS starts at a given vertex, which is at level 0. In the first stage, it visits all vertices at level 1. In the second stage, it visits all vertices at the second level. These new vertices are the ones which are adjacent to level 1 vertices. BFS continues this process until all the levels of the graph are completed. Generally, queue data structure is used for storing the vertices of a level. As similar to DFS, assume that initially all vertices are marked unvisited. Vertices that have been processed and removed from the queue are marked visited. We use a queue to represent the visited set as it will keep the vertices in the order of when they were first visited. The implementation for the above discussion can be given as void BFS, in TV, struct q create q on q, while u, date q, process u, for example, print visited equal tune. For example, if the adjacency matrix is used for representing the graph, then the condition be used for finding unvisited adjacent vertex of u is, if and g adj, for each unvisited adjacent node v of u, one void BFS traversal, for visited equal to 0, this loop is required if the graph has more than one component for if BFS. As an example, let us consider the same graph as that of the DFS example. The BFS traversal can be shown as, starting vertex A is marked unvisited. Assume this is AT, level 0. Q, CHA, 11001, 111001. Time complexity of BFS is O if we use adjacency lists for representing the graphs, and O for adjacency matrix representation. Applications of BFS: finding all connected components in a graph, finding all nodes within one connected component, finding the shortest path between two nodes. Testing a graph for bipartiteness, comparing DFS and BFS. Comparing BFS and DFS, the big advantage of DFS is that it has much lower memory requirements than BFS because it's not required to store all of the child pointers at each level. Depending on the data and what we are looking for, either DFS or BFS can be advantageous. For example, in a family tree, if we are looking for someone who's still alive and if we assume that person would be at the bottom of the tree, then DFS is a better choice. BFS would take a very long time to reach that last level. The DFS algorithm finds the goal faster. Now, if we were looking for a family member who died a very long time ago, then that person would be closer to the top of the tree. In this case, BFS finds faster than DFS. So, the advantages of either vary depending on the data and what we are looking for. DFS is related to pre-order traversal of a tree. Like pre-order traversal, DFS visits each node before its children. The BFS algorithm works similar to level order traversal of the trees. If someone asks whether DFS is better or BFS is better, the answer depends on the type of the problem that we are trying to solve. BFS visits each level one at a time, and if we know the solution we are searching for is at a low depth, then BFS is good. DFS is a better choice if the solution is at maximum depth. The below table shows the differences between DFS and BFS in terms of their applications. 9.6 Topological sort. Topological sort is an ordering of vertices in a directed acyclic graph in which each node comes before all nodes to which it has outgoing edges. As an example, consider the course prerequisite structure at universities. A directed edge indicates that course V must be completed before course W. Topological ordering for this example is the sequence which does not violate the prerequisite requirement. Every DAG may have one or more topological orderings. Topological sort is not possible if the graph has a cycle, since for two vertices V and W on the cycle, V precedes W and W precedes V. Topological sort has an interesting property. All pairs of consecutive vertices in the sorted order are connected by edges, then these edges form a directed Hamiltonian path in the DAG. If a Hamiltonian path exists, the topological sort order is unique. If a topological sort does not form a Hamiltonian path, DAG can have two or more topological orderings. In the graph below, 7, 5, 3, 11, 8, 2, 9, 10, and 3, 5, 7, 8, 11, 2, 9, 10 are both topological orderings. Initially, in degree is computed for all vertices, starting with the vertices which are having in degree 0. That means consider the vertices which do not have any prerequisite. To keep track of vertices with in degree 0, we can use a queue. All vertices of in degree 0 are placed on queue. While the queue is not empty, a vertex V is removed, and all edges adjacent to V have their in degrees decremented. A vertex is put on the queue as soon as its in degree falls to 0. The topological ordering is the order in which the vertices DQ. The time complexity of this algorithm is O if adjacency lists are used. Void topological sort, struct QQ, int counter, int V, W, Q equal to create Q, counter equal to 0, for if equal to 0 on Q, while V equal to DQ, topological order plus counter, for each W adjacent to V if equal to 0 on Q, if print df, delete Q. Total running time of topological sort is O. Note, the topological sorting problem can be solved with DFS. Refer to the problem section for the algorithm. Applications of topological sorting. Representing course prerequisites, detecting deadlocks, pipeline of computing jobs, checking for symbolic link loop, evaluating formulae in spreadsheet. 9.7 Shortest path algorithms. Let us consider the other important problem of a graph. Given a graph G equal to and A, distinguish vertex S, we need to find the shortest path from S to every other vertex in G. There are variations in the shortest path algorithms which depend on the type of the input graph and are given below. Variations of shortest path algorithms. Applications of shortest path algorithms. Finding fastest way to go from one place to another. Finding cheapest way to fly, send data from one city to another. Shortest path in unweighted graph. Let's be the input vertex from which we want to find the shortest path to all other vertices. Unweighted graph is a special case of the weighted shortest path problem, with all edges a weight of 1. The algorithm is similar to BFS, and we need to use the following data structures. A distance table with 3 columns. O, distance from source vertex. O path contains the name of the vertex through which we get the shortest distance. A queue is used to implement breadth first search. It contains vertices whose distance from the source node has been computed, and their adjacent vertices are to be examined. As an example, consider the following graph and its adjacency list representation. The adjacency list for this graph is E, G, F, G, F. Let S equal to C. The distance from C to C is 0. Initially, distances to all other nodes are not computed, and we initialize the second column in the distance table for all vertices with -1 as below. Algorithm. Void unweighted shortest path. Struct q, q create q, int v, w, on q. For distance equal to -1, distance equal to 0, while v equal to dq. For each w adjacent to v, if equal to -1, to distance plus 1, each vertex examined at most once path equal to v. On q, each vertex on queued at most once delete q. Running time, O, if adjacency lists are used. In for loop, we are checking the outgoing edges for a given vertex, and the sum of all examined edges in the while loop is equal to the number of edges, which gives O. If we use matrix representation, the complexity is O, because we need to read an entire row in the matrix of length or 5 or in order to find the adjacent vertices for a given vertex. Shortest path and weighted graph. A famous solution for the shortest path problem was developed by Dijkstra. Dijkstra's algorithm is a generalization of the BFS algorithm. The regular BFS algorithm cannot solve the shortest path problem, as it cannot guarantee that the vertex at the front of the queue is the vertex closest to source S. Before going to code, let us understand how the algorithm works. As in unweighted shortest path algorithm, here too we use the distance table. The algorithm works by keeping the shortest distance of vertex v from the source in the distance table. The value distance holds the distance from S to v. The shortest distance of the source to itself is 0. The distance table for all other vertices is set to -1 to indicate that those vertices are not already processed. After the algorithm finishes, the distance table will have the shortest distance from source S to each other vertex v. To simplify the understanding of Dijkstra's algorithm, let us assume that the given vertices are maintained in two sets. Initially, the first set contains only the source element, and the second set contains all the remaining elements. After the kth iteration, the first set contains k vertices which are closest to the source. These k vertices are the ones for which we have already computed the shortest distances from source. Notes on Dijkstra's algorithm. It uses greedy method, always pick the next closest vertex to the source. It uses priority queue to store unvisited vertices by distance from S. It does not work with negative weights. Difference between unweighted shortest path and Dijkstra's algorithm. 1. To represent weights in the adjacency list, each vertex contains the weights of the edges. 2. Instead of ordinary queue, we use priority queue, and the vertex with the smallest distance is selected for processing. 3. The distance to a vertex is calculated by the sum of the weights of the edges on the path from the source to that vertex. 4. We update the distances in case the newly computed distance is smaller than the old distance which we have already computed. Void Dijkstra compute new distance d equal to distance plus weight, if equal to -1, equal to distance new distance d. Insert w in the priority queue with priority d path equal to v, if new distance d, distance equal to new distance d. Update priority of vertex w to be d, path equal to v. The above algorithm can be better understood through an example, which will explain each step that is taken and how distance is calculated. The weighted graph below has 5 vertices from A and E. The value between the two vertices is known as the edge cost between two vertices. For example, the edge cost between A and C is 1. Dijkstra's algorithm can be used to find the shortest path from source A to the remaining vertices in the graph. Initially, the distance table is, after the first step, from vertex A, we can reach B and C. So, in the distance table, we update the reachability of B and C with their costs, and the same is shown below. Shortest path from B, C, from A. Now, let us select the minimum distance among all. The minimum distance vertex is C. That means we have to reach other vertices from these two vertices. For example, B can be reached from A and also from C. In this case, we have to select the one which gives the lowest cost. Since reaching B through C is giving the minimum cost, we update the distance table for vertex B with cost 3, and the vertex from which we got this cost is C. Shortest path to B, D, using C as intermediate vertex. The only vertex remaining is E. To reach E, we have to see all the paths through which we can reach E and select the one which gives the minimum cost. We can see that if we use B as the intermediate vertex through C, we get the minimum cost. The final minimum cost tree which Dijkstra's algorithm generates is performance. In Dijkstra's algorithm, the efficiency depends on the number of delete mins and updates for priority queues that are used. If a standard binary heap is used, then the complexity is O. The term E log V comes from E updates for the standard heap. If the set used is an array, then the complexity is O. Disadvantages of Dijkstra's algorithm. As discussed above, the major disadvantage of the algorithm is that it does a blind search, thereby wasting time and necessary resources. Another disadvantage is that it cannot handle negative edges. This leads to acyclic graphs and most often cannot obtain the right shortest path. Relatives of Dijkstra's algorithm. The Bellman-Ford algorithm computes single source shortest paths in a weighted digraph. It uses the same concept as that of Dijkstra's algorithm but can handle negative edges as well. It has more running time than Dijkstra's algorithm. Prim's algorithm finds a minimum spanning tree for a connected weighted graph. It implies that a subset of edges that form a tree where the total weight of all the edges in the tree is minimized. Bellman-Ford algorithm. If the graph has negative edge costs, then Dijkstra's algorithm does not work. The problem is that once a vertex u is declared known, it is possible that from some other unknown vertex 5, there is a path back to u that is very negative. In such a case, taking a path from S to V back to u is better than going from S to u without using V. A combination of Dijkstra's algorithm and unweighted algorithms will solve the problem. Initialize the queue with S. Then, at each stage, we dequeue a vertex 5. We find all vertices W adjacent to V such that distance to V plus weight old distance to W. We update W old distance and path, and place W on a queue if it is not already there. A bit can be set for each vertex to indicate presence in the queue. We repeat the process until the queue is empty. Void Bellman-Ford algorithm, struct q equal to create q, int v, w, on q, distance equal to 0, while v equal to dq. Assume the distance table is filled with int max for all adjacent vertices w of v. Compute new distance d distance plus weight if equal to distance plus weight, path equal to v, if nq. This algorithm works if there are no negative cost cycles. Each vertex can dequeue at most or 5 times, so the running time is O if adjacency lists are used. Overview of shortest path algorithms. 9.8 Minimal spanning tree. The spanning tree of a graph is a subgraph that contains all the vertices and is also a tree. A graph may have many spanning trees. As an example, consider a graph with 4 vertices as shown below. Let us assume that the corners of the graph are vertices. For this simple graph, we can have multiple spanning trees as shown below. The algorithm we will discuss now is minimum spanning tree in an undirected graph. We assume that the given graphs are weighted graphs. If the graphs are unweighted graphs, then we can still use the weighted graph algorithms by treating all weights as equal. A minimum spanning tree of an undirected graph G is a tree formed from graph edges that connect all the vertices of G with minimum total cost. A minimum spanning tree exists only if the graph is connected. There are 2 famous algorithms for this problem. Prim's algorithm. Kruskal's algorithm. Prim's algorithm. Prim's algorithm is almost the same as Dijkstra's algorithm. As in Dijkstra's algorithm, in Prim's algorithm, we keep the values distance and paths in the distance table. The only exception is that since the definition of distance is different, the updating statement also changes a little. The update statement is simpler than before. Void prims compute new distance d equal to distance plus weight if equal to -1. distance equal to weight, insert W in the priority Q with priority D path equal to V if new distance D, distance weight, or update priority of vertex W to be D, path equal to V. The entire implementation of this algorithm is identical to that of Dijkstra's algorithm. The running time is O2 without heaps and O using binary heaps. Kruskal's algorithm. The algorithm starts with 5 different trees. While constructing the minimum spanning tree, every time Kruskal's algorithm selects an edge that has minimum weight and then adds that edge if it doesn't create a cycle. So initially, there are 5 or single node trees in the forest. Adding an edge merges 2 trees into one. When the algorithm is completed, there will be only one tree, and that is the minimum spanning tree. There are 2 ways of implementing Kruskal's algorithm: by using disjoint sets, using union and find operations. By using priority queues, maintains weights in priority queue. The appropriate data structure is the union find algorithm. 2 vertices belong to the same set if and only if they are connected in the current spanning forest. Each vertex is initially in its own set. If U and V are in the same set, the edge is rejected because it forms a cycle. Otherwise, the edge is accepted, and a union is performed on the 2 sets containing U and V. As an example, consider the following graph. Now let us perform Kruskal's algorithm on this graph. We always select the edge which has minimum weight. From the above graph, the edges which have minimum weight are A, D, and B. From these 2, we can select one of them, and let us assume that we select add. DF is the next edge that has the lowest cost. B now has the lowest cost, and we select it. Next, AC and CE have the low cost of 7, and we select AC. Then we select CE as its cost is 7, and it does not form a cycle. The next low cost edges are CB and EF. But if we select CB, then it forms a cycle, so we discard it. This is also the case with EF, so we should not select those 2. And the next low cost is 9. Selecting BD forms a cycle, so we discard it. Adding EG will not form a cycle, and therefore with this edge we complete all vertices of the graph. Void Kruskal union return S. Note, for implementation of union and find operations, refer to the disjoint sets ADT chapter. The worst case running time of this algorithm is O, which is dominated by the heap operations. That means, since we are constructing the heap with E edges, we need O time to do that. 9.9 Graph algorithms, problems, and solutions. Problem -1. In an undirected simple graph with n vertices, what is the maximum number of edges? Self loops are not allowed. Solution, since every node can connect to all other nodes, the first node can connect to n1 nodes. The second node can connect to n2 nodes. The total number of edges is 1 plus 2 plus 3 plus n equal to 2 edges. Problem -2. How many different adjacency matrices does a graph with n vertices and E edges have? Solution, it's equal to the number of permutations of n elements, that is n. Problem 3. How many different adjacency lists does a graph with n vertices have? Solution, it's equal to the number of permutations of edges, that is E. Problem -4. Which undirected graph representation is most appropriate for determining whether or not a vertex is isolated? Solution, adjacency list. If we use the adjacency matrix, then we need to check the complete row to determine whether that vertex has edges or not. By using the adjacency list, it is very easy to check, and it can be done just by checking whether that vertex has null for next pointer or not. Problem -5 for checking whether there is a path from source S to target T, which one is best between disjoint sets and DFS? Solution, the table below shows the comparison between disjoint sets and DFS. The entries in the table represent the case for any pair of nodes. Problem -6. What is the maximum number of edges a directed graph with n vertices can have and still not contain a directed cycle? Solution, the number is V2. Any directed graph can have at most n2 edges. However, since the graph has no cycles, it cannot contain a self-loop, and for any pair x, y of vertices, at most 1 edge from and can be included. Therefore, the number of edges can be at most /2 as desired. It is possible to achieve 5/2 edges. Label n nodes 1, 2, n, and add an edge if and only if x, y. This graph has the appropriate number of edges and cannot contain a cycle. Problem -7. How many simple directed graphs with no parallel edges and self-loops are possible in terms of V? Solution. Since each vertex can connect to V, 1 vertices without self-loops. What are the differences between DFS and BFS? Problem 8. Solution. Problem. -9. Earlier in this chapter, we discussed minimum spanning tree algorithms. Now, give an algorithm for finding the maximum weight spanning tree in a graph. Solution. Given graph. Transform graph with negative edge weights. Using the given graph, construct a new graph with the same nodes and edges. But instead of using the same weights, take the negative of their weights. That means weight of an edge equal to negative of weight of the corresponding edge in the given graph. Now, we can use existing minimum spanning tree algorithms on this new graph. As a result, we will get the maximum weight spanning tree in the original one. Problem 10. Give an algorithm for checking whether a given graph G has simple path from source S to destination D. Assume the graph G is represented using the adjacent matrix. Solution. Let us assume that the structure for the graph is struct graph int 5 int e, number of vertices, number of edges int age matrix, 2-dimensional array for storing the connections. For each vertex, call DFS and check whether the current vertex is the same as the destination vertex or not. If they are the same, then return 1. Otherwise, call the DFS on its unvisited neighbors. One important thing to note here is that we are calling the DFS algorithm on vertices which are not yet visited. Void has simple path int t, visited equal to 1 if return 1, 4 if andend, visited if return 1, return 0. Time complexity, O, in the above algorithm, for each node, since we are not calling DFS on all of its neighbors, space complexity, O. Problem -11, count simple paths for a given. Graph G has simple path from source S to destination D. Assume the graph is represented using the adjacent matrix. Solution, similar to the discussion in problem 10, start at one node and call DFS on that node. As a result of this call, it visits all the nodes that it can reach in the given graph. That means it visits all the nodes of the connected component of that node. If there are any nodes that have not been visited, then again start at one of those nodes and call DFS. Before the first DFS in each connected component, increment the connected components count. Continue this process until all the graph nodes are visited. As a result, at the end we will get the total number of connected components. The implementation based on this logic is given below. Void count simple paths int t, visited equal to 1, if count plus plus, visited equal to 0, return 4, if andend, visited, DFS, visited equal to 0. Problem 12, all pairs shortest path problem, find the shortest graph distances between every pair of vertices in a given graph. Let us assume that the given graph does not have negative edges. Solution, the problem can be solved using n applications of Dijkstra's algorithm. That means we apply Dijkstra's algorithm on each vertex of the given graph. This algorithm does not work if the graph has edges with negative weights. Problem -13 in problem 12. How do we solve the all pairs shortest path problem if the graph has edges with negative weights? Solution. This can be solved by using the Floyd-Warshall algorithm. This algorithm also works in the case of a weighted graph where the edges have negative weights. This algorithm is an example of dynamic programming. Refer to the dynamic programming chapter. Problem -14 DFS application, cut vertex or articulation points. Solution. In an undirected graph, a cut vertex is a vertex, and if we remove it, then the graph splits into two disconnected components. As an example, consider the following figure. Removal of the D vertex divides the graph into two connected components. Similarly, removal of the C vertex divides the graph into. For this graph, A and C are the cut vertices. Note, a connected undirected graph is called biconnected if the graph is still connected after removing any vertex. DFS provides a linear time algorithm to find all cut vertices in a connected graph. Starting at any vertex, call a DFS and number the nodes as they are visited. For each vertex 5, we call this DFS number DFS num. The tree generated with DFS traversal is called DFS spanning tree. Then, for every vertex V in the DFS spanning tree, we compute the lowest numbered vertex, which we call low, that is reachable from V by taking 0 or more tree edges and then possibly one back edge. Based on the above discussion, we need the following information for this algorithm. The DFS num of each vertex in the DFS tree, and for each vertex phi, the lowest depth of neighbors of all descendants of V in the DFS tree, called the low. The DFS num can be computed during DFS. The low of V can be computed after visiting all descendants of V as the minimum of the DFS num of all neighbors of V, and the low of all children of V in the DFS tree. The root vertex is a cut vertex if and only if it has at least two children. A non-root vertex U is a cut vertex if and only if there is a son V of U such that low greater than or equal to DFS num. This property can be tested once the DFS is returned from every child of U, and if true, U separates the graph into different biconnected components. This can be represented by computing one biconnected component out of every such V, and then erasing the subtree of V from the tree. For the given graph, the DFS tree with DFS num low can be given as shown in the figure below. The implementation for the above discussion is int edge matrix nt DFS num n no m equal to 0, low void cut vertices equal to low DFS num plus plus. For if and n DFS num equal to -1, cut vertices if DFS num equal to print df low min, low, else is a back edge low equal to min DFS num. Problem -15. Let G be a connected graph of order n. What is the maximum number of cut vertices that G can contain? Solution, n, 2. As an example, consider the following graph. In the graph below, except for the vertices 1 and n, all the remaining vertices are cut vertices. This is because removing 1 and n vertices does not split the graph into two. This is a case where we can get the maximum number of cut vertices. Problem -16 DFS application, cut bridges or cut edges. Solution. Definition. Let G be a connected graph. An edge UV in G is called a bridge of G if G, UV is disconnected. As an example, consider the following graph. In the above graph, if we remove the edge UV, then the graph splits into two components. For this graph, UV is a bridge. The discussion we had for cut vertices holds good for bridges also. The only change is, instead of printing the vertex, we give the edge. The main observation is that an edge cannot be a bridge if it is part of a cycle. If is not part of a cycle, then it is a bridge. We can detect cycles in DFS by the presence of back edges, is a bridge if and only if none of V or V's children has a back edge to U or any of U's ancestors. To detect whether any of these children has a back edge to U's parent, we can use a similar idea as above to see what is the smallest DFS num reachable from the subtree rooted at V. int DFS num equal to 0 low void bridges else if DFS num equal to print as a bridge low min, low, is a back edge low equal to min DFS num. Problem 17 DFS application, discuss Euler circuits. Solution. Before discussing this problem, let us see the terminology. Eulerian tour, a path that contains all edges without repetition. Eulerian circuit, a path that contains all edges without repetition and starts and ends in the same vertex. Eulerian graph, a graph that contains an Eulerian circuit, even vertex, a vertex that has an even number of incident edges. Odd vertex, a vertex that has an odd number of incident edges. Euler circuit. For a given graph, we have to reconstruct the circuits using a pen, drawing each line exactly once. We should not lift the pen from the paper while drawing. That means we must find a path in the graph that visits every edge exactly once, and this problem is called an Euler path or Euler circuit problem. This puzzle has a simple solution based on DFS. An Euler circuit exists if and only if the graph is connected and the number of neighbors of each vertex is even. Start with any node, select any untraversed outgoing edge, and follow it. Repeat until there are no more remaining unselected outgoing edges. For example, consider the following graph. A legal Euler circuit of this graph is 1,341,235,441 in vertex 1, then select the edge to vertex 2, then select the edge to vertex 0. There are now no remaining unchosen edges from vertex 0, 0. We now have a circuit 0, 1, 2, 0 that does not traverse every edge. So we pick some other vertex that is on that circuit, say vertex 1. We then do another depth first search of the remaining edges. Say we choose the edge to node 3, then 4, then 1. Again, we are stuck. There are no more unchosen edges from node 1. We now splice this path 1, 3, 4, 1 into the old path 0, 1, 2, 0 to get 0, 1, 3, 4, 1, 2, 0. The unchosen edges now look like this. We can pick yet another vertex to start another DFS. If we pick vertex 2 and splice the path 2, 3, 5, 4, 2, then we get the final circuit 0, 1, 3, 4, 1, 2, 3, 5, 4, 2, 0. A similar problem is to find a simple cycle in an undirected graph that visits every vertex. This is known as the Hamiltonian cycle problem. Although it seems almost identical to the Euler circuit problem, no efficient algorithm for it is known. Notes. A connected undirected graph is Eulerian if and only if every graph vertex has an even degree, or exactly two vertices with an odd degree. A directed graph is Eulerian if it is strongly connected and every vertex has an equal in and out degree. Application. A postman has to visit a set of streets in order to deliver mails and packages. He needs to find a path that starts and ends at the post office and that passes through each street. Exactly once. This way the postman will deliver mails and packages to all the necessary streets, and at the same time will spend minimum time effort on the road. Problem -18 DFS application, finding strongly connected components. Solution. This is another application of DFS. In a directed graph, two vertices U and V are strongly connected if and only if there exists a path from U to V and there exists a path from V to U. The strong connectedness is an equivalence relation. A vertex is strongly connected with itself. If a vertex U is strongly connected to a vertex V, then V is strongly connected to U. If a vertex U is strongly connected to a vertex V and V is strongly connected to a vertex X, then U is strongly connected to X. What this says is, for a given directed graph, we can divide it into strongly connected components. This problem can be solved by performing two depth first searches. With two DFS searches, we can test whether a given directed graph is strongly connected or not. We can also produce the subsets of vertices that are strongly connected. Algorithm. Perform DFS on given graph G. Number vertices of given graph G according to a post-order traversal of depth first spanning forest. Construct graph G by reversing all edges in G. Perform DFS on GR. Always start a new DFS at the highest numbered vertex. Each tree in the resulting depth first spanning forest corresponds to a strongly connected component. Why this algorithm works? Let us consider two vertices, V and W. If they are in the same strongly connected component, then there are paths from V to W and from W to V in the original graph G, and hence also in GR. If two vertices V and W are not in the same depth first spanning tree of GR, clearly they cannot be in the same strongly connected component. As an example, consider the graph shown below on the left. Let us assume this graph is G. Now, as per the algorithm, performing DFS on this G graph gives the following diagram. The dotted line from C to A indicates a back edge. Now, performing post-order traversal on this tree gives D, C, B, and A. Now reverse the given graph G and call it G, and at the same time assign post-order numbers to the vertices. The reverse graph G will look like the last step is performing DFS on this reverse graph GR. While doing DFS, we need to consider the vertex which has the largest DFS number. So first we start at A, and with DFS we go to C, and then B. At B, we cannot move further. This says that, and. The implementation based on this discussion can be shown as graph represented in AdJ matrix. ENT AdJ matrix table vector NCC int counter equal to 0. This table contains the DFS search number INT DFS num, NUM equal to 0, low, void strongly connected components while equal to counter, table equal to counter, push, plus plus counter, problem -19 count the number of connected components of graph G, which is represented in the adjacent matrix. Solution. This problem can be solved with one extra counter in DFS. Visited is a global array. INT visited, void DFS, visited equal to 1, 4. For example, if the adjacency matrix is used for representing the graph, then the condition to be used for finding unvisited adjacent vertex of U is, if and in G, add G. For each unvisited adjacent node V of U, DFS, void DFS traversal, int count equal to 0 for visited equal to 0. This loop is required if the graph has more than one component for if DFS count plus plus return count. Time complexity, same as that of DFS, and it depends on implementation. With adjacency matrix, the complexity is O, and with adjacency matrix, the complexity is O. Problem 20. Can we solve the problem 19 using BFS? Solution. Yes. This problem can be solved with one extra counter in BFS. Void BFS, int V, Q, Q, equal to create Q, on Q, while U, DQ, process U. For example, print visited equal tune. For example, if the adjacency matrix is used for representing the graph, then the condition be used for finding unvisited adjacent vertex of U is, if and in G, add G. For each unvisited adjacent node V of U and Q, void BFS traversal for visited equal to 0, this loop is required if the graph has more than one component for if BFS. Time complexity, same as that of BFS, and it depends on implementation. With adjacency matrix, the complexity is O, and with adjacency matrix, the complexity is O. Problem 21. Let us assume that G is an undirected graph. Give an algorithm for finding a spanning tree, which takes O time complexity. Solution. The test for a cycle can be done in constant time by marking vertices that have been added to the set S. An edge will introduce a cycle if both its vertices have already been marked. Algorithm. S. Assume S is a set for each edge E, Euro E. Problem 22. Is there any other way of solving 0? Solution. Yes. We can run BFS and find the BFS tree for the graph, then start at the root element, and keep moving to the next levels. At the same time, we have to consider the nodes in the next level only once. That means if we have a node with multiple input edges, then we should consider only one of them. Otherwise, they will form a cycle. Problem -23. Detecting a cycle in an undirected graph. Solution. An undirected graph is a cyclic if and only if a DFS yields no back edges, edges where V has already been discovered and is an ancestor of U. Execute DFS on the graph. If there is a back edge, the graph has a cycle. If the graph does not contain a cycle, then or E or less than or 5 or and DFS cost O. If the graph contains a cycle, then a back edge is discovered after 2 or 5 or steps at most. Problem -24. Detecting a cycle in DAG. Solution. Cycle detection on a graph is different than on a tree. This is because in a graph, a node can have multiple parents. In a tree, the algorithm for detecting a cycle is to do a depth first search, marking nodes as they are encountered. If a previously marked node is seen again, then a cycle exists. This won't work on a graph. Let us consider the graph shown in the figure below. If we use a tree cycle detection algorithm, then it will report the wrong result. That means that this graph has a cycle in it, but the given graph does not have a cycle in it. This is because node 3 will be seen twice in a DFS starting at node 1. The cycle detection algorithm for trees can easily be modified to work for graphs. The key is that in a DFS of an acyclic graph, a node whose descendants have all been visited can be seen again without implying a cycle. But if a node is seen for the second time before all its descendants have been visited, then there must be a cycle. Can you see why this is? Suppose there is a cycle containing node A. This means that A must be reachable from one of its descendants. So when the DFS is visiting that descendant, it will see A again before it has finished visiting all of A's descendants. So there is a cycle. In order to detect cycles, we can modify the depth first search. AT detect cycle and has cycle visited equal tune. For if equal to U on and visited, return 1, else predecessor equal to U, return has cycle, return 0. Time complexity. O. Problem 25. Given a directed acyclic graph, give an algorithm for finding its depth. Solution. If it is an undirected graph, we can use the simple unweighted shortest path algorithm. We just need to return the highest number among all distances. For directed acyclic graph, we can solve by following the similar approach which we used for finding the depth in trees. In trees, we have solved this problem using level order. Traversal. Assuming the given graph is a DAG int depth in DAG, struct Q int counter int V W, Q equal to create Q, counter equal to 0 for if and Q, 0 and Q, while V equal to DQ, if. Counter plus plus if and Q, for each W adjacent to V if equal to 0, delete Q, return counter, and Q. Total running time is O. Problem 26. How many topological sorts of the following DAG are there? Solution. If we observe the above graph, there are 3 stages with 2 vertices. In the early discussion of this chapter, we saw that topological sort picks the elements with 0 in degree at any point of time. At each of the 2 vertices stages, we can first process either the top vertex or the bottom vertex. As a result, at each of these stages, we have 2 possibilities. So the total number of possibilities is the multiplication of possibilities at each stage, and that is 2 times 2 times 2 equal to 8. Problem 27. Unique topological ordering. Design an algorithm to determine whether a directed graph has a unique topological ordering. Solution. A directed graph has a unique topological ordering if and only if there is a directed edge between each pair of consecutive vertices in a topological order. This can also be defined as a directed graph has a unique topological ordering if and only if it has a Hamiltonian path. If the graph has multiple topological orderings, then a second topological order can be obtained by swapping a pair of consecutive vertices. Problem 28. Let us consider the prerequisites for courses at IIT Bombay. Suppose that all prerequisites are mandatory, every course is offered every semester, and there is no limit to the number of courses we can take in one semester. We would like to know the minimum number of semesters required to complete the major. Describe the data structure we would use to represent this problem, and outline a linear time algorithm for solving it. Solution. Use a directed acyclic graph. The vertices represent courses and the edges represent the prerequisite relation between courses at IIT Bombay. It is a DAG because the prerequisite relation has no cycles. The number of semesters required to complete the major is one more than the longest path in the DAG. This can be calculated on the DFS tree recursively in linear time. The longest path out of a vertex x is 0 if x has out degree 0, otherwise it is 1 plus max. Problem 29. At a university, let's say IIT Bombay, there is a list of courses along with their prerequisites. That means two lists are given. A, courses list. B, prerequisites. B contains couples where x, y, i.e. A, indicating that course x can't be taken before course y. Let us consider a student who wants to take only one course in a semester. Design a schedule for this student. Example A equal to, B equal to. One possible schedule could be Semester 1, Data Structures. Semester 2, Algorithms. Semester 3, C-Lang. Semester 4, OS. Semester 5, Company. Semester 6, Design Patterns. Semester 7, Programming. Solution. The solution to this problem is exactly the same as that of topological sort. Assume that the courses' names are integers in the range n is known. The relations between the courses will be represented by a directed graph G equal to, where 5 are the set of courses, and if course I is prerequisite of course J, E will contain the edge. Let us assume that the graph will be represented as an adjacency list. First, let's observe another algorithm to topologically sort a DAG in O. Find in degree of all the vertices, O. Repeat. Find a vertex V with in degree 0, output V, and remove it from G, along with its edges, O. Reduce the in degree of each node used such as was an edge in G, and keep a list of vertices with in degree 0, O. Repeat the process until all the vertices are removed. The time complexity of this algorithm is also the same as that of the topological sort, and it is O. Problem 30 and problem 29, a student wants to take all the courses in A in the minimal number of semesters. That means the student is ready to take any number of courses in a semester. Design a schedule for this scenario. One possible schedule is Semester 1, C-Lang, OS. Design Pattern Semester 2, Data Structures, CO, Programming Semester 3, Algorithms. Solution. A variation of the above topological sort algorithm with a slight change. In each semester, instead of taking one subject, take all the subjects with 0 in degree. That means execute the algorithm on all the nodes with degree 0. Time complexity. O. Problem minus 31 LCA of a DAG. Given a DAG and two vertices V and W, find the lowest common ancestor of V and W. Descendants that are also ancestors of V and W. Hint. Define the height of a vertex V in a DAG to be the length of the longest path from root to V. Among the vertices that are ancestors of both V and W, the one with the greatest height is an LCA of V and W. Problem 32. Shortest ancestral path. Given a DAG and two vertices V and W, find the shortest ancestral path between V and W. An ancestral path between V and W is a common ancestor X, along with the shortest path from V to X and a shortest path from W to X. The shortest ancestral path is the ancestral path whose total length is minimized. Hint. Run BFS 2 times. First run from V and second time from W. Find a DAG where the shortest ancestral path goes to a common ancestor X that is not an LCA. Problem 33. Let us assume that we have two graphs G1 and G2. How do we check whether they are isomorphic or not? Solution. There are many ways of representing the same graph. As an example, consider the following simple graph. It can be seen that all the representations below have the same number of vertices and the same number of edges. Definition. Graphs G1 equal to and G2 equal to are isomorphic if 1. There is a 1-to-1 correspondence from V1 to V2 and 2. There is a 1-to-1 correspondence from E1 to E2 that map each edge of G1 to G2. Now, for the given graphs, how do we check whether they are isomorphic or not? In general, it is not a simple task to prove that two graphs are isomorphic. For that reason, we must consider some properties of isomorphic graphs. That means those properties must be satisfied if the graphs are isomorphic. If the given graph does not satisfy these properties, then we say they are not isomorphic graphs. Property. Two graphs are isomorphic if and only if, for some ordering of their vertices, their adjacency matrices are equal. Based on the above property, we decide whether the given graphs are isomorphic or not. In order to check the property, we need to do some matrix transformation operations. Problem 34. How many simple undirected non-isomorphic graphs are there with n vertices? Solution. We will try to answer this question in 2 steps. First, we count all labeled graphs. Assume all the representations below are labeled with as vertices. The set of all such graphs for n equal to 3 are, there are only 2 choices for each edge. It either exists or it does not. Therefore, since the maximum number of edges is n2 equal to NCZ, the total number of undirected labeled graphs is. Problem 35. Hamiltonian path in DAGs. Given a DAG, design a linear time algorithm to determine whether there is a path that visits each vertex exactly once. Solution. The Hamiltonian path problem is an NP-complete problem. To solve this problem, we will try to give the approximation algorithm. Let us consider the topological sort algorithm for solving this problem. Topological sort has an interesting property, that if all pairs of consecutive vertices in the sorted order are connected by edges, then these edges form a directed Hamiltonian path in the DAG. If a Hamiltonian path exists, the topological sort order is unique. Also, if a topological sort does not form a Hamiltonian path, the DAG will have 2 or more topological orderings. Approximation algorithm. Compute a topological sort and check if there is an edge between each consecutive pair of vertices in the topological order. In an unweighted graph, find a path from S to T that visits each vertex exactly once. The basic solution based on backtracking is, we start at S and try all of its neighbors recursively, making sure we never visit the same vertex twice. The algorithm based on this implementation can be given as bool sentable, void Hamiltonian path, if else, check that we have seen all vertices. For if and then G edge, sentable equal to true, Hamiltonian path, sentable equal to false. Note that if we have a partial path from S to U using vertices S equal to V1, V2, V1 equal to U, then we don't care about the order in which we visited these vertices so as to figure out which vertex to visit next. All that we need to know is the set of vertices we have seen array and which vertex we are at right now. There are two possible sets of vertices and n choices for u. In other words, there are two n possible sentable arrays and n different parameters to Hamiltonian path. What Hamiltonian path does during any particular recursive call is completely determined by the sentable array and the parameter u. Problem 36 for a given graph G with n vertices, how many trees we can construct? Solution. There is a simple formula for this problem and it is named after Arthur Cayley. For a given graph with n labeled vertices, the formula for finding number of trees on is n minus 2. Below, the number of trees with different n values is shown. Problem minus 37 for a given graph G with n vertices, how many spanning trees can we construct? Solution. The solution to this problem is the same as that of problem 36. It is just another way of asking the same question, because the number of edges in both regular tree and spanning tree are the same. Problem minus 38. The Hamiltonian cycle problem, is it possible to traverse each of the vertices of a graph exactly once, starting and ending at the same vertex? Solution. Since the Hamiltonian path problem is an NP-complete problem, the Hamiltonian cycle problem is an NP-complete problem. A Hamiltonian cycle is a cycle that traverses every vertex of a graph exactly once. There are no known conditions in which are both necessary and sufficient, but there are a few sufficient conditions. For a graph to have a Hamiltonian cycle, the degree of each vertex must be 2 or more. The Peterson graph does not have a Hamiltonian cycle, and the graph is given below. In general, the more edges a graph has, the more likely it is to have a Hamiltonian cycle. Let G be a simple graph with n greater than or equal to 3 vertices. If every vertex has a degree of at least n, then G has a Hamiltonian cycle. 2. The best known algorithm for finding a Hamiltonian cycle has an exponential worst-case complexity. Note, for the approximation algorithm of Hamiltonian path, refer to the dynamic programming chapter. Problem minus 39. What is the difference between Dijkstra's and Prim's algorithm? Solution. Dijkstra's algorithm is almost identical to that of Prim's. The algorithm begins at a specific vertex and extends outward within the graph until all vertices have been reached. The only distinction is that Prim's algorithm stores a minimum cost edge, whereas Dijkstra's algorithm stores the total cost from a source vertex to the current vertex. More simply, Dijkstra's algorithm stores a summation of minimum cost edges, whereas Prim's algorithm stores, at most, one minimum cost edge. Problem minus 40. Reversing graph. Give an algorithm that returns the reverse of the directed graph. Solution. In graph theory, the reverse of a directed graph G is another directed graph on the same set of vertices with all the edges reversed. That means if G contains an edge, then the reverse of G contains an edge, and vice versa. Algorithm. Graph reverse the directed graph, create new graph with name reversed graph, and let us assume that this will contain the reversed graph. The reversed graph also will contain same number of vertices and edges. For each vertex of given graph G, for each vertex W adjacent to V, add the W to V edge in reversed graph. That means we just need to reverse the bits in adjacency matrix. Return reverse graph. Problem minus 41. Traveling salesperson problem. Find the shortest path in a graph that visits each vertex at least once, starting and ending at the same vertex. Solution. The traveling salesman problem is related to finding a Hamiltonian cycle. Given a weighted graph G, we want to find the shortest cycle that visits all the vertices. Approximation algorithm. This algorithm does not solve the problem, but gives a solution which is within a factor of 2 of optimal. 1. Find a minimal spanning tree. 2. Do a DFS of the MST. For details, refer to the chapter on complexity classes. Problem minus 42. Discuss bipartite matchings. Solution. In bipartite graphs, we divide the graphs into 2 disjoint sets, and each edge connects a vertex from one set to a vertex in another subset. Definition. A simple graph G equal to is called a bipartite graph if its vertices can be divided into 2 disjoint sets, 5 equal to V1 UV2, such that every edge has the form E equal to where a Euro V1 and B Euro V2. One important condition is that no vertices both in V1 or both in V2 are connected. Properties of bipartite graphs. A graph is called bipartite if and only if a given graph does not have an odd length cycle. A complete bipartite graph Km, N is a bipartite graph that has each vertex from one set adjacent to each vertex from another set. K, 2, 3. A subset of edges, MC, is a matching if no 2 edges have a common vertex. As an example, matching sets of edges are represented with dotted lines. A matching M is called maximum if it has the largest number of possible edges. In the graphs, the dotted edges represent the alternative matching for the given graph. A matching M is perfect if it matches all vertices. We must have V1 equal to V2 in order to have perfect matching. An alternating path is a path whose edges alternate between matched and unmatched edges. If we find an alternating path, then we can improve the matching. This is because an alternating path consists of matched and unmatched edges. The number of unmatched edges exceeds the number of matched edges by 1. Therefore, an alternating path always increases the matching by 1. The next question is, how do we find a perfect matching? Based on the above theory and definition, we can find the perfect matching with the following approximation algorithm. Matching algorithm. 1. Start at unmatched vertex. 2. Find an alternating path. 3. If it exists, change matching edges to no matching edges, and conversely, if it does not exist, choose another unmatched vertex. 4. If the number of edges equals V2, stop. Otherwise, proceed to step 1 and repeat, as long as all vertices have been examined without finding any alternating paths. Time complexity of the matching algorithm. The number of iterations is in O. The complexity of finding an alternating path using BFS is O. Therefore, the total time complexity is O. Problem minus 43. Marriage and personnel problem. Marriage problem. There are X men and Y women who desire to get married. Participants indicate who among the opposite sex could be a potential spouse for them. Every woman can be married to at most one man, and every man to at most one woman. How can we marry everybody to someone they like? Personnel problem. You are the boss of a company. The company has M workers and N jobs. Each worker is qualified to do some jobs, but not others. How will you assign jobs to each worker? Solution. These 2 cases are just another way of asking about bipartite graphs, and the solution is the same as that of problem 42. Problem 44. How many edges will be there in complete bipartite graph Km, N? Solution. M times N. This is because each vertex in the first set can connect all vertices in the second set. Problem 45. A graph is called a regular graph if it has no loops and multiple edges where each vertex has the same number of neighbors. That is, every vertex has the same degree. Now, if Km, N is a regular graph, what is the relation between M and N? Solution. Since each vertex should have the same degree, the relation should be M equal to N. Problem 46. What is the maximum number of edges in the maximum matching of a bipartite graph with N vertices? Solution. From the definition of matching, we should not have edges with common vertices. So, in a bipartite graph, each vertex can connect to only one vertex. Since we divide the total vertices into 2 sets, we can get the maximum number of edges if we divide them in half. Finally, the answer is N. Problem minus 47. Discuss planar graphs. Planar graph. Is it possible to draw the edges of a graph in such a way that the edges do not cross? Solution. A graph G is said to be planar if it can be drawn in the plane in such a way that no 2 edges meet each other except at a vertex to which they are incident. Any such drawing is called a plane drawing of G. As an example, consider the below graph. This graph we can easily convert to a planar graph as below. How do we decide whether a given graph is planar or not? The solution to this problem is not simple, but researchers have found some interesting properties that we can use to decide whether the given graph is a planar graph or not. Properties of planar graphs. If a graph G is a connected planar simple graph with 5 vertices, where V equal to 3 and E edges, then E equal to 3V to 6, K5 is non-planar. If a graph G is a connected planar simple graph with V vertices and E edges and number triangles, then E equal to 2V to 4, K3 is non-planar. If a graph G is a connected planar simple graph, then G contains at least one vertex of 5 degrees or less. A graph is planar if and only if it does not contain a subgraph that has K5 and K3 as a contraction. If a graph G contains a non-planar graph as a subgraph, then G is non-planar. If a graph G is a planar graph, then every subgraph of G is planar. For any connected planar graph G equal to, the following formula should hold: 5 plus F E equal to 2, where F stands for the number of faces. For any planar graph G equal to with K components, the following formula holds: 5 plus F E1 plus K. In order to test the planarity of a given graph, we use these properties and decide whether it is a planar graph or not. Note that all the above properties are only the necessary conditions but not sufficient. Problem minus 48. How many faces does K23 have? Solution. From the above discussion, we know that 5 plus F E equal to 2, and from an earlier problem, we know that E equal to MXN equal to 2 times 3 equal to 6, and 5 equal to M plus N equal to 5. 5 plus F, 6 equal to 2 equal to F equal to 3. Problem 49. Discuss graph coloring. Solution. AK. Coloring of a graph G is an assignment of one color to each vertex of G such that no more than K colors are used and no two adjacent vertices receive the same color. A graph is called K-colorable if and only if it has a K coloring. Applications of graph coloring. The graph coloring problem has many applications such as scheduling, register allocation in compilers, frequency assignment in mobile radios, etc. A click in a graph G is the maximum complete subgraph and is denoted by W. Chromatic number. The chromatic number of a graph G is the smallest number K such that G is K-colorable, and it is denoted by X. The lower bound for X is W, and that means W less than or equal to X. Properties of chromatic number. Let G be a graph with n vertices and G is its complement. Then, XA plus 1, where A is the maximum degree of G, XW greater than or equal to N, X plus W less than or equal to N plus 1. K-colorability problem given a graph G equal to and a positive integer K less than or equal to fifth, check whether G is K-colorable. This problem is NP's complete and will be discussed in detail in the chapter on complexity classes. Graph coloring algorithm, as discussed earlier, this problem is NP's complete. So we do not have a polynomial time algorithm to determine X. Let us consider the following approximation algorithm. Consider a graph G with two non-adjacent vertices A and B. The connection G1 is obtained by joining the two non-adjacent vertices A and B with an edge. The contraction G2 is obtained by shrinking into a single vertex C and by joining it to each neighbor in G of vertex A and of vertex B. A coloring of G in which A and B have the same color yields a coloring of G1. A coloring of G in which A and B have different colors yields a coloring of G2. Repeat the operations of connection and contraction in each graph generated until the resulting graphs are all cliques. If the smallest resulting clique is a K-clique, then equal to K. Important notes on graph coloring. Any simple planar graph G can be colored with 6 colors. Every simple planar graph can be colored with less than or equal to 5 colors. Problem 50. What is the 4 coloring problem? Solution. A graph can be constructed from any map. The regions of the map are represented by the vertices of the graph, and two vertices are joined by an edge if the regions corresponding to the vertices are adjacent. The resulting graph is planar. That means it can be drawn in the plane without any edges crossing. The 4-color problem is whether the vertices of a planar graph can be colored with at most 4 colors so that no two adjacent vertices use the same color. History. The 4-color problem was first given by Francis Guthrie. He was a student at University College London, where he studied under Auguste de Morgan. After graduating from London, he studied law, but some years later, his brother Frederick Guthrie had become a student of de Morgan. One day, Francis asked his brother to discuss this problem with de Morgan. Problem minus 51. When an adjacency matrix representation is used, most graph algorithms require time O, show that determining whether a directed graph represented in an adjacency matrix that contains a sink can be done in time O. A sink is a vertex with in degree or 5 or 1 and out degree 0. Solution: a vertex I is a sink if and only if M equal to 0 for all J and M equal to 1 for all J hashtag I. For any pair of vertices Y and J. Algorithm. Start at I equal to 1, J equal to 1. If M equal to 0, I wins, J plus plus. If M equal to 1, J wins, I plus plus. Proceed with this process until J equal to N or I equal to N plus 1. If I equal to N plus 1, the graph does not contain a sink. Otherwise, check row I, it should be all zeros, and check column I, it should be all but M ones. If so, T is a sink. Time complexity O because at most 2 or 5 or cells in the matrix are examined. Problem 52. What is the worst case memory usage of DFS? Solution: it occurs when the O, which happens if the graph is actually a list. So the algorithm memory efficient on graphs with small diameter is. Problem minus 53. Does DFS find the shortest path from start node to some node W? Solution: no. In DFS, it is not compulsory to select the smallest weight edge. Problem minus 54. True or false, Dijkstra's algorithm does not compute the all pairs shortest paths in a directed graph with positive edge weights because, running the algorithm a single time, starting from some single vertex X, it will compute only the min distance from X to Y for all nodes Y in the graph. Solution: true. Problem 55. True or false, Prim's and Kruskal's algorithms may compute different minimum spanning trees when run on the same graph. Solution: true. 10.1. What is sorting? Sorting is an algorithm that arranges the elements of a list in a certain order. The output is a permutation or reordering of the input. 10.2. Why is sorting necessary? Sorting is one of the important categories of algorithms in computer science, and a lot of research has gone into this category. Sorting can significantly reduce the complexity of a problem, and is often used for database algorithms and searches. 10.3. Classification of sorting algorithms. Sorting algorithms are generally categorized based on the following parameters. By number of comparisons. In this method, sorting algorithms are classified based on the number of comparisons. For comparison-based sorting algorithms, best case behavior is O, and worst case behavior is O. Comparison-based sorting algorithms evaluate the elements of the list by key comparison operation, and need at least O comparisons for most inputs. Later in this chapter, we will discuss a few non-comparison sorting algorithms like counting sort, bucket sort, radix sort, etc. Linear sorting algorithms impose few restrictions on the inputs to improve the complexity. By number of swaps. In this method, sorting algorithms are categorized by the number of swaps. By memory usage. Some sorting algorithms are in place, and they need O or O memory to create auxiliary locations for sorting the data temporarily. By recursion. Sorting algorithms are either recursive or non-recursive, and there are some algorithms which use both. By stability. Sorting algorithm is stable if for all indices I and j such that the key A equals key A. If record R precedes record R in the original file, record R precedes record R in the sorted list. Few sorting algorithms maintain the relative order of elements with equal keys by adaptability. With a few sorting algorithms, the complexity changes based on presortedness. Presortedness of the input affects the running time. Algorithms that take this into account are known to be adaptive. 10.4 Other classifications. Another method of classifying sorting algorithms is internal sort, external sort, internal sort. Sort algorithms that use main memory exclusively during the sort are called internal sorting algorithms. This kind of algorithm assumes high-speed random access to all memory. External sort, sorting algorithms that use external memory such as tape or disk during the sort come under this category. 10.5 Bubble sort. Bubble sort is the simplest sorting algorithm. It works by iterating the input array from the first element to the last, comparing each pair of elements and swapping them if needed. Bubble sort continues its iterations until no more swaps are needed. The algorithm gets its name from the way smaller elements bubble to the top of the list. Generally, insertion sort has better performance than bubble sort. Some researchers suggest that we should not teach bubble sort because of its simplicity and high time complexity. The only significant advantage that bubble sort has over other implementations is that it can detect whether the input list is already sorted or not. Implementation. Void bubble sort int n for if A, swap elements in temp equal to A equal to A equal to temp. Algorithm takes O. We can improve it by using one extra flag. No more swaps indicate the completion of sorting. If the list is already sorted, we can use this flag to skip the remaining passes. Void bubble sort improved. Int n, int pass, I, temp, swapped equal to 1, 4, swapped equal to 0, 4, if A, swap elements temp equal to A equal to A equal to temp, swapped equal to 1. This modified version improves the best case of bubble sort to O. Performance. 10.6 Selection sort. Selection sort is an in-place sorting algorithm. Selection sort works well for small files. It is used for sorting the files with very large values and small keys. This is because selection is made based on keys and swaps are made only when required. Advantages. Easy to implement. In-place sort. Disadvantages. Doesn't scale well O algorithm. 1. Find the minimum value in the list. 2. Swap it with the value in the current position. 3. Repeat this process for all the elements until the entire array is sorted. This algorithm is called selection sort since it repeatedly selects the smallest element. Implementation. Void selection, int n, int I, j, min, temp for min, I for if A, min equal to j. Swap elements temp equal to A equal to A equal to temp. Performance. Worst case complexity, O best case complexity, O average case complexity, O worst case space complexity, O auxiliary. 10.7 Insertion sort. Insertion sort is a simple and efficient comparison sort. In this algorithm, each iteration removes an element from the input data and inserts it into the correct position in the list being sorted. The choice of the element being removed from the input is random, and this process is repeated until all input elements have gone through. Advantages. Simple implementation. Efficient for small data. Adaptive. If the input list is presorted, then insertion sort takes O, where D is the number of inversions. Practically more efficient than selection and bubble sorts, even though all of them have O worst case complexity. Stable. Maintains relative order of input data if the keys are same. In place, it requires only a constant amount O of additional memory space. Online, insertion sort can sort the list as it receives it. Algorithm. Every repetition of insertion sort removes an element from the input data and inserts it into the correct position in the already sorted list until no input elements remain. Sorting is typically done in place. The resulting array after k iterations has the property where the first k plus 1 entries are sorted. Sorted partial result. Sorted partial result. Unsorted elements. Becomes. Implementation. Example. Given an array, 68,145,372, and the goal is to put them in ascending order. 68,172. 68,145372. 16,845,372. 1468. 5372. 1, 4, 5, 6, 8, 372. 1, 3, 4, 5, 6, 782. 1, 2, 3, 4, 5, 6, 7, 8. Analysis. Worst case analysis. Worst case occurs when for every I, the inner loop has to move all elements A. A, which happens when an equal to key is smaller than all of them. That takes time. Average case analysis. For the average case, the inner loop will insert A in the middle of A. This takes time. Performance. If every element is greater than or equal to every element to its left, the running time of insertion sort is. This situation occurs if the array starts out already sorted, and so an already sorted array is the best case for insertion sort. Worst case space complexity, O total, O auxiliary. Comparisons to other sorting algorithms. Insertion sort is one of the elementary sorting algorithms with O worst case time. Insertion sort is used when the data is nearly sorted or when the input size is small. For these reasons and due to its stability, insertion sort is used as the recursive base case for higher overhead divide and conquer sorting algorithms, such as merge sort or quick sort. Notes. N2 bubble sort takes comparisons and swaps in both average case 2, and in worst case. Selection sort takes N2 comparisons and N swaps, 2. And insertion sort takes 4 N2 comparisons and swaps in average case and in the worst 8. Case they are double. Insertion sort is almost linear for partially sorted input. Selection sort is best suited for elements with bigger values and small keys. 10.8 Shell sort. Shell sort was invented by Donald Shell. This sorting algorithm is a generalization of insertion sort. Insertion sort works efficiently on input that is already almost sorted. Shell sort is also known as n-gap insertion sort. Instead of comparing only the adjacent pair, shell sort makes several passes and uses various gaps between adjacent elements. In insertion sort, comparisons are made between the adjacent elements. At most, one inversion is eliminated for each comparison done with insertion sort. The variation used in shell sort is to avoid comparing adjacent elements until the last step of the algorithm. So, the last step of shell sort is effectively the insertion sort algorithm. It improves insertion sort by allowing the comparison and exchange of elements that are far away. This is the first algorithm which got less than quadratic complexity among comparison sort algorithms. Shell sort is actually a simple extension for insertion sort. The primary difference is its capability of exchanging elements that are far apart, making it considerably faster for elements to get to where they should be. For example, if the smallest element happens to be at the end of an array, with insertion sort it will require the full array of steps to put this element at the beginning of the array. However, with shell sort, this element can jump more than one step at a time and reach the proper destination in fewer exchanges. The basic idea in shell sort is to exchange every HGH element in the array. Now this can be confusing, so we'll talk more about this. H determines how far apart element exchange can happen. Say for example, take H is 13. The first element is exchanged with the 14th element if necessary. The second element with the 15th element, and so on. Now if we take has1, it is exactly the same as a regular insertion sort. Shell sort works by starting with big enough H so as to allow eligible element exchanges that are far apart. Once a sort is complete with a particular H, the array can be said as H sorted. The next step is to reduce H by a certain sequence, and again perform another complete H sort. Once H is 1 and H sorted, the array is completely sorted. Notice that the last sequence for FT is 1, so the last sort is always an insertion sort, except by this time the array is already well formed and easier to sort. Shell sort uses a sequence HHHT called the increment sequence. Any increment sequence is fine as long as H equal to 1, and some choices are better than others. Shell sort makes multiple passes through the input list and sorts a number of equally sized sets using the insertion sort. Shell sort improves the efficiency of insertion sort by quickly shifting values to their destination. Implementation. Void shell sort int array underscore size int I j h v equal to 4 4 equal to 4 v equal to a j equal to I while v a alj equal to v j equal to h. Note that when h equal to 1, the algorithm makes a pass over the entire list, comparing adjacent elements but doing very few element exchanges. For h equal to 1, shell sort works just like insertion sort, except the number of inversions that have to be eliminated is greatly reduced by the previous. Steps of the algorithm with h greater than 1. Analysis. Shell sort is efficient for medium-sized lists. For bigger lists, the algorithm is not the best choice. It is the fastest of all O-sorting algorithms. The disadvantage of shell sort is that it is a complex algorithm and not nearly as efficient as the merge, heap, and quicksorts. Shell sort is significantly slower than the merge, heap, and quicksorts, but is a relatively simple algorithm, which makes it a good choice for sorting lists of less than 5,000 items unless speed is important. It is also a good choice for repetitive sorting of smaller lists. The best case in shell sort is when the array is already sorted in the right order. The number of comparisons is less. The running time of shell sort depends on the choice of increment sequence. Performance. 10.9 Merge sort. Merge sort is an example of the divide and conquer strategy. Important notes. Merging is the process of combining two sorted files to make one bigger sorted file. Selection is the process of dividing a file into two parts, k smallest elements and nk largest elements. Selection and merging are opposite operations. O selection splits a list into two lists. O merging joins two files to make one file. Merge sort is quicksort's complement. Merge sort accesses the data in a sequential manner. This algorithm is used for sorting a linked list. Merge sort is insensitive to the initial order of its input. In quicksort, most of the work is done before the recursive calls. Quicksort starts with the larger subfile and finishes with the small ones, and as a result, it needs stack. Moreover, this algorithm is not stable. Merge sort divides the list into two parts, then each part is conquered individually. Merge sort starts with the small subfiles and finishes with the largest one. As a result, it doesn't need stack. This algorithm is stable. Implementation. Void merge sort in temp int left int right, while temp a, when left equal to left plus 1, temp underscore pos plus 1, while temp a, mid equal to mid plus 1, temp underscore pos plus 1, for a equal to temp, right equal to right 1. Analysis. In merge sort, the input list is divided into two parts, and these are solved recursively. After solving the subproblems, they are merged by scanning the resultant subproblems. Let us assume T is the complexity of merge sort with n elements. The recurrence for the merge sort can be defined as recurrence for merge sort is T equal to 2 trillions plus O. Using master theorem, we get T equal to O. Note, for more details, refer to divide and conquer chapter. Performance. 10.10 Heap sort. Heap sort is a comparison-based sorting algorithm and is part of the selection sort family. Although somewhat slower in practice on most machines than a good implementation of quicksort, it has the advantage of a more favorable worst-case O runtime. Heap sort is an in-place algorithm but is not a stable sort. Performance. For other details on heap sort, refer to the priority queues chapter. 10.011 Quicksort. Quicksort is an example of a divide and conquer algorithmic technique. It is also called partition exchange sort. It uses recursive calls for sorting the elements, and it is one of the famous algorithms among comparison-based sorting algorithms. Divide. The array A is partitioned into two non-empty subarrays A and A, such that each element of A is less than or equal to each element of A. The index Q is computed as part of this partitioning procedure. Conquer. The two subarrays A and A are sorted by recursive calls to quicksort. Algorithm. The recursive algorithm consists of 4 steps. 1. If there are 1 or no elements in the array to be sorted, return. 2. Pick an element in the array to serve as the pivot point. 3. Split the array into two parts, one with elements larger than the pivot and the other with elements smaller than the pivot. 4. Recursively repeat the algorithm for both halves of the original array. Implementation. Void quicksort, int low, int high, int pivot, termination condition. If pivot partition, quicksort in partition, int left, right, pivot underscore item equal to A, left equal to low, right equal to high, while move left while item pivot, while pivot underscore item left plus plus, move right while item pivot, while pivot underscore item right, if swap, right is final position for the pivot, A equal to pivot underscore item, return right. Analysis. Let us assume that T be the complexity of quicksort and also assume that all elements are distinct. Recurrence for T depends on two subproblem sizes which depend on partition element. If pivot is ita smallest element, then exactly items will be in left part and in right part. Let us call it as I split. Since each element has equal probability of selecting it as pivot, the probability of selecting ith element is n. Best case, each partition splits array in halves and gives T equal to 2 trillions plus O equal to O. Worst case, each partition gives unbalanced splits and we get T equal to T plus O equal to O. The worst case occurs when the list is already sorted and last element chosen as pivot. Average case, in the average case of quicksort, we do not know where the split happens. For this reason, we take all possible values of split locations, add all their complexities, and divide with n to get the average case complexity. T equal to n plus 1 1 equal to 1 1 equal to equal to n plus t plus n plus 1. Since we are dealing with best case, we can assume t and t are equal. Multiply both sides by n. Same formula for n1. Subtract the n1 formula from n. NTT equal to 2 trillions plus 2n. Divide with n plus 1. Time complexity. T equal to O. Performance. Randomized quicksort. In average case behavior of quicksort, we assume that all permutations of the input numbers are equally likely. However, we cannot always expect it to hold. We can add randomization to an algorithm in order to reduce the probability of getting worst case in quicksort. There are two ways of adding randomization in quicksort, either by randomly placing the input data in the array or by randomly choosing an element in the input data for pivot. The second choice is easier to analyze and implement. The change will only be done at the partition algorithm. In normal quicksort, pivot element was always the leftmost element in the list to be sorted. Instead of always using A as pivot, we will use a randomly chosen element from the subarray allow high in the randomized version of quicksort. It is done by exchanging element A to each an element chosen at random from A. This ensures that the pivot element is equally likely to be any of the high, low, +1 elements in the subarray. Since the pivot element is randomly chosen, we can expect the split of the input array to be reasonably well balanced on average. This can help in preventing the worst case behavior of quicksort, which occurs in unbalanced partitioning. Even though the randomized version improves the worst case complexity, its worst case complexity is still O. One way to improve randomized quicksort is to choose the pivot for partitioning more carefully than by picking a random element from the array. One common approach is to choose the pivot as the median of a set of 3 elements randomly selected from the array. 10.12 Tree sort. Tree sort uses a binary search tree. It involves scanning each element of the input and placing it into its proper position in a binary search tree. This has 2 phases. First phase is creating a binary search tree using the given array elements. Second phase is traversing the given binary search tree in order, thus resulting in a sorted array. Performance. The average number of comparisons for this method is O, but in worst case, the number of comparisons is reduced by O, a case which arises when the sort tree is skew tree. 10.13 Comparison of sorting algorithms. 10.14 Linear sorting algorithms. In earlier sections, we have seen many examples of comparison-based sorting algorithms. Among them, the best comparison-based sorting has the complexity O. In this section, we will discuss other types of algorithms, linear sorting algorithms. To improve the time complexity of sorting these algorithms, we make some assumptions about the input. A few examples of linear sorting algorithms are counting sort, bucket sort, radix sort. 10.15 Counting sort. Counting sort is not a comparison sort algorithm and gives O complexity for sorting. To achieve O complexity, counting sort assumes that each of the elements is an integer in the range 1 to k, for some integer k. When if equal to O, the counting sort runs in O time. The basic idea of counting sort is to determine, for each input element x, the number of elements less than 10th. This information can be used to place it directly into its correct position. For example, if 10 elements are less than x, then x belongs to position 11 in the output. In the code below, A is the input array with length n. In counting sort, we need 2 more arrays. Let us assume array B contains the sorted output, and the array C provides temporary storage. Void counting sort, int n, int b, int k, int c, I, j. Complexity, O for C equal to 0. Complexity, O for C, equal to C plus 1. C now contains the number of elements equal to I. Complexity, O for C plus C. C now contains the number of elements Si. Complexity, O for B, equal to A, C, equal to C1. Total complexity, O plus O plus O plus O equal to O if K equal to O. Space complexity, O if K equal to O. Note, counting works well if K equal to O. Otherwise, the complexity will be greater. 10.16 Bucket sort. Like counting sort, bucket sort also imposes restrictions on the input to improve the performance. In other words, bucket sort works well if the input is drawn from fixed set. Bucket sort is the generalization of counting sort. For example, assume that all the input elements from that is the set of integers in the interval. That means k is the number of distant elements in the input. Bucket sort uses k counters. The ith counter keeps track of the number of occurrences of the ith element. Bucket sort with 2 buckets is effectively a version of quicksort with 2 buckets. For bucket sort, the hash function that is used to partition the elements need to be very good and must produce ordered hash. If ik then hash hash. Second, the elements to be sorted must be uniformly distributed. The aforementioned aside, bucket sort is actually very good considering that counting sort is reasonably speaking its upper bound, and counting sort is very fast. The particular distinction for bucket sort is that it uses a hash function to partition the keys of the input array so that multiple keys may hash to the same bucket. Hence, each bucket must effectively be a growable list, similar to radix sort. In the below code, insertion sort is used to sort each bucket. This is to inculcate that the bucket sort algorithm does not specify which sorting technique to use on the buckets. A programmer may choose to continuously use bucket sort on each bucket until the collection is sorted. Whichever sorting method is used on the bucket sort still tends toward O. Hashtag define buckets 10 void bucket sort int array underscore size int I j k int buckets for buckets equal to 0 for plus plus buckets for 4 k greater than 0 k a equal to j. Complexity O. Space complexity O 10.17 radix sort. Similar to counting sort and bucket sort, this sorting algorithm also assumes some kind of information about the input elements. Suppose that the input values to be sorted are from base D. That means all numbers are D-digit numbers. In radix sort, first sort the elements based on the last digit. These results are again sorted by second digit. Continue this process for all digits until we reach the most significant digits. Use some stable sort to sort them by last digit, then stable sort them by the second least significant digit, then by the third, etc. If we use counting sort as the stable sort, the total time is O approximately equal to O. Algorithm. 1. Take the least significant digit of each element. 2. Sort the list of elements based on that digit, but keep the order of elements with the same digit. 3. Repeat the sort with each more significant digit. The speed of radix sort depends on the inner basic operations. If the operations are not efficient enough, radix sort can be slower than other algorithms such as quicksort and merge sort. These operations include the insert and delete functions of the sublists and the process of isolating the digit we want. If the numbers are not of equal length, then a test is needed to check for additional digits that need sorting. This can be one of the slowest parts of radix sort and also one of the hardest to make efficient. Since radix sort depends on the digits or letters, it is less flexible than other sorts. For every different type of data, radix sort needs to be rewritten, and if the sorting order changes, the sort needs to be rewritten again. In short, radix sort takes more time to write, and it is very difficult to write a general-purpose radix sort that can handle all kinds of data. For many programs that need a fast sort, radix sort is a good choice. Still, there are faster sorts, which is one reason why radix sort is not used as much as some other sorts. Time complexity, OO, if D is small. 10.18 Topological sort. Refer to Graph Algorithms chapter. 10.19 External sorting. External sorting is a generic term for a class of sorting algorithms that can handle massive amounts of data. These external sorting algorithms are useful when the files are too big and cannot fit into main memory. As with internal sorting algorithms, there are a number of algorithms for external sorting. One such algorithm is external merge sort. In practice, these external sorting algorithms are being supplemented by internal sorts. Simple external merge sort. A number of records from each tape are read into main memory, sorted using an internal sort, and then output to the tape. For the sake of clarity, let us assume that 900 megabytes of data needs to be sorted using only 100 megabytes of RAM. 1. Read 100 megabytes of the data into main memory and sort by some conventional method. 2. Write the sorted data to disk. 3. Repeat steps 1 and 2 until all of the data is sorted in chunks of 100 megabytes. Now we need to merge them into one single sorted output file. 4. Read the first 10 megabytes of each sorted chunk in main memory and allocate the remaining 10 megabytes for output buffer. 5. Perform a 9-way merge sort and store the result in the output buffer. If the output buffer is full, write it to the final sorted file. If any of the 9 input buffers gets empty, fill it with the next 10 megabytes of its associated 100 megabytes sorted chunk, or if there is no more data in the sorted chunk, mark it as exhausted and do not use it for merging. The above algorithm can be generalized by assuming that the amount of data to be sorted exceeds the available memory by a factor of k. Then, k chunks of data need to be sorted, and a k-way merge has to be completed. If x is the amount of main memory available, there will be k input buffers and one output buffer of size x each. Depending on various factors, better performance can be achieved if the output buffer is made larger. Complexity of the two-way external merge sort. In each pass we read plus write each page in file. Let us assume that there are n pages in file. That means we need plus 1 number of passes. The total cost is 2n plus 1. 10.20 Sorting problems and solutions. Problem 1. Given an array A of n numbers containing the repetition of some number. Give an algorithm for checking whether they're repeated elements or not. Assume that we are not allowed to use additional space storage. Solution. Since we are not allowed to use extra space, one simple way is to scan the elements one by one and for each element check whether that element appears in the remaining elements. If we find a match, we return true. In check duplicates in array, int n. For if equal to a, return false, return true. Each iteration of the inner j index loop uses O space, and for a fixed value of I, the j loop executes n I times. The outer loop executes n 1 times, so the entire function uses time proportional to none n in sigma I equal to n, time complexity, O, space complexity, O, 2n equal to O, 2. Problem 2. Can we improve the time complexity of problem 1? Solution, yes, using sorting technique. In T check duplicates in array, int n. For heap sort algorithm, refer priority queues chapter heap sort. For if equal to a, return false, return true. Heap sort function takes O time and requires O space. The scan clearly takes n, 1 iterations each iteration using O time. The overall time is O equal to O. Time complexity, O, space complexity, O. Note, for variations of this problem, refer searching chapter. Problem -3 given an array A, where each element of the array represents a vote in the election. Assume that each vote is given as an integer representing the E of the chosen candidate. Give an algorithm for determining who wins the election. Solution. This problem is nothing but finding the element which repeated the maximum number of times. The solution is similar to the problem 1 solution. Keep track of counter. Int check who wins the election. Int n. If equal to a. Counter plus if max counter. Return candidate A. Time complexity. O. Space complexity. O. Note. For variations of this problem, refer to searching chapter. Problem -4. Can we improve the time complexity of problem 3? Assume we don't have any extra space. Solution. Yes. The approach is to sort the votes based on candidate ID, then scan the sorted array and count up which candidate so far has the most votes. We only have to remember the winner, so we don't need a clever data structure. We can use heap sort as it is an in-place sorting algorithm. Int check who wins the election, int n, if max counter current counter, else max counter current counter, return candidate. Since heap sort time complexity is O and in place, it only uses an additional O of storage in addition to the input array. The scan of the sorted array does a constant time conditional n 1 times, thus using O time. The overall time bound is O. Problem -5. Can we further improve the time complexity of problem 3? Solution. In the given problem, the number of candidates is less, but the number of votes is significantly large. For this problem, we can use counting sort. Time complexity O(n) is the number of votes in the array. Space complexity O. K is the number of candidates participating in the election. Problem -6 given an array A of n elements, each of which is an integer in the range. How do we sort the array in O time? Solution. If we subtract each number by 1, then we get the range. If we consider all numbers as 2-digit base n, each digit ranges from 0 to n21. Sort this using radix sort. This uses only 2 calls to counting sort. Finally, add 1 to all the numbers. Since there are 2 calls, the complexity is O, approximately equal to O. Problem -7 for problem 6. What if the range is? Solution. If we subtract each number by 1, then we get the range. Considering all numbers as 3-digit base n, each digit ranges from 0 to n31. Sort this using radix sort. This uses only 3 calls to counting sort. Finally, add 1 to all the numbers. Since there are 3 calls, the complexity is O, approximately equal to O. Problem -8, given an array with n integers, each a value less than n100, can it be sorted in linear time? Solution, yes. The reasoning is same as in of problem 6 and problem 7. Problem 9, let A and B be 2 arrays of n elements each. Given a number k, give an O-time algorithm for determining whether there exists A I A and B euro B, such that A plus B equal to k. Solution, since we need O, it gives us a pointer that we need to sort, so we will do that. Int find, int b, int n, k, int I, c, heap sort, O for, OC, KB. 0 if, return 1, O return 0. Note, for variations of this problem, refer to searching chapter. Problem -10, let A, B, and C be 3 arrays of n elements each. Given a number k, give an O-time algorithm for determining whether there exists a euro A, B euro B, and C euro C, such that A plus B plus C equal to k.
Solution. Refer to searching chapter. Problem 11.
Given an array of n elements, can we output in sorted order the k elements following the median in sorted order in time O? Solution, yes. Find the median and partition the median. With this, we can find all the elements greater than it. Now find the kth largest element in this set and partition it, and get all the elements less than it. Output the sorted list of the final set of elements. Clearly, this operation takes O time. Problem 12. Consider the sorting algorithms: bubble sort, insertion sort, selection sort, merge sort, heap sort, and quick sort. Which of these are stable? Solution. Let us assume that A is the array to be sorted. Also, let us say R and S have the same key, and R appears earlier in the array than S. That means R is at A, and S is at A, with IJ. To show any stable algorithm, in the sorted output, R must precede S bubble sort. Yes. Elements change order only when a smaller record follows a larger. Since S is not smaller than R, it cannot precede it. Selection sort, no. It divides the array into sorted and unsorted portions and iteratively finds the minimum values in the unsorted portion. After finding a minimum x, if the algorithm moves x into the sorted portion of the array by means of a swap, then the element swapped could be r, which then could be moved behind s. This would invert the positions of r and s, so in general it is not stable. If swapping is avoided, it could be made stable, but the cost in time would probably be very significant. Insertion sort, yes. As presented, when s is to be inserted into sorted subarray A, only records larger than s are shifted. Thus r would not be shifted during s's insertion and hence would always precede it. Merge sort, yes. In the case of records with equal keys, the record in the left subarray gets preference. Those are the records that came first in the unsorted array. As a result, they will precede later records with the same key. Heap sort, no. Suppose I equal to 1 and r and s happen to be the two records with the largest keys in the input. Then r will remain in location 1 after the array is heapified, and will be placed in location n in the first iteration of heap sort. Thus s will precede r in the output. Quicksort, no. The partitioning step can swap the location of records many times, and thus two records with equal keys could swap position in the final output. Problem 13. Consider the same sorting algorithms as that of problem 12. Which of them are in place? Solution. Bubble sort, yes, because only two integers are required. Insertion sort, yes, since we need to store two integers and a record. Selection sort, yes. This algorithm would likely need space for two integers and one record. Merge sort, no. Arrays need to perform the merge. Heap sort, yes, since the heap and partially sorted array occupy opposite ends of the input array. Quicksort, no, since it is recursive and stores O activation records on the stack. Modifying it to be non-recursive is feasible, but non-trivial. Problem 14. Among quicksort, insertion sort, selection sort, and heap sort algorithms, which one needs the minimum number of swaps? Solution. Selection sort. It needs n swaps only. Problem -15. What is the minimum number of comparisons required to determine if an integer appears more than n/2 times in a sorted array of n integers? Solution. Refer to searching chapter. Problem 16. Sort an array of zeros, ones, and twos, given an array consisting of zeros, ones, and twos, give an algorithm for sorting A. The algorithm should put all O's first, then all ones and all twos last. Example, input equal to, output equal to. Solution. Use counting sort. Since there are only 3 elements and the maximum value is 2, we need a temporary array with 3 elements. Time complexity. O. Space complexity. O. Note, for variations of this problem, refer to searching chapter. Problem -17. Is there any other way of solving problem 16? Solution. Using quicksort. Since we know that there are only 3 elements, 0, 1, and 2 in the array, we can select one as a pivot element for quicksort. Quicksort finds the correct place for 1 by moving all 0 feet to the left of 1 and all 2 feet to the right of 1. For doing this, it uses only one scan. Time complexity. O. Space complexity. O. Note, for efficient algorithm, refer to searching chapter. Problem 18 array. How do we find a number that appeared the maximum number of times in n? Solution. One simple approach is to sort the given array and scan the sorted array. While scanning, keep track of the elements that occur the maximum number of times. Algorithm. Quicksort int I, j, count equal to 1, number equal to a, j equal to 0, for if equal to a, count plus number equal to a, j equal to I, printf. Time complexity equal to time for sorting plus time for scan equal to O plus O equal to O. Space complexity O. Note, for variations of this problem, refer to searching chapter. Problem 19. Is there any other way of solving problem 18? Solution. Using binary tree. Create a binary tree with an extra field count, which indicates the number of times an element appeared in the input. Let us say we have created a binary search tree. Now, do the in-order traversal of the tree. The in-order traversal of BST produces the sorted list. While doing the in-order traversal, keep track of the maximum element. Time complexity, O plus O, approximately equal to O. The first parameter is for constructing the BST, and the second parameter is for in-order traversal. Space complexity, O, approximately equal to O, since every node in BST needs 2 extra pointers. Problem 20. Is there yet another way of solving problem 18? Solution. Using hash table. For each element of the given array, we use a counter, and for each occurrence of the element, we increment the corresponding counter. At the end, we can just return the element which has the maximum counter. Time complexity, O. Space complexity, O. For constructing the hash table, we need O. Note, for the efficient algorithm, refer to the searching chapter. Problem 21. Given a 2 GB file with 1 string per line, which sorting algorithm would we use to sort the file and why? Solution. When we have a size limit of 2 GB, it means that we cannot bring all the data into the main memory. Algorithm. How much memory do we have available? Let's assume we have x MB of memory available. Divide the file into k chunks, where xk 2 GB. Bring each chunk into memory and sort the lines as usual algorithm. Now bring the next chunk into memory and sort. Save the lines back to the file. Once we're done, merge them one by one. In the case of one set finishing, bring more data from the particular chunk. The above algorithm is also known as external sort. Step 3 to 4 is known as k-way merge. The idea behind going for an external sort is the size of data. Since the data is huge and we can't bring it to the memory, we need to go for a disk-based sorting algorithm. Problem, -22, nearly sorted. Given an array of n elements, each which is at most k positions from its target position, devise an algorithm that sorts in O time. Solution, divide the elements into nk groups of size k, and sort each piece in O time, let's say using merge sort. This preserves the property that no element is more than k elements out of position. Now, merge each block of k elements with the block to its left. Problem 23. Is there any other way of solving problem 22? Solution, insert the first k elements into a binary heap. Insert the next element from the array into the heap, and delete the minimum element from the heap. Repeat. Problem 24. Merging k-sorted lists. Given k-sorted lists with a total of n elements, give an O algorithm to produce a sorted list of all n elements. NK solution. Simple algorithm for merging k-sorted lists. Consider groups each having equal to elements. Take the first list and merge it with the second list using a linear time algorithm for merging 2 sorted lists, such as the merging algorithm used in merge sort. Then, merge the resulting list of 2 nk elements with a third list, and then merge the resulting list of elements with the fourth list. Repeat this until we end up with a single sorted list of all n elements. 3 nk. Time complexity. In each iteration, we are merging k elements. Problem 25. Can we improve the time complexity of problem 24? Solution. One method is to repeatedly pair up the lists and then merge each pair. This method can also be seen as a tail component of the execution merge sort, where the analysis is clear. This is called the tournament method. The maximum depth of the tournament method is lock, and in each iteration, we are scanning all the n elements. Time complexity, O. Problem 26. Is there any other way of solving problem 24? Solution. The other method is to use a rain priority queue for the minimum elements of each of the F lists. At each step, we output the extracted minimum of the priority queue, determine from which of the K lists it came, and insert the next element from that list into the priority queue. Since we are using priority queue, that maximum depth of priority queue is log. Time complexity, O. Problem 27. Which sorting method is better for linked lists? Solution. Merge sort is a better choice. At first appearance, merge sort may not be a good selection since the middle node is required to subdivide the given list into two sublists of equal length. We can easily solve this problem by moving the nodes alternatively to two lists. Then, sorting these two lists recursively and merging the results into a single list will sort the given one. Type edef struct list node list equal to null, struct list node list equal to null, struct list node list equal to null, struct list node list equal to null if return first, while append if append, list one head linked list merge sort, list linked list merge sort, return merge. Note, append appends the first argument to the tail of a singly linked list whose head and tail are defined by the second and third arguments. All external sorting algorithms can be used for sorting linked lists, since each involved file can be considered as a linked list that can only be accessed sequentially. We can sort a doubly linked list using its next fields as if it was a singly linked one, and reconstruct the prev fields after sorting with an additional scan. Problem -28. Can we implement linked list sorting with quicksort? Solution. The original quicksort cannot be used for sorting singly linked lists. This is because we cannot move backward in singly linked lists. But we can modify the original quicksort and make it work for singly linked lists. Let us consider the following modified quicksort implementation. The first node of the input list is considered a pivot and is moved to equal. The value of each node is compared with the pivot and moved to less if the node's value is smaller than the pivot. Then, less and larger are sorted recursively. Finally, joining less, equal, and larger into a single list yields a sorted one. Append appends the first argument to the tail of a singly linked list whose head and tail are defined by the second and third arguments. On return, the first argument will be modified so that it points to the next node of the list. Join appends the list whose head and tail are defined by the third and fourth arguments to the list whose head and tail are defined by the first and second arguments. For simplicity, the first and fourth arguments become the head and tail of the resulting list. Type edef struct list node less head equal to null, list tail equal to null, struct list node equid equal to null, eqtail null, struct list node lar head equal to null, lar tail equal to null, struct list node current equal to first, into pivot, info, if return, pivot current data, append, while info equal to current data, if append else append, quicksort, join, first equal to less head, last equal to lar tail. Problem 29, given an array of 100,000 pixel color values, each of which is an integer in the range, which sorting algorithm is preferable for sorting them? Solution, counting sort. There are only 256 key values, so the auxiliary array would only be of size 256, and there would be only two passes through the data, which would be very efficient in both time and space. Problem, -30 similar to problem 29, if we have a telephone directory with 10 million entries, which sorting algorithm is best? Solution, bucket sort. In bucket sort, the buckets are defined by the last 7 digits. This requires an auxiliary array of size 10 million and has the advantage of requiring only one pass through the data on disk. Each bucket contains all telephone numbers with the same last 7 digits but with different area codes. The buckets can then be sorted by area code with selection or insertion sort. There are only a handful of area codes. Problem -31, given algorithm for merging case-sorted lists. Solution, refer to priority queues chapter. Problem -32, given a big file containing billions of numbers. Find maximum 10 numbers from this file. Solution, refer to priority queues chapter. Problem -33. There are two sorted arrays A and B. The first one is of size m plus n containing only m elements. Another one is of size n and contains n elements. Merge these two arrays into the first array of size m plus n such that the output is sorted. Solution, the trick for this problem is to start filling the destination array from the back with the largest elements. We will end up with a merged and sorted destination array. Void merge A, int m, int b, int n, else. Time complexity, O. Space complexity, O. Problem, -34 nuts and bolts problem. Given a set of n nuts of different sizes and n bolts such that there is a 1-to-1 correspondence between the nuts and the bolts, find for each nut its corresponding bolt. Assume that we can only compare nuts to bolts. We cannot compare nuts to nuts and bolts to bolts. Alternative way of framing the question, we are given a box which contains bolts and nuts. Assume there are n nuts and n bolts and that each nut matches exactly one bolt. By trying to match a bolt and a nut, we can see which one is bigger, but we cannot compare two bolts or two nuts directly. Design an efficient algorithm for matching the nuts and bolts. Solution, brute force approach. Start with the first bolt and compare it with each nut until we find a match. In the worst case, we require n comparisons. Repeat this for successive bolts on all remaining gives O complexity. Problem 35 for problem 34, can we improve the complexity? Solution, in problem 34 we got O complexity in the worst case. Its analysis is the same as that of quicksort. The improvement is also along the same lines. To reduce the worst case complexity, instead of selecting the first bolt every time, we can select a random bolt and match it with nuts. This randomized selection reduces the probability of getting the worst case, but still the worst case is O. Problem -36 for problem 34, can we further improve the complexity? Solution, we can use a divide and conquer technique for solving this problem, and the solution is very similar to randomized quicksort. For simplicity, let us assume that bolts and nuts are represented in two arrays B and N. The algorithm first performs a partition operation as follows. Pick a random bolt EB. Using this bolt, rearrange the array of nuts into 3 groups of elements. First, the nut smaller than B, then the nut that matches B, and, finally, the nuts larger than B. Next, using the nut that matches B, perform a similar partition on the array of bolts. This pair of partitioning operations can easily be implemented in O time, and it leaves the bolts and nuts nicely partitioned so that the pivot bolt and nut are aligned with each other, and all other bolts and nuts are on the correct side of these pivots. Smaller nuts and bolts precede the pivots, and larger nuts and bolts follow the pivots. Our algorithm then completes by recursively applying itself to the subarray to the left and right of the pivot position to match these remaining bolts and nuts. We can assume by induction on n that these recursive calls will properly match the remaining bolts. To analyze the running time of our algorithm, we can use the same analysis as that of randomized quicksort. Therefore, applying the analysis from quicksort, the time complexity of our algorithm is O. Alternative analysis, we can solve this problem by making a small change to quicksort. Let us assume that we pick the last element as the pivot, say it is a nut. Compare the nut with only bolts as we walk down the array. This will partition the array for the bolts. Every bolt less than the partition nut will be on the left, and every bolt greater than the partition nut will be on the right. While traversing down the list, find the matching bolt for the partition nut. Now we do the partition again, using the matching bolt. As a result, all the nuts less than the matching bolt will be on the left side, and all the nuts greater than the matching bolt will be on the right side. Recursively call on the left and right arrays. The time complexity is O approximately equal to O. Problem -37, given a binary tree, can we print its elements in sorted order in O time by performing an in-order tree traversal? Solution, yes, if the tree is a binary search tree. For more details, refer to trees chapter. Problem -38, given an array of elements, convert it into an array such that A, B, C, D, E, F, and so on. Solution, sort the array, then swap every adjacent element to get the final result. Hashtag include algorithm converter rate of sawtooth wave. Int a, int n equal to size of I equal to 1, temp, sort, for if temp equal to a equal to a equal to temp, for, printf. The time complexity is O approximately equal to O for sorting in a scan. Problem minus 39. Can we do problem 38 with O time? Solution. Make sure all even position elements are greater than their adjacent odd elements, and we don't need to worry about odd position elements. Traverse all even position elements of input array and do the following. If the current element is smaller than the previous odd element, swap previous and current. If the current element is smaller than the next odd element, swap next and current. Convert array to sawtooth wave. Int a, int n equal to size of I equal to 1, temp sort for if a, temp equal to a equal to a equal to temp if a, temp a equal to a equal to temp for count a. The time complexity is O. Merge sort uses divide and conquer strategy backtracking approach problem minus 40 heuristic search greedy approach. Solution. Refer theory section. Problem minus 41. Which of the following algorithm design techniques is used in the quicksort algorithm? Dynamic programming backtracking divide and conquer greedy method. Solution. Refer theory section. Problem minus 42. For merging two sorted lists of sizes m and n into a sorted list of size m plus n, we require comparisons of O. Solution. We can use merge sort logic. Refer theory section. Problem. Minus 43 quicksort is run on two inputs shown below to sort in ascending order. 1, 2, 3, n, 1, n 2, 2, 1. Let Cohen and C2 be the number of comparisons made for the input and respectively. Then, C1, C2, C1, C2, Key1 equal to C2. We cannot say anything for arbitrary n. Solution. Since the given problems needs the output in ascending order, quicksort on already sorted order gives the worst case. So, generates worst case and needs fewer comparisons. Problem, minus 44, give the correct matching for the following pairs. O. Selection. Insertion sort. Binary search. Merge sort. A minus R and B. PC, SD. A minus PB, for A. Refer theory section. Problem 45 lets be a sorted array of n integers. Let T denote the time taken for the most efficient algorithm to determine if there are two elements with sum less than 1000 in S. Which of the following statements is true? A. T is OB, n t log C, log T D, T equal to. Solution. Since the given array is already sorted, it is enough if we check the first two elements of the array. Problem 46. The usual implementation of insertion sort to sort an array uses linear search to identify the position where an element is to be inserted into the already sorted part of the array. If instead we use binary search to identify the position, the worst case running time will remain, become 2, become O, become. Solution. If we use binary search, then there will be log comparisons in the worst case, which is O. But the algorithm as a whole will still have a running time of on average because of the series of swaps required for each insertion. Problem 47. In quicksort, for sorting n elements, the n, fourth smallest element is selected as pivot using an O-time algorithm. What is the worst case time complexity of the quicksort? O. Solution. The recursion expression becomes T equal to T plus N. Solving the recursion using variant of master theorem, we get O. Problem 48. Consider the quicksort algorithm. Suppose there's a procedure for finding a pivot element which splits the list into two sublists, each of which contains at least 1/5 of the elements. Let T be the number of comparisons required to sort n elements. Then A, T2 trillions plus NB, DT plus T plus NC, T less than or equal to 2 trillions plus ND, T less than or equal to 2 trillions plus N. Solution. For the case where n/5 elements are in one subset, T comparisons are needed for the first subset with n/5 elements, T is for the rest 4 n/5 elements, and N is for finding the pivot. If there are more than n5 elements in one set, then other set will have less than 4 n/5 elements, and time complexity will be less than T plus N. Problem minus 49. Which of the following sorting algorithms has the lowest worst case complexity? Merge sort, bubble sort, quicksort, selection sort. Solution. Refer theory section. Problem 50. Which one of the following in place sorting algorithms needs the minimum number of swaps? Quicksort, insertion sort, selection sort, heap sort. Solution. Refer theory section. Problem minus 51. You have an array of n elements. Suppose you implement quicksort by always choosing the central element of the array as the pivot. Then the tightest upper bound for the worst case performance is O. Solution. When we choose the first element as the pivot, the worst case of quicksort comes if the input is sorted, either in ascending or descending order. Problem 52. Let P be a quicksort program to sort numbers in ascending order using the first element as pivot. Let T and T be the number of comparisons made by P for the inputs and respectively. Which one of the following holds? T equal to 5, T equal to T. Solution. Quicksort's worst case occurs when first element is chosen as pivot with sorted arrays. Problem 53. The minimum number of comparisons required to find the minimum and the maximum of 100 numbers is. Solution. 147. Problem minus 54. The number of elements that can be sorted in T time using heap sort is O. Solution. Sorting an array with K elements takes time as K grows. We want to choose K such that equal to O. Choosing K equal to O doesn't necessarily work, since O equal to O. On the other hand, if you choose K equal to T, then the runtime of the sort will be. Notice that 1, log tends toward 1 as n goes to infinity, so the above expression actually is as required. Therefore, if you try to sort an array of size using heap sort as a function of n, the runtime is. Problem 55. Which one of the following is the tightest upper bound that represents the number of swaps required to sort n numbers using selection sort? O. Solution. Selection sort requires only O swaps. Problem minus 56. Which one of the following is the recurrence equation for the worst case time complexity of the quicksort algorithm for sorting n numbers? In the recurrence equations given in the options below, C is a constant. T equal to 2 trillions plus Cn. T plus T plus Cn. T 2 trillions plus Cn. Solution. When the pivot is the smallest element at partitioning on a block of size n, the result yields one empty subblock, one element in the correct place, and subblock of size n, 1. Problem minus 57. True or false? In randomized quicksort, each key is involved in the same number of comparisons. Solution. False. Problem minus 58. True or false? If quicksort is written so that the partition algorithm always uses the median value of the segment as the pivot, then the worst case performance is O. Solution. True. 1101. What is searching? In computer science, searching is the process of finding an item with specified properties from a collection of items. The items may be stored as records in a database, simple data elements in arrays, text in files, nodes in trees, vertices and edges in graphs, or they may be elements of other search spaces. 11.2. Why do we need searching? Searching is one of the core computer science algorithms. We know that today's computers store a lot of information. To retrieve this information proficiently, we need very efficient searching algorithms. There are certain ways of organizing the data that improves the searching process. That means if we keep the data in proper order, it is easy to search the required element. Sorting is one of the techniques for making the elements ordered. In this chapter, we will see different searching algorithms. 11.3 types of searching. Following are the types of searches which we will be discussing in this book. Unordered linear search, sorted, ordered linear search, binary. Search interpolation search, binary search trees, symbol tables, and hashing string searching algorithms, tries, ternary search, and suffix trees. 11.4 Unordered linear search. Let us assume we're given an array where the order of the elements is not known. That means the elements of the array are not sorted. In this case, to search for an element, we have to scan the complete array and see if the element is there in the given list or not. Int unordered linear search, int n, int data, for, if equal to data, return I, return -1. Time complexity, in the worst case, we need to scan the complete array. Space complexity, 1105 sorted ordered linear search. If the elements of the array are already sorted, then in many cases, we don't have to scan the complete array to see if the element is there in the given array or not. In the algorithm below, it can be seen that at any point, if the value at A is greater than the data to be searched, then we just return -1 without searching the remaining array. Int ordered linear search, int n, int data, for, if equal to data, return I, else if data, return -1, return -1. Time complexity of this algorithm is O. This is because, in the worst case, we need to scan the complete array, but in the average case, it reduces the complexity even though the growth rate is the same. Space complexity, O. Note, for the above algorithm, we can make further improvement by incrementing the index at a faster rate. This will reduce the number of comparisons for searching in the sorted list. 1106 binary search. Let us consider the problem of searching a word in a dictionary. Typically, we directly go to some approximate page and start searching from that point. If the name that we are searching is the same, then the search is complete. If the page is before the selected pages, then apply the same process for the first half, otherwise apply the same process to the second half. Binary search also works in the same way. The algorithm applying such a strategy is referred to as binary search algorithm. Iterative binary search algorithm, int binary search iterative, int n, int data, int low equal to 0, int high, and 1. While equal to mid low plus /2, to avoid overflow, if equal to data, return mid, else if data, low, mid +1, else high equal to mid, 1, return -1. Recursive binary search algorithm, int binary search recursive, int low, int high, int data, int mid low /2. To avoid overflow, if return -1, if data, return mid, else if data, return binary search recursive, else return binary search recursive, return -1. Recurrence for binary search is t equal to t22 plus. This is because we are always considering only half of the input list and throwing out the other half. Using divide and conquer master theorem, we get t equal to O. Time complexity, O. Space complexity, O. 11.7 interpolation search. Undoubtedly, binary search is a great algorithm for searching with average running time complexity of lone. It always chooses the middle of the remaining search space, discarding one half or the other, again depending on the comparison between the key value found at the estimated position and the key value sought. The remaining search space is reduced to the part, before or after the estimated position. In the mathematics, interpolation is a process of constructing new data points within the range of a discrete set of known data points. In computer science, one often has a number of data points which represent the values of a function for a limited number of values of the independent variable. It is often required to interpolate the value of that function for an intermediate value of the independent variable. 4. Example, suppose we have a table like this, which gives some values of an unknown function. Interpolation provides a means of estimating the function at intermediate points, such as x equal to 55. F. There are many different interpolation methods, and one of the simplest methods is linear interpolation. Since 55 is midway between 50 and 60, it is reasonable to take f midway between f equal to 50 and f equal to 60, which yields 55%. The interpolation takes two data points, say and the interpolant is given by. With above inputs, what will happen if we don't use the constant 1/2, but another more accurate constant k that can lead us closer to the searched item? Low data to be searched. High. This algorithm tries to follow the way we search a name in a phone book, or a word in the dictionary. We humans know in advance that in case the name we're searching starts with a M, like monk, for instance, we should start searching near the middle of the phone book. Thus, if we're searching the word career in the dictionary, you know that it should be placed somewhere at the beginning. This is because we know the order of the letters, we know the interval, and somehow we intuitively know that the words are dispersed equally. These facts are enough to realize that the binary search can be a bad choice. Indeed, the binary search algorithm divides the list in two equal sublists, which is useless if we know in advance that the searched item is somewhere in the beginning or the end of the list. Yes, we can use also jump search if the item is at the beginning, but not if it is at the end. In that case, this algorithm is not so effective. The interpolation search algorithm tries to improve the binary search. The question is how to find this value. Well, we know bounds of the interval, and looking closer to the image above, we can define the following formula. This constant k is used to narrow down the search space. For binary search, this constant k is /2. Now we can be sure that we're closer to the search value. On average, the interpolation search makes about log comparisons, where n is the number of elements to be searched. In the worst case, it can make up to O comparisons. In interpolation sequential search, interpolation is used to find an item near the one being searched for, then linear search is used to find the exact item. For this algorithm to give best results, the dataset should be ordered and uniformly distributed. In interpolation search, int data, int low 0, mid, high size of 1, while mid low. A, if, return mid 1, if high, mid 1, else return 1, low, mid 1. 1108, comparing basic searching algorithms. Note, for discussion on binary search trees, refer trees chapter. 11.9 symbol tables and hashing, refer to symbol tables and hashing chapters. 11.10 string searching algorithms, refer to string algorithms chapter. 11.1 one searching, problems and solutions. Problem, -1 given an array of n numbers, give an algorithm for checking whether there are any duplicate elements in the array or no. Solution, this is one of the simplest problems. One obvious answer to this is exhaustively searching for duplicates in the array. That means for each input element, check whether there is any element with the same value. This we can solve just by using two simple for loops. The code for the solution can be given as Void check duplicates brute force. Int n for if a printf return printf. Time complexity O for 2 nested for loops. Space complexity O problem -2. Can we improve the complexity of problem? 1 foot solution? Solution, yes. Sort the given array. After sorting, all the elements with equal values will be adjacent. Now, do another scan on this sorted array and see if there are elements with the same value and adjacent. Void check duplicate sorting. Int n sort for if a sort the array printf return printf. Time complexity O for sorting. Space complexity O. Problem 3. Is there any alternative way of solving problem 1? Solution, yes, using hash table. Hash tables are a simple and effective method used to implement dictionaries. Average time to search for an element is O, while worst case time is O. Refer to hashing chapter for more details on hashing algorithms. As an example, consider the array a equal to. Scan the input array and insert the elements into the hash. For each inserted element, keep the counter as 1. This indicates that the corresponding element has occurred already. For the given array, the hash table will look like. Now, if we try inserting 2, since the counter value of 2 is already 1, we can say the element has appeared twice. Time complexity O, space complexity O, problem -4. Can we further improve the complexity of problem? 1 solution. Solution. Let us assume that the array elements are positive numbers and all the elements are in the range 0 to n1. For each element A, go to the array element whose index is A. That means select A and mark A. Continue this process until we encounter the element whose value is already negated. If one such element exists, then we say duplicate elements exist in the given array. As an example, consider the array A equal to. Initially, at step 1, negate A. At step 2, negate A. At step 3, negate A. At step 4, negate A. At step 4, observe that A is already negative. That means we have encountered the same value twice. Void check duplicates int n for if less than 0, printf return, else A equal to A printf. Time complexity O, since only one scan is required. Space complexity O, notes. This solution does not work if the given array is read only. This solution will work only if all the array elements are positive. If the elements range is not in 0 to n, 1, then it may give exceptions. Problem -5 given an array of n numbers. Give an algorithm for finding the element which appears the maximum number of times in the array. Brute force solution. One simple solution to this is, for each input element, check whether there is any element with the same value, and for each such occurrence, increment the counter. Each time, check the current counter with the max counter, and update it if this value is greater than max counter. This we can solve just by using 2 simple for loops. Into max repetitions brute force, int n, for if equal to A, counter plus plus, if max equal to counter, return max. Time complexity, O for 2 nested for loops. Space complexity, O. Problem -6, can we improve the complexity of problem 5 solution? Solution, yes. Sort the given array. After sorting, all the elements with equal values come adjacent. Now, just do another scan on this sorted array and see which element is appearing the maximum number of times. Time complexity, O. Space complexity, O. Problem -7. Is there any other way of solving problem 5? Solution, yes, using hash table. For each element of the input, keep track of how many times that element appeared in the input. That means the counter value represents the number of occurrences for that element. Time complexity, O. Space complexity, O. Problem -8 or problem 5. Can we improve the time complexity? Assume that the elements range is 1 to n. That means all the elements are within this range only. Solution, yes. We can solve this problem in 2 scans. We cannot use the negation technique of problem -3 for this problem because of the number of repetitions. In the first scan, instead of negating, add the value n. That means for each occurrence of an element, add the array size to that element. In the second scan, check the element value by dividing it by n, and return the element which gives the maximum value. The code based on this method is given below. Void max repetitions int n, int I equal to 0, max equal to 0, max index for a %n, plus equal to n, for if n max, max equal to an, max index equal to I, return max index. Notes. This solution does not work if the given array is read only. This solution will work only if the array elements are positive. If the elements range is not in 1 to n, then it may give exceptions. Time complexity, O, since no nested for loops are required. Space complexity, O. Problem -9. Given an array of n numbers, give an algorithm for finding the first element in the array which is repeated. For example, in the array A equal to, the first repeated number is 3. That means we need to return the first element among the repeated elements. Solution. We can use the brute force solution that we used for problem 1. For each element, since it checks whether there is a duplicate for that element or not, whichever element duplicates first will be returned. Problem -10 for problem 9. Can we use the sorting technique? Solution. No. For proving the failed case, let us consider the following array. For example, A equal 2. After sorting, we get A equal 2. In this sorted array, the first repeated element is 2, but the actual answer is 3. Problem 11 for problem 9. Can we use hashing technique? Solution. Yes. But the simple hashing technique which we use for problem 3 will not work. For example, if we consider the input array as A equal to, then the first repeated element is 3, but using our simple hashing technique, we get the answer as 2. This is because 2 is coming twice before 3. Now let us change the hashing table behavior so that we get the first repeated element. Let us say, instead of storing one value, initially we stored the position of the element in the array. As a result, the hash table will look like, now if we see 2 again, we just negate the current value of 2 in the hash table. That means we make its counter value as -2. The negative value in the hash table indicates that we have seen the same element 2 times. Similarly, for 3 also, we negate the current value of the hash table, and finally the hash table will look like. After processing the complete input array, scan the hash table and return the highest negative index value from it. The highest negative value indicates that we have seen that element first and also repeating. What if the element is repeated more than twice? In this case, just skip the element if the corresponding value I is already negative. Problem 12. For problem 9, can we use the technique that we used for problem 3? Solution, no. As an example of contradiction, for the array A equal to the first repeated element is 3, but with negation technique the result is 2. Problem 13. Finding the missing number, we are given a list of n, 1 integers, and these integers are in the range of 1 to n. There are no duplicates in the list. One of the integers is missing in the list. Given an algorithm to find the missing integer. Example, IPOP5. Brute force solution. One simple solution to this is, for each number in 1 to n, check whether that number is in the given array or not. Int find missing number, int n, for if equal to I, found equal to 1, if return I, return -1. Time complexity, O. Space complexity, O. Problem -14 for problem 3. Can we use sorting technique? Solution, yes. Sorting the list will give the elements in increasing order, and with another scan, we can find the missing number. Time complexity, O for sorting. Space complexity, O. Problem -15 for problem 13. Can we use hashing technique? Solution, yes. Scan the input array and insert elements into the hash. For inserted elements, keep counter as 1. This indicates that the corresponding element has occurred already. Now, scan the hash table and return the element which has counter value 0. Time complexity, O. Space complexity, O. Problem -16 for problem 13. Can we improve the complexity? Solution, yes. We can use summation formula. 1. Get the sum of numbers, sum equal to n times /2. 2. Subtract all the numbers from sum and you will get the missing number. Time complexity, O for scanning the complete array. Problem 17. In problem -13, if the sum of the numbers goes beyond the maximum allowed integer, then there can be integer overflow and we may not get the correct answer. Can we solve this problem? Solution. 1. XOR all the array elements, let the result of XOR be 10th 2, XOR all numbers from 1 to n, let XOR be y. 3. XOR of x and y gives the missing number. Int find missing number, int n, int I, x, y, for x to the power of a, for y to the power of equal to I. In fact, one variable is enough. Return x to the power of y. Time complexity, O for scanning the complete array. Space complexity, O. Problem 18. Find the number occurring an odd number of times. Given an array of positive integers, all numbers occur an even number of times except one number which occurs an odd number of times. Find the number in O time in constant space. Example IPO, p equal to 3. Solution. Do a bitwise XOR of all the elements. We get the number which has odd occurrences is because XOR equal to 0. This. Time complexity, O. Space complexity, O. Problem 19. Find the two repeating elements in a given array. Given an array with size, all elements of the array are in range 1 to n, and also all elements occur only once except two numbers which occur twice. Find those two repeating numbers. For example, if the array is 4, 2, 4, 5, 2, 3, 1 with size equal to 7, and n equal to 5, this input has n plus 2 equal to 7 elements, with all elements occurring once except 2, and 4 which occur twice. So the output should be 42. Solution. One simple way is to scan the complete array for each element of the input elements. That means use two loops. In the outer loop, select elements one by one and count the number of occurrences of the selected element in the inner loop. For the code below, assume that print repeated elements is called with n plus 2 to indicate the size. Void print repeated elements int size for if equal to a, print ef. Time complexity, O. Space complexity, O. Problem 20 for problem 19. Can we improve the time complexity? Solution. Sort the array using any comparison sorting algorithm and see if there are any elements which are contiguous with the same value. Time complexity, O. Space complexity, O. Problem 21 for problem 19. Can we improve the time complexity? Solution. Use count array. This solution is like using a hash table. For simplicity, we can use array for storing the counts. Traverse the array once and keep track of the count of all elements in the array using a temporary count of size n. When we see an element whose count is already set, print it as duplicate. For the code below, assume that print repeated elements is called with n plus 2 to indicate the size. Void print repeated elements, int size, int count calc, for count plus if, 2, print ef. Time complexity, O. Space complexity, O. Problem 22. Consider problem 19. Let us assume that the numbers are in the range 1 to n. Is there any other way of solving the problem? Solution, yes, by using XOR operation. Let the repeating numbers be x and y. If we XOR all the elements in the array and also all integers from 1 to n, then the result will be x XOR y. The 1/4 in binary representation of x XOR y correspond to the different bits between x and y. If the kth bit of x XOR y is 1, we can XOR all the elements in the array and also all integers from 1 to n whose kth bits are 1. The result will be 1 of x and y. Void print repeated elements in size, right underscore most underscore set underscore bit underscore no equal to XOR, and get the right most set bit in right underscore most underscore set underscore bit underscore no. Now divide elements in two sets by comparing right most set for XOR of first set in A, XOR of second set in A, x to the power of I for else I equal to y to the power of XOR of second set in A, and 1, 2, n. Print. Time complexity, O. Space complexity, O. Problem 23. Consider problem 19. Let us assume that the numbers are in the range 1 to n. Is there yet other way of solving the problem? Solution. We can solve this by creating two simple mathematical equations. Let us assume that two numbers we are going to find are x and y. We know the sum of n numbers is n2 and the product is n. Make two equations using these sum and product formulae and get values of two unknowns using the two equations. Let the summation of all numbers in an array be s and product be p, and the numbers which are being repeated are x and y. Using the above two equations, we can find out x and y. There can be an addition and multiplication overflow problem with this approach. Time complexity, O. Space complexity, O. Problem 24. Similar to problem 19, let us assume that the numbers are in the range 1 to n. Also n, one elements are repeating thrice and remaining element repeated twice. Find the element which repeated twice. Solution. If we XOR all the elements in the array and all integers from 1 to n, then all the elements which are repeated thrice will become 0. This is because since the element is repeating thrice and XOR another time from range makes that element appear 4 times. As a result, the output of XOR A equal to 0. It is the same case with all elements that are repeated 3 times. With the same logic, for the element which repeated twice, if we XOR the input elements and also the range, then the total number of appearances for that element is 3. As a result, the output of XOR A equal to A. Finally, we get the element which repeated twice. Time complexity, O. Space complexity, O. Problem 25. Given an array of n elements, find two elements in the array such that their sum is equal to given element k brute force solution. One simple solution to this is, for each input element, check whether there is any element whose sum is k. This we can solve just by using two simple for loops. The code for this solution can be given as void brute force search int n int k for if plus a equal to k, printf return printf. Time complexity, O. This is because of two nested for loops. Space complexity, O. Problem 26 for problem 25. Can we improve the time complexity? Solution, yes. Let us assume that we have sorted the given array. This operation takes O. On the sorted array, maintain indices low index equal to 0 and high index equal to n1 and compute a plus a. If the sum equals k, then we are done with the solution. If the sum is less than k, decrement high index. If the sum is greater than k, increment low index. Void search, int n, int k, int low index, hill index, sum, sort for sum equal to a plus a, if, print ef return, 1 else, if low index plus 1, else hill index 1 return. Time complexity, O. If the given array is already sorted, then the complexity is O. Space complexity, O. Problem minus 27%. Does the solution of problem 25 work even if the array is not sorted? Solution, yes. Since we are checking all possibilities, the algorithm ensures that we get the pair of numbers if they exist. Problem 28. Is there any other way of solving problem minus 25? Solution, yes, using hash table. Since our objective is to find two indexes of the array whose sum is k. Let us say those indexes are x and y. That means a plus a equal to k. What we need is, for each element of the input array a, check whether a also exists in the input array. Now, let us simplify that, searching with hash table. Algorithm. For each element of the input array, insert it into the hash table. Let us say the current element is a. Before proceeding to the next element, we check whether a also exists in the hash table or not. Their existence of such number indicates that we are able to find the indexes. Otherwise, proceed to the next input element. Time complexity, O. Space complexity, O. Problem 29, given an array A of n elements, find three indices I, j, and k such that a2 plus a 2 equal to a 2. Solution. Algorithm. Sort the given array in place. For each array index, I compute a 2 and store an array. Search for two numbers in array from 0 to I, one which adds to a similar to problem. This will give us the result in O time. If we find such a sum, return true, otherwise continue. Sort the input array for a equal to a for res equal to false. If problem 11 divided by 12 solution. Time complexity. Time for sorting plus n times equal to O plus n times O equal to n2. Space complexity, O. Problem minus 32 elements whose sum is closest to 0. Given an array with both positive and negative numbers, find the two elements such that their sum is closest to 0. For the below array, algorithm should give minus 80 and 85. Example, 160 to 1070 to 8085. Brute force solution for each element, find the sum with every other element in the array, and compare sums. Brute force sum, the minimum sum. Void two elements with min sum, int n, return. Initialization of values, min underscore I equal to 0, min underscore j equal to 1, min underscore sum equal to a plus a. For sum equal to a plus a, if abs, min underscore sum equal to sum, min underscore I equal to I, min underscore j equal to j. Printf ar. Time complexity, O. Space complexity, O. Problem 31. Can we improve the time complexity of problem? Solution, use sorting, algorithm. 1. Sort all the elements of the given input array. 2. Maintain two indexes, one at the beginning and the other at the ending. Also, maintain two variables to keep track of the smallest positive sum closest to 0 and the smallest negative sum closest to 0. 3. While ij, a, if the current pair sum is 0 and positive closest, then update the positive closest. Decrement jb. If the current pair sum is 0 and negative closest, then update the negative closest. Increment I, c, else print the pair. Void two elements with min sum, int n, else print f plus a, return positive closest, negative closest. Time complexity, O for sorting. Space complexity, O. Problem 32, given an array of n elements. Find three elements in the array such that their sum is equal to given element k. Brute force solution. The default solution to this is, for each pair of input elements, check whether there is any element whose sum is k. This we can solve just by using three simple for loops. The code for this solution can be given as void brute force search, int n, int data, print ef. Time complexity, O for three nested for loops. Space complexity, O. Problem minus 33. Does the solution of problem 32 work even if the array is not sorted? Solution, yes. Since we are checking all possibilities, the algorithm ensures that we can find three numbers whose sum is k if they exist. Problem minus 34. Can we use sorting technique for solving problem 32? Solution, yes. Void search, int n, int data, sort no for if plus a equal to data, 1 printf return, else if plus aj, data, I equal to I plus 1, else j1, return. Time complexity, time for sorting plus time for searching in sorted list equal to O plus O, approximately equal to O. This is because of two nested for loops. Space complexity, O. Problem minus 35. Can we use hashing technique for solving problem 32? Solution, yes. Since our objective is to find three indexes of the array whose sum is k. Let us say those indexes are x, y, and z. That means a plus a equal to k. Let us assume that we have kept all possible sums along with their pairs in hash table. That means the key to hash table is ka, and values for ka are all possible pairs of input whose sum is if a. Algorithm. Before starting the search, insert all possible sums with pairs of elements into the hash table. For each element of the input array, insert into the hash table. Let us say the current element is a. Check whether there exists a hash entry in the table with key ka. If such element exists, then scan the element pairs of ka and return all possible pairs by including a also. If no such element exists as key, then go to next element. Time complexity. The time for storing all possible pairs in hash table plus searching OO. Space complexity, O. Equal to O plus. Problem minus 36. Given an array of n integers, the sum problem is to find three integers whose sum is closest to 0. Solution. This is the same as that of problem 32 with k value is 0. Problem 37. Let A be an array of n distinct integers. Suppose A has the following property. There exists an index 1 less than or equal to k less than or equal to n such that A, an increasing sequence, and A is a decreasing sequence. Design and analyze an efficient algorithm for finding k. Similar question, let us assume that the given array is sorted but starts with negative numbers and ends with positive numbers. In this array, find the starting index of the positive numbers. Assume that we know the length of the input array. Design AO algorithm. Solution. Let us use a variant of the binary search. In T search, int n, int first, int last, end of else, end of while. The recursion equation is T equal to 2 trillions plus C. Using master theorem, we get O, problem minus 38. If we don't know n, how do we solve the problem minus 37%? Solution. Repeatedly compute A, and so on, until we find a value of n such that a greater than 0. Time complexity, O, since we are moving at the rate of 2. Refer to Introduction to Analysis of Algorithms chapter for details on this. Problem 39, given an input array of size unknown with all ones in the beginning and O's in the end. Find the index in the array from where zeros start. Consider there are millions of ones and O's in the array. E.g., array contents 1,111,111. Solution. This problem is almost similar to problem 38. Check the bits at the rate of 2k, where k equal to 0, 12. Since we are moving at the rate of 2, the complexity is O. Problem 40. Given a sorted array of n integers that has been rotated an unknown number of times, give a O algorithm that finds an element in the array. Example, find 5 in array output 8. Solution. Let us assume that the given array is A and use the solution of problem 37 with an extension. The function below find pivot returns the k value. Find the pivot point, divide the array into two subarrays, and call binary search. The main idea for finding the pivot point is, for a sorted and pivoted array, the pivot element is the only element for which the next element to it is smaller than it. Using the above criteria and the binary search methodology, we can get pivot element in O time. Algorithm. 1. Find out the pivot point and divide the array into two subarrays. 2. Now call binary search for one of the two subarrays. A. If the element is greater than the first element, then search in left subarray, else search in right subarray. B. 3. If element is found in selected subarray, then return index, else return -1. Int find pivot, int start, int finish, int search, int n, int x, return -1. -1 if element is not found, complexity O. Time problem -41. For problem 40, can we solve with recursion? Solution, yes. Int binary search rotated, int e start, int finish, int data, int mid start plus. 2 if return -1, if return mid, else if equal to A, start half is in sorted order. If end and data A, return binary search rotated, else return binary search rotated, else A equal to A, finish half is in sorted order. If end and data less than equal to else A, return binary search rotated, return binary search rotated. Time complexity. O problem. -42 bitonic search. An array is bitonic if it is comprised of an increasing sequence of integers followed immediately by a decreasing sequence of integers. Given a bitonic array A of n distinct integers, describe how to determine whether a given integer is in the array in O steps. Solution. The solution is the same as that for problem 37. Problem 43, yet other way of framing problem 37%. Let A be an array that starts out increasing, reaches a maximum, and then decreases. Design an O algorithm to find the index of the maximum value. Problem -44 integers. Give an O algorithm for computing the median of a sequence of n. Solution. Sort and return element at n. Problem -45 plus n, time. Given two sorted lists of size m and n, find median of all elements in O log m. Solution. Refer to divide and conquer chapter. Problem -46. Given a sorted array A of n elements, possibly with duplicates, find the index of the first occurrence of a number in O time. Solution. To find the first occurrence of a number, we need to check for the following condition. Return the position if any one of the following is true. In binary search first occurrence, int low, int high, int data, int mid, if mid low. 2 equal to plus, if equal to data, or equal to data and data. Return mid. Give preference to left half of the array, else if greater than equal to data, else return -1. Return binary search first occurrence, return binary search first occurrence. Time complexity. O. Problem 47, given a sorted array A of n elements, possibly with duplicates. Find the index of the last occurrence of a number in O time. Solution. To find the last occurrence of a number, we need to check for the following condition. Return the position if any one of the following is true. Mid equal to high and equal to data, or A equal to data and a data. Int binary search last occurrence, int low, int high, int data, int mid, if mid low. 2 equal to if equal to data, or equal to data and data. Return mid. Give preference to right half of the array, else if less than equal to data, else return -1. Return binary search last occurrence, return binary search last occurrence. Time complexity. O. Problem -48, given a sorted array of n elements, possibly with duplicates. Find the number of occurrences of a number. Brute force solution, do a linear search of the array and increment count as and when we find the element data in the array. Int t linear search count, int n, int data, int count equal to 0 for if equal to data, count plus return count. Time complexity. O. Problem -49. Can we improve the time complexity of problem 48? Solution, yes. We can solve this by using one binary search call followed by another small scan. Algorithm, do a binary search for the data in the array. Let us assume its position is k. Now traverse towards the left from k and count the number of occurrences of data. Let this count be left count. Similarly, traverse towards right and count the number of occurrences of data. Let this count be right count. Total number of occurrences equal to left count plus 1 plus right count. Time complexity, O, where 5 is the number of occurrences of data. Problem 50. Is there any alternative way of solving problem 48? Solution. Algorithm. Find first occurrence of data and call its index as first occurrence. Find last occurrence of data and call its index as last occurrence. Return last occurrence, first occurrence plus 1. Time complexity equal to O. Problem -51. What is the next number in the sequence 1102 and why? Solution. Read the given number loudly. This is just a fun problem. 1 1, 2 1s, 1 2, 1 1, 12 11. So the answer is, the next number is the representation of the previous number by reading it loudly. Problem -52, finding second smallest number efficiently. Solution. We can construct a heap of the given elements using up just less than n comparisons. Then we find the second smallest using lone comparisons for the getMax operation. Overall, we get n plus lone plus constant. Problem 53. Is there any other solution for problem 52? Solution. Alternatively, split the n numbers into groups of 2. Perform n2 comparisons successively to find the largest, using a tournament-like method. The first round will yield the maximum in n1 comparisons. The second round will be performed on the winners of the first round and the ones that the maximum popped. This will yield lone 1 comparison for a total of n plus lon 2. The above solution is called the tournament problem. Problem -54, an element is a majority if it appears more than n2 times. Given algorithm takes an array of n element as argument and identifies a majority. Solution. The basic solution is to have 2 loops and keep track of the maximum count for all different elements. If the maximum count becomes greater than n2, then break the loops and return the element having maximum count. If maximum count doesn't become more than n2, then the majority element doesn't exist. Time complexity, O. Space complexity, O. Problem 55. Can we improve problem 54 time complexity to O? Solution. Using binary search, we can achieve this. Node of the binary search tree will be as follows. Insert elements in BST one by one, and if an element is already present, then increment the count of the node. At any stage, if the count of a node becomes more than n2, then return. This method works well for the cases where n2 plus 1 occurrences of the majority element are present at the start of the array, for example. Time complexity. If a binary search tree is used, then worst time complexity will be O. If a balanced binary search tree is used, then O. Space complexity, O. Problem, -56. Is there any other of achieving O complexity for problem 54? Solution. Sort the input array and scan the sorted array to find the majority element. Time complexity, O. Space complexity, O. Problem, -57. Can we improve the complexity for problem 54? Solution. If an element occurs more than n 2 times in A, then it must be the median of A. But the reverse is not true, so once the median is found, we must check to see how many times it occurs in A. We can use linear selection, which takes O time. In T, check majority. In N, 1, use linear selection to find the median M of A. 2, do. One more pass through A and count the number of occurrences of M, A. If M occurs more than n 2 times, then return true. B, otherwise return false. Problem, -58. Is there any other way of solving problem 54? Solution. Since only one element is repeating, we can use a simple scan of the input array by keeping track of the count for the elements. If the count is 0, then we can assume that the element visited for the first time, otherwise that the resultant element. Int majority num A, int n, int count equal to 0, element equal to -1, 4. If the counter is 0, then set the current candidate to majority num and set the counter to 1. If element A, count equal to 1, else if, else. Increment counter if the counter is not 0 and element is same as current candidate. Count plus plus. Decrement counter if the counter is not 0 and element is different from current candidate. Count, return element. Time complexity, O. Space complexity, O. Problem, -59. Given an array of 2 n elements of which n elements are the same and the remaining n elements are all different. Find the majority element. Solution. The repeated elements will occupy half the array. No matter what arrangement it is, one of the below will be true, only. All duplicate elements will be at a relative distance of 2 from each other. X, n, 1, 100, n, 54, n. N. At least 2 duplicate elements will be next to each other. X, n, 1100, n, 54, n, 1, n, 54,100, 110,000, and 54, n. In worst case, we will need 2 passes over the array. First pass, compare A and A. Second pass, compare A and A. Something will match and that's your element. This will cost O in time and O in space. Problem 60. Given an array with 2 n plus 1 integer elements, n elements appear twice in arbitrary places in the array, and a single integer appears only once somewhere inside. Find a lonely integer with O operations and O extra memory. Solution. Except for one element, all elements are repeated. We know that A XOR A equal to 0. Based on this, if we XOR all the input elements, then we get the remaining element. INT solution. Int I res for res equal to res to the power of A return res. Time complexity, O. Space complexity, O. Problem, -61. Throwing eggs from an n-story building. Suppose we have an n-story building and a number of eggs. Also assume that an egg breaks if it is thrown from floor F or higher and will not break otherwise. Devise a strategy to determine floor F while breaking O eggs. Solution. Refer to divide and conquer chapter. Problem 62. Local minimum of an array. Given an array A of n distinct integers, design an O algorithm to find a local minimum and index I such that A. Solution. Check the middle value A and 2 neighbors A and A. If A is local minimum, stop, otherwise search in half with smaller neighbor. Problem, -63. Given an nxn array of elements such that each row is in ascending order and each column is in ascending order, devise an O algorithm to determine if a given element X is in the array. You may assume all elements in the nxn array are distinct. Solution. Let us assume that the given matrix is A. Start with the last row, first column. If the element we are searching for is greater than the element at A, then the first column can be eliminated. If the search element is less than the element at A, then the last row can be completely eliminated. Once the first column or the last row is eliminated, start the process again with the left bottom end of the remaining array. In this algorithm, there would be maximum n elements that the search element would be compared with. Time complexity, O. This is because we will traverse at most 2 endpoints. Space complexity, O. Problem 64. Given an nxn array A of n2 numbers, give an O algorithm to find a pair of indices, I and j such that A, and A. Solution. This problem is the same as problem 63. Problem 65, given n times n matrix, and in each row all ones are followed by zeros. Find the row with the maximum number of zeros. Solution. Start with first row, last column. If the element is 0, then move to the previous column in the same row, and at the same time increase the counter to indicate the maximum number of 0 feats. If the element is 1, then move to the next row in the same column. Repeat this process until you reach last row, first column. Time complexity, O, approximately equal to O. Problem 66, given an input array of size unknown, with all numbers in the beginning and special symbols in the end. Find the index in the array from where the special symbols start. Solution. Refer to divide and conquer chapter. Problem, -67, separate even and odd numbers given an array A. Write a function that segregates even and odd numbers. The function should put all even numbers first and then odd numbers. Example, input equal to output equal to. Note, in the output, the order of numbers can be changed. That is, in the above example, 34 can come before 12, and 3 can come before 9. Solution. The problem is very similar to separate zeros and ones in an array, and both problems are variations of the famous Dutch national flag problem. Algorithm. The logic is similar to quicksort. 1. Initialize 2 index variables left and right, left equal to 0, right equal to n1. 2. Keep incrementing the left index until you see an odd number. 3. Keep decrementing the right index until you see an even number. 4. If left, right, then swap A and A. Void Dutch national flag, int n, left plus plus, right, time complexity, O. The following is another way of structuring problem 67, but with a slight difference. Separate zeros and ones in an array. We are given an array of zeros and ones in random order. Separate O's on the left side and ones on the right side of the array. Traverse the array only once. Input array equal to output array equal to. Solution, counting zeros or ones. 1. Count the number of zeros. Let the count be C. 2. Once we have the count, put C zeros at the beginning and 1 foot at the remaining n C positions in the array. Time complexity, O. This solution scans the array 2 times. Problem minus 69. Can we solve problem 68 in one scan? Solution. Yes. Use 2 indexes to traverse. Maintain 2 indexes. Initialize the first index left as O and the second index right as N1. Do the following while left right. 1. Keep the incrementing index left while there are OS in it. 2. Keep the decrementing index right while there R is in it. 3. If left right, then exchange A and A. Function to put all OS on left and all 1 second on right void separate on int n. Initialize left and right indexes. Int t left equal to 0, right, N1. While increment left index while we see 0 at left. While equal to 0 and dan left right, left plus plus. Decrement right index while we see 1 at right. While 1 and dan left right, right. If left is smaller than right, then there is a 1 at left and a 0 at right. Swap A and A. If A equal to 0, A equal to 1, left plus plus, right. Time complexity, O. Space complexity, O. Problem 70. Sort an array of 0s, 1s, and 2s. Give an array consisting of 0s, 1s, and 2s. Give an algorithm for sorting A. The algorithm should put all O's first, then all 1s, and finally all 2s at the end. Example input equal to, output equal to. Solution. Void sorting, int n, int low 0, mid 0, high n1, while switch, case 0, case 1, swap A, low plus plus, mid plus plus, break mid plus plus, break, case 2, swap A, high. Break. Time complexity, O. Space complexity, O. Problem minus 71. Maximum difference between 2 elements, given an array A of integers, find out the difference between any 2 elements such that the larger element appears after the smaller number in A. Examples, if array is then returned value should be 8. If array is then the returned value should be 2. Solution, refer to divide and conquer chapter. Problem 72, given an array of 101 elements. Out of 101 elements, 25 elements are repeated twice, 12 elements are repeated 4 times, and 1 element is repeated 3 times. Find the element which repeated 3 times in O. Solution, before solving this problem, let us consider the following XOR operation property, A XOR A equal to 0. That means, if we apply the XOR on the same elements, then the result is 0. Algorithm. XOR all the elements of the given array and assume the result is A. After this operation, 2 occurrences of the number which appeared 3 times become 0 and 1 occurrence remains the same. The 12 elements that are appearing 4 times become 0. The 25 elements that are appearing 2 times become 0. So just XORing all the elements gives the result. Time complexity, O, because we are doing only one scan. Space complexity, O. Given a number n, give an algorithm for finding the number of trailing zeros in problem minus 73, n. Solution. Int number of trailing zeros in number, int I, count equal to 0, if return minus 1, for count plus equal to ni, return count. Time complexity, O. Problem minus 74. Given an array of 2 n integers in the following format, al a a, and b b b, bn. Shuffle the array to a b, a b, a b, and bn without any extra memory. Solution. A brute force solution involves 2 nested loops to rotate the elements in the second half of the array to the left. The first loop runs n times to cover all elements in the second half of the array. The second loop rotates the elements to the left. Note that the start index in the second loop depends on which element we are rotating, and the end index depends on how many positions we need to move to the left. Void shuffle array, for printf. Time complexity, O. Problem 75. Can we improve problem 74 solution? Solution, refer to the divide and conquer chapter. A better solution of time complexity O can be achieved using the divide and concur technique. Let us look at an example. 1. Start with the array A, A, B, 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 B. 2. Split the array into 2 halves, A, A, B, B, 3, 3, 4. Split A, A, B, B into al A, B, B, then split A, B, B into A, B, B. 5. Exchange elements around the center for each subarray you get, A, B, a B, and A, B, a B. Exchange elements around the center, exchange A with B, B, and you get A, B, B, A, B, B. Note that this solution only handles the case when n equal to 21, where I 0, 1, 2, 3, etc. In our example, n equal to 2 to the power of 2 equal to 4, which makes it easy to recursively split the array into 2 halves. The basic idea behind swapping elements around the center before calling the recursive function is to produce smaller size problems. A solution with linear time complexity may be achieved if the elements are of a specific nature. For example, if you can calculate the new position of the element using the value of the element itself. This is nothing but a hashing technique. Problem minus 76, given an array A, find the maximum J, I such that AA. For example, input and output 6. Solution, brute force approach, run 2 loops. In the outer loop, pick elements 1 by 1 from the left. In the inner loop, compare the picked element with the element starting from the right side. Stop the inner loop when you see an element greater than the picked element, and keep updating the maximum J, I so far. Int max int xdiff, int n, int maxdiff equal to minus 1, int I, j, 4, 4, if and then maxdiff j, I, return maxdiff. Time complexity, O. Space complexity, O. Problem minus 77. Can we improve the complexity of problem 76? Solution. To solve this problem, we need to get 2 optimum indexes of A, left index I, and right index j. For an element A, we do not need to consider A for the left index if there is an element smaller than A on the left side of A. Similarly, if there is a greater element on the right side of A, then we do not need to consider this j for the right index. So we construct 2 auxiliary arrays, left mins and right maxes, such that left mins holds the smallest element on the left side of A, including A, and right maxes holds the greatest element on the right side of A, including A. After constructing these 2 auxiliary arrays, we traverse both these arrays from left to right. While traversing left mins and right maxes, if we see that left mins is greater than right maxes, then we must move ahead in left mins because all elements on the left of left mins are greater than or equal to left mins. Otherwise, we must move ahead in right maxes to look for a greater y, I value. Int max index diff lint A, int n, if right maxes, max diff max, jj plus 1, else I equal to I plus 1, return max diff. Time complexity, O. Space complexity, O. Problem 78. Given an array of elements, how do you check whether the list is pairwise sorted or not? A list is considered pairwise sorted if each successive pair of numbers is in sorted order. Solution. In check pairwise sorted, int n, if return 1, 4, if A, return 0, return 1. Time complexity, O. Space complexity, O. Problem minus 79. Given an array of n elements, how do you print the frequencies of elements without using extra space? Assume all elements are positive, editable, and less than n. Solution, use negation technique. Void frequency counter, int n, else, frequency counter size off, return 0. Array should have numbers in the range The if condition, greater than 0 and a greater than 0, means that both the numbers at indices POS and expected POS are actual numbers in the array, but not their frequencies. So we will swap them so that the number at the index POS will go to the position where it should have been if the numbers 1, 2, 3, n are kept in 0, 1, 2, and 1 indices. In the above example input array, initially POS equal to 0, so 10 at index 0 will go to index 9 after the swap. As this, the first occurrence of 10, make it to -1. Note that we are storing the frequencies as negative numbers to differentiate between actual numbers and frequencies. The else if condition greater than 0 means a is a number, and a is its frequency without including the occurrence of a. So increment the frequency by 1. As we count its occurrence, we need to move to next POS, so POS plus plus. But before moving to that next position, we should make the frequency of the number POS plus 1, which corresponds to index POS of 0, since such a number has not yet occurred. The final else part means the current index POS already has the frequency of the number POS plus 1, so move to the next POS, hence POS plus plus. Time complexity, O. Space complexity, O. Problem 80, which is faster, and by how much? A linear search of only 1,000 elements on a 5 GAZ computer, or a binary search of 1 million elements on a 1 GAZ computer. Assume that the execution of each instruction on the 5 GAZ computer is 5 times faster than on the 1 GAZ computer, and that each iteration of the linear search algorithm is twice as fast as each iteration of the binary search algorithm. 1 million solution, a binary search of 1 million elements would require log 2, or about 20 iterations at most. A linear search of 1,000 elements would require 500 iterations on the average. Therefore, binary search would be equal to 25% faster than linear search. However, since linear search 5 2 iterations are twice as fast, binary search would be, or about 12 times faster than linear search overall, on the same machine. Since we run them on different machines where an instruction on the 5 GHZ machine is 5 times faster than an instruction on a 1 GOZ machine, binary search would be, or about 2 times faster than linear search. The key idea is that software improvements can make an algorithm run much faster without having to use more powerful software. 12.5. Selection algorithms. Chapter 12, 12.1. What are selection algorithms? Selection algorithm is an algorithm for finding the KTH smallest largest number in a list. This includes finding the minimum, maximum, and median elements. For finding the KTH order statistic, there are multiple solutions which provide different complexities, and in this chapter we will enumerate those possibilities. 12.2 Selection by sorting. A selection problem can be converted to a sorting problem. In this method, we first sort the input elements and then get the desired element. It is efficient if we want to perform many selections. For example, let us say we want to get the minimum element. After sorting the input elements, we can simply return the first element. Now, if we want to find the second smallest element, we can simply return the second element from the sorted list. That means for the second smallest element, we are not performing the sorting again. The same is also the case with subsequent queries. Even if we want to get KTH smallest element, just one scan of the sorted list is enough to find the element. From the above discussion, what we can say is, with the initial sorting, we can answer any query in one scan, O. In general, this method requires O time, where N is the length of the input list. Suppose we are performing n queries, then the average cost per operation N lone is just NO. This kind of analysis is called amortized analysis. 12.3 Partition-based selection algorithm. For the algorithm, check problem 6. This algorithm is similar to quicksort. 12.4 Linear selection algorithm, median of medians algorithm. Refer to problem 11, median of mediae. Finding the k smallest elements in sorted order. For the algorithm, check problem 6. This algorithm is similar to quicksort. 12.6 Selection algorithms, problems, and solutions. Problem -1, find the largest element in an array A of size n. Solution, scan the complete array and return the largest element. Void find largest in array, int large equal to A4. If large equal to A, print if. Time complexity, O space complexity O. Note, any deterministic algorithm that can find the largest of n keys by comparison of keys takes at least n-1 comparisons. Problem -2, find the smallest and largest elements in an array A of size n. Solution, void find smallest and largest in array, int n, int small equal to A, int large equal to A4. If small equal to A, else if large equal to A, print F. Time complexity, O, space complexity, O. The worst case number of comparisons is 2, n, 1. Problem -3, can we improve the previous algorithms? Solution, yes. We can do this by comparing in pairs. N is assumed to be even. Compare in pairs. Void find with pair comparison. Int n, int large equal to small equal to -1. For if A, if small equal to A, if large, increment I by 2. Large equal to A, 1 else. If small equal to A, if large equal to A, print F. Time complexity, O, space complexity, O3 n 2, if n is even number of comparisons 2, 3, and 3, if n is odd. Summary. Note, for divide and conquer techniques, refer to divide and conquer chapter. Problem -4 elements. Give an algorithm for finding the second largest element in the given input list of. Solution, brute force method, algorithm, find largest element needs n1 comparisons. Delete the largest element, again find largest element needs n2 comparisons. Total number of comparisons n1 plus n2 equal to 2 n to 3. Problem 5, can we reduce the number of comparisons in problem 4? Solution. Solution, the tournament method. For simplicity, assume that the numbers are distinct and that n is a power of 2. We pair the keys and compare the pairs in rounds until only one round remains. If the input has 8 keys, there are 4 comparisons in the first round, 2 in the second, and 1 in the last. The winner of the last round is the largest key. The figure below shows the method. The tournament method directly applies only when n is a power of 2. When this is not the case, we can add enough items to the end of the array to make the array size a power of 2. If the tree is complete, then the maximum height of the tree is lone. If we construct the complete binary tree, we need n1 comparisons to find the largest. The second largest key has to be among the ones that were lost in a comparison with the largest one. That means the second largest element should be one of the opponents of the largest element. The number of keys that are lost to the largest key is the height of the tree, that is lon. Then using the selection algorithm to find the largest among them, take lon1 comparisons. Thus the total number of comparisons to find the largest and second largest keys is n plus lon 2. 18. Problem 6, find the k smallest elements in an array S of n elements using partitioning method. Solution, brute force approach, scan through the numbers k times to have the desired element. This method is the one used in bubble sort, every time we find out the smallest element in the whole sequence by comparing every element. In this method, the sequence has to be traversed k times. So the complexity is O. Problem -7, can we use the sorting technique for solving problem 6? Solution, yes. Sort and take the first k elements. 1. Sort the numbers. 2. Pick the first k elements. The time complexity calculation is trivial. Sorting of n numbers is of O and picking k elements is of O. The total complexity is O equal to O. Problem minus 8. Can we use the tree sorting technique for solving problem 6? Solution, yes. Once step 2 is over, the balanced tree with k elements will have the smallest k elements. The only. 1. Insert all the elements in a binary search tree. 2. Do an in-order traversal and print k elements, which will be the smallest ones. So, we have the k smallest elements. The cost of creation of a binary search tree with n elements is O, and the traversal up to k elements is O. Hence, the complexity is O equal to O. Disadvantage. If the numbers are sorted in descending order, we will be getting a tree which will be skewed towards the left. In that case, the construction of the tree will be 0 plus 1 plus 2 plus n equal to which is O. To escape from this, we can keep the tree balanced, so that the 2 cost of constructing the tree will be only none. Problem minus 9. Can we improve the tree sorting technique for solving problem 6? Solution, yes. Use a smaller tree to give the same result. 1. Take the first k elements of the sequence to create a balanced tree of k nodes. 2. Take the remaining numbers one by one, and, if the number is larger than the largest element of the tree, return. B. If the number is smaller than the largest element of the tree, remove the largest element of the tree and add the new element. This step is to make sure that a smaller element replaces a larger element from the tree, and of course the cost of this operation is log, since the tree is a balanced tree of k elements. Remaining task is to print out the largest element of the tree. Time complexity. 1. For the first k elements we make the tree, hence the cost is clock. 2. For the rest nk elements, the complexity is O. Step 2 has a complexity of log. The total cost is clock plus log O. This bound is actually better than the ones provided earlier. Equal to log, which is. Problem minus 10. Can we use the partitioning technique for solving problem 6? Solution, yes. Algorithm. 1. Choose a pivot from the array. 2. Partition the array so that a less than equal to pivot point less than equal to 1 high a pivot point plus. 3. If k pivot point, then it must be on the left of the pivot, so do the same method recursively on the left part. 4. If k equal to pivot point, then it must be the pivot and print all the elements from low to pivot point. 5. If k pivot point, then it must be on the right of pivot, so do the same method recursively on the right part. The top level call would be k smallest equal to selection. int selection, int pivot point, if else, return s, pivot point partition. If return s, we can print all the elements from low to pivot point. Else if return selection, void partition, int I, j, pivot item, s, j equal to low. For if pivot item, j plus plus, swap s and s, pivot point equal to j, swap s and pivot point, return pivot point. Time complexity, O in worst case as similar to quicksort. Although the worst case is the same as that of quicksort, this performs much better on the average. Problem 11. Find the kth smallest element in an array S of n elements in best possible way. Solution. This problem is similar to problem 6, and all the solutions discussed for problem 6 are valid for this problem. The only difference is that instead of printing all the k elements, we print only the kth element. We can improve the solution by using the median of medians algorithm. Median is a special case of the selection algorithm. The algorithm selection to find the kth smallest element from set A of n elements is as follows. Algorithm selection. 1. Partition A into CL length groups with each group having 5 items. 2. Sort each group separately. 3. Find the median of each of the groups and store them in some array. 5. 4. Use selection recursively to find the median of A. Let us say the median of medians is M. 5. Let Q equal to hashtag elements of a smaller than M. 6. If return M. Partition with pivot. 7. Else partition A into X and Y. X equal to item smaller than M. 8. Y equal to. Next, form a subproblem. If return selection. 9. Else. Return selection. Before developing recurrence, let us consider the representation of the input below. In the figure, each circle is an element and each column is grouped with 5 elements. The black circles indicate the median in each group of 5 elements. As discussed, sort each column using constant time insertion sort. Median of medians. After sorting, rearrange the medians so that all medians will be in ascending order. In the figure above, the gray circled item is the median of medians. It can be seen that at least 1/2 of 5 element group medians M. Also, these 1/2 of 5 element groups contribute 3 elements that are M except 2 groups. Similarly, at least 1/2 of 5 element groups contribute 3 elements that are M as shown above. 1/2 of 5 element groups contribute 3 elements, except 2 groups gives 3, 11, 11 to 2, remaining are 3 and 6. N, 3 and 6, 7 and 10 plus 6. Since 7 and 10 plus 6 is greater than 3 and 6, 2 remaining are 3 and 6, 7 and components in recurrence. In our selection algorithm, we choose M, which is the median of medians, to be a pivot, and partition A into 2 sets X and Y. We need to select the set which gives maximum size. The time in function selection when called from procedure partition. The number of keys in the input to this call to selection is the number of comparisons required to partition the array. This number is length, let us say n, have established the following. Recurrence, t equal to t plus o plus max. From the above discussion, we have seen that if we select median of medians M as pivot, the partition sizes are 7n, 3n to 6, and 10 plus 6. If we select the maximum of these, then we get. Problem 12 and problem 11, we divided the input array into groups of 5 elements. The constant 5 play an important part in the analysis. Can we divide in groups of 3, which work in linear time? Solution, in this case, the modification causes the routine to take more than linear time. In the worst case, at least half of the medians found in the grouping step are greater than the 3 median of medians M, but 2 of those groups contribute less than 2 elements larger than M. So as an upper bound, the number of elements larger than the pivot point is at least. Likewise, this is a lower bound. Thus up to n2 and to 4 equal to plus 4 elements are fed into the recursive call to select. The recursive step that finds the median of medians runs on a problem of size, and consequently the time recurrence is n. Assuming that 2 and 3 t2 plus 4 greater than or equal to t greater than or equal to 3 trillion size. T is monotonically increasing. We may conclude that greater than or equal to 2 trillions, and we can say the upper bound for this is 3 plus O, which is O. Therefore, we cannot select 3 as the group. Problem minus 13, as in problem 12. Can we use groups of size 7? Solution. Following a similar reasoning, we once more modify the routine, now using groups of 7 instead of 5. In the worst case, at least half the medians found in the grouping step are greater than the median of medians M, but 2 of those groups contribute less than 4 elements larger than M. So as an upper bound, the number of elements larger than the pivot point is at least. Likewise, this is a lower bound. Thus up to n2 and 7 recursive call to select. The recursive step that finds the median of medians runs on a problem of size, and consequently the time recurrence is equal to 5n plus 8 elements are fed into the 5n less than or equal to c 1/2 1/2, COE 3/4 3 1/2 3 plus 8 plus n 9c. Therefore, we can select 7. This is bounded above by n provided that c as the group size. Problem -14 given two arrays each containing n sorted elements, given O-time algorithm to find the median of all two n elements. Solution. The simple solution to this problem is to merge the two lists and then take the average of the middle two elements. But the merge would be O, so that doesn't satisfy the problem statement. To get ln complexity, let mediana and median be the medians of the respective lists. If mediana equal to median, then that is the overall median of the union, and we are done. Otherwise, the median of the union must be between mediana and median. Suppose that mediana median. Then we need to find the median of the union of the following two sets. So we can do this recursively by resetting the boundaries of the two arrays. The algorithm tracks both arrays using two indices. These indices are used to access and compare the median of both arrays to find where the overall median lies. Void find median, int alo, int ahi, int b, int lo, int b, amid alo plus /2, amed equal to a, b amid b below plus /2, b amid equal to b, if, handle the boundary cases and solve its smaller problem in O time. Return, else if find median, else find median. Time complexity, O, since we are reducing the problem size by half every time. Problem 15, let A and B be two sorted arrays of n elements each. We can easily find the kth smallest element in A in O time by just outputting A. Similarly, we can easily find the kth smallest element in B. Give an O-time algorithm to find the kth smallest element overall, that is the kth smallest in the union of A and B. Solution is just another way of asking problem 14. Problem -16. Find the k smallest elements in sorted order. Given a set of n elements from a totally ordered domain, find the k smallest elements and list them in sorted order. Analyze the worst case running time of the best implementation of the approach. Solution, sort the numbers and list the k smallest. T equal to time complexity of sort plus listing k smallest elements equal to O plus O equal to O. Problem -17 for problem 16. If we follow the approach below, then what is the complexity? Solution, using the priority queue data structure from heap sort, construct a min heap over the set and perform extract min k times. Refer to the priority queues chapter for more details. Problem -18 for problem 16. If we follow the approach below, then what is the complexity? Find the kth smallest element of the set, partition around this pivot element, and sort the k smallest elements. Solution. T equal to time complexity of kth, smallest plus finding pivot plus sorting prefix equal to O plus O plus O equal to. Since less than or equal to n, this approach is better than problem 16 and problem 17. So 19, find k nearest neighbors to the median of n distinct numbers in O time. Solution, let us assume that the array elements are sorted. Now find the median of n numbers and n call its index as x. All we need to do is select k elements with the smallest absolute differences from the median, moving from x1 to 0 and x plus 1 ton 1 when the median is at index m. Time complexity, each step takes e. So the total time complexity of the algorithm is O. Problem -20. Is there any other way of solving problem 19? Solution, assume for simplicity that n is odd and k is even. If set A is in sorted order, the median is in position n2, and the k numbers in A that are closest to the median are in positions /2 through /2. We first use linear time selection to find the /2, n2, and /2 elements, and then pass through set A to find the numbers less than the /2 element, greater than the /2 element, and not equal to the n2 element. The algorithm takes O time as we use linear time selection exactly 3 times and traverse the n numbers in a once. Problem -21 given coordinates of n houses, where should you build a road parallel to x-axis to minimize the construction cost of building driveways? Solution, the road costs nothing to build. It is the driveways that cost money. The driveway cost is proportional to its distance from the road. Obviously, they will be perpendicular. The solution is to put the street at the median of the y coordinates. Problem 22, given a big file containing billions of numbers, find the maximum 10 numbers from that file. Solution, refer to the priority queues chapter. Problem 23, suppose there is a milk company. The company collects milk every day from all its agents. The agents are located at different places. To collect the milk, what is the best place to start so that the least amount of total distance is traveled? Solution, starting at the median reduces the total distance traveled because it is the place which is at the center of all the places. 13.1 Introduction. Since childhood, we all have used a dictionary, and many of us have a word processor which comes with a spell checker. The spell checker is also a dictionary but limited in scope. There are many real-time examples for dictionaries, and a few of them are spell checker, the data dictionary found in database management applications. Symbol tables generated by loaders, assemblers, and compilers. Routing tables and networking components. In computer science, we generally use the term symbol table rather than dictionary when referring to the abstract data type. 13.2. What are symbol tables? We can define the symbol table as a data structure that associates a value with a key. It supports the following operations. Search whether a particular name is in the table. Get the attributes of that name. Modify the attributes of that name. Insert a new name and its attributes. Delete a name and its attributes. There are only 3 basic operations on symbol tables: searching, inserting, and deleting. Example, DNS lookup. Let us assume that the key in this case is the URL and the value is an IP address. Insert URL with specified IP address. Given URL, find corresponding IP address. 13.3 Symbol table implementations. Before implementing symbol tables, let us enumerate the possible implementations. Symbol tables can be implemented in many ways, and some of them are listed below. Unordered array implementation. With this method, just maintaining an array is enough. It needs O time for searching, insertion, and deletion in the worst case. Ordered array implementation. In this, we maintain a sorted array of keys and values. Store in sorted order by key. Keys, ith largest key. Values equal to value associated with ith largest key. Since the elements are sorted and stored in arrays, we can use a simple binary search for finding an element. It takes O time for searching, and O time for insertion, and deletion in the worst case. Unordered linked list implementation. Just maintaining a linked list with 2 data values is enough for this method. It needs O time for searching, insertion, and deletion in the worst case. Ordered linked list implementation. In this method, while inserting the keys, maintain the order of keys in the linked list, even if the list is sorted. In the worst case, it needs O time for searching, insertion, and deletion. Binary search trees implementation. Refer to trees chapter. The advantages of this method are, it does not need much code and it has a fast search. Balanced binary search trees implementation. Refer to trees chapter. It is an extension of binary search trees implementation and takes O in worst case for search, insert, and delete operations. Ternary search implementation. Refer to String Algorithms chapter. This is one of the important methods used for implementing dictionaries. Hashing implementation. This method is important. For a complete discussion, refer to the hashing chapter. 13.4 Comparison table of symbols for implementations. Let us consider the following comparison table for all the implementations. Notes. In the above table, n is the input size. Table indicates the possible implementations discussed in this book. But there could be other implementations. 14.1. What is hashing? Hashing is a technique used for storing and retrieving information as quickly as possible. It is used to perform optimal searches and is useful in implementing symbol tables. 14.2. Why hashing? In the trees chapter, we saw that balanced binary search trees support operations such as insert, delete, and search in O time. In applications, if we need these operations in O, then hashing provides a way. Remember that worst case complexity of hashing is still O, but it gives O on the average. 14.3 Hash table ADT. The common operations for hash table are: create hash table creates a new hash table, hash search searches the key in hash table, hash insert inserts a new key into hash table, hash delete deletes a key from hash table, delete hash table deletes the hash table. 14.4 Understanding hashing. In simple terms, we can treat array as a hash table. For understanding the use of hash tables, let us consider the following example. Give an algorithm for printing the first repeated character if there are duplicated elements in it. Let us think about the possible solutions. The simple and brute force way of solving is, given a string, for each character check whether that character is repeated or not. The time complexity of this approach is O with O space complexity. Now, let us find a better solution for this problem. Since our objective is to find the first repeated character, what if we remember the previous characters in some array? We know that the number of possible characters is 256. Create an array of size 256 and initialize it with all zeros. For each of the input characters, go to the corresponding position and increment its count. Since we are using arrays, it takes constant time for reaching any location. While scanning the input, if we get a character whose counter is already 1, then we can say that the character is the one which is repeating for the first time. Char first repeated Charles count, ++ if printf returns 0. Why not arrays? In the previous problem, we have used an array of size 256 because we know the number of different possible characters in advance. Now, let us consider a slight variant of the same problem. Suppose the given array has numbers instead of characters. Then how do we solve the problem? Universe of possible keys, 0, 1, 2, 3, 5, 6. In this case, the set of possible values is infinity. Creating a huge array and storing the counters is not possible. That means there are a set of universal keys and limited locations in the memory. If we want to solve this problem, we need to somehow map all these possible keys to the possible memory locations. From the above discussion and diagram, it can be seen that we need a mapping of possible keys to one of the available locations. As a result, using simple arrays is not the correct choice for solving the problems where the possible keys are very big. The process of mapping the keys to locations is called hashing. Note, for now, do not worry about how the keys are mapped to locations. That depends on the function used for conversions. One such simple function is key % table size. 14.5 components of hashing. Hashing has 4 key components. 1. Hash table. 2. Hash functions. 3. Collisions. 4. Collision resolution techniques. 14.6 Hash table. Hash table is a generalization of array. With an array, we store the element whose key is k at a position k of the array. That means, given a key k, we find the element whose key is k by just looking in the kth position of the array. This is called direct addressing. Direct addressing is applicable when we can afford to allocate an array with one position for every possible key. But if we do not have enough space to allocate a location for each possible key, then we need a mechanism to handle this case. Another way of defining the scenario is, if we have less locations and more possible keys, then simple array implementation is not enough. In these cases, one option is to use hash tables. Hash table or hash map is a data structure that stores the keys and their associated values, and hash table uses a hash function to map keys to their associated values. The general convention is that we use a hash table when the number of keys actually stored is small relative to the number of possible keys. 14.7% hash function. The hash function is used to transform the key into the index. Ideally, the hash function should map each possible key to a unique slot index, but it is difficult to achieve in practice. Given a collection of elements, a hash function that maps each item into a unique slot is referred to as a perfect hash function. If we know the elements in the collection will never change, then it is possible to construct a perfect hash function. Unfortunately, given an arbitrary collection of elements, there is no systematic way to construct a perfect hash function. Luckily, we do not need the hash function to be perfect to still gain performance efficiency. One way to always have a perfect hash function is to increase the size of the hash table so that each possible value in the element range can be accommodated. This guarantees that each element will have a unique slot. Although this is practical for small numbers of elements, it is not feasible when the number of possible elements is large. For example, if the elements were 9-digit social security numbers, this method would require almost 1 billion slots. If we only want to store data for a class of 25 students, we will be wasting an enormous amount of memory. Our goal is to create a hash function that minimizes the number of collisions, is easy to compute, and evenly distributes the elements in the hash table. There are a number of common ways to extend the simple remainder method. We will consider a few of them here. The folding method for constructing hash functions begins by dividing the elements into equal-sized pieces. These pieces are then added together to give the resulting hash value. For example, if our element was the phone number 43655554601, we would take the digits and divide them into groups of 2. After the addition, 43 plus 65 plus 55 plus 46 plus 01, we get 210. If we assume our hash table has 11 slots, then we need to perform the extra step of dividing by 11 and keeping the remainder. In this case, 210% 11 is 1, so the phone number 43655554601 hashes to slot 1. Some folding methods go one step further and every other piece before the addition. For the above example, we get 43 plus 56 plus 55 plus 64 plus 01 to 219, which gives 219% 11 equal to 10, plus 01 to 2's hash function. Associated with the creation of hash tables are: an efficient hash function should be designed so that it distributes the index values of inserted objects uniformly across the table. An efficient collision resolution algorithm should be designed so that it computes an alternative index for a key whose hash index corresponds to a location previously inserted in the hash table. We must choose a hash function which can be calculated quickly, returns values within the range of locations in our table, and minimizes collisions. Characteristics of good hash functions. A good hash function should have the following characteristics: minimize collision, be easy and quick to compute, distribute key values evenly in the hash table, use all the information provided in the key, have a high load factor for a given set of keys. 14.8 load factor. The load factor of a non-empty hash table is the number of items stored in the table divided by the size of the table. This is the decision parameter used when we want to rehash or expand the existing hash table entries. This also helps us in determining the efficiency of the hashing function. That means it tells whether the hash function is distributing the keys uniformly or not. 14.9 collisions. Hash functions are used to map each key to a different address space, but practically it is not possible to create such a hash function, and the problem is called collision. Collision is the condition where two records are stored in the same location. 14.10 collision resolution techniques. The process of finding an alternate location is called collision resolution. Even though hash tables have collision problems, they are more efficient in many cases compared to all other data structures like search trees. There are a number of collision resolution techniques, and the most popular are direct chaining and open addressing. Direct chaining, an array of linked list application. O separate chaining. Open addressing, array-based implementation. Linear probing. O quadratic probing. Double hashing. 14.11 separate chaining. Collision resolution by chaining combines linked representation with hash table. When two or more records hash to the same location, these records are constituted into a singly linked list called a chain. Universe of possible keys. 14.12 open addressing. In open addressing, all keys are stored in the hash table itself. This approach is also known as closed hashing. This procedure is based on probing. A collision is resolved by probing. Linear probing. The interval between probes is fixed at 1. In linear probing, we search the hash table sequentially, starting from the original hash location. If a location is occupied, we check the next location. We wrap around from the last table location to the first table location if necessary. The function for rehashing is the following. One of the problems with linear probing is that table items tend to cluster together in the hash table. This means that the table contains groups of consecutively occupied locations that are called clustering. Clusters can get close to one another and merge into a larger cluster. Thus, the one part of the table might be quite dense, even though another part has relatively few items. Clustering causes long probe searches and therefore decreases the overall efficiency. The next location to be probed is determined by the step size, where other step sizes are possible. The step size should be relatively prime to the table size, that is, their greatest common divisor should be equal to 1. If we choose the table size to be a prime number, then any step size is relatively prime to the table size. Clustering cannot be avoided by larger step sizes. Quadratic probing. The interval between probes increases proportionally to the hash value. The problem of clustering can be eliminated if we use the quadratic probing method. In quadratic probing, we start from the original hash location I. If a location is occupied, we check the locations I plus 1 to the power of 2, I plus 2 to the power of 2, I plus 32, I plus 4 to the power of 2. We wrap around from the last table location to the first table location if necessary. The function for rehashing is the following. Rehash equal to % table size. Example, let us assume that the table size is 11. Hash function, h equal to key mod 11. Insert keys. 31 mod 119, 19 mod 11, insert key. 19 mod 11 12, mod 11 12, 2 112, mod 11 equal to 22 plus 12, 2, thus 2 to the power of 2 equal to 6. 9 mod 11 equal to 99 plus 12, 9 plus 2 to the power of 2 through 2 mod 11, 2, 11. Quadratic probing. Still there are chances of clustering. Clustering is caused by multiple search keys mapped to the same hash key. Thus, the probing sequence for such search keys is prolonged by repeated conflicts along the probing sequence. Both linear and quadratic probing use a probing sequence that is independent of the search key. Double hashing. The interval between probes is computed by another hash function. Double hashing reduces clustering in a better way. The increments for the probing sequence are computed by using a second hash function. The second hash function h should be h0 and h hashtag h. We first probe the location h. If the location is occupied, we probe the location h plus 2 h. Example, table size is 11. Hash function, assume h equal to key mod 11 and h equal to 7, 0, 1, 2, 3, 58, 4, 0, 1, 2, 58 free function and h equal to 7s, and h mod 113. 14 mod 1133 plus 7 equal to 10. 91 mod 113, 113, 25, 10, 58 mod 130 plus 3, 3 plus 2 times 3 equal to 9. 14.13, 3 plus 3 mod 113. The choice between linear probing and double hashing depends on the cost of computing the hash function and on the load factor of the table. Both use few probes, but double hashing take more time because it hashes to compare two hash functions for long keys. Comparisons: open addressing versus separate chaining. It is somewhat complicated because we have to account for the memory usage. Separate chaining uses extra memory for links. Open addressing needs extra memory implicitly within the table to terminate the probe sequence. Open addressed hash tables cannot be used if the data does not have unique keys. An alternative is to use separate chain hash tables. Comparisons: open addressing methods. 14.14 How hashing gets O complexity. From the previous discussion, one doubts how hashing gets O if multiple elements map to the same location. The answer to this problem is simple. By using the load factor, we make sure that each block on the average stores the maximum number of elements less than the load factor. Also, in practice, this load factor is a constant. As a result, searching in 20 elements or 10 elements becomes constant. If the average number of elements in a block is greater than the load factor, we rehash the elements with a bigger hash table size. One thing we should remember is that we consider average occupancy when deciding the rehash. The access time of the table depends on the load factor, which in turn depends on the hash function. This is because hash function distributes the elements to the hash table. For this reason, we say hash table gives O complexity on average. Also, we generally use hash tables in cases where searches are more than insertion and deletion operations. 14.15 Hashing techniques. There are two types of hashing techniques: static hashing and dynamic hashing. Static hashing. If the data is fixed, then static hashing is useful. In static hashing, the set of keys is kept fixed and given in advance, and the number of primary pages in the directory are kept fixed. Dynamic hashing. If the data is not fixed, static hashing can give bad performance, in which case dynamic hashing is the alternative, in which case the set of keys can change dynamically. 14.1. 6 problems for which hash tables are not suitable, problems for which data ordering is required, problems having multidimensional data, problems that have dynamic data. Prefix searching, especially if the keys are long and of variable lengths, problems in which the data does not have unique keys. 14.17 Bloom filters. A Bloom filter is a probabilistic data structure, which was designed to check whether an element is present in a set with memory and time efficiency. It tells us that the element either definitely is not in the set or may be in the set. The base data structure of a Bloom filter is a bit vector. The algorithm was invented in 1970 by Burton Bloom, and it relies on the use of a number of different hash functions. How it works? Now that the bits in the bit vector have been set for element and element, we can query the Bloom filter to tell us if something has been seen before. The element is hashed, but instead of setting the bits, this time a check is done, and if the bits that would have been set are already set, the Bloom filter will return true that the element has been seen before. A Bloom filter starts off with a bit array initialized to 0. To store a data value, we simply apply k different hash functions and treat the resulting k values as indices in the array, and we set each of the k array elements to 1. We repeat this for every element that we encounter. Now suppose an element turns up and we want to know if we've seen it before. What we do is apply the k hash functions and look up the indicated array elements. If any of them are 0, we can be 100% sure that we have never encountered the element before. If we had, the bit would have been set to 1. However, even if all of them are 1, we still can't conclude that we have seen the element before, because all of the bits could have been set by the k hash functions applied to multiple other elements. All we can conclude is that it is likely that we have encountered element before. Note that it is not possible to remove an element from a Bloom filter. The reason is simply that we can't unset a bit that appears to belong to an element because it might also be set by another element. If the bit array is mostly empty, that is set to 0, and the k hash functions are independent of one another, then the probability of a false positive is low. For example, if there are only k bits set, we can conclude that the probability of a false positive is very close to 0, as the only possibility of error is that we entered a data item that produced the same k hash values, which is unlikely as long as the has functions are independent. As the bit array fills up, the probability of a false positive slowly increases. Of course, when the bit array is full, every element queried is identified as having been seen before. So clearly, we can trade space for accuracy as well as for time. One-time removal of an element from a Bloom filter can be simulated by having a second Bloom filter that contains elements that have been removed. However, false positives in the second filter become false negatives in the composite filter, which may be undesirable. In this approach, reading a previously removed item is not possible, as one would have to remove it from the removed filter. Selecting hash functions. The requirement of designing k different independent hash functions can be prohibitive for large k. For a good hash function with a wide output, there should be little, if any, correlation between different bit fields of such a hash. So this type of hash can be used to generate multiple different hash functions by slicing its output into multiple bit fields. Alternatively, one can pass k different initial values to a hash function that takes an initial value or add these values to the key. For larger m and or k, independence among the hash functions can be relaxed with negligible increase in the false positive rate. Selecting size of bit vector. A Bloom filter with 1% error and an optimal value of k, in contrast, requires only about 9.6 bits per element, regardless of the size of the elements. This advantage comes partly from its compactness inherited from arrays and partly from its probabilistic nature. The 1% false positive rate can be reduced by a factor of 10 by adding only about 4.8 bits per element. Space advantages. While risking false positives, Bloom filters have a strong space advantage over other data structures for representing sets, such as self-balancing binary search trees, tries, hash tables, or simple arrays or linked lists of the entries. Most of these require storing at least the data items themselves, which can require anywhere from a small number of bits for small integers to an arbitrary number of bits, such as for strings. Linked structures incur an additional linear space overhead for pointers. However, if the number of potential values is small and many of them can be in the set, the Bloom filter is easily surpassed by the deterministic bit array, which requires only 1 bit for each potential element. Time advantages. Bloom filters also have the unusual property that the time needed either to add items or to check whether an item is in the set is a fixed constant O, completely independent of the number of items already in the set. No other constant space set data structure has this property, but the average access time of sparse hash tables can make them faster in practice than some Bloom filters. In a hardware implementation, however, the Bloom filter shines because its k lookups are independent and can be parallelized. Implementation. Refer to Problems section. 14.18 Hashing, Problems and Solutions. Problem 1. Implement a separate chaining collision resolution technique. Also discuss time complexities of each function. Solution. To create a hash table of given size, say n, we allocate an array of n L pointers to list, initialized to null. To perform search, insert, delete operations, we first compute the index of the table from the given key by using hash function and then do the corresponding operation in the linear list maintained at that location. To get uniform distribution of keys over a hash table, maintain table size as the prime number. Hashtag define load factor 20 struct list node struct hash table new node. Key, index, new node, data equal to data, new node next equal to h table next equal to new node, h table b count plus plus, h count plus plus, if rehash, return 1, int hash delete, return 0, void rehash, create hash table, O, hash search, O average. Hash insert, O average, hash delete 1, average, O, problem -2, given an array of characters, given algorithm for removing the duplicates. Solution, start with the first character and check whether it appears in the remaining part of the string using a simple linear search. If it repeats, bring the last character to that position and decrement the size of the string by 1. Continue this process for each distinct character of the given string. Int elem, for if e, return 1, return 0, int remove duplicates, int m equal to 0. For if a equal to a, return m. Time complexity, O. Space complexity, O. Problem 3, can we find any other idea to solve this problem in better time than O? Observe that the order of characters in solutions do not matter. Solution, use sorting to bring the repeated characters together. Finally, scan through the array to remove duplicates in consecutive positions. Int t compare return a b, void remove duplicates. Int last current quick sort size off compare, current 0 last 0 for I if s 0. Time complexity, O. Space complexity, O. Problem -4, can we solve this problem in a single pass over given array? Solution, we can use hash table to check whether a character is repeating in the given string or not. If the current character is not available in hash table, then insert it into hash table and keep that character in the given string also. If the current character exists in the hash table, then skip that character. Void remove duplicates, int src dst, struct hash table h equal to create hash table, current equal to last equal to 0, for current plus plus if s equal to 0, s equal to s, hash insert. Time complexity, O on average. Space complexity, O. Problem 5. Given two arrays of unordered numbers, check whether both arrays have the same set of numbers. Solution, let us assume that two given arrays are A and B. A simple solution to the given. Problem is, for each element of A, check whether that element is in B or not. A problem arises with this approach if there are duplicates. For example, consider the following inputs. The above algorithm gives the wrong result because for each element of A there is an element in B also. But if we look at the number of occurrences, they are not the same. This problem we can solve by moving the elements which are already compared to the end of the list. That means if we find an element in B, then we move that element to the end of B, and in the next searching we will not find those elements. But the disadvantage of this is it needs extra swaps. Time complexity of this approach is O, since for each element of A, we have to scan B. Problem -6. Can we improve the time complexity of problem 5? Solution, yes. To improve the time complexity, let us assume that we have sorted both the lists. Since the sizes of both arrays are n, we need O time for sorting them. After sorting, we just need to scan both the arrays with 2 pointers and see whether they point to the same element every time, and keep moving the pointers until we reach the end of the arrays. Time complexity of this approach is O. This is because we need O for sorting the arrays. After sorting, we need O time for scanning, but it is less compared to O. Problem -7. Can we further improve the time complexity of problem 5? Solution, yes, by using a hash table. For this, consider the following algorithm. Algorithm. Construct a hash table with array A elements as keys. While inserting the elements, keep track of the number frequency for each number. That means if there are duplicates, then increment the counter of that corresponding key. After constructing the hash table for A's elements, now scan the array B. For each occurrence of B's elements, reduce the corresponding counter values. At the end, check whether all counters are 0 or not. If all counters are 0, then both arrays are the same, otherwise the arrays are different. Time complexity, O for scanning the arrays. Space complexity, O for hash table. Problem -8, given a list of number pairs, if pair exists and pair exists, report all such pairs. For example, in we see that and are present. Report this pair when you encounter. We call such pairs symmetric pairs. So, give an efficient algorithm for finding all such pairs. Solution, by using hashing, we can solve this problem in just one scan. Consider the following algorithm. Algorithm. Read the pairs of elements one by one and insert them into the hash table. For each pair, consider the first element as key and the second element as value. While inserting the elements, check if the hashing of the second elements of the current pair is the same as the first number of the current pair. If they are the same, then that indicates a symmetric pair exits and output that pair. Otherwise, insert that element into that. That means use the first number of the current pair as key and the second number as value and insert them into the hash table. By the time we complete the scanning of all pairs, we have output all the symmetric pairs. Time complexity, O for scanning the arrays. Note that we are doing a scan only of the input. Space complexity, O for hash table. Problem -9, given a singly linked list, check whether it has a loop in it or not. Solution, using hash tables. Algorithm. Traverse the linked list nodes one by one. Check if the node's address is there in the hash table or not. If it is already there in the hash table, that indicates we are visiting a node which was already visited. This is possible only if the given linked list has a loop in it. If the address of the node is not there in the hash table, then insert that node's address into the hash table. Continue this process until we reach the end of the linked list or we find the loop. Time complexity, O for scanning the linked list. Note that we are doing a scan only of the input. Space complexity, O for hash table. Note, for an efficient solution, refer to the linked lists chapter. Problem 10, given an array of 101 elements. Out of them, 50 elements are distinct, 24 elements are repeated 2 times, and 1 element is repeated 3 times. Find the element that is repeated 3 times in O. Solution using hash tables. Algorithm. Scan the input array one by one. Check if the element is already there in the hash table or not. If it is already there in the hash table, increment its counter value. If the element is not there in the hash table, insert that node into the hash table with counter value 1. Continue this process until reaching the end of the array. Time complexity, O, because we are doing 2 scans. Space complexity, O for hash table. Note, for an efficient solution, refer to the searching chapter. Problem 11. Given m sets of integers that have n elements in them, provide an algorithm to find an element which appeared in the maximum number of sets. Solution using hash tables. Algorithm. Scan the input sets one by one. For each element, keep track of the counter. The counter indicates the frequency of occurrences in all the sets. After completing the scan of all the sets, select the one which has the maximum counter value. Time complexity, O, because we need to scan all the sets. Space complexity, O for hash table, because in the worst case, all the elements may be different. Problem 12, given 2 sets A and B, and a number k, give an algorithm for finding whether there exists a pair of elements, one from A and one from B, that add up to k. Solution, for simplicity, let us assume that the size of A is m and the size of B is n. Algorithm. Select the set which has minimum elements. For the selected set, create a hash table. We can use both key and value as the same. Now scan the second array and check whether it exists in the hash table or not. If it exists, then return the pair of elements. Otherwise, continue until we reach the end of the set. Time complexity, O, because we are doing 2 scans. Space complexity, O for hash table. We can select the small set for creating the hash table. Problem 13. Give an algorithm to remove the specified characters from a given string, which are given in another string. Solution, for simplicity, let us assume that the maximum number of different characters is 256. First, we create an auxiliary array initialized to 0. Scan the characters to be removed, and for each of those characters, we set the value to 1, which indicates that we need to remove that character. After initialization, scan the input string, and for each of the characters, we check whether that character needs to be deleted or not. If the flag is set, then we simply skip to the next character, otherwise we keep the character in the input string. Continue this process until we reach the end of the input string. All these operations we can do in place as given below. Void remove chars, char remove these chars, int srcln day, distinct, int auxi, additional array for auxi equal to 0, set true for all characters to be removed, srcindex equal to 0, while auxi equal to 1, srcind plus plus, copy chars unless it must be removed, srcind destined equal to 0, while if str equal to str. Time complexity, time for scanning the characters to be removed, plus time for scanning the input array equal to O plus O, approximately equal to O, where m is the length of the characters to be removed and n is the length of the input string. Space complexity, O, length of the characters to be removed. But since we are assuming the maximum number of different characters is 256, we can treat this as a constant. But we should keep in mind that when we are dealing with multi-byte characters, the total number of different characters is much more than 256. Problem -14, give an algorithm for finding the first non-repeated character in a string. For example, the first non-repeated character in the string abstab is z. Solution, the solution to this problem is trivial. For each character in the given string, we can scan the remaining string if that character appears in it. If it does not appear, then we are done with the solution and we return that character. If the character appears in the remaining string, then go to the next character. Char first non-repeated char, if return str, found the first non-repeated character. Time complexity O for 2 for loops. Space complexity O. Problem -15. Can we improve the time complexity of problem 13? Solution, yes. By using hash tables, we can reduce the time complexity. Create a hash table by reading all the characters in the input string and keeping count of the number of times each character appears. After creating the hash table, we can read the hash table entries to see which element has a count equal to 1. This approach takes O space, but reduces the time complexity also to O char, first non-repeated char using hash printf. Time complexity, we have O to create the hash table and another O to read the entries of hash table. So the total time is O plus O equal to O, approximately equal to O. Space complexity, O for keeping the count values. Problem -16 given a string, give an algorithm for finding the first repeating letter in a string. Solution. The solution to this problem is somewhat similar to problem 13 and problem 15. The only difference is, instead of scanning the hash table twice, we can give the answer in just one scan. This is because while inserting into the hash table, we can see whether that element already exists or not. If it already exists, then we just need to return that character. Char, first repeated char using hash else count, plus if printf return 0. Time complexity, we have O for scanning and creating the hash table. Note that we need only one scan for this problem. So the total time is O. Space complexity, O for keeping the count values. Problem -17, given an array of n numbers, create an algorithm which displays all pairs whose sum is S. Solution, this problem is similar to problem 12, but instead of using two sets, we use only one. Set, algorithm. Scan the elements of the input array one by one and create a hash table. Both key and value can be the same. After creating the hash table, again scan the input array and check whether exits in the hash table or not. If it exits, then return the pair of elements. Otherwise, continue and read all the elements of the array. Time complexity, we have O to create the hash table and another O to read the entries of the hash table. So the total time is O plus O equal to O, approximately equal to O. Space complexity, O for keeping the count values. Problem 18. Is there any other way of solving problem 17? Solution, yes. The alternative solution to this problem involves sorting. First, sort the input array. After sorting, use two pointers, one at the starting and another at the ending. Each time add the values of both the indexes and see if their sum is equal to S. If they are equal, then print that pair. Otherwise, increase the left pointer if the sum is less than S, and decrease the right pointer if the sum is greater than S. Time complexity, time for sorting plus time for scanning equal to O plus O, approximately equal to O. Space complexity, O. Problem 19. We have a file with millions of lines of data. Only 2 lines are identical, the rest are unique. Each line is so long that it may not even fit in the memory. What is the most efficient solution for finding the identical lines? Solution, since a complete line may not fit into the main memory, read the line partially and compute the hash from that partial line. Then read the next part of the line and compute the hash. This time use the previous hash also while computing the new hash value. Continue this process until we find the hash for the complete line. Do this for each line and store all the hash values in a file. If at any point you get same hash value, read the corresponding lines part by part and compare. Note, refer to searching chapter for related problems. Problem -20 if h is the hashing function and is used to hash n keys into a table of sizes where n less than equal to s, the expected number of collisions involving a particular key x is less than 1, less than n, less than s, n less than 2. Solution, A. Problem -21 implement Bloom filters. Solution, a Bloom filter is a data structure designed to tell, rapidly and memory efficiently, whether an element is present in a set. It is based on a probabilistic mechanism where false positive retrieval results are possible, but false negatives are not. At the end, we will see how to tune the parameters in order to minimize the number of false positive results. Let's begin with a little bit of theory. The idea behind the Bloom filter is to allocate a bit vector of length m, initially all set to 0, and then choose k independent hash functions h1, h2, hk, each with range. When an element A is added to the set, then the bits at positions h1, h2, hk, and the bit vector are set to 1. Given a query element q, we can test whether it is in the set using the bits at positions h1, h2, hk in the vector. If any of these bits is 0, we report that q is not in the set, otherwise we report that q is. The thing we have to care about is that in the first case, there remains some probability that q is not in the set, which could lead us to a false positive response. Type edef, unsigned int, struct bloom in bloom array size, unsigned char bloom array, int n hash functions, hash function pointer funcs array, hashtag define set bloom bit, hashtag define get bloom bit, and struct bloom create bloom, return null, if char bit, size ef4, if %blm bloom array size, return 0, return 1, unsigned int shifted 0 hash, unsigned int h0, while h to the power of h5, plus plus key plus plus, return h, unsigned int hash, unsigned int h0, hash underscore th equal to 0, while h, key plus plus. 1 1 1. Return h, nt test return -1, if close, while if, printf, p star talk, delete bloom, return 1. String algorithms, chapter 15. 15.1 Introduction. To understand the importance of string algorithms, let us consider the case of entering the URL in any browser. You will observe that after typing the prefix of the URL, a list of all possible URLs is displayed. That means the browsers are doing some internal processing and giving us the list of matching URLs. This technique is sometimes called auto-completion. Similarly, consider the case of entering the directory name in the command line interface. After typing the prefix of the directory name, if we press the tab button, we get a list of all matched directory names available. This is another example of auto-completion. In order to support these kinds of operations, we need a data structure which stores the string data efficiently. In this chapter, we will look at the data structures that are useful for implementing string algorithms. We start our discussion with the basic problem of strings. Given a string, how do we search a substring? This is called a string matching problem. After discussing various string matching algorithms, we will look at different data structures for storing strings. 15.2 String matching algorithms. In this section, we concentrate on checking whether a pattern P is a substring of another string T or not. Since we are trying to check a fixed string P, sometimes these algorithms are called exact string matching algorithms. To simplify our discussion, let us assume that the length of given text T is n, and the length of the pattern P, which we are trying to match, has the length m. That means T has the characters from 0 to n, 1, and P has the characters from 0 to m1. This algorithm is implemented in C++ as str. In the subsequent sections, we start with the brute force method and gradually move towards better algorithms. Brute force method. Robin-Karp string matching algorithm. String matching with finite automata. KMP algorithm. Boyer-Moore algorithm. Suffix trees. 15.3 brute force method. In this method, for each possible position in the text T, we check whether the pattern P matches or not. Since the length of T is n, we have n plus 1 possible choices for comparisons. This is because we do not need to check the last m, 1 locations of T, as the pattern length is m. The following algorithm searches for the first occurrence of a pattern string P in a text string T. Algorithm. Int brute force string match, int n, int p, int m. 4, int j equal to 0, equal to while equal to T. jj plus 1. If return -1, return I. Time complexity, O times m, approximately equal to O. Space complexity, O, or a bean carp string matching algorithm. In this method, we will use the hashing technique, and instead of checking for each possible position in T, we check only if the hashing of P and the hashing of M characters of T give the same result. Initially, apply the hash function to the first M characters of T, and check whether this result and P's hashing result is the same or not. If they are not the same, then go to the next character of T, and again apply the hash function to M characters. If they are the same, then we compare those M characters of T with P selecting hash function. At each step, since we are finding the hash of M characters of T, we need an efficient hash function. If the hash function takes O complexity in every step, then the total complexity is O. This is worse than the brute force method because first we are applying the hash function and also comparing. Our objective is to select a hash function which takes O complexity for finding the hash of M characters of T every time. Only then can we reduce the total complexity of the algorithm. If the hash function is not good, the complexity of the Rabin-Karp algorithm is O times M, approximately equal to O. If we select a good hash function, the complexity of the Rabin-Karp algorithm complexity is O. Now let us see how to select a hash function which can compute the hash of M characters of T at each step in O. For simplicity, let's assume that the characters used in string T are only integers. That means all characters in Thai. Since all of them are integers, we can view a string of M consecutive characters as decimal numbers. For example, string 61,815 corresponds to the number 61815. With the above assumption, the pattern P is also a decimal value, and let us assume that the decimal value of P is P. For the given text T, let T denote the decimal value of length M substring T for I equal to 0, 1, in M1. So T equal to P if and only if T equal to P. We can compute P in O time using Horner's rule as the code for the above assumption is value equal to 0 for value equal to value 10, value equal to value plus P. We can compute all T for I equal to 0, 1, n, m, 1 values in a total of O me. The value of Tn be similarly computed from T, O me. To compute the remaining values T, understand that T can be computed from T in constant time. For example, if T equal to 123,456 and M equal to 3. T10 plus 4 equal to 234 if T. Step-by-step explanation. First, remove the first digit, 123 to 101 equal to 23. Second, multiply by 10 to shift it, 23 times 10 equal to 230. Third, add last digit, 230 plus 4 equal to 234. The algorithm runs by comparing T with P. When T equal to P, then we have found the substring PT, starting from position 1, in 15.5 string matching with finite automata. In this method, we use the finite automata, which is the concept of the theory of computation. Before looking at the algorithm, first let us look at the definition of finite automata. Finite automata. A finite automaton F is a 5-tuple, where Q is a finite set of states, QOQ is the start state, ACQ is a set of accepting states, sigma is a finite input alphabet, S is the transition function that gives the next state for a given current state and input. How does finite automata work? The finite automaton F begins in state QO, reads characters from sigma one at a time. If F is in state Q and reads input character A, F moves to state. At the end, if its state is an A, then we say F accepted the input string read so far. If the input string is not accepted, it is called the rejected string. Example, let us assume that Q equal to, sigma equal to, as shown in the transition table diagram. This accepts strings that end in an odd number of A's. For example, ABRA is accepted, AA is rejected. Input. Important notes for constructing the finite automata. For building the automata, first we start with the initial state. The FA will be in state K if K characters of the pattern have been matched. If the next text character is equal to the pattern character C, we have matched K plus 1 characters, and the FA enters state K plus 1. If the next text character is not equal to the pattern character, then the FA go to a state 0, 1, 2, or K, depending on how many initial pattern characters match the text characters ending with C, matching algorithm. Now, let us concentrate on the matching algorithm. For a given pattern P, first we need to build a finite automaton F. Oh, the state set is Q equal to. Oh, the start state is 0. Oh, the only accepting state is M. Oh, time to build F can be large if sigma is large. Scan the text string T to find all occurrences of the pattern P. String matching is efficient. Each character is examined exactly once constant time for each character, but the time to compute 8 is O. This is because has O entries. If we assume sigma is constant, then the complexity becomes O. Algorithm. Input, pattern string P, 6 and F. Goal. All valid shifts displayed finite automata string matcher, int M, F8, 9 equal to 0 for 9 to 8, if print EF. Time complexity. O, 15.6 KMP algorithm. As before, let us assume that T is the string to be searched and P is the pattern to be matched. This algorithm was presented by Knuth, Morris, and Pratt. It takes O time complexity for searching a pattern. To get O time complexity, it avoids the comparisons with elements of T that were previously involved in comparison with some element of the pattern P. The algorithm uses a table, and in general we call it prefix function, or prefix table, or fail function F. First we will see how to fill this table and later how to search for a pattern using this table. The prefix function, F for a pattern, stores the knowledge about how the pattern matches against shifts of itself. This information can be used to avoid useless shifts of the pattern P. It means that this table can be used for avoiding backtracking on the string T. Prefix table, int F. Assume F is a global array void prefix table, int M, int I equal to 1, j equal to 0, f equal to 0, while if equal to p, f equal to j plus 1, I plus plus, j plus plus, else, if else, j equal to f equal to 0, I plus plus. As an example, assume that p equal to b, a, ACA. For this pattern, let us follow the step-by-step instructions for filling the prefix table f. Initially, m equal to length equal to 7, f equal to 0, and f equal to 0. Step 2, j equal to 0, f equal to 1. Step 3, j equal to 1, f equal to 2. Step 4, I equal to 4, j equal to 2, f equal to 3. Step 5, j equal to 1, f equal to 1. At this step, the filling of the prefix table is complete. Matching algorithm. The KMP algorithm takes pattern P, string T, and prefix function F as input, and finds a match of P and T. Int KMP, int N, int P, int M, else if JF, else I++, return -1. Time complexity, O, where M is the length of the pattern, and N is the length of the text to be searched. Space complexity, O. Now, to understand the process, let us go through an example. Assume that t equal to bakba, baba, bakaka, and pia, babaka. Since we have already filled the prefix table, let us use it and go to the matching algorithm. Initially, n equal to size of t equal to 15, m equal to size of p equal to 7. Step 1, I equal to 0, j equal to 0, comparing p with t. P does not match with p. P will be shifted one position to the right. Step 2, I equal to 1, j equal to 0, comparing p with t. P matches with t. Since there is a match, p is not shifted. Step 3, I equal to 2, j equal to 1, comparing p with t. P does not match with t. Backtracking on p, comparing p and t. Step 4, I equal to 3, j equal to 0, comparing p with t. P does not match with t. Step 5, I equal to 4, j equal to 0, comparing p with t. P matches with t. Step 6, I equal to 5, j equal to 1, comparing p with t. P matches with t. Step 7, I6, j equal to 2, comparing p with t. P matches with t. Step 8, 7, j equal to 3, comparing p with t. P matches with 7. Step 9, I equal to 8, j equal to 4, comparing p with t. P matches with t. Step 10, I equal to 9, j equal to 5, comparing p with t. P does not match with t. Backtracking on p, comparing p with t, because after mismatch, equal to f equal to 3, comparing p with t. Step 11, I equal to 10, j equal to 4, comparing p with t. P matches with t. Step 12, I equal to 11, j equal to 5, comparing p with t. P matches with t. Step 13, I equal to 12, j equal to 6, comparing p with t. P matches with t. Pattern p has been found to completely occur in string t. The total number of shifts that took place for the match to be found are I, m equal to 13 minus 7 equal to 6 shifts. Notes. KMP performs the comparisons from left to right. KMP algorithm needs a pre-processing which takes O space and time complexity. Searching takes O time complexity. Point 7 Boyer-Moore algorithm. Like the KMP algorithm, this also does some pre-processing, and we call it last function. The algorithm scans the characters of the pattern from right to left, beginning with the rightmost character. During the testing of a possible placement of pattern P in T, a mismatch is handled as follows. Let us assume that the current character being matched is T equal to C, and the corresponding pattern character is P. If C is not contained anywhere in P, then shift the pattern P completely past T. Otherwise, shift P until an occurrence of character C in P is aligned with T. This technique avoids needless comparisons by shifting the pattern relative to the text. The last function takes O time. Therefore, the worst case running time of the Boyer-Moore algorithm is O. This indicates that the worst case running time is quadratic, in the case of n equal to m, the same as the brute force algorithm. The Boyer-Moore algorithm is very fast on the large alphabet. For the small alphabet, Boyer-Moore is not preferable. For binary strings, the KMP algorithm is recommended. For the very shortest patterns, the brute force algorithm is better. 15.8 data structures for storing strings. If we have a set of strings and a word which we want to search in that set, in order to perform the search operation faster, we need an efficient way of storing the strings. To store sets of strings, we can use any of the following data structures. Hashing tables, binary search trees, tries, ternary search trees, 15.9 hash tables for strings. As seen in the hashing chapter, we can use hash tables for storing the integers or strings. In this case, the keys are nothing but the strings. The problem with hash table implementation is that we lose the ordering information. After applying the hash function, we do not know where it will map to. As a result, some queries take more time. For example, to find all the words starting with the letter K. With hash table representation, we need to scan the complete hash table. This is because the hash function takes the complete key, performs hash on it, and we do not know the location of each word. 15.10 binary search trees for strings. In this representation, every node is used for sorting the strings alphabetically. This is possible because the strings have a natural ordering, A comes before B, which comes before C, and so on. This is because words can be ordered and we can use a binary search tree to store and retrieve them. For example, let us assume that we want to store the following strings using BSTs. This is a career monk string. For the given string, there are many ways of representing them in BST. One such possibility is shown in the tree below. Issues with binary search tree representation. This method is good in terms of storage efficiency, but the disadvantage of this representation is that at every node, the search operation performs the complete match of the given key with the node data, and as a result, the time complexity of the search operation increases. So, from this we can say that BST representation of strings is good in terms of storage, but not in terms of time. 15.11 tries. Now, let us see the alternative representation that reduces the time complexity of the search operation. The name try is taken from the word tree. What is a try? A tray is a tree, and each node in it contains the number of pointers equal to the number of characters of the alphabet. For example, if we assume that all the strings are formed with English alphabet characters A to Z, then each node of the tree contains 26 pointers. A try data structure can be declared as struct tree node char data contains the current node character. Int isend of string indicates whether the string formed from root 2, current node is a string or not struct tree node child, pointers to other try nodes. Suppose we want to store the strings A, all, ALS, and as. Tree for these strings will look like character. Why tries? The tries can insert and find strings in O time. This is much faster than hash table and binary search tree representations. Tray declaration. The structure of the tree node has data, isend string, and has a collection of child nodes. It also has one more method called subnode. This method takes a character as argument and will return the child node of that character type if that is present. The basic element, tree node of a try data structure looks like this. Struct tree node int isend of string, struct tree node child, struct tree node try node subnode. For if data equal to C, return root child, return null. Now that we have defined our try node, let's go ahead and look at the other operations of tree. Fortunately, the tree data structure is simple to implement since it has two major methods, insert and search. Let's look at the elementary implementation of both these methods. Inserting a string in try. To insert a string, we just need to start at the root node and follow the corresponding path. Once we reach the null pointer, we just need to create a skew of tail nodes for the remaining characters of the given string. Void insert in tree if return if struct tree node new node equal to malloc new node data word for new node child equal to null. If new node is end string equal to 1, else new node child equal to insert in try word plus 1, return new node root child insert in tree word plus 1, return root. Time complexity, where L is the length of the string to be inserted. Note, for real dictionary implementation, we may need a few more checks such as checking whether the given string is already there in the dictionary or not. Searching a string in try. The same as the case with the search operation, we just need to start at the root and follow the pointers. The time complexity of the search operation is equal to the length of the given string that want to search. int search and try, if return -1, if return 1, else return -1, if return search and tree, word +1, else return -1, time complexity O, where L is the length of the string to be searched. Issues with tries representation. The main disadvantage of tries is that they need a lot of memory for storing the strings. As we have seen above, for each node we have too many node pointers. In many cases, the occupancy of each node is less. The final conclusion regarding tries data structure is that they are faster but require huge memory for storing the strings. Note, there are some improved tries representations called trie compression techniques. But even with those techniques, we can reduce the memory only at the leaves and not at the internal nodes. 15.12 Ternary search trees. This representation was initially provided by John Bentley and Sedgwick. A ternary search tree takes the advantages of binary search trees and tries. That means it combines the memory efficiency of BSTs and the time efficiency of tries. Ternary search trees declaration. Struct TST node, char data, data I send off string, int I send off string, struct TST node left, struct TST node EQ, 779 data equal to data data struct TST node right. The ternary search tree uses 3 pointers. The left pointer points to the TST containing all the strings which are alphabetically less than data. The right pointer points to the TST containing all the strings which are alphabetically greater than data. The EQ pointer points to the TST containing all the strings which are alphabetically equal to data. That means if we want to search for a string, and if the current character of the input string and the data of current node in TST are the same, then we need to proceed to the next character in the input string and search it in the subtree which is pointed by EQ. Inserting strings in ternary search tree. For simplicity, let us assume that we want to store the following words in TST: boats, boat, bat, and bats. Initially, let us start with the boat string. B. Now if we want to insert the string boat, then the TST becomes, now let us insert the next string, bat. Now let us insert the final word, bats. Based on these examples, we can write the insertion algorithm as below. We will combine the insertion operation of BST and tries. Struct TST node insert in TST, root malloc, root data equal to word, root isendov string equal to 1, equal to root left, root EQ, equal to root right, equal to null if root left insert in T, equal to else if, equal to if, root EQ insert in TST, else root isendov string equal to 1, equal to else root right insert in TST, return root. Time complexity O, where L is the length of the string to be inserted. Searching in ternary search tree. If after inserting the words we want to search for them, then we have to follow the same rules as that of binary search. The only difference is, in case of match, we should check for the remaining characters instead of return. Also, like BSTs, we will see both recursive and non-recursive versions of the search method. ENT search in TST recursive, return -1. Time complexity O, where L is the length of the string to be searched. Displaying all words of ternary search tree. If we want to print all the strings of TST, we can use the following algorithm. If we want to print them in sorted order, we need to follow the in-order traversal of TST. Char word void display all words, E++, display all words, finding the length of the largest word in TST. This is similar to finding the height of the BST and can be found as int max length of largest word in TST. If return 0, return max length of largest word in TST, +1, max length of largest word in TST. 15.13, comparing BSTs, tries, and TSTs. Hash table and BST implementation stores complete the string at each node. As a result, they take more time for searching, but they are memory efficient. TSTs can grow and shrink dynamically, but hash tables resize only based on load factor. TSTs can display the words in sorted order, but in hash tables we cannot get the sorted order. TSTs allow partial search, whereas BSTs and hash tables do not support it. Tries perform search operations very fast, but they take huge memory for storing the string. TSTs combine the advantages of BSTs and tries. That means they combine the memory efficiency of BSTs and the time efficiency of tries. 15.1 for suffix trees. Suffix trees are an important data structure for strings. With suffix trees, we can answer the queries very fast, but this requires some pre-processing and construction of a suffix tree. Even though the construction of a suffix tree is complicated, it solves many other string-related problems in linear time. Note, suffix trees use a tree for one string, whereas hash tables, BSTs, tries, and TSTs store a set of strings. That means a suffix tree answers the queries related to one string. Let us see the terminology we use for this representation. Prefix and suffix. Given a string t equal to t1, t2. Trademark. The prefix of t is a string t1, t, where I can take values from 1 to n. For example, if t equal to banana, then the prefixes of t are b, ba, ban, bana, banan, banana. Similarly, given a string t equal to t12, t, the suffix of t is a string t, where I can take values from n to 1. For example, if t equal to banana, then the suffixes of t are a, na, ana, nana, anana, banana. Observation. From the above example, we can easily see that for a given text t in pattern p, the exact string matching problem can also be defined as find a suffix of t such that p is a prefix of this suffix, or find a prefix of t such that p is a suffix of this prefix. Example, let the text to be searched be t equal to ACBKBC and the pattern BP equal to KKB. For this example, p is a prefix of the suffix KKBAC and also a suffix of the prefix ACBKB. What is a suffix tree? In simple terms, the suffix tree for text t is a tree-like data structure that represents the suffixes of t. The definition of suffix trees can be given as a suffix tree for an n-character string t is a rooted tree with the following properties. A suffix tree will contain n leaves which are numbered from 1 to n. Each internal node should have at least 2 children. Each edge in a tree is labeled by a non-empty substring of t. No 2 edges of a node begin with the same character. The paths from the root to the leaves represent all the suffixes of t. The construction of suffix trees. Algorithm. 1. Let S be the set of all suffixes of t. Append $ to each of the suffixes. Sort the suffixes in S based on their first character. 2, 3. For each group SC. S group has only one element, then create a leaf node. Otherwise, find the longest common prefix of the suffixes in SC group, create an internal node, and recursively continue with step 2, S being the set of remaining suffixes from S after splitting off the longest common prefix. For better understanding, let us go through an example. Let the given text be t equal to tatat. For this string, give a number to each of the suffixes. Now sort the suffixes based on their initial characters. In the 3 groups, the first group has only one element. So as per the algorithm, create a leaf node for it as shown below. Now we have to remove the longest common prefix from the S2 and S3 group elements. Now, for S2 and S3, let us find the longest prefix in the group, and the result is shown below. For S2 and S3, create internal nodes, and the edge contains the longest common prefix of those groups. Our next step is solving S2 and S3 recursively. First, let us take S2. In this group, if we sort them based on their first character, it is easy to see that the first group contains only one element $, and the second group also contains only one element $. Since both groups have only one element, we can directly create leaf nodes for them. At this step, both S1 and S2 elements are done, and the only remaining group is S3. As similar to earlier steps, in the S3 group, if we sort them based on their first character, it is easy to see that there is only one element in the first group, and it is $. For S3 remaining elements, remove the longest common prefix. In the S3 second group, there are two elements, $, and $. We can directly add the leaf nodes for the first group element $. Let us add S3 subtree as shown below. Now, S3 contains two elements. If we sort them based on their first character, it is easy to see that there are only two elements, and among them, one is $, and other is $. We can directly add the leaf nodes for them. Let us add S3 subtree as shown below. Since there are no more elements, this is the completion of the construction of the suffix tree for string t equal to ... The time complexity of the construction of a suffix tree using the above algorithm is O, where n is the length of the input string because there are n distinct suffixes. The longest has length n, the second longest has length n1, and so on. Note, there are O algorithms for constructing suffix trees. To improve the complexity, we can use indices instead of string for branches. Applications of suffix trees. All the problems below on strings can be solved with suffix trees very efficiently. Exact string matching, given a text t and a pattern p, how do we check whether p appears in t or not? Longest repeated substring, given a text t, how do we find the substring of t that is the maximum repeated substring? Longest palindrome, given a text t, how do we find the substring of t that is the longest palindrome of t? Longest common substring, given two strings, how do we find the longest common substring? Longest common prefix, given two strings x and y, how do we find the longest common prefix? How do we search for a regular expression in given text t? Given a text t and a pattern p, how do we find the first occurrence of p in t? 15.15 String algorithms, problems and solutions. Problem 1, given a paragraph of words, give an algorithm for finding the word which appears the maximum number of times. If the paragraph is scrolled down, give the maximum occurring word. Thus, it should be dynamic. Solution, for this problem we can use a combination of priority queues and tries. We start by creating a tree in which we insert a word as it appears and at every leaf of tree. Its node contains that word along with a pointer that points to the node in the heap which we also create. This heap contains nodes whose structure contains a counter. This is its frequency and also a pointer to that leaf of tree, which contains that word so that there is no need to store the word twice. Whenever a new word comes up, we find it in tree. If it is already there, we increase the frequency of that node in the heap corresponding to that word, and we call it hepify. This is done so that at any point of time we can get the word of maximum frequency. While scrolling, when a word goes out of scope, we decrement the counter in heap. If the new frequency is still greater than 0, hepify the heap to incorporate the modification. If the new frequency is 0, delete the node from heap and delete it from tree. Problem -2, given two strings, how can we find the longest common substring? Solution, let us assume that the given two strings are t1 and t2. The longest common substring of two strings, t1 and t2, can be found by building a generalized suffix tree for t1 and t2. That means we need to build a single suffix tree for both the strings. Each node is marked to indicate if it represents a suffix of t1 or t2 or both. This indicates that we need to use different marker symbols for both the strings. After constructing the common suffix tree, the deepest node marked for both t1 and t2 represents the longest common substring. Another way of doing this is we can build a suffix tree for the string t1 $t2 hashtag. This is equivalent to building a common suffix tree for both the strings. Time complexity O, where m and n are the lengths of input strings t1 and t2. Problem 3, longest palindrome, given a text t. How do we find the substring of t, which is the longest palindrome of t? Solution, the longest palindrome of t can be found in no time. The algorithm is, first build a suffix tree for t $reverse hashtag or build a generalized suffix tree for t in reverse. After building the suffix tree, find the deepest node marked with both $ and hashtag. Basically, it means find the longest common substring. Problem -4, given a string, give an algorithm for finding the next word in the dictionary. Solution, let us assume that we are using try for storing the dictionary words. To find the next word in tries, we can follow a simple approach as shown below. Starting from the rightmost character, increment the characters one by one. Once we reach Z, move to the next character on the left side. Whenever we increment, check if the word with the incremented character exists in the dictionary or not. If it exists, then return the word, otherwise increment again. If we use TST, then we can find the in-order successor for the current word. Problem -5, give an algorithm for reversing a string. Solution, if the str is editable char reversing string, char temp start end, if return str, for, n++, end, for equal to temp str, str equal to str, str equal to temp, return str. Time complexity, O, where n is the length of the given string. Space complexity, O. Problem -6. If the string is not editable, how do we create a string that is the reverse of the given string? Solution, if the string is not editable, then we need to create an array and return the pointer of that. If str is a const string char reversing string temp ptr, 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 ptr equal to temp, return ptr. Time complexity, OO, where n is the length of the given string. Space complexity, O. Problem -7. Can we reverse the string without using any temporary variable? Solution, yes. We can use XOR logic for swapping the variables. Char reversing string int start 0 and strlen -1, while str to the power equal to str to the power of equal to str plus start, and return str. Time complexity, OO, where n is the length of the given string. Space complexity, O. Problem -8, given a text and a pattern, give an algorithm for matching the pattern in the text. Assume, and are the wildcard characters. Solution, brute force method. For efficient method, refer to the theory section. int pattern matching, if return 1, if return p equal to 0. If return pattern matching or a pattern matching, if return pattern matching or a pattern matching, if return pattern matching, return -1. Length of the text and n is the length of the pattern. Space complexity, O. Problem 9. Give an algorithm for reversing words in a sentence. Example, input. This is a career monk string. Output, string monk career A is this. Solution, start from the beginning and keep on reversing the words. The below implementation assumes that is the delimiter for words in given sentence. Void reverse words in sentences, void reversing string, in start, in end for temp equal to str, str equal to str, stir start equal to temp. Time complexity, O approximately equal to O, where n is the length of the string. Space complexity, O problem -10 permutations of a string. Give an algorithm for printing all possible permutations of the characters in a string. Unlike combinations, two permutations are considered distinct if they contain the same characters but in a different order. For simplicity, assume that each occurrence of a repeated character is a distinct character. That is, if the input is AAA, the output should be 6 repetitions of AAA. The permutations may be output in any order. Solution: the solution is reached by generating n strings, each of length n, where n is the length of the input string. Void permutations. Problem 11. Combinations. Combinations of a string. Unlike permutations, two combinations are considered to be the same if they contain the same characters, but may be in a different order. Give an algorithm that prints all possible combinations of the characters in a string. For example, AC and AB are different combinations from the input string ABC, but AB is the same as BA. Solution: the solution is achieved by generating nr strings, each of length between 1 and n, where n is the length of the given input string. Algorithm. For each of the input characters A, B, if there are any remaining characters, generate combinations with those remaining characters. Put the current character in output string and print it. Void combinations: int length equal to strlen for combination original, combination equal to 0, print ef, if combinations. Problem 12. Given a string ABCBCBA, give an algorithm for recursively removing the adjacent characters if they are the same. For example, ABCBCBA and then ABC BACBA. Solution: first we need to check if we have a character pair. If yes, then cancel it. Now check for next character and previous element. Keep canceling the characters until we either reach the start of the array, reach the end of the array, or don't find a pair. Void remove adjacent pairs while equal to str and I++ jstr equal to str, cancel pairs. Problem -13. Given a set of characters chars and a input string input, find the minimum window in str which will contain all the characters in chars in complexity O. For example, input equal to abacb and chars equal to aab has the minimum window BA. Solution: this algorithm is based on the sliding window approach. In this approach, we start from the beginning of the array and move to the right. As soon as we have a window which has all the required elements, try sliding the window as far right as possible with all the required elements. If the current window length is less than the minimum length found until now, update the minimum length. For example, if the input array is a BACBA and the minimum window should cover characters AAB, then the sliding window will move like this. 2. 1. Make an integer array should find of len 256. Each element of this array will have the count of how many times we need to find the element of ASCII value I. Make another array has found of 256 elements, which will have the count of the required elements found until now. 3. Count less than equal to 0, 4 while input. A. If input element is not to be found, continue. B. If input element is required equal to increase count by 1. C. If count is length of char's array, slide the window as much right as possible. D. If current window length is less than min length found until now, update min length. Hashtag define max 256. Void min length window chars in T should find equal to, has found equal to, in J equal to 0, C and T 0, start 0, finish min window. Int max in charlen strlen, iplen strlen, 4 should find, finish equal to iplen, 4, or plus equal to 1, if continue, has found input plus equal to 1, if greater than equal to has found, C and T plus plus, if, while equal to 0 or has found, should find input, if has found, should find input, J plus plus has found, if, min window I, J plus 1, finish equal to I, start equal to J, print F. Complexity: if we walk through the code, I and J can traverse at most n steps, where n is the input. Size: in the worst case, adding to a total of 2n times. Therefore, time complexity is O. Problem 14. We are given a 2D array of characters and a character pattern. Give an algorithm to find if the pattern is present in the 2D array. The pattern can be in any order, but we can't use the same character twice while matching. Return 1 if match is found, 0 if not. For example, find Microsoft in the below matrix. Solution: manually finding the solution of this problem is relatively intuitive. We just need to describe an algorithm for it. Ironically, describing the algorithm is not the easy part. How do we do it manually? First, we match the first element, and when it is matched, we match the second element in the 8 neighbors of the first match. We do this process recursively, and when the last character of the input pattern matches, return true. During the above process, take care not to use any cell in the 2D array twice. For this purpose, you mark every visited cell with some sign. If your pattern matching fails at some point, start matching from the beginning in the remaining cells. When returning, you unmark the visited cells. Let's convert the above intuitive method into an algorithm. Since we are doing similar checks for pattern matching every time, a recursive solution is what we need. In a recursive solution, we need to check if the substring passed is matched in the given matrix or not. The condition is not to use the already used cell, and to find the already used cell, we need to add another 2D array to the function. Also, we need the current position of the input matrix from where we need to start. Since we need to pass a lot more information than is actually given, we should be having a wrapper function to initialize the extra information to be passed. Algorithm: if we are past the last character in the pattern, return true. If we get a used cell again, return false if we got past the 2D matrix. Return false if searching for first element and cell doesn't match. Find match with next cell in row first order. Otherwise, if character matches, mark this cell as used. Res find match with next position of pattern in 8 neighbors, mark this cell as unused. Return res. Otherwise, return false. Hashtag define max 100 boolean fin match wrapper, sharpat, int in row, int n col. Return find match, level index till which pattern is matched, and xy, current position in 2D array boolean find match. Sharpat int used or int x int y int in row int ncol int level. If pattern matched equal to return true. If return false if equal to pat undan level equal to 0 if return find match. Next element in same row else ifly return find match. First element from same column else return false. Else if pat equal to boolean res used 1, marking this cell as used. Finding subpattern in 8 neighbors res false or find match false or find match false or and find match false or and y greater than 0. Find match false or find match false or false used equal to 0 return res else return false, marking this cell as unused. Problem 15. Given 2 strings, str and str, write a function that prints all interleavings of the given 2 strings. We may assume that all characters in both strings are different. Example: input, str equal to ab, str equal to cd, and output, abcd, acbd, acdb, cab. If cd or cd, an interleaved string of given 2 strings preserves the order of characters in individual strings. For example, in all the interleavings of above first example, a comes before b, and c comes before d. Solution: let the length of str be m, and the length of str be n. Let us assume that all characters in str and str are different. Let count be the count of all interleaved strings in such strings. The value of count can be written as following. To print all interleavings, we can first fix the first character of strl in output string and recursively call for str and str. And then we can fix the first character of str and recursively call for str and str. Void print interleavings. Base case, if all characters of str and str have been included in output string, then print the output string if print f. If some characters of str are left to be included, then include the first character from the remaining characters and recur for rest if istr equal to str, print interleavings. If some characters of str are left to be included, then include the first character from the remaining characters and recur for rest if istr equal to str, print interleavings. Allocates memory for output string and uses print interleavings for printing all interleavings void print. Allocate memory for the output string char istr equal to malloc sizef. Set the terminator for the output string istr equal to 0. Print all interleavings using print interleavings print interleavings. Free. Problem -16 given a matrix with size nxn containing random integers. Give an algorithm which checks whether rows match with a column or not. For example, if ith row matches with jth column and ith row contains the elements, then one column would also contain the elements. Solution, we can build a trie for the data in the columns. Then we can compare the rows with the tree. This would allow us to exit as soon as the beginning of a row does not match any column. Also, this would let us check a row against all columns in one pass. If we do not want to waste memory for empty pointers, then we can further improve the solution by constructing a suffix tree. Problem -17, write a method to replace all spaces in a string with %20. Assume string has sufficient space at end of string to hold additional characters. Solution, find the number of spaces. Then, starting from n, replace the characters. Starting from n reduces the overwrites. Void encode space with string char space equal to %20, int string length equal to strlen, if. Time complexity, O. Space complexity, O. Here, we do not have to worry about the space needed for extra characters. Problem 18, running length encoding. Write an algorithm to compress the given string by using the count of repeated characters, and if new corn press string length is not smaller than the original string, then return the original string. Solution, with extra space of O. String compress string char last input star dot t in size 0 count equal to 1 equal to char temp string str for I++ if else count plus etoa str plus equal to last str plus equal to temp last equal to input star dot t count equal to 1 str plus last plus temp. If the compressed string size is greater than input string, return input string. If greater than equal to input star length, return input star, else return str. Time complexity, O. Space complexity, O, but it uses a temporary array of size 2 without extra space. Char compress string if return current char last char compress string length index 1 counter index if else counter plus input stir equal to last char for length e plus input stir num to string got at counter equal to 1 return current char. Time complexity, O. Space complexity, O. Algorithms design techniques chapter 16. 16.1 Introduction. In the previous chapters, we have seen many algorithms for solving different kinds of problems. Before solving a new problem, the general tendency is to look for the similarity of the current problem to other problems for which we have solutions. This helps us in getting the solution easily. In this chapter, we will see different ways of classifying the algorithms, and in subsequent chapters, we will focus on a few of them. 16.2 Classification. There are many ways of classifying algorithms, and a few of them are shown below. Implementation method, design method. Other classifications. 16.3 Classification by implementation method. Recursion or iteration. A recursive algorithm is one that calls itself repeatedly until a base condition is satisfied. It is a common method used in functional programming languages like C, C++, etc. Iterative algorithms use constructs like loops and sometimes other data structures like stacks and queues to solve the problems. Some problems are suited for recursive and others are suited for iterative. For example, the Towers of Hanoi problem can be easily understood in recursive implementation. Every recursive version has an iterative version and vice versa. Procedural or declarative. In declarative programming languages, we say what we want without having to say how to do it. With procedural programming, we have to specify the exact steps to get the result. For example, SQL is more declarative than procedural because the queries don't specify the steps to produce the result. Examples of procedural languages include C, PHP, and Perl. Serial or parallel or distributed. In general, while discussing the algorithms, we assume that computers execute one instruction at a time. These are called serial algorithms. Parallel algorithms take advantage of computer architectures to process several instructions at a time. They divide the problem into subproblems and serve them to several processors or threads. Iterative algorithms are generally parallelizable. If the parallel algorithms are distributed onto different machines, then we call such algorithms distributed algorithms. Deterministic or non-deterministic. Deterministic algorithms solve the problem with a predefined process, whereas non-deterministic algorithms guess the best solution at each step through the use of heuristics. Exact or approximate. As we have seen, for many problems we are not able to find the optimal solutions. That means the algorithms for which we are able to find the optimal solutions are called exact algorithms. In computer science, if we do not have the optimal solution, we give approximation algorithms. Approximation algorithms are generally associated with NP-hard problems. 16.4 Classification by design method. Another way of classifying algorithms is by their design method. Greedy method. Greedy algorithms work in stages. In each stage, a decision is made that is good at that point, without bothering about the future consequences. Generally, this means that some local best is chosen. It assumes that the local best selection also makes for the global optimal solution. Divide and conquer. The DNC strategy solves a problem by 1. Divide, breaking the problem into subproblems that are themselves smaller instances of the same type of problem. 2. Recursion, recursively solving these subproblems. 3. Conquer, appropriately combining their answers. Examples. Merge sort and binary search algorithms. Dynamic programming. Dynamic programming and memoization work together. The difference between DP and divide and conquer is that in the case of the latter, there is no dependency among the subproblems, whereas in DP, there will be an overlap of subproblems. By using memoization, DP reduces the exponential complexity to polynomial complexity, etc. for many problems. The difference between dynamic programming and recursion is in the memoization of recursive calls. When subproblems are independent and if there is no repetition, memoization does not help, hence dynamic programming is not a solution for all problems. By using memoization, dynamic programming reduces the complexity from exponential to polynomial, linear programming. In linear programming, there are inequalities in terms of inputs and maximizing some linear function of the inputs. Many problems can be discussed using linear programming. Reduction. In this method, we solve a difficult problem by transforming it into a known problem for which we have asymptotically optimal algorithms. In this method, the goal is to find a reducing algorithm whose complexity is not dominated by the resulting reduced algorithms. For example, the selection algorithm for finding the median in a list involves first sorting the list and then finding out the middle element in the sorted list. These techniques are also called transform and conquer. 16.5 other classifications. Classification by research area. In computer science, each field has its own problems and needs efficient algorithms. Examples: search algorithms, sorting algorithms, merge algorithms, numerical algorithms, graph algorithms, string algorithms, geometric algorithms, combinatorial algorithms, machine learning, cryptography, parallel algorithms, data compression algorithms, parsing techniques, and more. Classification by complexity. In this classification, algorithms are classified by the time they take to find a solution based on their input size. Some algorithms take linear time complexity, and others take exponential time, and some never halt. Note that some problems may have multiple algorithms with different complexities. Randomized algorithms. A few algorithms make choices randomly. For some problems, the fastest solutions must involve randomness. Example: quicksort, branch and bound enumeration and backtracking. These were used in artificial intelligence, and we do not need to explore these fully. For the backtracking method, refer to the recursion and backtracking chapter. Note, in the next few chapters we discuss the greedy, divide and conquer, and dynamic programming design methods. These methods are emphasized because they are used more often than other methods to solve problems. 17.1 Introduction. Let us start our discussion with simple theory that will give us an understanding of the greedy technique. In the game of chess, every time we make a decision about a move, we have to also think about the future consequences, whereas in the game of tennis, our action is based on the immediate situation. This means that in some cases, making a decision that looks right at that moment gives the best solution, but in other cases it doesn't. The greedy technique is best suited for looking at the immediate situation. 17.2 Greedy strategy. Greedy algorithms work in stages. In each stage, a decision is made that is good at that point, without bothering about the future. This means that some local best is chosen. It assumes that a local good selection makes for a global optimal solution. 17.3 Elements of greedy algorithms. The two basic properties of optimal greedy algorithms are 1. Greedy choice property. 2. Optimal substructure, greedy choice property. This property says that the globally optimal solution can be obtained by making a locally optimal solution. The choice made by a greedy algorithm may depend on earlier choices but not on the future. It iteratively makes one greedy choice after another and reduces the given problem to a smaller one. Optimal substructure. A problem exhibits optimal substructure if an optimal solution to the problem contains optimal solutions to the subproblems. That means we can solve subproblems and build up the solutions to solve larger problems. 17.4 Does greedy always work? Making locally optimal choices does not always work. Hence, greedy algorithms will not always give the best solutions. We will see particular examples in the problem section and in the dynamic programming chapter. 17 Have advantages and disadvantages of greedy method. The main advantage of the greedy method is that it is straightforward, easy to understand, and easy to code. In greedy algorithms, once we make a decision, we do not have to spend time re-examining the already computed values. Its main disadvantage is that for many problems, there is no greedy algorithm. That means, in many cases, there is no guarantee that making locally optimal improvements in a locally optimal solution gives the optimal global solution. 17.6 Greedy applications. Sorting, selection sort, topological sort, priority queues, heap sort, Huffman coding compression algorithm, Prim's and Kruskal's algorithms, shortest path in weighted graph, coin change problem, fractional knapsack problem, disjoint sets union by size and union by height, job scheduling algorithm. Greedy techniques can be used as an approximation algorithm for complex problems. 17.7 Understanding greedy technique. For better understanding, let us go through an example. Huffman coding algorithm. Definition. Given a set of n characters from the alphabet A and their associated frequency for a q, find a binary code for each character C, E, A, such that sigma C euro A for a q binary code or is minimum, where binary code represents the length of binary code of character C. That means the sum of the lengths of all character codes should be minimum. The basic idea behind the Huffman coding algorithm is to use fewer bits for more frequently occurring characters. The Huffman coding algorithm compresses the storage of data using variable length codes. We know that each character takes 8 bits for representation, but in general, we do not use all of them. Also, we use some characters more frequently than others. When reading a file, the system generally reads 8 bits at a time to read a single character. But this coding scheme is inefficient. The reason for this is that some characters are more frequently used than other characters. Let's say that the character E is used 10 times more frequently than the character Q. It would then be advantageous for us to instead use a 7-bit code for E and a 9-bit code for Q, because that could reduce our overall message length. On average, using Huffman coding on standard files can reduce them anywhere from 10% to 30% depending on the character frequencies. The idea behind the character coding is to give longer binary codes for less frequent characters and groups of characters. Also, the character coding is constructed in such a way that no two character codes are prefixes of each other. An example. Let's assume that after scanning a file we find the following character frequencies. Given this, create a binary tree for each character that also stores the frequency with which it occurs. The algorithm works as follows. In the list, find the two binary trees that store minimum frequencies at their nodes. Connect these two nodes at a newly created common node that will store no character but will store the sum of the frequencies of all the nodes connected below it. So our picture looks like this. Repeat this process until only one tree is left. Once the tree is built, each leaf node corresponds to a letter with a code. To determine the code for a particular node, traverse from the root to the leaf node. For each move to the left, append a 0 to the code, and for each move to the right, append a 1. As a result, for the above generated tree, we get the following codes. Calculating bits saved. Now, let us see how many bits that Huffman coding algorithm is saving. All we need to do for this calculation is see how many bits are originally used to store the data, and subtract from that the number of bits that are used to store the data using the Huffman code. In the above example, since we have 6 characters, let's assume each character is stored with a 3-bit code. Since there are 133 such characters, the total number of bits used is 3 times 133 equal to 399. Using the Huffman coding frequencies, we can calculate the new total number of bits used. Huffman coding algorithm, int n, temp malloc, equal to temp left delete min, temp right delete min, temp data, temp left data plus temp right data, insert temp to pq, return pq. Time complexity, since there will be one build underscore heap, two n to do delete underscore mins, and n to inserts on a priority queue that never has more than n elements. Refer to the priority queues chapter for details. 17.8 Greedy algorithms, problems, and solutions. Problem -1, given an array f with size n. Assume the array content f indicates the length of the ith file and we want to merge all these files into one single file. Check whether the following algorithm gives the best solution for this problem or not. Algorithm, merge the files contiguously. That means select the first two files and merge them. Then select the output of the previous merge and merge with the third file, and keep going. Note, given two files A and B with sizes m and n, the complexity of merging is O. Solution, this algorithm will not produce the optimal solution. For a counterexample, let us consider the following file sizes array. As per the above algorithm, we need to merge the first two files, and as a result we get the following list of files. In the list below, 15 indicates the cost of merging two files with sizes 10 and 5. Similarly, merging 15 with the next file 100 produces. For the subsequent steps, the list becomes, finally, the total cost of merging equal to cost of all merging operations equal to 15 plus 115 plus 165 plus 185 plus 200 plus 115 plus is optimal or not, consider the order. For this example, following the same approach, the total cost of merging equal to 15 plus 30 plus 50 plus 100 plus 200 equal to 395. So, the given algorithm is not giving the best solution. Problem -2, similar to problem 1. Does the following algorithm give the optimal solution? Algorithm, merge the files in pairs. That means after the first step, the algorithm produces the n2 intermediate files. For the next step, we need to consider these intermediate files and merge them in pairs and keep going. Note, sometimes this algorithm is called two-way merging. Instead of two files at a time, if we merge k files at a time, then we call it k-way merging. Solution, this algorithm will not produce the optimal solution, and consider the previous example for a counterexample. As per the above algorithm, we need to merge the first pair of files, the second pair of files, and the third pair of files. As a result, we get the following list of files. Similarly, merge the output in pairs and this step produces. Finally, the total cost of merging equal to cost of all merging operations equal to 15 plus 150 plus 35 plus 165 plus 185 equal to 50. This is much more than 395. So, the given algorithm is not giving the best solution. Problem -3. In problem 1, what is the best way to merge all the files into a single file? Solution, using the greedy algorithm, we can reduce the total time for merging the given files. Let us consider the following algorithm. Algorithm 1. Store file sizes in a priority queue. The key of elements are file lengths. 2. Repeat the following until there is only one file. A. Extract two smallest elements x and y. B. Merge x and y and insert this new file in the priority queue. Variant of same algorithm. 1. Sort the file sizes in ascending order. 2. Repeat the following until there is only one file. A. Take the first two elements x and y. B. Merge x and y and insert this new file in the sorted list. To check the above algorithm, let us trace it with the previous example. The given array is, as per the above algorithm. After sorting the list, it becomes, we need to merge the two smallest files, and as a result, we get the following list of files. In the list below, 15 indicates the cost of merging two files with sizes 10 and 5. Similarly, merging the two smallest elements produces. For the subsequent steps, the list becomes merging 20 and 30, merging 20 and 30. Finally, the total cost of merging equal to cost of all merging operations equal to 15 plus 30 plus 50 plus 100 plus 200 equal to cost of all merging operations equal optimal solution for this merging problem. Time complexity, time using heaps to find best merging pattern, plus the optimal cost of merging the files. Problem 4, interval scheduling algorithm, given a set of n intervals s equal to. Let us assume that we want to find a maximum subset S of S such that no pair of intervals in S overlaps. Check whether the following algorithm works or not. Algorithm. While, select the interval I that overlaps the least number of other intervals. Add to final solution, set S. Remove all intervals from S that overlap with I. Solution. This algorithm does not solve the problem of finding a maximum subset of non-overlapping intervals. Consider the following intervals. The optimal solution is, however, the interval that overlaps with the fewest others is C, and the given algorithm will select C first, MC and K. Problem -5 in problem 4, if we select the interval that starts earliest, does it give the optimal solution? Solution, no, it will not give the optimal solution. Let us consider the example below. It can be seen that the optimal solution is 4, whereas the given algorithm gives 1. Optimal solution, given algorithm gives. Problem 6. In problem 4, if we select the shortest interval, does it give the optimal solution? Solution, this also will not give the optimal solution. Let us consider the example below. It can be seen that the optimal solution is 2, whereas the algorithm gives 1. Optimal solution, current algorithm gives. Problem -7 for problem 4, what is the optimal solution? Solution. Now, let us concentrate on the optimal greedy solution. Algorithm. Sort intervals according to the rightmost ends for every consecutive interval. If the leftmost end is after the rightmost end of the last selected interval, then we select this interval. Otherwise, we skip it and go to the next interval. Time complexity equal to time for sorting plus time for scanning equal to O equal to O. Consider the following problem. Problem -8. Input S equal 2 of intervals. The interval we can treat as A. Request for a room for a class with time start to time ND. Output. Find an assignment of classes to rooms that uses the fewest number of rooms. Consider the following iterative algorithm. Assign as many classes as possible to the first room, then assign as many classes as possible to the second room, then assign as many classes as possible to the third room, etc. Does this algorithm give the best solution? Note, in fact, this problem is similar to the interval scheduling algorithm. The only difference is the application. Solution. This algorithm does not solve the interval coloring problem. Consider the following intervals. A, B, C, D, E, F, G. Maximizing the number of classes in the first room results in having in one room, and classes A, D, and E each in their own rooms for a total of 4. The optimal solution is to put A in one room, in another, and in another for a total of 3 rooms. Problem -9 for problem -8, consider the following algorithm. Process the classes in increasing order of start times. Assume that we are processing class C. If there is a room R such that R has been assigned to an earlier class, and C can be assigned to R without overlapping previously assigned classes, then assign C to R. Otherwise, put C in a new room. Does this algorithm solve the problem? Solution. This algorithm solves the interval coloring problem. Note that if the greedy algorithm creates a new room for the current class C, then because it examines classes in order of start times, C, start point must intersect with the last class in all of the current rooms. Thus, when greedy creates the last room, N, it is because the start time of the current class intersects with N, one other classes. But we know that for any single point in any class, it can only intersect with at most S other class, so it must then be that NS. As S is a lower bound on the total number needed, and greedy is feasible, it is thus also optimal. Note, for optimal solution, refer to problem 7, and for code, refer to problem 10. Problem -10. Suppose we are given two arrays start and finish listing the start and finish times of each class. Our task is to choose the largest possible subset xie so that for any pair I, j, I, x either start finish or start finish. Solution. Our aim is to finish the first class as early as possible because that leaves us with the most remaining classes. We scan through the classes in order of finish time, and whenever we encounter a class that doesn't conflict with the latest class so far, then we take that class. int largest tasks, int n, in finish, sort finish, rearrange start to match, count equal to 1, x equal to 1, for, if finish, count plus 1, x. This algorithm clearly runs in O time due to sorting. Problem -11. Consider the making change problem in the country of India. The input to this problem is an integer m. The output should be the minimum number of coins to make m rupees of change. In India, assume the available coins are 1,510,202,550 rupees. Assume that we have an unlimited number of coins of each type. For this problem, does the following algorithm produce the optimal solution or not? Take as many coins as possible from the highest denominations. So for example, to make change for 234 rupees, the greedy algorithm would take 4 50 rupee coins, 1 25 rupee coin, 1 5 rupee coin, and 4 1 rupee coins. Solution. The greedy algorithm is not optimal for the problem of making change with the minimum number of coins when the denominations are 15,102,025 and 50. In order to make 40 rupees, the greedy algorithm would use 3 coins of 2,510 and 5 rupees. The optimal solution is to use 2 20 shilling coins. Note, for the optimal solution, refer to the dynamic programming chapter. Problem 12. Let us assume that we are going for a long drive between cities A and B. In preparation for our trip, we have downloaded a map that contains the distances in miles between all the petrol stations on our route. Assume that our car's tanks can hold petrol for n miles. Assume that the value n is given. Suppose we stop at every point. Does it give the best solution? Solution. Here the algorithm does not produce optimal solution. Obvious reason, filling at each petrol station does not produce optimal solution. Problem 13 for problem 12. Stop if and only if you don't have enough petrol to make it to the next gas station, and if you stop, fill the tank up all the way. Prove or disprove that this algorithm correctly solves the problem. Solution. The greedy approach works. We start our trip from A with a full tank. We check our map to determine the farthest petrol station on our route within n miles. We stop at that petrol station, fill up our tank, and check our map again to determine the farthest petrol station on our route within n miles from this stop. Repeat the process until we get to B. Note, for code, refer to dynamic programming chapter. Problem 14, fractional knapsack problem. Given items T, 1T. T, with associated weights S1, S2. S and benefit values Vx, V2, Vn. How can we maximize the total benefit considering that we are subject to an absolute weight limit C? Solution. Algorithm. 1. Compute value per size density for each item D. 2. Sort each item by its value density. 3. Take as much as possible of the density item not already in the bag. Equal to VI silicon. Time complexity, O for sorting, and O for greedy selections. Note, the items can be entered into a priority queue and retrieved one by one until either the bag is full or all items have been selected. This actually has a better runtime of O, where C is the number of items that actually get selected in the solution. There is a savings in runtime if C equal to O, but otherwise there is no change in the complexity. Problem 15, number of railway platforms. At a railway station, we have a timetable with the train's arrivals and departures. We need to find the minimum number of platforms so that all the trains can be accommodated as per their schedule. Example, the timetable is as given below. The answer is 3. Otherwise, the railway station will not be able to accommodate all the trains. Solution. Let's take the same example as described above. Calculating the number of platforms is done by determining the maximum number of trains at the railway station at any time. First, sort all the arrival and departure times in an array. Then, save the corresponding arrivals and departures in the array also. After sorting, our array will look like this. Now modify the array by placing 1 for A and -1 for D. The new array will look like this. Finally, make a cumulative array out of this. 1, 2, 1, 23, 2, 1, 0. Our solution will be the maximum value in this array. Here it is 3. Note, if we have a train arriving and another departing at the same time, then put the departure time first in the sorted array. Problem -16. Consider a country with very long roads and houses along the road. Assume that the residents of all houses use cell phones. We want to place cell phone towers along the road, and each cell phone tower covers a range of 7 kilometers. Create an efficient algorithm that allows for the fewest cell phone towers. Solution. The algorithm to locate the least number of cell phone towers. 1. Start from the beginning of the road. 2. Find the first uncovered house on the road. 3. If there is no such house, terminate this algorithm. Otherwise, go to next step. 4. Locate a cell phone tower 7 miles away after we find this house along the road. 5. Go to step 2. Problem 17, preparing songs cassette. Suppose we have a set of N songs and want to store these on a tape. In the future, users will want to read those songs from the tape. Reading a song from a tape is not like reading from a disc. First, we have to fast forward past all the other songs, and that takes a significant amount of time. Let it be an array listing the lengths of each song, specifically song I has length A. If the songs are stored in order from 1 to N, then the cost of accessing the KTH song is. The cost reflects the fact that before we read song K, we must first scan past all the earlier songs on the tape. If we change the order of the songs on the tape, we change the cost of accessing the songs, with the result that some songs become more expensive to read, but others become cheaper. Different song orders are likely to result in different expected costs. If we assume that each song is equally likely to be accessed, which order should we use if we want the expected cost to be as small as possible? Solution. The answer is simple. We should store the songs in the order from shortest to longest. Storing the short songs at the beginning reduces the forwarding times for the remaining jobs. Problem -18. Let us consider a set of events at Hightex. Assume that there are n events where each takes 1 unit of time. Event I will provide a profit of p rupees greater than 0 if started at or before time t. where t is an arbitrary number. If an event is not started by t, then there is no benefit in scheduling it at all. All events can start as early as time 0. Give the efficient algorithm to find a schedule that maximizes the profit. Solution. Algorithm. Sort the jobs according to floor. Let time t be the current time being considered. All jobs y, where floor equal to t, are inserted into a priority queue with the profit g, used as the key. A delete max is performed to select the job to run at time t. Then t is decremented and the process is continued. Clearly the time complexity is O. The sort takes O and there are at most n insert and delete max operations performed on the priority queue, each of which takes O time. Problem 19. Let us consider a customer care server with n customers to be served in the queue. For simplicity, assume that the service time required by each customer is known in advance, and it is W 1 minute for customer on. So if, for example, the customers are served in order of increasing I, then the ITH customer has to 2 to 1 wait, W, minutes. The total waiting time of all customers can be given as J equal to 1I1 equal to W. What is the best way to serve the customers so that the total waiting time can be reduced? Solution. This problem can be easily solved using greedy technique. Since our objective is to reduce the total waiting time, what we can do is select the customer whose service time is less. That means if we process the customers in the increasing order of service time, then we can reduce the total waiting time. Time complexity. O. Divide and conquer algorithms. Chapter 18. 18.1 Introduction. In the greedy chapter, we have seen that for many problems, the greedy strategy failed to provide optimal solutions. Among those problems, there are some that can be easily solved by using the divide and conquer technique. Divide and conquer is an important algorithm design technique based on recursion. The D and C algorithm works by recursively breaking down a problem into 2 or more subproblems of the same type until they become simple enough to be solved directly. The solutions to the subproblems are then combined to give a solution to the original problem. 18.2. What is divide and conquer strategy? The D and C strategy solves a problem by divide, breaking the problem into subproblems that are themselves smaller instances of the same type of problem. 2. Recursion, recursively solving these subproblems. 3. Conquer, appropriately combining their answers. 18.3. Does divide and conquer always work? It's not possible to solve all the problems with the divide and conquer technique. As per the definition of D and C, the recursion solves the subproblems which are of the same type. For all problems, it is not possible to find the subproblems which are the same size, and D and C is not a choice for all problems. 18.4 Divide and conquer visualization. For better understanding, consider the following visualization. Assume that n is the size of the original problem. As described above, we can see that the problem is divided into subproblems with each of size nb. We solve the subproblems recursively and combine their solutions to get the solution for the original problem. Divide and conquer. If P is very small so that a solution is obvious, return solution, divide the problem P into K subproblems P1, P2, PK, return, divide and conquer, divide and conquer. 18.5 Understanding divide and conquer. For a clear understanding of DC, let us consider a story. There was an old man who was a rich farmer and had 7 sons. He was afraid that when he died, his land and his possessions would be divided among his 7 sons, and that they would quarrel with one another. So he gathered them together and showed them 7 sticks that he had tied together and told them that anyone who could break the bundle would inherit everything. They all tried, but no one could break the bundle. Then the old man untied the bundle and broke the sticks one by one. The brothers decided that they should stay together and work together and succeed together. The moral for problem solvers is different. If we can't solve the problem, divide it into parts and solve one part at a time. In earlier chapters, we have already solved many problems based on D and C strategy, like binary search, merge sort, quicksort, etc. Refer to those topics to get an idea of how D and C works. Below are a few other real-time problems which can easily be solved with D and C strategy. For all these problems, we can find the subproblems which are similar to the original problem. Looking for a name in a phone book, we have a phone book with names in alphabetical order. Given a name, how do we find whether that name is there in the phone book or not? Breaking a stone into dust. We want to convert a stone into dust. Finding the exit in a hotel, we are at the end of a very long hotel lobby with a long series of doors with one door next to us. We are looking for the door that leads to the exit. Finding our car in a parking lot. 18.6 Advantages of divide and conquer. Solving difficult problems. D and C is a powerful method for solving difficult problems. As an example, consider the Tower of Hanoi problem. This requires breaking the problem into subproblems, solving the trivial cases, and combining the subproblems to solve the original problem. Dividing the problem into subproblems so that subproblems can be combined again is a major difficulty in designing a new algorithm. For many such problems, D and C provides a simple solution. Parallelism. Since D and C allows us to solve the subproblems independently, this allows for execution in multiprocessor machines, especially shared memory systems where the communication of data between processors does not need to be planned in advance, because different subproblems can be executed on different processors. Memory access. D and C algorithms naturally tend to make efficient use of memory caches. This is because once a subproblem is small, all its subproblems can be solved within the cache without accessing the slower main memory. 18.7 Disadvantages of divide and conquer. One disadvantage of the D and C approach is that recursion is slow. This is because of the overhead of the repeated subproblem calls. Also, the D and C approach needs stack for storing the calls. Actually, this depends upon the implementation style. With large enough recursive base cases, the overhead of recursion can become negligible for many problems. Another problem with D and C is that for some problems, it may be more complicated than an iterative approach. For example, to add n numbers, a simple loop to add them up in sequence is much easier than a D and C approach that breaks the set of numbers into 2 halves, adds them recursively, and then adds the sums. 18.8 Master Theorem. As stated above, in the D and C method, we solve the subproblems recursively. All problems are generally defined in terms of recursive definitions. These recursive problems can easily be solved using Master Theorem. For details on Master Theorem, refer to the Introduction to Analysis of Algorithms chapter. Just for continuity, let us reconsider the Master Theorem. If the recurrence is of the form t equal to at plus o, where a greater than or equal to 1, b greater than 1, k greater than or equal to o, and p is a real number, then the complexity can be directly given as. If a bk, then t equal to o1. 2, if a equal to bk. b, if p equal to -1, then t equal to. c, if p less than -1, then t equal to. 3, if a bk. a, if p greater than 0, then t equal to o. If p less than 0, then t equal to o. 18.9 Divide and conquer applications. Binary search, merge sort and quicksort, median finding, min and max finding, matrix multiplication, closest pair problem. 18.10. Divide and conquer problems and solutions. Problem 1. Let us consider an algorithm A, which solves problems by dividing them into 5 subproblems of half the size, recursively solving each subproblem, and then combining the solutions in linear time. What is the complexity of this algorithm? N. As per the description, the algorithm divides the problem into 5 subproblems with each of size 2, so we need to solve 5 trillion subproblems. After solving these subproblems, the given array is scanned to combine these solutions. The total recurrence algorithm for this problem can be given as t equal to 5 trillions plus O. Using the master theorem, we get the complexity O approximately equal to O approximately equal to O. Solution. Let us assume that the input size is n, and t defines the solution to the given problem. Problem -2. Similar to problem 1, an algorithm B solves problems of size n by recursively solving 2 subproblems of size n, 1, and then combining the solutions in constant time. What is the complexity of this algorithm? Solution. Let us assume that the input size is n, and t defines the solution to the given problem. As per the description of algorithm, we divide the problem into 2 subproblems with each of size n, so we have to solve 2 trillion subproblems. After solving these subproblems, the algorithm takes only a constant time to combine these solutions. The total recurrence algorithm for this problem can be given as, using master theorem, we get the complexity as O equal to O. Problem -3n. Again, similar to problem 1, another algorithm C solves problems of size n by dividing them into 9 subproblems of size 3, recursively solving each subproblem, and then combining the solutions in O time. What is the complexity of this algorithm? Solution. Let us assume that input size is n, and t defines the solution to the given problem. As per the description of algorithm, we divide the problem into 9 subproblems with each of size 3, so we need to solve 97 subproblems. After solving the subproblems, the algorithm takes n, quadratic time to combine these solutions. The total recurrence algorithm for this problem can be given as t equal to 9 trillions plus O. Using D and C master theorem, we get the complexity as O. Problem -4, write a recurrence and solve it. Void function, if, printf, function. Solution. Let us assume that input size is n and t defines the solution to the given problem. As per the given code, after printing the character and dividing the problem into 2 subproblems with each of size and solving them. So we need to solve 2 trillion subproblems. After solving these subproblems, the algorithm is not doing anything for combining the solutions. The total recurrence algorithm for this problem can be given as, using master theorem, we get the complexity as O approximately equal to 0 equal to O. Problem -5 given an array, give an algorithm for finding the maximum and minimum. Solution. Refer selection algorithms chapter. Problem 6 discuss binary search and its complexity. Solution. Refer searching chapter for discussion on binary search. Analysis. Let us assume that input size is n, and t defines the solution to the given problem. The elements are in sorted order. In binary search, we take the middle element and check whether the element to be searched is equal to that element or not. If it is equal, then we return that element. If the element to be searched is greater than the middle element, then we consider the right subarray for finding the element and discard the left subarray. Similarly, if the element to be searched is less than the middle element, then we consider the left subarray for finding the element and discard the right subarray. What this means is, in both the cases, we are discarding half of the subarray and considering the remaining half only. Also, at every iteration, we are dividing the elements into 2 equal halves. As per the above discussion, every time we divide the problem into 2 subproblems with each of size and solve 1 t subproblem. The total recurrence algorithm for this problem can be n2 given as. Using master theorem, we get the complexity as O. Problem -7. Consider the modified version of binary search. Let us assume that the array is divided into 3 equal parts instead of 2 equal parts. Write the recurrence for this ternary search and find its complexity. Solution. From the discussion on problem 5, binary search has the recurrence relation t equal to t plus O. Similar to the problem 5 discussion, instead of 2 in the recurrence relation, we use 3. That indicates that we are dividing the array into 3 subarrays with equal size and considering only one of them. So, the recurrence for the ternary search can be given as, using master theorem, we get the complexity as O approximately equal to O approximately equal to O. Problem 8. In problem 5, what if we divide the array into 2 sets of sizes approximately 1/3 and 2/3? Solution. We now consider a slightly modified version of ternary search in which only one comparison is made, which creates 2 partitions, one of roughly elements and the other of n, 2, and 3. 2 and 3 here, the worst case comes when the recursive call is in the larger element part. So the recurrence corresponding to this worst case is, using master theorem, we get the complexity as O. It is interesting to note that we will get the same result for general k-array search as n approaches infinity. Problem 9 discuss merge sort and its complexity. Solution. Refer to sorting chapter for discussion on merge sort. In merge sort, if the number of elements are greater than 1, then divide them into 2 equal subsets, the algorithm is recursively invoked on the subsets, and the return sorted subsets are merged to provide a sorted list of the original set. The recurrence equation of the merge sort algorithm is, if we solve this recurrence using D and C master theorem, it gives O complexity. Problem 10 discuss quicksort and its complexity. Solution. Refer to sorting chapter for discussion on quicksort. For quicksort, we have different complexities for best case and worst case. Best case in quicksort, if the number of elements is greater than 1, then they are divided into 2 equal subsets, and the algorithm is recursively invoked on the subsets. After solving the subproblems, we don't need to combine them. This is because in quicksort, they are already in sorted order, but we need to scan the complete elements to partition the elements. The recurrence equation of quicksort best case is, if we solve this recurrence using master theorem of D and C gives O complexity. Worst case, in the worst case, quicksort divides the input elements into 2 sets, and one of them contains only 1 element. That means other set has n, 1 elements to be sorted. Let us assume that the input size is n, and t defines the solution to the given problem. So we need to solve t subproblems. But to divide the input into 2 sets, quicksort needs 1 scan of the input elements. After solving these subproblems, the algorithm takes only a constant time to combine these. The total recurrence algorithm for this problem can be given as solutions. This is clearly a summation recurrence equation. So t equal to n2 equal to O. Note, for the average case analysis, refer to sorting chapter. Problem -11, given an infinite array in which the first n cells contain integers in sorted order, and the rest of the cells are filled with some special symbol. Assume we do not know the n value. Give an algorithm that takes an integer k as input and finds a position in the array containing k if such a position exists in O time. Solution. Since we need an O algorithm, we should not search for all the elements of the given list complexity. To get O complexity, one possibility is to use binary search. But in the given scenario, we cannot use binary search as we do not know the end of the list. Our first problem is to find the end of the list. To do that, we can start at the first element and keep searching with doubled index. That means we first search at index 1, then 2, 4, 8. In T, find an infinite series, while mid equal to /2 plus 1, if equal to dollar, r equal to mid, else 1 equal to mid. It is clear that once we've identified a possible interval A in which k might be, its length is at most n, so searching for k using binary search takes O time. Problem 12, given a sorted array of non-repeated integers A, check whether there is an index I for which A equal to I. Give a divide and conquer algorithm that runs in time O. Solution, we can't use binary search on the array as it is. If we want to keep the O property of the solution, we have to implement our own binary search. If we modify the array and subtract I from A, we can then use binary search. The complexity for doing so is O. Problem -13, we are given two sorted lists of size n. Give an algorithm for finding the median element in the union of the two lists. Solution, we use the merge sort process. Use merge procedure of merge sort. Keep track of the count while comparing elements of two arrays. If the count becomes n, we have reached the median. Take the average of the elements at indexes n1 and n in the merged array. Time complexity, O. Problem -14. Can we give the algorithm if the size of the two lists are not the same? Solution, the solution is similar to the previous problem. Let us assume that the lengths of two lists are manned n. In this case, we need to stop when the counter reaches /2. Time complexity, O/2. Problem -15. Can we improve the time complexity of problem 13 to O? Solution, yes, using the DNC approach. Let us assume that the given two lists are LUN and L2. Algorithm. Find the medians of the given sorted input arrays LUN and L2. Assume that those medians are M and M. 2. If M and M are equal, then return M. If M is greater than M, then the final median will be below two subarrays. 3. From first element L1 to M. 4, 5. From M to last element of L2. 6, 7. From M to last element of L1. 8. From first element of L2 to M. 9. Repeat the above process until the size of both the subarrays becomes 2. If M is greater than M, then median is present in one of the two subarrays below. 10. If size of the two arrays is 2, then use the formula below to get the median. Median L2 plus min L2/2. Time complexity, O, since we are considering only half of the input and throwing the remaining half. Problem -16 given an input array A. Let us assume that there can be duplicates in the list. Now search for an element in the list in such a way that we get the highest index if there are duplicates. Solution, refer to searching chapter. Problem -17, discuss Strawson's matrix multiplication algorithm using divide and conquer. That means, given two nxn matrices A and B, compute the n times n matrix C equal to A times B, where the elements of C are given by. Solution, before Strawson's algorithm, first let us see the basic divide and conquer algorithm. The general approach we follow for solving this problem is given below. To determine C, we need to multiply the ith row of A with jth column of B. Initialize C for I equal to 1 to n for J equal to 1 to n for K equal to 1 to nc plus equal to a B. The matrix multiplication problem can be solved with a D and C technique. To implement a D and C algorithm, we need to break the given problem into several subproblems that are similar to the original one. In this instance, we view each of the nxn matrices as a 2 times 2 matrix, the elements of submatrices. So the original matrix multiplication, C equal to A plus B, can be written as, which are 22, equal to B 1.1, B 1.2, times A 2, 2, B 2, 1, B 2, 2, where each Aij by J and Cij is a times matrix. From the given definition of C, we get that the result submatrices can be computed as follows. Here the symbols plus and times are taken to mean addition and multiplication of matrices. Matrix, in order to compute the original nxn matrix multiplication, we must compute 8 x products followed by 4 x matrix sums. Since matrix addition is an O operation, the total running time for the multiplication operation is given by the recurrence. Using master theorem, we get T equal to O. Fortunately, it turns out that one of the 8 matrix multiplications is redundant. Consider the following series of 7x matrices. Each equation above has only one multiplication. 10 additions and 7 multiplications are required to compute MO through M6. Given MO through M6, we can compute the elements of the product matrix C as follows. This approach requires 7 matrix multiplications and 18 times additions. Therefore, the 22 worst case running time is given by the following recurrence. Using master theorem, we get T equal to O equal to O. Problem -18, stock pricing problem. Consider the stock price of careermonk.com in n consecutive days. That means the input consists of an array with stock prices of the company. We know that the stock price will not be the same on all the days. In the input stock prices, there may be dates where the stock is high when we can sell the current holdings, and there may be days when we can buy the stock. Now our problem is to find the day on which we can buy the stock and the day on which we can sell the stock so that we can make maximum profit. Solution, as given in the problem, let us assume that the input is an array with stock prices. Let us say the given array is a day. From this array, we have to find 2 days such a way that we can make maximum profit. Also, another point to make is that the buy date should be before sell date. One simple approach is to look at all possible buy and sell dates. Void stock strategy, int n, int buy date index, int sell data index, int j, profit equal to 0, buy to tell index equal to 0, sell to tell index equal to 0.4, indicates buy date, indicates sell date for if, a profit AA, buy date index equal to I, sell data index equal to j. The two nested loops take n2 computations, so this takes time. Problem 19 for problem 18, can we improve the time complexity? Solution, yes, by opting for the divide and conquer O solution. Divide the input list into 2 parts and recursively find the solution in both the parts. Here, we get 3 cases. Buy to tell index and sell to tell index both are in the earlier time period. Buy to tell index and sell to tell index both are in the later time period. Buy to tell index is in the earlier part and sell to tell index is in the later part of the time period. The first 2 cases can be solved with recursion. The third case needs care. This is because buy to tell index is one side and sell to tell index is on other side. In this case, we need to find the minimum and maximum prices in the 2 subparts, and this we can solve in linear time. Void stock strategy, I int left into right, declare the necessary variables if return mid left plus 2 equal to stock strategy equal to stock strategy, min left min, max right max, profit L max right A if return, else if return, else return. Algorithm stock strategy is used recursively on 2 problems of half the size of the input, and in addition, time is spent searching for the maximum and minimum prices. So the time complexity is characterized by the recurrence T equal to 2 trillions plus O, and by the master theorem, we get O. Problem 20, we are testing unbreakable laptops, and our goal is to find out how unbreakable they really are. In particular, we work in an n-story building and want to find out the lowest floor from which we can drop the laptop without breaking it. Suppose we are given 2 laptops and want to find the highest ceiling possible. Give an algorithm that minimizes the number of tries we need to make f is sublinear, as a linear f yields a trivial solution. Solution: for the given problem, we cannot use binary search, as we cannot divide the problem and solve it recursively. Let us take an example for understanding the scenario. Let us say 14 is the answer. That means we need 14 drops to find the answer. First, we drop from height 14, and if it breaks, we try all floors from 1 to 13. If it doesn't break, then we are left 13 drops, so we will drop it from 14 plus 13 plus 1 equal to 28th floor. The reason being, if it breaks at the 28th floor, we can try all the floors from 15 to 27 in 12 drops. If it did not break, then we are left with 11 drops, and we can try to figure out the floor in 14 drops. From the above example, it can be seen that we first tried with a gap of 14 floors, and then followed by 13 floors, then 12, and so on. So if the answer is k, then we are trying the intervals at k, k1, k. Given that the number of floors is n, we have to relate these two. Since the maximum floor from which we can try is n, the total skip should be less than n. This gives complexity of this process is O. Problem minus 21 given n numbers, check if any two are equal. Solution, refer to searching chapter. Problem 22 given algorithm to find out if an integer is a square. E.g. 16 is, 15 isn't. Solution, initially let us say I equal to 2. Compute the value I times I, and see if it is equal to the given number. If it is equal, then we are done, otherwise increment the I law. Continue this process until we reach I times I greater than or equal to the given number. Time complexity, O, space complexity, 0. Problem 23, given an array of 2 n integers in the following format, AL AA, and BBB, BN. Shuffle the array to a B, a B, a B, and BN without any extra memory. Solution, let us take an example. 1. Start with the array AA, AB, B, B, B. 2. Split the array into 2 halves, A, 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 B, B, B. 3. Exchange elements around the center, exchange AA with BB, you get AA, BB, AA, BB. 4. Split AA, BB into AA, BB, then split AB into AB. 5. Exchange elements around the center for each subarray, you get AL, BAB, and a BAB. Please note that this solution only handles the case when n equal to 2, where I 0, 1, 2, 3, etc. In our example, n equal to 2 to the power of 2 equal to 4, which makes it easy to recursively split the array into 2 halves. The basic idea behind swapping elements around the center before calling the recursive function is to produce smaller size problems. A solution with linear time complexity may be achieved if the elements are of a specific nature. For example, you can calculate the new position of the element using the value of the element itself. This is a hashing technique. Void shuffle array, int1, int r shuffle array, recursively call the function on the left and right, recursively call the function on the right. Time complexity. O. Problem minus 24 nuts and bolts problem. Given a set of n nuts of different sizes and n bolts such that there is a 1-to-1 correspondence between the nuts and the bolts, find for each nut its corresponding bolt. Assume that we can only compare nuts to bolts. Solution, refer to sorting chapter. Problem 25, maximum value, contiguous subsequence, given a sequence of n numbers A. A, give an algorithm for finding a contiguous subsequence A for which the sum of elements in the subsequence is maximum. Example 20 and 7. Solution, divide this input into 2 halves. The maximum contiguous subsequent sum can occur in one of 3 ways. Case 1, it can be completely in the first half. Case 2, it can be completely in the second half. Case 3, it begins in the first half and ends in the second half. We begin by looking at case 3. To avoid the nested loop that results from considering all n2 starting points and n2 ending points independently, replace 2 nested loops with 2 consecutive loops. The consecutive loops, each of size n2, combine to require only linear work. Any contiguous subsequence that begins in the first half and ends in the second half must include both the last element of the first half and the first element of the second half. What we can do in cases 1 and 2 is apply the same strategy of dividing into more halves. In summary, we do the following. 1. Recursively compute the maximum contiguous subsequence that resides entirely in the first half. 2. Recursively compute the maximum contiguous subsequence that resides entirely in the 3. Compute, via 2 consecutive loops, the maximum contiguous subsequence sum that begins in the first half but ends in the second half. Second half 4. Choose the largest of the 3 sums. Int maximum rec, int left, int right, max left border sum, 4 right border sum, plus equal to A if right border sum, max right border sum equal to right border sum, return max, int max subsequent sum, return n greater than 0, maximum rec, 0. The base case cost is 1. The program performs 2 recursive calls plus the linear work involved in computing the maximum sum for case 3. The recurrence relation is using D and C master theorem, we get the time complexity as T equal to O. Note, for an efficient solution, refer to the dynamic programming chapter. Problem 26, closest pair of points, given a set of n points, S equal 2, where pi equal 2. Find the pair of points having the smallest distance among all pairs. Solution, let us assume that we have sorted the points. Since the points are in one dimension, all the points are in a line after we sort them. The complexity of sorting is O. After sorting, we can go through them to find the consecutive points with the least difference. So the problem in one dimension is solved in O time, which is mainly dominated by sorting time. Time complexity, O. Problem minus 27 for problem 26. How do we solve it if the points are in two-dimensional space? Solution, before going to the algorithm, let us consider the following mathematical equation. The above equation calculates the distance between 2 points P1 equal 2 and P equal 2. Brute force solution. Calculate the distances between all the pairs of points. From n points, there are nc2 ways of selecting 2 points. After finding distances for all n2 possibilities, we select the one which is giving the minimum distance, and this takes O. The overall time complexity is O. Problem 28, give O solution for closest pair problem. Solution, to find O solution, we can use the DNC technique. Before starting the divide and conquer process, let us assume that the points are sorted by increasing x coordinate. Divide the points into 2 equal halves based on median of x coordinates. That means the problem is divided into that of finding the closest pair in each of the 2 halves. For simplicity, let us consider the following algorithm to understand the process. Algorithm. 1. Sort the given points in S based on their x coordinates. Partition S into 2 subsets S1 and S2 about the line 1 through median of S. This step is the divide part of the DNC technique. Find the closest pairs in S1 and S2 and call them L and R recursively. 2. Now, steps 4 to 8 form the combining component of the DNC technique. 3. 4. Let us assume that 8 equal to min. 5. Eliminate points that are farther than 8 apart from. 6. Consider the remaining points and sort based on their y-coordinates. L. Scan the remaining points in the y order and compute the distances of each point to all its neighbors that are distanced no more than 2 times 8. That's the reason for sorting. According to y, 8. If any of these distances is less than and then update 8. Line passing through the median point and divides the set into 2 equal parts, combining the results in linear time. Line passing through the median point and divides the set into 2 equal parts. Let 8 equal to min, where L is the solution to first subproblem and R is the solution to second subproblem. The possible candidates for closest pair which are across the dividing line are those which are less than 8 pistons from the line. So we need only the points which are inside the 2 times 8 area across the dividing line as shown in the figure. Now, to check all points within distance 8 from the line, consider the following figure. From the above diagram, we can see that a maximum of 12 points can be placed inside the square with a distance not less than 8. That means we need to check only the distances which are within 11 positions in the sorted list. This is similar to the one above, but with the difference that in the above combining of subproblems, there are no vertical bounds. So we can apply the 12-point box tactic over all the possible boxes in the 2 times 8 area with the dividing line as the middle line. As there can be a maximum of n such boxes in the area, the total time for finding the closest pair in the corridor is O analysis. 1. Step 1 and step 2 take O for sorting and recursively finding the minimum. 2. Step -4 takes O. 3. Step 5 takes O for scanning and eliminating. 4. Step -6 takes O for sorting. 5. Step -7 takes O for scanning. The total complexity, T equal to O plus O plus O plus O plus O approximately equal to O. Problem -29. To calculate Kn, give algorithm and discuss its complexity. Solution. The naive algorithm to compute K is start with 1 and multiply by K until reaching Kn. For this approach, there are n 1 multiplications and each takes constant time giving a O algorithm. But there is a faster way to compute K. For example, note that taking the square of a number needs only 1 multiplication. This way, to compute 924, we need only 5 multiplications instead of 23. int exponential if return 1, else if a equal to exponential, return a k, else a equal to exponential, return aa. Let t be the number of multiplications required to compute kn. For simplicity, assume k equal to 2 to the power of 1 for some greater than or equal to 1. Using master theorem, we get d equal to O. Problem 30, the skyline problem. Given the exact locations and shapes of n rectangular buildings in a 2-dimensional city, there is no particular order for these rectangular buildings. Assume that the bottom of all buildings lie on a fixed horizontal line. The input is a list of triples, 1 per building. A building B1 is represented by the triple where 1 denote the exposition of the left edge and Ri denote the exposition of the right edge, and H denotes the building's height. Give an algorithm that computes the skyline of these buildings, eliminating hidden lines. In the diagram below, there are 8 buildings represented from left to right by the triplets, and the output is a collection of points which describe the path of the skyline. In some versions of the problem, this collection of points is represented by a sequence of numbers P1, P2, W, Pn, such that the point P represents a horizontal line drawn at height P, if I is even, and it represents a vertical line drawn at position P, if I is odd. In our case, the collection of points will be a sequence of P1, P2, Pn pairs of where P represents the H, height of the skyline at position X. In the diagram above, the skyline is drawn with a thick line around the buildings, and it is represented by the sequence of position height pairs. And also, assume that R of the rightmost building can be maximum of 1000. That means the L, CEO, ordinate of left building can be minimum of 1, and R of the rightmost building can be maximum of 1000. Solution. The most important piece of information is that we know that the left and right coordinates of each and every building are non-negative integers less than 1000. Now, why is this important? Because we can assign a height value to every distinct x coordinate where I is between 0 and 9999. Algorithm. Allocate an array for 1000 elements and initialize all of the elements to 0. Algorithm. Rahax. Iterate over all of the buildings, and for every b, building iterate on the range of where 1 is the left, r is the right coordinate of the building b. For every x element of this range, check if h, oxites, that is if building b, is taller than the current height value at position x. If so, replace oxites with high. Once we checked all the buildings, the oxites array stores the heights of the tallest buildings at every position. There is one more thing to do. Convert the oxites array to the expected output format. That is to a sequence of position height pairs. It's also easy. Just map each and every I index to an pair. Hashtag includes sto.h greater than hashtag define max right most building ri 1000 int oxites int skyline brute force int c left h right I prev int right most building re equal to 0 while equal to 203. For if h oxites equal to h, if prev equal to 0, right most building re right. For if printf prev oxites printf return 0. Let's have a look at the time complexity of this algorithm. Assume that n indicates the number of buildings in the input sequence and m indicates the maximum coordinate. From the above code, it is clear that for every new input building, we are traversing from left to right to update the heights. In the worst case, with n equal size buildings, each having 1 equal to 0 left and r equal to m1 right coordinates, that is every building spans over the whole interval. Thus, the running time of setting the height of every position is O. The overall time complexity is O, which is a lot larger than O if mn. Problem -31. Can we improve the solution of the problem? 30. Solution. It would be a huge speed up if somehow we could determine the skyline by calculating the height for those coordinates only where it matters, wouldn't it? Intuition tells us that if we can insert a building into an existing skyline, then instead of all the coordinates the building spans over, we only need to check the height at the left and right coordinates of the building plus those coordinates of the skyline the building overlaps with and may modify. Is merging 2 skylines substantially different from merging a building with a skyline? The answer is, of course, no. This suggests that we use divide and conquer. Divide the input of n buildings into 2 equal sets. Compute the skyline for each set, then merge the 2 skylines. Inserting the buildings one after the other is not the fastest way to solve this problem as we've seen it above. If, however, we first merge pairs of buildings into skylines, then we merge pairs of these skylines into bigger skylines, and then merge pairs of these bigger skylines into even bigger ones, then, since the problem size is halved in every step after long steps, we can compute the final skyline. Class skyline divide and conquer. Result. Push underscore back, 0, return result int mid, 2, vector pair int left skyline equal to get skyline. I. Vector pair int right skyline get skyline, vector pair int and t result equal to Mergasky lines. Return result, vector pair int t Mergasky lines, while and j equal to right skyline. Dot size, else, while, result. Push underscore back I++ return result. N, 0, and b equal to, for example, given two skylines a equal to. Clearly, we merge the list of a's and b's just like in the standard merge algorithm. But in addition to that, we have to decide on the correct height in between these boundary values. We use two variables, current height and current t, to store the current height of the first and the second skyline, respectively. When comparing the head entry of the two skylines, we introduce a new stri whose x-coordinate is the minimum of the entry's x-coordinates, and whose height is the maximum of current height and current height. This algorithm has a structure similar to merge sort, so the overall running time of the divide and conquer approach will be O, Dynamic Programming, Chapter 19. 19.1 Introduction. In this chapter, we will try to solve the problems for which we failed to get the optimal solutions using other techniques. Dynamic programming is a simple technique, but it can be difficult to master. One easy way to identify and solve DP problems is by solving as many problems as possible. The term programming is not related to coding, but it is from literature and means filling tables. 19.2. What is dynamic programming strategy? Dynamic programming and memoization work together. The main difference between dynamic programming and divide and conquer is that in the case of the latter, subproblems are independent, whereas in DP there can be an overlap of subproblems. By using memoization, dynamic programming reduces the exponential complexity to polynomial complexity, etc., for many problems. The major components of DP are: recursion solves subproblems recursively. Memoization stores already computed values in table. Dynamic programming equal to recursion plus memoization. 19.3 Properties of dynamic programming strategy. The two dynamic programming properties which can tell whether it can solve the given problem not are, or optimal substructure. An optimal solution to a problem contains optimal solutions to subproblems. Overlapping subproblems, a recursive solution contains a small number of distinct subproblems repeated many times. 19.4 Can dynamic programming solve all problems? Like greedy and divide and conquer techniques, DP cannot solve every problem. There are problems which cannot be solved by any algorithmic technique. The difference between dynamic programming and straightforward recursion is in memoization of recursive calls. If the subproblems are independent and there is no repetition, then memoization does not help. So dynamic programming is not a solution for all problems. 19.5 Dynamic programming approaches. Basically, there are two approaches for solving DP problems: bottom-up dynamic programming, top-down dynamic programming, bottom-up dynamic programming. In this method, we evaluate the function starting with the smallest possible input argument value, and then we step through possible values, slowly increasing the input argument value. While computing the values, we store all computed values in a table. As larger arguments are evaluated, pre-computed values for smaller arguments can be used. Top-down dynamic programming. In this method, the problem is broken into subproblems. Each of these subproblems is solved, and the solutions remembered, in case they need to be solved. Also, we save each computed value as the final action of the recursive function, and as the first action we check if pre-computed value exists. Bottom-up versus top-down programming. In bottom-up programming, the programmer has to select values to calculate and decide the order of calculation. In this case, all subproblems that might be needed are solved in advance and then used to build up solutions to larger problems. In top-down programming, the recursive structure of the original code is preserved, but unnecessary recalculation is avoided. The problem is broken into subproblems. These subproblems are solved, and the solutions remembered, in case they need to be solved again. Note, some problems can be solved with both the techniques, and we will see examples in the next section. 19.6 Examples of dynamic programming algorithms. Many string algorithms, including longest common subsequence, longest increasing subsequence, longest common substring, edit distance. Algorithms on graphs can be solved efficiently: Bellman-Ford algorithm for finding the shortest distance in a graph, Floyd's all-pair shortest path algorithm, etc., chain matrix multiplication, subset sum, zero first knapsack, traveling salesman problem, and many more. 19.7 Understanding dynamic programming. Before going to problems, let us understand how DP works through examples. Fibonacci series. In Fibonacci series, the current number is the sum of previous two numbers. The Fibonacci series is defined as follows. The recursive implementation can be given as: in T, recursive Fibonacci, if return 0, if return 1, return recursive Fibonacci plus recursive Fibonacci. Solving the above recurrence gives: note for proof, refer to introduction chapter. How does memoization help? Calling fib produces a call tree that calls the function on the same value many times. In the above example, fib was calculated 3 times. If n is big, then many more values of fib are recalculated, which leads to an exponential time algorithm. Instead of solving the same subproblems again and again, we can store the previous calculated values and reduce the complexity. Memoization works like this. Start with a recursive function and add a table that maps the function's parameter values to the results computed by the function. Then if this function is called twice with the same parameters, we simply look up the answer in the table. Improving. Now, we see how DP reduces this problem complexity from exponential to polynomial. As discussed earlier, there are two ways of doing this. One approach is bottom-up. These methods start with lower values of input and keep building the solutions for higher values. int fib, int fib. Check for base cases equal to if return 1, fib equal to 1, fib equal to 1, for fibly minus 1, plus fibla 2, return fib. The other approach is top-down. In this method, we preserve the recursive calls and use the values if they are already computed. The implementation for this is given as: in tfib, in Fibonacci, if return 1, if equal to 0, return fib Fibonacci plus Fibonacci. Note, for all problems, it may not be possible to find both top-down and bottom-up programming solutions. Both versions of the Fibonacci series implementations clearly reduce the problem complexity to O. This is because if a value is already computed, then we are not calling the subproblems again. Instead, we are directly taking its value from the table. Time complexity, O, space complexity, O for table. Further improving, one more observation from the Fibonacci series is: the current value is the sum of the previous two calculations only. This indicates that we don't have to store all the previous values. Instead, if we store just the last two values, we can calculate the current value. The implementation for this is given below. In Fibonacci, into 0, b1, sum, I for sum equal to a plus b, a equal to b, 1 billion equal to sum, return sum. Time complexity, O, space complexity, O. Note, this method may not be applicable for all problems. Observations. While solving the problems using DP, try to figure out the following. See how the problems are defined in terms of subproblems recursively. See if we can use some table to avoid the repeated calculations. Factorial of a number. As another example, consider the factorial problem n is the product of all integers between n and 1. The definition of recursive factorial can be given as n equal to n, 1 equal to 1, 0 equal to 1. This definition can easily be converted to implementation. Here the problem is finding the value of n, and the subproblem is finding the value of. In the recursive case, when n is greater than 1, the function calls itself to find the value of, and multiplies that with n. In the base case, when n is 0 or 1, the function simply returns 1. In fact, if return 1, else if return 1, else. Recursive case, multiply n by factorial, return n fact. The recurrence for the above implementation can be given as t equal to n times t, approximately equal to O time complexity, O, space complexity, O recursive calls need a stack of size n. In the above recurrence relation and implementation, for any n value, there are no repetitive calculations and the factorial function is not getting any benefits with dynamic programming. Now, let us say we want to compute a series of m for some arbitrary value m. Using the above algorithm, for each such call, we can compute it in O, for example, to find both n and m. We can use the above approach, wherein the total complexity for finding n and m is O. Time complexity, O, space complexity, O recursive calls need a stack of size equal to the maximum of m and n. Improving, now let us see how dp reduces the complexity. From the above recursive definition, it can be seen that fact is calculated from fact and n and nothing else. Instead of calling fact every time, we can store the previous calculated values in a table and use these values to calculate a new value. This implementation can be given as, in facto in fact if return 1, else if return 1, already calculated, case else if, equal to 0, return facto, else, recursive case, multiply n by factorial return facto equal to n fact. For simplicity, let us assume that we have already calculated n and want to find m. For finding m, we just need to see the table and use the existing entries if they are already computed. If mn, then we do not have to recalculate m. If mn, then we can use n, and call the factorial on the remaining numbers only. The above implementation clearly reduces the complexity to O. This is because if the fact is already there, then we are not recalculating the value again. If we fill these newly computed values, then the subsequent calls further reduce the complexity. O for table. 19.8 longest common subsequence. Given two strings, string x of length m and string y of length n, find the longest common subsequence, the longest sequence of characters that appear left to right in both strings. For example, if x equal to abcbdab and y equal to bdsaba, the LCS equal 2. We can see there are several optimal solutions. Brute force approach, one simple idea, is to check every subsequence of x to see if it is also a subsequence of y. Checking takes O time, and there are two subsequences of 10th the running time, thus is exponential O and is not good for large sequences. Recursive solution. Before going to DP solution, let us form the recursive solution for this, and later we can add memoization to reduce the complexity. Let's start with some simple observations about the LCS problem. If we have two strings, say abcbdab and bdsaba, and if we draw lines from the letters in the first string to the corresponding letters in the second, no two lines cross. From the above observation, we can see that the current characters of x and y may or may not match. That means, suppose that the two first characters differ. Then it is not possible for both of them to be part of a common subsequence. One or the other will have to be removed. Finally, observe that once we have decided what to do with the first characters of the strings, the remaining subproblem is again a LCS problem on two shorter strings. Therefore, we can solve it recursively. The solution to LCS should find two sequences in x and y, and let us say the starting index of sequence in x is I and the starting index of sequence in y is j. Also, assume that x is a substring of x starting at character 1 and going until the end of x, and that y is a substring of y starting at character j and going until the end of y. Based on the above discussion, here we get the possibilities as described below. Y, 1 plus LCS 1 if x, 2 if x hashtag y, LCS, skipping JTH character of y, 3 if x y, LCS, skipping IDH character of 10th in the first case. If x is equal to y, we get a matching pair and can count it towards the total length of the LCs. Otherwise, we need to skip either EF character of x or GTH character of y and find the longest common subsequence. Now, LCS can be defined as 0, LCS max, LCS, 1 plus LCEs, if I equal to morge equal to n, if x hashtag y, if x equal to y. LCS has many applications. In web searching, if we find the smallest number of changes that are needed to change one word into another. A change here is an insertion, deletion, or replacement of a single character. Initial call, LCS length, int, LCS length, int I, int m, int y, int j, int n. If return 0, else if equal to y, return 1 plus LCS length, else return max LCS length. This is a correct solution, but it is very time consuming. For example, if the two strings have no matching characters, the last line always gets executed, which gives close to O. DP solution, adding memoization. The problem with the recursive solution is that the same subproblems get called many different times. A subproblem consists of a call to LCS length, with the arguments being two suffixes of x and y, so there are exactly possible subproblems. If there are nearly two recursive calls, some of these subproblems must be being solved over and over. The DP solution is to check whenever we want to solve a subproblem whether we've already done it before, so we look up the solution instead of solving it again. Implemented in the most direct way, we just add some code to our recursive solution. To do this, look up the code. This can be given as int LCS length, int m, int y, int n, for LCS equal to 0, for LCS equal to 0, for LCS, matching x to y if equal to y, LCS, plus, we get a matching pair. The other two cases, inserting a gap if LCS equal to LCS, if LCS, return LCS equal to LCS. First, take care of the base cases. We have created an LCS table with one row and one column larger than the length of the two strings. Then run the iterative DP loops to fill each cell in the table. This is like doing recursion backwards, or bottom up. The value of LCs depends on three other values, LCs and LCs, all of which have larger values of I or j. They go through the table in the order of decreasing I and j values. This will guarantee that when we need to fill in the value of LCS, we already know the values of all the cells on which it depends. Time complexity, O, since I takes values from 1 to m, and in j takes values from 1 to n. Space complexity, O. Note, in the above discussion, we have assumed LCS is the length of the LCS with x and yj, n. We can solve the problem by changing the definition as LCS is the length of the LCs with x and. Printing the subsequence, the above algorithm can find the length of the longest common subsequence but cannot give the actual longest subsequence. To get the sequence, we trace it through the table. Start at cell. We know that the value of LC5 was the maximum of 3 values of the neighboring cells, so we simply recompute LC5 and note which cell gave the maximum value. Then we move to that cell, and repeat this until we hit the boundary of the table. Every time we pass through a cell where x equal to y, we have a matching pair and print x. At the end, we will have printed the longest common subsequence in O time. An alternative way of getting path is to keep a separate table for each cell. This will tell us which direction we came from when computing the value of that cell. At the end, we again start at cell and follow these directions until the opposite corner of the table. From the above examples, I hope you understood the idea behind DP. Now let us see more problems which can be easily solved using the DP technique. Note, as we have seen above, in DP the main component is recursion. If we know the recurrence, then converting that to code is a minimal task. For the problems below, we concentrate on getting the recurrence. 19.9 Dynamic Programming, Problems and Solutions. Problem -1, convert the following recurrence to code. T equal to 2. Solution, the code for the given recursive formula can be given as int f in sum equal to 0 if, base case return 2, recursive case for sum plus equal to 2 ff return sum. Problem -2, can we improve the solution to problem 1 using memoization of DP? Solution, yes. Before finding a solution, let us see how the values are calculated. T equal to 2t equal to 2ttt equal to 2tt plus 2ttt equal to 2tt plus 2tt plus 2tt. From the above calculations, it is clear that there are lots of repeated calculations with the same input values. Let us use a table for avoiding these repeated calculations, and the implementation can be given as int f t equal to 2 for t equal to 0 for t plus equal to tt return t, time complexity O, 2 for loops, space complexity O for table. Problem -3, can we further improve the complexity of problem 2? Solution, yes, since all subproblem calculations are dependent only on previous calculations, code can be modified as int f t equal to 2, t equal to 2tt for t equal to t plus 2tt return t. Time complexity O, since only 1 for loop, space complexity O. Problem -4, maximum value. Contiguous subsequence, given an array of n numbers, give an algorithm for finding a contiguous subsequence A for which the sum of elements is maximum. Example, 20 and 7. Solution, input array, A of n numbers. Goal, if there are no negative numbers, then the solution is just the sum of all elements in the given array. If negative numbers are there, then our aim is to maximize the sum. One simple and brute force approach is to see all possible sums and select the one which has maximum value. Int max contiguous sum in n, int maximum equal to 0 for 4, int current sum equal to 0 for current sum plus equal to A if maximum current sum, for each possible start point. For each possible endpoint, return maximum. Time complexity O, space complexity O. Problem -5, can we improve the complexity of problem 4? Solution, yes. One important observation is that if we have already calculated the sum for the subsequence I, j, 1, then we need only one more addition to get the sum for the subsequence I, j. But the problem 4 algorithm ignores this information. If we use this fact, we can get an improved algorithm with a running time O. Int max contiguous sum, int n, int maximum equal to 0, 4, int current sum equal to 0, 4 current sum plus equal to A if 1 return maximum, maximum current sum. Time complexity O, space complexity O. Problem -6, can we solve problem 4 using dynamic programming? Solution, yes. For simplicity, let us say M indicates maximum sum over all windows ending at I. Given array, A, recursive formula considers the case of selecting ith element. A. To find maximum sum, we have to do one of the following and select maximum among them. Either extend the old sum by adding A, or start new window starting with one element A, where M plus A indicates the case of extending the previous sum by adding A and 0 indicates the new window starting at A. Int max contiguous sum, int n equal to int m0, maximum equal to 0, if greater than 0, m equal to A, else m equal to 0, for if plus or greater than 0, else m equal to m plus A, m equal to 0, for if maximum equal to m, return maximum. Time complexity O, space complexity O for table. Problem 7. Is there any other way of solving problem 4? Solution, yes. We can solve this problem without DP too. The algorithm is a little tricky. One simple way is to look for all positive contiguous segments of the array, and keep track of the maximum sum contiguous segment among all positive segments. Each time we get a positive sum, compare it with sum so far and update sum so far if it is greater than sum so far. Let us consider the following code for the above observation. Int max contiguous sum, int n, cementing here plus A, if cementing here equal to 0, continue if sum so far cementing here equal to return sum so far. Note, the algorithm doesn't work if the input contains all negative numbers. It returns 0 if all numbers are negative. To overcome this, we can add an extra check before the actual implementation. The phase will look if all numbers are negative, and if they are, it will return maximum of them. Time complexity O, n, because we are doing only one scan. Space complexity O for table. Problem -8. In problem 7 solution, we have assumed that M indicates maximum sum over all windows ending at I. Can we assume M indicates maximum sum over all windows starting at I and ending at N? Solution, yes. For simplicity, let us say M indicates maximum sum over all windows starting at I. Given array, A, recursive formula considers the case of selecting ith element. A2, find maximum window, we have to do one of the following and select maximum among them. Either extend the old sum by adding A, or start new window starting with one element A, where M plus A indicates the case of extending the previous sum by adding A, and 0 indicates the new window starting at A. Time complexity O, space complexity O for table. Note, for O solution, refer to the divide and conquer chapter. Problem -9, given a sequence of n numbers A, give an algorithm for finding a contiguous subsequence A for which the sum of elements in the subsequence is maximum. Here the condition is we should not select two contiguous numbers. Solution, let us see how DP solves this problem. Assume that M represents the maximum sum from 1 to I numbers without selecting two contiguous numbers. While computing M, the decision we have to make is whether to select the ith element or not. This gives us two possibilities, and based on this we can write the recursive formula A's. The first case indicates whether we are selecting the ith element or not. If we don't select the ith element, then we have to maximize the sum using the elements 1 to I, 1. If ith element is selected, then we should not select I, first element, and need to maximize the sum using 1 to I, 2 elements. In the above representation, the last two cases indicate the base cases. Given array, A, recursive formula considers the case of selecting ith element. int max sum with not will continuous numbers, int n, int m equal to A, m equal to APA. A, for m equal to mi minus 2 plus A. M plus A, return m. Time complexity, O. Space complexity, O. Problem minus 10. In problem 9, we assume that m represents the maximum sum from 1 to I numbers without selecting two contiguous numbers. Can we solve the same problem by changing the definition as m represents the maximum sum from I to n numbers without selecting two contiguous numbers? Solution, yes. Let us assume that m represents the maximum sum from I to n numbers without selecting two contiguous numbers. Given array, A, recursive formula considers the case of selecting ith element. A. As similar to problem 9 solution, we can write the recursive formula as, the first case indicates whether we are selecting the ith element or not. If we don't select the ith element, then we have to maximize the sum using the elements I plus 1 to n. If ith element is selected, then we should not select I plus first element, need to maximize the sum using I plus 2 to n elements. In the above representation, the last two cases indicate the base cases. Time complexity, O. Space complexity, O. Problem 11, given a sequence of n numbers A. Give an algorithm for finding a contiguous subsequence A for which the sum of elements in the subsequence is maximum. Here the condition is we should not select three continuous numbers. Solution, input, array A of n numbers. Given array A, recursive formula considers the case of selecting ith element. Assume that m represents the maximum sum from 1 to I numbers without selecting three contiguous numbers. While computing m, the decision we have to make is whether to select ith element or not. This gives us the following possibilities. In the given problem, the restriction is not to select three continuous numbers, but we can select two elements continuously and skip the third one. That is what the first case says in the above recursive formula. That means we are skipping A. The other possibility is selecting ith element and skipping second I, first element. This is the second case. The third term defines the case of not selecting ith element, and as a result, we should solve the problem with I1 elements. Time complexity, O. Space complexity, O. Problem 12. In problem 11, we assume that m represents the maximum sum from 1 to I numbers without selecting three contiguous numbers. Can we solve the same problem by changing the definition as m represents the maximum sum from I to n numbers without selecting three contiguous numbers? Solution, yes. The reasoning is very much similar. Let us see how DP solves this problem. Assume that m represents the maximum sum from I to n numbers without selecting three contiguous numbers. Given array, A, recursive formula considers the case of selecting ith element. While computing m, the decision we have to make is whether to select ith element or not. This gives us the following possibilities. In the given problem, the restriction is to not select three continuous numbers, but we can select two elements continuously and skip the third one. That is what the first case says in the above recursive formula. That means we are skipping A. The other possibility is selecting ith element and skipping second I, first element. This is the second case. And the third case is not selecting ith element, and as a result, we should solve the problem with I plus 1 elements. Time complexity, O. Space complexity, O. Problem minus 13 Catalan numbers. How many binary search trees are there with n vertices? Solution, binary search tree is a tree where the left subtree elements are less than the root element, and the right subtree elements are greater than the root element. This property should be satisfied at every node in the tree. The number of BSTs with n nodes is called Catalan number and is denoted by C. For example, there are 2 BSTs with 2 nodes and 5 BSTs with 3 nodes. Let us assume that the nodes of the tree are numbered from 1 to n. Among the nodes, we have to select some node as root, and then divide the nodes which are less than root node into left subtree, and elements greater than root node into right subtree. Since we have already numbered the vertices, let us assume that the root element we selected is th element. If we select ith element as root, then we get I1 elements on left subtree and n, I elements on right subtree. Since C is the Catalan number for n elements, C1 represents the Catalan number for left subtree elements and Copernicium represents the Catalan number for right subtree elements. The two subtrees are independent of each other, so we simply multiply the two numbers. That means the Catalan number for a fixed I value is C minus 1 times Ci. Since there are n nodes, for I we will get n choices. The total Catalan number with n nodes can be given as, in Catalan number if return 1, in count equal to 0 for count plus Catalan number, return count. Time complexity, O. For proof, refer introduction chapter. Problem minus 14. Can we improve the time complexity of problem 13 using DP? Solution. The recursive call C depends only on the numbers CO to C minus 1, and for any value of I, there are a lot of recalculations. We will keep a table of previously computed values of C. If the function Catalan number is called with parameter 1, and if it has already been computed before, then we can simply avoid recalculating the same subproblem. In table, in Catalan number, if equal to 1, return table, table equal to 0, for table plus Catalan number, return table. The time complexity of this implementation O, because to compute Catalan number, we need to compute all of the Catalan number values between 0 and n1, and each one will be computed exactly once in linear time. In mathematics, Catalan number can be represented by direct equation as n. Problem minus 15 matrix product parenthesizations. Given a series of matrices, a 1 times a 2 times a 3 times n, with their dimensions, what is the best way to parenthesize them so that produces the minimum number of total multiplications? Assume that we are using standard matrix and not Strasson's matrix multiplication algorithm. Solution, input, sequence of matrices a 1 times a 2 times a 3 times A, where A is a P, 1 times Pj. The dimensions are given in an array P goal. Parenthesize the given matrices in such a way that it produces the optimal number of multiplications needed to compute a 1 times a 2 times a 3 times n. For the matrix multiplication problem, there are many possibilities. This is because matrix multiplication is associative. It does not matter how we parenthesize the product, the result will be the same. As an example, for 4 matrices A, B, C, and D, the possibilities could be: multiplying matrix with matrix requires PQR multiplications. Each of the above possibilities produces a different number of products during multiplication. To select the best one, we can go through each possible parenthesization, but this requires O time and is very slow. Now let us use DP to improve this time complexity. Assume that M represents the least number of multiplications needed to multiply A, AJ. The above recursive formula says that we have to find point K such that it produces the minimum number of multiplications. After computing all possible values for K, we have to select the K value which gives minimum value. We can use one more table to reconstruct the optimal parenthesizations. Compute the M and S in a bottom-up fashion. P is the sizes of the matrices. Matrix I has the dimension P x P. M is the best cost of multiplying matrices I through JS saves the multiplication point, and we use this for backtracing. Void matrix chain order in T length. How many subproblems are there? In the above formula, I can range from 1 to n, and j can range from 1 to n. So there are a total of n 2 subproblems, and also we are doing n 1 such operations. So the time complexity is O. Space complexity, O, problem 16 for the problem 15. Can we use greedy method? Solution: greedy method is not an optimal way of solving this problem. Let us go through some counterexample for this. As we've seen already, greedy method makes the decision that is good locally, and it does not consider the future optimal solutions. In this case, if we use greedy, then we always do the cheapest multiplication first. Sometimes it returns a parenthesization that is not optimal. Example, consider a 1 times a2 times a 3 with dimensions 3 times 100, 100 times 2, and 2 times 2. Based on greedy, we parenthesize them as a 1 times with 102, 2 plus 3, 1000, and 2 equal to 1000 multiplications. But the optimal solution to this problem is times a3 with 3, 100 plus 3, 22 equal to 612. Multiplications, we cannot use greedy for solving this problem. Problem 17, integer knapsack problem. Given n types of items, where the ith item type has an integer size s and a value v, we need to fill a knapsack of total capacity c with items of maximum value. We can add multiple items of the same type to the knapsack. Note, for fractional knapsack problem, refer to greedy algorithms chapter. Solution: input n types of items where ite type item has the size s and value v. Also assume infinite number of items for each item type. Goal: fill the knapsack with capacity c by using n types of items and with maximum value. One important note is that it's not compulsory to fill the knapsack completely. That means filling the knapsack completely if we get a value 5 and without filling the knapsack completely with value u, and if 5u, then we consider the second one. In this case, we are basically filling the knapsack of size c1. If we get the same situation for c1 also, then we try to fill the knapsack with c2 size and get the maximum value. Let us say m denotes the maximum value we can pack into a j-size knapsack. We can express m recursively in terms of solutions to subproblems as follows. For this problem, the decision depends on whether we select a particular th item or not for a knapsack of size j. If we select ith item, then we add its value v to the optimal solution and decrease the size of the knapsack to be solved to j, s. If we do not select the item, then check whether we can get a better solution for the knapsack of size j, 1. The value of m will contain the value of the optimal solution. We can find the list of items in the optimal solution by maintaining and following back pointers. Time complexity, finding each m value will require O time, and we need to sequentially compute c such values. Therefore, total running time is space complexity. Problem minus 18 0 to 1 knapsack problem for problem 17. How do we solve it if the items are not duplicated? Real-time example, suppose we are going by flight, and we know that there is a limitation on the luggage weight. Also, the items which we are carrying can be of different types. In this case, our objective is to select the items with maximum value. That means we need to tell the customs officer to select the items which have more weight and less value. Solution: input is a set of n items with sizes s and values phi, and a knapsack of size c, which we need to fill with a subset of items from the given set. Let us try to find the recursive formula for this problem using dp. Let m represent the optimal value we can get for filling up a knapsack of size j with items 1, I. The recursive formula can be given as time complexity, O, since there are nc subproblems to be solved and each of them takes O to compute. Space complexity, O, whereas integer knapsack takes only O. Now let us consider the following diagram, which helps us in reconstructing the optimal solution and also gives further understanding. Size of below matrix is mj. Since I takes values from 1, n and j takes values from 1, c, there are a total of nc subproblems. Now let us see what the above formula says. M indicates the case of not selecting the ith item. In this case, since we are not adding any size to the knapsack, we have to use the same knapsack size for subproblems, but excluding the ith item. The remaining items are I1. M plus v indicates the case where we have selected the ith item. If we add the ith item, then we have to reduce the subproblem knapsack size to j, s, and at the same time we need to add the value v to the optimal solution. The remaining items are I1. Now, after finding all m values, the optimal objective value can be obtained as max. This is because we do not know what amount of capacity gives the best solution. In order to compute some value m, we take the maximum of m and m plus v. These two values and m appear in the previous row and also in some previous columns. So m can be computed just by looking at two values in the previous row in the table. Problem 19, making change, given n types of coin denominations of values v1, v2, vn. Assume v1 equal to 1, so that we can always make change for any amount of money c. Give an algorithm which makes change for an amount of money c with as few coins as possible. Solution: this problem is identical to the integer knapsack problem. In our problem, we have coin denominations each of value v. We can construct an instance of a knapsack problem for each item that has a sizes s, which is equal to the value of v coin denomination. In the knapsack, we can give the value of every item as -1. Now it is easy to understand an optimal way to make money c with the fewest coins is completely equivalent to the optimal way to fill the knapsack of size c. This is because since every value has a value of -1, and the knapsack algorithm uses as few items as possible which correspond to as few coins as possible. Let us try formulating the recurrence. Let m indicate the minimum number of coins required to make change for the amount of money equal to j. What this says is, if coin denomination I was the last denomination coin added to the solution, then the optimal way to finish the solution with that one is to optimally make change for the amount of money j, v, and then add one extra coin of value c. In table, initialization int making change if return -1, if return 0, If equal to -1, return table, int a and s equal to -1. For equal to a and s min, return table a and s plus 1. Time complexity, O, since we are solving C subproblems, and each of them requires minimization of n terms. Space complexity, O. Problem, 20th longest increasing subsequence given a sequence of n numbers a, 1. And determine a subsequence of maximum length in which the values in the subsequence form a strictly increasing sequence. Solution, input, sequence of n, numbers a1, n. Goal, to find a subsequence that is just a subset of elements and does not happen to be contiguous. But the elements in the subsequence should form a strictly increasing sequence, and at the same time, the subsequence should contain as many elements as possible. For example, if the sequence is then, are all increasing subsequences, the longest one of them is, and we want an algorithm for finding it. First, let us concentrate on the algorithm for finding the longest subsequence. Later, we can try printing the sequence itself by tracing the table. Our first step is finding the recursive formula. First, let us create the base conditions. If there is only one element in the input sequence, then we don't have to solve the problem, and we just need to return that element. For any sequence, we can start with the first element. Since we know the first number in the LIs, let's find the second number. If a is larger than a, then include a also. Otherwise, we are done. The LS is the one-element sequence. Now, let us generalize the discussion and decide about ith element. Let L represent the optimal subsequence, which is starting at position A and ending at A. The optimal way to obtain a strictly increasing subsequence ending at position 1 is to extend some subsequence starting at some earlier position j. For this, the recursive formula can be written as: the above recurrence says that we have to select some earlier position j, which gives the maximum sequence. The one in the recursive formula indicates the addition of ith element. Now, after finding the maximum sequence for all positions, we have to select the one among all positions, which gives the maximum sequence, and it is defined as max int list table int longest increasing sequence int n. For if return max, max equal to list table. Time complexity, O, since 2 for loops. Space complexity, O for table. Problem 21, longest increasing subsequence. In problem 20, we assume that L represents the optimal subsequence, which is starting at position A and ending at A. Now, let us change the definition of L as L represents the optimal subsequence, which is starting at position A and ending at A. With this approach, can we solve the problem? Solution, yes. N. Let L represent the optimal subsequence, which is starting at position A and ending at A. The optimal way to obtain a strictly increasing subsequence starting at position I is going to be to extend some subsequence starting at some later position j. For this, the recursive formula can be written as: we have to select some later position j, which gives the maximum sequence. The one in the recursive formula is the addition of ith element. After finding the maximum sequence for all positions, select the one among all positions, which gives the maximum sequence, and it is defined as max int list table int longest increasing sequence int n. For try picking a larger second element for if a and list table plus 1, list table plus 1. For if return max, max equal to list table. Time complexity, O, since 2 nested for loops. Space complexity, O for table. Problem. -22, is there an alternative way of solving problem 21? Solution, yes. The other method is to sort the given sequence and save it into another array, and then take out the longest common subsequence of the two arrays. This method has a complexity of O. For LCS problem, refer theory section of this chapter. Problem 23, box stacking. Assume that we are given a set of n rectangular 3D boxes. The dimensions of ith box are height h, width w, and depth d. Now we want to create a stack of boxes which is as tall as possible, but we can only stack a box on top of another box if the dimensions of the 2D base of the lower box are each strictly larger than those of the 2D base of the higher box. We can rotate a box so that any side functions as its base. It is possible to use multiple instances of the same type of box. Solution, box stacking problem can be reduced to LS, problem 21. Input, n boxes with height h, width w, and depth d. For all n boxes, we have to consider all the orientations with respect to rotation. That is, if we have in the original set a box with dimensions 1 times 2 times 3, then we consider 3 boxes. 1, 2, decreasing base area, j. This simplification allows us to forget about the rotations of the boxes, and we just focus on the stacking of n boxes with each height as h and a base area of. Also assume that w less than or equal to d. Now what we do is make a stack of boxes that is as tall as possible and has maximum height. We allow a box I on top of box j only if box I is smaller than box j in both the dimensions. That means if w, w, and in d, d. Now let us solve this using dp. First, select the boxes in the order of decreasing base area. Now, let us say h represents the tallest stack of boxes with box j on top. This is very similar to the LS problem because the stack of n boxes with ending box j is equal to finding a subsequence with the first j boxes due to the sorting by decreasing base area. The order of the boxes on the stack is going to be equal to the order of the sequence. Now we can write h recursively. In order to form a stack which ends on box j, we need to extend a previous stack ending at I. That means we need to put j box at the top of the stack. To put j box at the top of the stack, we should satisfy the condition w, w, and d, d. Based on this logic, we can write the recursive formula as: similar to the LIS problem, at the end we have to select the best j over all potential values. This is because we are not sure which box might end up on top. Time complexity, O. Problem 24, building bridges in India. Consider a very long straight river which moves from north to south. Assume there are n cities on both sides of the river, n cities on the left of the river, and n cities on the right side of the river. Also, assume that these cities are numbered from 1 to n, but the order is not known. Now we want to connect as many left. Write pairs of cities as possible with bridges such that no two bridges cross. When connecting cities, we can only connect city I on the left side to city Y on the right side. Solution. Input, 2 pairs of sets with each numbered from 1 to n. Goal, construct as many bridges as possible without any crosses between left side cities to right side cities of the river. River, left city side. To understand better, let us consider the diagram below. In the diagram, it can be seen that there are n cities on the left side of river and n cities on the right side of river. Also, note that we are connecting the cities which have the same number. Our goal is to connect the maximum cities on the left side of river to cities on the right side of the river without any cross edges. Just to make it simple, let us sort the cities on one side of the river. If we observe carefully, since the cities on the left side are already sorted, the problem can be simplified to finding the maximum increasing sequence. That means we have to use the LA solution for finding the maximum increasing sequence on the right side cities of the river. Time complexity, O. Problem 25, subset sum. Given a sequence of n positive numbers a, 1, and give an algorithm which checks whether there exists a subset of A whose sum of all numbers is T. Solution: this is a variation of the knapsack problem. As an example, consider the following array. Suppose we want to check whether there is any subset whose sum is 17. The answer is yes, because the sum of 4 plus 13 equal to 17, and therefore is such a subset. Let us try solving this problem using dp. We will define n xt matrix, where n is the number of elements in our input array, and t is the sum we want to check. Let m equal to 1 if it is possible to find a subset of the numbers 1 through I that produce sum, and m equal to 0 otherwise. According to the above recursive formula similar to the knapsack problem, we check if we can get the sum j by not including the element I in our subset, and we check if we can get the sum j by including I and checking if the sum j, A, exists without the ith element. This is identical to knapsack, except that we are storing 0 divided by 1s instead of values. In the below implementation, we can use binary or operation to get the maximum among m and m. Int seed subset sum, int n, int t, int I, j, m equal to 0, for m equal to 0. For m equal to m or m, return m. How many subproblems are there? In the above formula, I can range from 1 to n, and j can range from 1 to t. There are a total of nt subproblems, and each one takes O. So the time complexity is O, and this is not polynomial, as the running time depends on two variables, and we can see that they are an exponential function of the other. Space complexity, O. Problem 26, given a set of n integers and the sum of all numbers is at most if. Find the subset of these n elements whose sum is exactly half of the total sum of n numbers. Solution: assume that the numbers are a 1. A. Let us use dp to solve this problem. We will create a Boolean array t with size equal to k plus 1. Assume that t is 1 if there exists a subset of given n elements whose sum is x. That means after the algorithm finishes, t will be 1, if and only if there is a subset of the numbers that has sum k. Once we have that value, then we just need to return t. If it is 1, then there is a subset that adds up to half the total sum. Initially, we set all values of t to 0, then we set t to 1. This is because we can always build 0 by taking an empty set. If we have no numbers in A, then we are done. Otherwise, we pick the first number, A. We can either throw it away or take it into our subset. This means that the new t should have t and t set to 1. This creates the base case. We continue by taking the next element of A. Suppose that we have already taken care of the first I1 elements of A. Now we take A and look at our table T. After processing 1 elements, the array T has a 1 in every location that corresponds to a sum that we can make from the numbers we have already processed. Now we add the new number, A. What should the table look like? First of all, we can simply ignore A. That means no one should disappear from T. We can still make all those sums. Now consider some location of T that has a 1 in it. It corresponds to some subset of the previous numbers that add up to J. If we add A to that subset, we will get a new subset with total sum J plus A. So we should set T to 1 as well. That's all. Based on the above discussion, we can write the algorithm as bool T, bool subset half sum, int n, tj plus A equal to 1, return T. In the above code, J loop moves from right to left. This reduces the double counting problem. That means if we move from left to right, then we may do the repeated calculations. Time complexity O for the 2 for loops. Space complexity O for the Boolean table T. Problem minus 27. Can we improve the performance of problem 26? Solution: yes. In the above code, what we are doing is the inner J loop is starting from K and moving left. That means it is unnecessarily scanning the whole table every time. What we actually want is to find all the 1 entries. At the beginning, only the 0th entry is 1. If we keep the location of the rightmost 1 entry in a variable, we can always start at that spot and go left instead of starting at the right end of the table. To take full advantage of this, we can sort it first. That way, the rightmost 1 entry will move to the right as slowly as possible. Finally, we don't really care about what happens in the right half of the table, because if t is 1, then t must also be 1 eventually. It corresponds to the complement of the subset that gave us x. The code based on above discussion is given below. Int t in subset half sum efficient, int n, int k equal to 0 for k plus equal to a sort t equal to 1. Initialize the table for t equal to 0, int r equal to 0. Rightmost 1 entry 4, greater than equal to 4, return t, if, process the numbers 1 by 1 t, equal to 1, r min. After the improvements, the time complexity is still O, but we have removed some useless steps. Problem 28, partition. Partition problem is to determine whether a given set can be partitioned into 2 subsets such that the sum of elements in both subsets is the same. For example, if A equal to 1, 5, 11, 5, the array can be partitioned as AND. Similarly, if A equal to, the array cannot be partitioned into equal subsets. Solution: let us try solving this problem another way. Following are the 2 main steps to solve this problem. 1. Calculate the sum of the array. If the sum is odd, there cannot be 2 subsets with an equal sum, so return false. 2. If the sum of the array elements is even, calculate sum/2 and find a subset of the array with a sum equal to sum/2. The first step is simple. The second step is crucial, and it can be solved either using recursion or dynamic programming. Recursive solution. Following is the recursive property of the second step mentioned above. Let subsetsum be the function that returns true if there is a subset of A with sum equal to sum/2. The is-subsetsum problem can be divided into 2 subproblems. A is subsetsum without considering last element. B is subsetsum considering the last element and n to n, 1. If any of the above subproblems return true, then return true. Subsetsum equal to is subsetsum, a utility function that returns true if there is a subset of A with sum equal to given some bool subsetsum int n in sum. If return true, if return false, if last element is greater than sum, then ignore it if sum, return subsetsum or subsetsum, returns true if A can be partitioned in 2 subsets of equal sum, otherwise false bool find partition, int n, calculate sum of all elements in sum equal to 0 for sum plus equal to A. If sum is odd, there cannot be 2 subsets with equal sum if return false. Find if there is subset with sum equal to half of total sum, return subset sum. Time complexity 0 in worst case. This solution tries 2 possibilities for every element. Dynamic programming solution. The problem can be solved using dynamic programming when the sum of the elements is not too big. We can create a 2D array part of size, and we can construct the solution in a bottom-up manner such that every filled entry has a following property. Part equal to true if a subset of has sum equal to sum/2, otherwise false. returns true if A can be partitioned in two subsets of equal sum, otherwise false bool. Find partition int n in sum equal to 0, int I, j. Calculate sum of all elements for sum plus equal to A if return false bool part. Initialize top row as true for part equal to true. Initialize leftmost column, except part, as 0 for part equal to false. Fill the partition table in bottom-up manner for part equal to part, if part, or a party, A, return part. Time complexity, O. Space complexity, O. Please note that this solution will not be feasible for arrays with a big sum. Problem -29. Counting Boolean parenthesizations. Let us assume that we are given a Boolean expression consisting of symbols true, false, and, or, and, XOR. Find the number of ways to parenthesize the expression such that it will evaluate to true. For example, there is only one way to parenthesize true and false XOR true such that it evaluates to true. Solution: let the number of symbols be n and between symbols. There are Boolean operators like AND or XOR, etc. For example, if n equal to 4, t or f and t XOR f. Our goal is to count the numbers of ways to parenthesize the expression with Boolean operators so that it evaluates to true. In the above case, if we use t or XOR f, then it evaluates to true. Tor XOR f equal to true. Now let us see how DP solves this problem. Let t represent the number of ways to parenthesize the sub-expression with symbols I, j with Boolean operators so that it evaluates to true. Also, I and j take the values from 1 to n. For example, in the above case, t equal to 0 because there is no way to parenthesize the expression f and t XOR f to make it true. Just for simplicity and similarity, let f represent the number of ways to parenthesize the sub-expression with symbols I, j with Boolean operators so that it evaluates to false. The base cases are t and f. Now we are going to compute t and f for all values of I. Similarly, t and f for all values of I, and so on. Now let's generalize the solution. Where total t plus f and, or, XOR. What this above recursive formula says is, t indicates the number of ways to parenthesize the expression. Let us assume that we have some subproblems which are ending at k. Then the total number of ways to parenthesize from I to j is the sum of counts of parenthesizing from I to k and from k plus 1 to j. To parenthesize between k and k plus 1, there are three ways, and, or, and, XOR. If we use in between k and k plus 1, then the final expression becomes true only when both are true. If both are true, then we can include them to get the final count. If we use or, then if at least one of them is true, the result becomes true. Instead of including all three possibilities for or, we are giving one alternative where we are subtracting the false cases from total possibilities. The same is the case with XOR. The conversation is as in the above two cases. After finding all the values we have to select the value of k, which produces the maximum count, and fork there are I to j, 1 possibilities. How many subproblems are there? In the above formula, I can range from 1 to n, and j can range from 1 to n. So there are a total of n2 subproblems, and also we are doing summation for all such values. So the time complexity is O. Problem -30. Optimal binary search trees. Given a set of n keys A, build the best binary search tree for the elements of A. Also assume that each element is associated with frequency, which indicates the number of times that a particular item is searched in the binary search trees. That means we need to construct a binary search tree so that the total search time will be reduced. Solution before solving the problem. Let us understand the problem with an example. Let us assume that the given array is a equal to. There are many ways to represent these elements, two of which are listed below. Of the two, which representation is better? The search time for an element depends on the depth of the node. The average number of comparisons for the first tree is 1 plus 2 plus 2 plus 3 plus 3, 115, equal 2, and for the second tree, the average number of comparisons is tree gives better results. 1 plus 2 plus 3 plus 3 plus 4, 13, equal to of the two, the first 5, 5. If frequencies are not given, and if we want to search all elements, then the above simple. Calculation is enough for deciding the best tree. If the frequencies are given, then the selection depends on the frequencies of the elements and also the depth of the elements. For simplicity, let us assume that the given array is A, and the corresponding frequencies are in array. F indicates the frequency of IT element A. With this, the total search time S of the tree with root can be defined as, in the above expression, depth plus 1 indicates the number of comparisons for searching the ITH element. Since we are trying to create a binary search tree, the left subtree elements are less than root element and the right subtree elements are greater than root element. If we separate the left subtree time and right subtree time, then the above expression can be written as, where R indicates the position of the root element in the array. If we replace the left subtree and right subtree times with their corresponding recursive calls, then the expression becomes ns equal to s plus I equal to 1. Binary search tree node declaration. Refer to trees chapter. Implementation. Struct binary search tree node optimal BST int f int low int high root left optimal BST equal to root left optimal BST root data A if min time equal to s return min time malloc. Problem -31 edit distance. Given two strings A of length m and B of length n. Transform A into B with a minimum number of operations of the following types. Delete a character from A, insert a character into A, or change some character in A into a new character. The minimal number of such operations required to transform A into B is called the edit distance between A and B. Solution. Input two text strings A of length m and B of length n. Goal. Convert string A into B with minimal conversions. Before going to a solution, let us consider the possible operations for converting string A into B. If mn, we need to remove some characters of A. If m equal to n, we may need to convert some characters of A. If mn, we need to remove some characters from A. So, the operations we need are the insertion of a character, the replacement of a character, and the deletion of a character, and their corresponding cost codes are defined below. Costs of operations, CD. Now let us concentrate on the recursive formulation of the problem. Let T represents the minimum cost required to transform first I characters of A to first characters of B. That means A to B. Based on the above discussion, we have the following cases. If we delete ith character from A, then we have to convert remaining I, 1 characters of A to J characters of B. If we insert if character in A, then convert these I characters of A to J 1 characters of B. If A equal to B, then we have to convert the remaining I, 1 characters of A to J, 1 characters of B. If a B, then we have to replace ith character of A to jth character of B and convert remaining I, 1 characters of A to J, 1 characters of B, after calculating all the possibilities we have to select the one which gives the lowest cost. How many subproblems are there? In the above formula, I can range from 1 to m, and j can range from 1 to n. This gives m n subproblems, and each one takes O, and the time complexity is O. Space complexity, O, where m is number of rows and n is number of columns in the given matrix. Problem 32, all pairs shortest path problem, Floyd's algorithm, given a weighted directed graph G equal to, where V equal to. Find the shortest path between any pair of nodes in the graph. Assume the weights are represented in the matrix C, where C indicates the weight between the nodes I and J. Also, C equal to infinity, or -1, if there is no path from node I to node J. Solution? Let us try to find the DP solution for this problem. The Floyd's algorithm for all pairs shortest path problem uses matrix A to compute the lengths of the shortest paths. Initially, from the definition, C equal to infinity if there is no path from I to J, the algorithm makes n passes over A. Let A1. A be the values of A on the n passes, with AO being the initial value. Just after the first iteration, AK1 equal to smallest length of any path from vertex 1 to vertex J that does not pass through the vertices. That means it passes through the vertices, possibly through. In each iteration, the value A is updated with minimum of A-1 and AK-1 plus AK-1. The KTH pass explores whether the vertex K lies on an optimal path from I to J for all I, J. The same is shown in the diagram below. Void Floyd, int AOR, int n. Time complexity, O, problem -33. Optimal strategy for a game, consider a row of n coins of values V1 Vn, where n is even. We play this game with the opponent. In each turn, a player selects either the first or last coin from the row, removes it from the row permanently, and receives the value of the coin. Determine the maximum possible amount of money we can definitely win if we move first. Alternative way of framing the question, given n pots, each with some number of gold coins, are arranged in a line. You are playing a game against another player. You take turns picking a pot of gold. You may pick a pot from either end of the line, remove the pot, and keep the gold pieces. The player with the most gold at the end wins. Develop a strategy for playing this game. Solution, let us solve the problem using our DP technique. For each turn, either we or our opponent selects the coin only from the ends of the row. Solution. Let us solve the problem using our DP technique. For each turn, either we or our opponent selects the coin only from the ends of the row. Let us define the subproblems as 5 denotes the maximum possible value we can definitely win if it is our turn, and the only coins remaining are V, Vj. Base case is 5, 5 for all values of I. From these values, we can compute 5, 5, and so on. Now let us define 5 for each subproblem as, in the recursive call, we have to focus on ith coin to jth coin. Since it is our turn to pick the coin, we have two possibilities. Either we can pick V or Vj. The first term indicates the case if we select ith coin, and the second term indicates the case if we select jth coin. The outer max indicates that we have to select the coin which gives maximum value. Now let us focus on the terms. Selecting ith coin. If we select the ith coin, then the remaining range is from I plus 1 to j. Since we selected the ith coin, we get the value V for that. From the remaining range, I plus 1 to j, the opponents can select either I plus first coin or jth coin, but the opponent's selection should be minimized as much as possible. The same is described in the below figure. Selecting the jth coin, here also the argument is the same as above. If we select the jth coin, then the remaining range is from ataj 1. Since we selected the jth coin, we get the value Vj for that. From the remaining range I to j1, the opponent can select either the ith coin or the j first coin, but the opponent's selection should be minimized as much as possible. How many subproblems are there? In the above formula, I can range from 1 to n, and j can range from 1 to n. There are a total of n 2 subproblems, and each takes O, and the total time complexity is O. Problem, minus 34 tiling. Assume that we use dominoes measuring 2 times 1 to tile an infinite strip of height 2. How many ways can one tile a 2 times n strip of square cells with 1 times dominoes? Solution. Notice that we can place tiles either vertically or horizontally. For placing vertical tiles, we need a gap of at least 2 times 2. For placing horizontal tiles, we need a gap of 2 times 1. In this manner, the problem is reduced to finding the number of ways to partition n using the numbers 1 and 2 with order considered relevant. For example, 11 equal to 1 plus 2 plus 2 plus 1 plus 2 plus 2 plus 1. Also, every character A is a palindrome of length 1. Therefore, the base cases are given by A equal to 1. Let us define the maximum length palindrome for the substring A. Also, every character A is a palindrome of length 1. Therefore, the base cases are given by A equal to 1. Let us define the maximum length palindrome for the substring A as L. If we have to find such arrangements for 12, we can either place a 1 at the end, or we can add 2 in the arrangements possible with 10. Similarly, let us say we have f possible arrangements for n, then for, we can either place just 1 at the end, or we can find possible arrangements for, and put a 2 at the end. Going by the above theory, let's verify the above theory for our original problem. In how many ways can we fill a 2 times 1 strip, only one vertical tile? In how many ways can we fill a 2 times 2 strip, 2 tiles, either 2 horizontal or 2 vertical? In how many ways can we fill a 2 times 3 strip, 3 either put a vertical tile in the 2 solutions possible for a 2 times 2 strip, or put 2 horizontal tiles in the only solution possible for a 2 times 1 strip? Similarly, in how many ways can we fill a 2 times n strip, either put a vertical tile in the solutions possible for 2x strip, or put 2 horizontal tiles in the solution possible for 2 times strip? That's how we verified that our final solution is ff2 equal to fn1 plus f minus 2 with f1 equal to 1. And, problem 35 longest palindrome subsequence, a sequence is a palindrome if it reads the same whether we read it left or right to left. For example, A, C, G, 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 C, A. Given a sequence of length n, devise an algorithm to output the length of the longest palindrome subsequence. For example, the string A, G, C, T, C, B, M, A, A, C, T, G, G, A has many palindromes as subsequences. For instance, A, G, T, C, M, C, T, G, A has length 9. Solution, let us use DP to solve this problem. If we look at the substring A of the string A, then we can find a palindrome sequence of length at least 2 if A equal to A. If they are not the same, then we have to find the maximum length palindrome in subsequences A and A. L equal to 1 plus 2 if A equal to SL, L, otherwise L1 for all I equal to 1 to N. Int longest palindrome subsequence, int N, return max, else L equal to max L. Time complexity, first for loop takes O time, while the second for loop takes O, which is also O. Therefore, the total running time of the algorithm is given by O. Problem 36 longest palindrome substring given a string A, we need to find the longest substring of as such that the reverse of it is exactly the same. Solution. The basic difference between the longest palindrome substring and the longest palindrome subsequence is that in the case of the longest palindrome substring, the output string should be the contiguous characters, which gives the maximum palindrome. And in the case of the longest palindrome subsequence, the output is the sequence of characters where the characters might not be contiguous, but they should be in an increasing sequence with respect to their positions in the given string. Brute force solution exhaustively checks all n2 possible substrings of the given n-length string, tests each one if it's a palindrome, and keeps track of the longest one seen so far. This has worst case complexity O, but we can easily do better by realizing that a palindrome is centered on either a letter or a space between letters. Therefore, we can examine all n+1 possible centers and find the longest palindrome for that center, keeping track of the overall longest palindrome. This has worst case complexity O. Let us use DP to solve this problem. It is worth noting that there are no more than O substrings in a string of length n. Therefore, we could scan each substring, check for a palindrome, and update the length of the longest palindrome substring discovered so far. Since the palindrome test takes time linear in the length of the substring, this idea takes O algorithm. We can use DP to improve this. For 1 less than or equal to I less than or equal to j less than or equal to n, define. Also, for string of length at least 3, note that in order to obtain a well-defined recurrence, we need to explicitly initialize 2 distinct diagonals of the Boolean array L, since the recurrence for entry uses the value, which is 2 diagonals away from. Time complexity. First for loop takes O time, while the second for loop takes O, which is also O. Therefore, the total running time of the algorithm is given by O. Problem 37. Given 2 strings S and T, give an algorithm to find the number of times S appears in T. It's not compulsory that all characters of S should appear contiguous to T. For example, if S equal to AB and T equal to ABCB, then the solution is 4, because AB is appearing 4 times in ABCB. Solution, input, given two strings S and T goal, count the number of times that S appears in T. Assume L represents the count of how many times I characters of S are appearing in J characters of T. If we concentrate on the components of the above recursive formula, if J equal to 0, then since T is empty, the count becomes 0. If I equal to 0, then we can treat empty string S also appearing in T, and we can give the count as 1. If S equal to T, it means IDTH character of S and JTH character of T are the same. In this case, we have to check the subproblems with I, 1 characters of S and J, 1 characters of T, and also we have to count the result of I characters of S with E, 1 characters of T. This is because even all I characters of S might be appearing in J, 1 characters of T. If S not equal to T, then we have to get the result of subproblem with I, 1 characters of S and J characters of T. After computing all the values, we have to select the one which gives the maximum count. How many subproblems are there? In the above formula, I can range from 1 to M, and J can range from 1 to N. There are a total of n subproblems, and each one takes O. Time complexity is O. Space complexity, O, where M is number of rows and N is number of columns in the given matrix. Problem 38, given a matrix with n rows and m columns. In each cell, there are a number of apples. We start from the upper left corner of the matrix. We can go down or right one cell. Finally, we need to arrive at the bottom right corner. Find the maximum number of apples that we can collect. When we pass through a cell, we collect all the apples left there. Solution. Let us assume that the given matrix is A. The first thing that must be observed is that there are at most 2 ways we can come to a cell, from the left and from the top. To find the best solution for that cell, we have to have already found the best solutions for all of the cells from which we can arrive to the current cell. From above, a recurrent relation can be easily obtained as S must be calculated by going first from left to right in each row and process the rows from top to bottom, or by going first from top to bottom in each column and process the columns from left to right. How many such subproblems are there? In the above formula, I can range from 1 to N and J can range from 1 to M. There are a total of run subproblems, and each one takes O. Time complexity is O. Space complexity, O, where M is number of rows and N is number of columns in the given matrix. Problem 39, similar to problem 38, assume that we can go down, right one cell, or even in a diagonal direction. We need to arrive at the bottom right corner. Give DP solution to find the maximum number of apples we can collect. Solution, yes. The discussion is very similar to problem 38. Let us assume that the given matrix is A. The first thing that must be observed is that there are at most 3 ways we can come to a cell, from the left, from the top, or from the top diagonal. To find the best solution for that cell, we have to have already found the best solutions for all of the cells from which we can arrive to the current cell. From above, a recurrent relation can be easily obtained. S must be calculated by going first from left to right in each row and process the rows from top to bottom, or by going first from top to bottom in each column and process the columns from left to right. How many such subproblems are there? In the above formula, I can range from 1 to N and J can range from 1 to M. There are a total of Mn subproblems, and each one takes O. Time complexity is O. Space complexity, O, where M is number of rows and N is number of columns in the given matrix. Problem 40, maximum size square submatrix with all 1 foots, given a matrix with 0 feet and 1 foots, give an algorithm for finding the maximum size square submatrix with all is. For example, consider the binary matrix below. The maximum square submatrix with all set bits is. Solution. Let us try solving this problem using DP. Let the given binary matrix be B. The idea of the algorithm is to construct a temporary matrix L, in which each entry L represents size of the square submatrix with all 1s, including B, and B is the rightmost and bottommost entry in the submatrix. Algorithm. 1. Construct a sum matrix L for the given matrix BA. Copy first row and first columns as is from B to LB. For other entries, use the following expressions to construct L. 2. Find the maximum entry in L. 3. Using the value and coordinates of maximum entry in L, print submatrix of B. How many subproblems are there? In the above formula, I can range from 1 to N, and J can range from 1 to M. There are a total of NM subproblems, and each one takes O. Time complexity is O. Space complexity is O, where N is number of rows and M is number of columns in the given matrix. Problem 41, maximum size submatrix with all 1 foots, given a matrix with 0 feet and 1s, give an algorithm for finding the maximum size submatrix with all is. For example, consider the binary matrix below. The maximum submatrix with all set bits is. Solution. If we draw a histogram of all 1 foot cells in the above rows for a particular row, then maximum all 1 foot submatrix ending in that row will be equal to maximum area rectangle in that histogram. Below is an example for 3 RJ row in the above discussed matrix. If we calculate this area for all the rows, maximum area will be our answer. We can extend our solution very easily to find start and end coordinates. For this, we need to generate an auxiliary matrix S, where each element represents the number of is above and including it, up until the first 0. S for the above matrix will be as shown below. Now we can simply call our maximum rectangle and histogram on every row in S, and update the maximum area every time. Also, we don't need any extra space for saving S. We can update original matrix to S, and after calculation, we can convert S back to A. Problem 42, maximum sum submatrix, given an n times n matrix M of positive and negative integers, give an algorithm to find the submatrix with the largest possible sum. Solution, let AUX represent the sum of rectangular subarray of M, with one corner at entry and the other at. Since there are n such possibilities, we can compute them in O time. After computing all possible sums, the sum of any rectangular subarray of M can be computed in constant time. This gives an O algorithm. We simply guess the lower left and the upper right corner of the rectangular subarray, and use the AUX table to compute its sum. Problem 43. Can we improve the complexity of problem 42? Solution, we can use the problem 4 solution with little variation, as we have seen that the maximum sum array of a 1D array algorithm scans the array 1 entry at a time, and keeps a running total of the entries. At any point, if this total becomes negative, then set it to 0. This algorithm is called Kadane's algorithm. We use this as an auxiliary function to solve a 2-dimensional problem in the following way. Time complexity. O, problem 44. Given a number n, find the minimum number of squares required to sum a given number n. Examples, min equal to 1 equal to 12, min equal to 2 equal to 12 plus 12, min equal to 1 equal to 22, min equal to 2 equal to 32 plus 22. Solution. This problem can be reduced to a coin change problem. The denominations are 1, 2. Now, we just need to make change for n with a minimum number of denominations. Problem 45, finding optimal number of jumps to reach last element given an array. Start from the first element and reach the last by jumping. The jump length can be at most the value at the current position in the array. The optimum result is when you reach the goal, in the minimum number of jumps. Example, given array equal to, possible ways to reach the end are 0, 2, 3, 4, 0, 1, 4. Since second solution has only 2 jumps, it is the optimum result. Solution, this problem is a classic example of dynamic programming. Though we can solve this by brute force, it would be complex. We can use the LAI's problem approach for solving this. As soon as we traverse the array, we should find the minimum number of jumps for reaching that position and update our result array. Once we reach the end, we have the optimum solution at last index in result array. How can we find the optimum number of jumps for every position? For first index, the optimum number of jumps will be 0. Please note that if value at first index is 0, we can't jump to any element and return infinite. For n plus first element, initialize result as infinite. Then we should go through a loop from 0, n, and at every index on, we should see if we are able to jump to n plus 1 from I or not. If possible, then see if total number of jumps plus 1 is less than result, then update result, else just continue to next index. The above code will return optimum number of jumps. To find the jump indexes as well, we can very easily modify the code as per requirement. Time complexity, since we are running 2 loops here and iterating from 0 to I in every loop, then total time takes will be 1 plus 2 plus 3 plus 4 plus n, 1. So time efficiency O equal to O/2 equal to O. Space complexity O space for result array. Problem 46, explain what would happen if a dynamic programming algorithm is designed to solve a problem that does not have overlapping subproblems. Solution, it will be just a waste of memory because the answers of subproblems will never be used again, and the running time will be the same as using the divide and conquer algorithm. Problem 47, Christmas is approaching. You're helping Santa Claus to distribute gifts to children. For ease of delivery, you are asked to divide n gifts into 2 groups such that the weight difference of these 2 groups is minimized. The weight of each gift is a positive integer. Please design an algorithm to find an optimal division minimizing the value. Difference. The algorithm should find the minimal weight difference as well as the groupings in O time, where S is the total weight of these n gifts. Briefly justify the correctness of your algorithm. Solution. This problem can be converted into making one set as close to as possible. We consider an equivalent problem of making one set as close to as possible. Define FD to be the minimal gap between the weight of the bag and W when using the first I gifts only. Wog, we can assume the weight of the bag is always less than or equal to W. Then fill the DP table for 0 less than or equal to less than or equal to n, and 0 less than or equal to W less than or equal to, in which F equal to W for all W. And this takes O time. FD is the minimum gap. Finally, to reconstruct the answer, we backtrack from. During backtracking, if FD equal to FD, then I is not selected in the bag and we move to F. Otherwise, I is selected and we move to F. Problem 48. A circus is designing a tower routine consisting of people standing atop one another's shoulders. For practical and aesthetic reasons, each person must be both shorter and lighter than the person below him or her. Given the heights and weights of each person in the circus, write a method to compute the largest possible number of people in such a tower. Solution. It is same as box stacking and longest increasing subsequence problem. Complexity classes, chapter 20, 20.1 introduction. In the previous chapters, we have solved problems of different complexities. Some algorithms have lower rates of growth while others have higher rates of growth. The problems with lower rates of growth are called easy problems, and the problems with higher rates of growth are called hard problems. This classification is done based on the running time that an algorithm takes for solving the problem. There are lots of problems for which we do not know the solutions. All the problems we have seen so far are the ones which can be solved by computer in deterministic time. Before starting our discussion, let us look at the basic terminology we use in this chapter. 20.2 Polynomial exponential time. Exponential time means, in essence, trying every possibility, and they are very slow in nature. Polynomial time means having some clever algorithm to solve a problem, and we don't try every possibility. Mathematically, we can represent these as polynomial time is O for some k, exponential time is O for some k. 20.3. What is a decision problem? A decision problem is a question with a yes/no answer, and the answer depends on the values of input. For example, the problem, given an array of n numbers, check whether there are any duplicates or not, is a decision problem. The answer for this problem can be either yes or no, depending on the values of the input array. 20.4 Decision procedure. For a given decision problem, let us assume we have given some algorithm for solving it. The process of solving a given decision problem in the form of an algorithm is called a decision procedure for that problem. 20.5 What is a complexity class? In computer science, in order to understand the problems for which solutions are not there, the problems are divided into classes and we call them as complexity classes. In complexity theory, a complexity class is a set of problems with related complexity. It is the branch of theory of computation that studies the resources required during computation to solve a given problem. The most common resources are time and space. 20.6 Types of complexity classes. P class. The complexity class P is the set of decision problems that can be solved by a deterministic machine in polynomial time. P problems are a set of problems whose solutions are easy to find. NP class. The complexity class NP is the set of decision problems that can be solved by a non-deterministic machine in polynomial time. NP class problems refer to a set of problems whose solutions are hard to find but easy to verify. For better understanding, let us consider a college which has 500 students on its roll. Also, assume that there are 100 rooms available for students. A selection of 100 students must be paired together in rooms, but the dean of students has a list of pairings of certain students who cannot room together for some reason. The total possible number of pairings is too large, but the solutions provided to the dean are easy to check for errors. If one of the prohibited pairs is on the list, that's an error. In this problem, we can see that checking every possibility is very difficult, but the result is easy to validate. That means, if someone gives us a solution to the problem, we can tell them whether it is right or not in polynomial time. Based on the above discussion, for NP class problems, if the answer is yes, then there is a proof of this fact, which can be verified in polynomial time. Co-NP class. CO, NP is the opposite of NP. If the answer to a problem in CO, NP is no, then there is a proof of this fact that can be checked in polynomial time. Relationship between P, NP, and co-NP. Every decision problem in P is also in NP. If a problem is in P, we can verify yes answers in polynomial time. Similarly, any problem in P is also in CO, NP. One of the important open questions in theoretical computer science is whether or not P equal to NP. Nobody knows. Intuitively, it should be obvious that P not equal to NP, but nobody knows how to prove it. Another open question is whether NP and CO NP are different. Even if we can verify every yes answer quickly, there's no reason to think that we can also verify no answers quickly. It is generally believed that NP not equal to CO NP, but again, nobody knows how to prove it. NP hard class is a class of problems such that every problem in NP reduces to it. All NP hard problems are not in NP, so it takes a long time to even check them. That means if someone gives us a solution for NP hard problem, it takes a long time for us to check whether it is right or not. A problem K is NP hard indicates that if a polynomial time algorithm exists for K, then a polynomial time algorithm for every problem is NP. Thus, NP complete class. Finally, a problem is NP-complete if it is part of both NP-hard and NP. NP-complete problems are the hardest problems in NP. If anyone finds a polynomial time algorithm for one NP-complete problem, then we can find polynomial time algorithm for every NP-complete problem. This means that we can check and answer fast and every problem in NP reduces to it. Relationship between P, NP co-NP, NP-hard, and NP-complete. From the above discussion, we can write the relationships between different components as shown below. NP-complete. The set of problems that are NP-hard is a strict superset of the problems that are NP-complete. Some problems are NP-hard, but not in NP. NP-hard problems might be impossible to solve in general. We can tell the difference in difficulty between NP-hard and NP-complete problems because the class NP includes everything easier than its toughest problems. If a problem is not in NP, it is harder than all the problems in NP. Does P equal to NP? If P equal to NP, it means that every problem that can be checked quickly can be solved quickly. This is a big question, because right now there are lots of NP-complete problems that can't be solved quickly. If P equal to NP, that means there's a way to solve them fast. Remember that quickly means not trial and error. It could take a billion years, but as long as we didn't use trial and error, it was quick. In future, a computer will be able to change that billion years into a few minutes. 20.7% reductions. Before discussing reductions, let us consider the following scenario. Assume that we want to solve problem X but feel it's very complicated. In this case, what do? The first thing that comes to mind is, if we have a similar problem to that of X, then we try to map X to Y and use Y's solution to solve X also. This process is called reduction. In order to map problem X to problem Y, we need some algorithm, and that may take linear time or more. Based on this discussion, the cost of solving problem X can be given as. Now, let us consider the other scenario. For solving problem X, sometimes we may need to use Y's algorithm multiple times. In that case, cost of solving X equal to number of times cost of solving X plus reduction time. The main thing in NP-complete is reducibility. That means we reduce given NP-complete problems to other known NP-complete problem. Since the NP-complete problems are hard to solve, and in order to prove the given NP-complete problem is hard, we take one existing hard problem and try to map given problem to that, and finally, we prove that the given problem is hard. Note, it's not compulsory to reduce the given problem to known hard problem to prove its hardness. Sometimes, we reduce the known hard problem to given problem. Important NP-complete problems. Satisfiability problem, a Boolean formula is in conjunctive normal form if it is a conjunction of several clauses, each of which is the disjunction of several literals, each of which is either a variable or its negation. For example, to the power of a 5. A 3 CNF formula is a CNF formula with exactly 3 literals per clause. The previous example is not a 3 CNF formula, since its first clause has 5 literals and its last clause has only 2. 2SAT problem, 3SAT is just sat restricted to 3 CNF formulas. Given a 3 CNF formula, is there an assignment to the variable so that the formula evaluates to true? 2SAT problem, 2SAT is just sat restricted to 2 CNF formulas. Given a 2 CNF formula, is there an assignment to the variable so that the formula evaluates to true? Circuit satisfiability problem, given a Boolean combinational circuit composed of and or and not gates, is it satisfiable? That means, given a Boolean circuit consisting of and or and not gates properly connected by wires, the circuit sat problem is to decide whether there exists an input assignment for which the output is true. Hamiltonian path problem, given an undirected graph, is there a path that visits every vertex exactly once? Hamiltonian cycle problem, given an undirected graph, is there a cycle that visits every vertex exactly once? Directed Hamiltonian cycle problem, given a directed graph, is there a cycle that visits every vertex exactly once? Traveling salesman problem, given a list of cities and their pairwise distances, the problem is to find the shortest possible tour that visits each city exactly once. Shortest path problem, given a directed graph and 2 vertices S and T, check whether there is a shortest simple path from S to T. Graph coloring, a k-torture coloring of a graph is to map one of k colors to each vertex so that every edge has 2 different colors at its endpoints. The graph coloring problem is to find the smallest possible number of colors in a legal coloring. 3 color problem, given a graph, is it possible to color the graph with 3 colors in such a way that every edge has 2 different colors? Click. Given a graph, the click problem is to compute the number of nodes in its largest complete subgraph. That means we need to find the maximum subgraph, which is also a complete graph. Independent set problem. Let G be an arbitrary graph. An independent set in G is a subset of the vertices of G with no edges between them. The maximum independent set problem is the size of the largest independent set in a given graph. Vertex cover problem. A vertex cover of a graph is a set of vertices that touches every edge in the graph. The vertex cover problem is to find the smallest vertex cover in a given graph. Subset sum problem. Given a set S of integers and an integer t, determine whether 5 has a subset whose elements sum to t. Integer programming. Given integers bi, a. Find 0 first variables x that satisfy a linear system of equations. In the figure, arrows indicate the reductions. For example, ham cycle can be reduced to CNF say t. Same is the case with any pair of problems. For our discussion, we can ignore the reduction process for each of the problems. There is a theorem called Cook's theorem which proves that circuit satisfiability problem is NP-hard. That means circuit satisfiability is a known NP-hard problem. Note, since the problems below are NP-complete, they are NP and NP-hard too. For simplicity, we can ignore the proofs for these reductions. 20.8 complexity classes, problems, and solutions. Problem 1. What is a quick algorithm? Solution. A quick algorithm means not trial and error solution. It could take a billion years, but as long as we do not use trial and error, it is efficient. Future computers will change those billion years to a few minutes. Problem 2. What is an efficient algorithm? Solution. An algorithm is said to be efficient if it satisfies the following properties. Scale with input size. Don't care about constants. Asymptotic running time, polynomial time. Problem -3. Can we solve all problems in polynomial time? Solution, no. The answer is trivial because we have seen lots of problems which take more than polynomial time. Problem -4. Are there any problems which are NP-hard? Solution, by definition, NP-hard implies that it is very hard. That means it is very hard to prove and to verify that it is hard. Cook's theorem proves that circuit satisfiability problem is NP-hard. Problem 5, for 2SAT problem, which of the following are applicable? P, NP, comp, NP-hard. Comp hard, NP-complete, comp complete. Solution, 2SAT is solvable in polytime. So it is P, NP, and co-NP. Problem -6 for 3SAT problem, which of the following are applicable? P, NP, comp, NP, hard. Comp hard, NP-complete, comp complete. Solution, 3SAT is NP-complete. So it is NP, NP-hard, and NP-complete. Problem -7 for 2-click problem, which of the following are applicable? RNP, comp, NP-hard, comp hard, NP-complete, comp complete. Solution, 2-click is solvable in polytime time. So it is P, NP, and co-NP. Problem -8 for 3-click problem, which of the following are applicable? RNP, comp, NP, hard, comp hard, NP-complete, comp complete. Solution, 3-click is solvable in polytime time. So it is P, NP, and co-NP. Problem 9. Consider the problem of determining. For a given Boolean formula, check whether every assignment to the variable satisfies it. Which of the following is applicable? P, NP, comp, NP, hard, NP, complete, comp, complete. Solution. Tautology is the complementary problem to satisfiability, which is NP complete, so tautology is co-NP complete. So it is comp hard, and co-NP complete. Problem 10, let S be an NP complete problem, and Q and R be two other problems not known to be an NP. Q is polynomial time reducible to S, and S is polynomial time reducible to R. Which one of the following statements is true? R is NP complete, R is NP hard, Q is NP complete, Q is NP hard. Solution. R is NP hard. Problem -11. Let it be the problem of finding a Hamiltonian cycle in a graph G equal to, with 5 divisible by 3, and B, the problem of determining if Hamiltonian cycle exists in such graphs. Which one of the following is true? Both A and B are NP hard. A is NP hard, but B is not A is NP hard, but B is not neither A nor B is NP hard. Solution. Both A and B are NP hard. Problem 12 true. Let A be a problem that belongs to the class NP. State which of the following is. There is no polynomial time algorithm for A. If A can be solved deterministically in polynomial time, then P equal to NP. If A is NP hard, then it is NP complete. A may be undecidable. Solution. If A is NP hard, then is NP complete. Problem 13. Suppose we assume vertex cover is known to be NP complete. Based on our reduction, can we say independent set is NP complete? Solution. Yes. This follows from the two conditions necessary to be NP complete. Independent set is an NP as stated in the problem. A reduction from a known NP complete problem. Problem 14. Suppose independent set is known to be NP complete. Based on our reduction, is vertex cover NP complete? Solution. No. By reduction from vertex cover to independent set, we do not know the difficulty of solving independent set. This is because independent set could still be a much harder problem than vertex cover. We have not proved that. Problem -15. The class of NP is the class of languages that cannot be accepted in polynomial time. Is it true? Explain. Solution. The class of NP is the class of linguistics that can be verified in polynomial. The class of P is the class of files that can be seen in polynomial team. The class of P is the class of languages that can be accepted in polynomial time. PC, NP, and languages in P can be accepted in polynomial time. The description, languages in NP cannot be accepted in polynomial time, is wrong. The term NP comes from non-deterministic polynomial time and is derived from an alternative characterization by using non-deterministic polynomial time Turing machines. It has nothing to do with cannot be accepted in polynomial time. Problem -16. Different encodings would cause different time complexity for the same algorithm. Is it true? Solution. True. The time complexity of the same algorithm is different between unary encoding and binary encoding. But if the two encodings are polynomially related, then changing between them will not cause the time complexity to change. Problem 17. If P equal to NP, then NPCCP. Is it true? Solution. True. If P equal to NP, then for any language like NPC, L, i.e. NPC, is NP hard. By the first condition, like NPCCNP equal to P equal to NPCCP. Problem 18. If NPCCP, then P equal to NP. Is it true? Solution. True. All the NP problem can be reduced to arbitrary NPC problem in polynomial time, and NPC problems can be solved in polynomial time because NPCCP, NP problem solvable in polynomial time, equal to NPCP, and trivially PCNP implies NP equal to P. 21.1 Introduction. In this chapter, we will cover the topics which are useful for interviews and exams. 21.2 Hacks on bitwise programming. In C and C++, we can work with bits effectively. First, let us see the definitions of each bit operation, and then move on to different techniques for solving the problems. Basically, there are 6 operators that C and C++ support for bit manipulation. 21.2.1 Bitwise and. The bitwise entests 2 binary numbers and returns bit values of 1 for positions where both numbers had a 1, and bit values of 0 where both numbers did not have 1. 0, 1,000,011, and 0, 10,101. 0, 11. 21.2.2 Bitwise or. The bitwiser tests 2 binary numbers and returns bit values of 1 for positions where either bit or both bits are 1. The result of 0 only happens when both bits are 0. 0, 1,000,000, and 11, 0, 10,101. 0, 1,001,101. It happens where both bits are 0. 0, 1 named numbers, and returns bit values of 1 for positions where both bits are different. If they are the same, then the result is 0. 0, 1,001,011 lambda, 0, 10,101. 0, 1,011,110. Them, 1,101. To the left and fills vacated bit positions with 0. 2, 0, 1,001,011. 0, 100, and 1,100. 21.2.5 Bitwise right shift. The bitwise right shift moves all bits in the number to the right. 2, 100, and 1,011. Note the use of? For the fill bits. Where the left shift filled the vacated positions with 0, a right shift will do the same only when the value is unsigned. If the value is signed, then a right shift will fill the vacated bit positions with the signed bit or 0, whichever one is implementation defined. So the best option is to never right shift signed values. 21.2.6 Bitwise complement. The bitwise complement inverts the bits in a single binary number, 0, 1,000,111. 10,110,100. 21.2.7 Checking whether KTF is set or not. Let us assume that the given number is n. Then for checking the KTH bit, we can use the expression n and. If the expression is true, then we can say the KTH bit is set. Example, 1k, 100001000 n, and 0001000. 21.2.8 Setting KTH bit. For a given number n, to set the KTH bit, we can use the expression n or 1 and 0, 1000, 100. 21.2.9 Clearing KTH bit. To clear KTH bit of a given number n, we can use the expression n and approximately. Example, approximately 11,110,111. February 21st, 2010, toggling KTH bit. For a given number n, for toggling the KTH bit, we can use the expression n to the power of. Example, 1k, 100,000,100 n to the power of 0, 1,001,100 n for toggling first 2011, toggling rightmost 1 bit. For a given number n, for toggling rightmost 1 bit, we can use the expression n and n1. Example, February 21st, 2012, isolating rightmost 1 bit. For a given number n, for isolating rightmost 1 bit, we can use the expression n and n. and n. And n. Note, for computing n, use 2's complement representation. That means toggle all bits and add 1. February 21st, 2013, isolating rightmost 0 bit. For a given number n, for isolating rightmost 0 bit, we can use the expression n and n plus 1. Example, February 21st, 2014, checking whether number is power of 2 or not. And n, 101,000,1010. 0. Given number n, to check whether the number is in 2n form for not, we can use the expression if. Example, February 21st, 2015, multiplying number by power of 2. For a given number n, to multiply the number with 2k, we can use the expression nk. Example, February 21st, 2016, dividing number by power of. For a given number n, to divide the number with 2k, we can use the expression nk. February 21st, 2017, finding modulo of a given number. For a given number n, to find the percent, we can use the expression n and 0 times. Similarly, to find percent 32, use the expression n and 0 times. Note, similarly, we can find modulo value of any number. February 21st, 2018, reversing the binary number. For a given number n, to reverse the bits of binary number, we can use the following code snippet. Unsigned int n reverse equal to n, int s equal to sizeof, for n reverse equal to 1, n reverse or equal to n and 1, s, n reverse equal to s. Time complexity. This requires 1 iteration per bit, and the number of iterations depends on the size of the number. February 21st, 2019, counting number of ones in number. For a given number n, to count the number of ones in its binary representation, we can use any of the following methods. Method 1, process bit by bit with bitwise an operator. Unsigned int n, unsigned int count equal to 0, while count plus n and 1, n equal to 1. Time complexity. This approach requires 1 iteration per bit, and the number of iterations depends on system. Method 2, using modulo approach. Unsigned int n, unsigned int count equal to 0, while if count plus plus, n equal to n/2. Time complexity. This requires 1 iteration per bit, and the number of iterations depends on system. Method 3, using toggling approach n and n, 1. Unsigned int n, unsigned int count equal to 0, while count plus plus, n equal to n minus 1. Time complexity. The number of iterations depends on the number of 1 bits in the number. Method 4, using preprocessing idea. In this method, we process the bits in groups. For example, if we process them in groups of 4 bits at a time, we create a table which indicates the number of ones for each of those possibilities. The following code to count the number of is in the number with this approach. Int table 0 1 1 2 1 2 2 3 1 2 2 3 3 3 3 3 4. Intake table return count. Time complexity. This approach requires 1 iteration per 4 bits, and the number of iterations depends on system. February 21st, 2020, creating mask for trailing zeros. For a given number n, to create a mask for trailing zeros, we can use the expression 1. Example, note, in the above case, we are getting the mask as all zeros because there are no trailing zeros. February 2007, 2021, swap all odd and even bits. Example, find even bits of given number equal to n and aux AA, find odd bits of given number equal to n and 0 times 0 0 0 0 1000 and 10 0 1 million and 1. Even equal to 1000 and 0 times and 10. Final expression. Even equal to 1 first, 2022. Final expression. To replace mid equal to /2 with something much faster, we can use mid equal to 1. Note that using /2 for midpoint calculations won't work correctly when integer overflow becomes an issue. We can use bit shifting and also overcome a possible overflow issue, low plus /2, and the bit shifting operation for this is low 1. 21.3 other programming questions with solutions. Problem 1, give an algorithm for printing the matrix elements in spiral order. Solution, non-recursive solution, involves directions right, left, up, down, and dealing their corresponding indices. Once the first row is printed, direction changes to down, the row is discarded by incrementing the upper limit. Once the last column is printed, direction changes to left, the column is discarded by decrementing the right-hand limit. Void spiral, int row start equal to 0, column start equal to 0, int row end n1, column end equal to n1, while int I row start, j column start, for printf, forge column end, 1i, j greater than, column start, j, printf, for printf, row start plus plus, column start plus plus, row end, column end, time complexity, O. Space complexity, O. Problem 2, give an algorithm for shuffling the desk of cards. Solution, assume that we want to shuffle an array of 52 cards from 0 to 51 with no repeats, such as we might want for a deck of cards. First, fill the array with the values in order, then go through the array and exchange each element with a randomly chosen element in the range from itself to the end. It's possible that an element will swap with itself, but there is no problem with that. Void shuffle, int n, cards equal to cards equal to temp, printf, for printf. Time complexity, O. Space complexity, O. Problem 3. Reversal algorithm for array rotation. Write a function rotate d, n, that rotates a of size n by d elements. For example, the array 1, 2, 3, 4, 5, 6, 7 becomes 3, 4, 5, 6, 7, 1, 2 after 2 rotations. Solution, consider the following algorithm. Algorithm rotate d, n, reverse, 1d, reverse, d, plus 1, n, reverse, 1, n. Let A be the two parts of the input arrays where A equal to array and B equal to array. The idea of the algorithm is reverse A to get ARB. AR is reverse of A, reverse B to get ARBR. BR is reverse of B, reverse all to get R equal to BA. For example, if array equal to, d equal to 2, and n equal to 7, then a equal to and b equal to reverse a, we get arb equal to reverse b, we get arbr equal to reverse all, we get r equal to. Implementation. Function to left rotate array of size n by d void left rotate int d int n for print f print ef. Function to reverse array from index start to end void reverse int d start int end int I int temp. While temp equal to array equal to array equal to temp start plus plus end. Problem -4. Suppose you were given an array S and a procedure reverse which reverses the order of elements in between positions I and j. What does the following sequence do? Where 1k less than equal to n, reverse. A rotates S left by k positions, leaves S unchanged. C reverses all elements of SD, none of the above. Solution. Effect of the above three reversals for any k is equivalent to left rotation of the array of n by k size. Problem -5. Finding anagrams in dictionary. You are given these two files, dictionary.txt and jumbles.txt. The jumbles.txt file contains a bunch of scrambled words. Your job is to print out those jumbled words, one word to a line. After each jumbled word, print a list of real dictionary words that could be formed by unscrambling the jumbled word. The dictionary words that you have to choose from are in the dictionary.txt file. Sample content of jumbles.txt. Step 1. Initialization. NWA, Weenanu Wayne. Sleep, sleepy. RPOIMS, semi-pro-imposer promise. Et niner, renitent. Ahikri, hierarchy. Dika, acid kade. Dobo, blood. Solution step by step. Open the dictionary.txt file and read the words into an array. Declare a hash table variable. Step 2. Process the dictionary for each dictionary word in the array. Do the following. We now have a hash table where each key is the sorted form of a dictionary word and the value associated to it is a string or array of dictionary words that sort to that same key. Remove the new line off the end of each word via chomp. Make a sorted copy of the word, that is, rearrange the individual chars in the string to be sorted alphabetically. Think of the sorted word as the key value, and think of the set of all dictionary words that sort to the exact same keyword as being the value of the key. Query the hash table to see if the sorted word is already one of the keys. If it is not already present, then insert the sorted word as key and the unsorted original of the word as the value. Else concat the unsorted word onto the value string already out there. Step 3. Process the jumbled word file. Read through the jumbled word file one word at a time. As you read each jumbled word, chomp it and make a sorted copy. Print the unsorted jumbled word. Query the hash table for the sorted copy. If found, print the associated value on same line as key and then a new line. Step 4. Celebrate. We are all done. Sample code in Perl, hashtag step 1 open, while at not underscore sorted split at sorted sort, $name join, if $jum equal to $chomp, at not sorted 1 split, at sorted 1 sort, $name join, if print, and $jum, no matches, else at value split, shashtik $name print, and $jum, at values. Problem 6 pathways given a matrix as shown below, calculate the number of ways for reaching destination B from A. Solution. Before finding the solution, we try to understand the problem with a simpler version. The smallest problem that we can consider is the number of possible routes in a 1 times 1 grid. 1. From the above figure it can be seen that. 2. From both the bottom left and the top right corners, there's only one possible route to the destination. From the top left corner, there are trivially 2 possible routes. Similarly, for 2 times and 3 times grids, we can fill the matrix as. From the above discussion, it is clear that to reach the bottom right corner from left top corner, the paths are overlapping. As unique paths could overlap at certain points, we could try to alter the previous algorithm as a way to avoid following the same path again. If we start filling 4 times and 5 times, we can easily figure out the solution based on our childhood mathematics concepts. Are you able to figure out the pattern? It is the same as Pascal's triangle, so to find the number of ways, we can simply scan through the table and keep counting them while we move from left to right and top to bottom. We can even solve this problem with mathematical equation of Pascal's triangle. Problem -7. Given a string that has a set of words and spaces, write a program to move the spaces to front of string. You need to traverse the array only once, and you need to adjust the string in place. Input equal to move these spaces to beginning, output equal to move these possessed to beginning. Solution. Maintain 2 indices y and j, traverse from end to beginning. If the current index contains char, swap chars in index 1 with index j. This will move all the spaces to beginning of the array. Void my swap, int I int t, char temp equal to a all, a equal to temp, void move spaces to begin, int I equal to strlen -1, int j equal to I for if my swap, void test code, char spar equal to move these spaces to beginning. Printf, move spaces to begin, printf. Time complexity, O, where n is the number of characters in the input array. Space complexity, O. Problem 8 for the problem 7, can we improve the complexity? Solution. We can avoid a swap operation with a simple counter. But it does not reduce the overall complexity. Void moves spaces to begin, int n equal to strlen -1, count equal to n, int I equal to n, for if equal to a, while a equal to, in t test code, char spar equal to, move these spaces to beginning, printf, move space to begin. But there's in input array. Space complexity, O. Problem -9. Given a string that has a set of words and spaces, write a program to move the spaces to end of string. You need to traverse the array only once, and you need to adjust the string in place. Input equal to move these spaces to end, output equal to move these spaces to end. Solution. Traverse the array from left to right. While traversing, maintain a counter for non-space elements in array. For every non-space character A, put the element at A and increment count. After complete traversal, all non-space elements have already been shifted to front end and count is set as index of first 0. Now, all we need to do is run a loop which fills all elements with spaces from count till end of the array. Void move space stoned, void test code, char spar equal to move these spaces to end, printf move space stoned, printf if a equal to a, while a equal to. Time complexity, O, where n is number of characters in input array. Space complexity, O. Problem -10 moving zeros to end, given an array of n integers, move all the zeros of a given array to the end of the array. For example, if the given array is, it should be changed to. The order of all other elements should be same. Solution. Maintain 2 variables I and j and initialize with 0 for each of the array element A. If a non-zero element, then replace the element A with element A. Variable I will always be incremented till n1, but we will increment j only when the element pointed by I is non-zero. Void move zeros to end, int size, int I, int size equal to size of move zeros to on for printf, return 0. Time complexity, O. Space complexity, O. Problem 11 for problem 10. Can we improve the complexity? Solution. Using simple swap technique, we can avoid the unnecessary second while loop from the above code. void myswap, int I, int j, int temp a equal to a equal to temp, void move 0 stolen, int len, int I, j 4, if, equal to 0 myswap. Time complexity O, space complexity O, problem minus 12, variant of problem 10 and problem 11, given an array containing negative and positive numbers, give an algorithm for separating positive and negative numbers in it. Also, maintain the relative order of positive and negative numbers. Input, minus 5, 3, 2, minus 1, 4, minus 8 output. 518,342. Thous. Equal to 0 with a less than 0. Problem minus 13 solution given a number, swap odd and even bits. In T-swap, int mask 0 is a, int mask equal to 0 times return, or problem minus 14 count the number of set bits in all numbers from 1 to n solution. We can use the technique of section February 21st, 2019 and iterate through all the numbers from 1 to n. Int counting number of phones into n, unsigned int n, return count. Problem 15 count the number of set bits in all numbers from 1 to n. Solution, we can use the technique of section February 21st, 2019 and iterate through all the numbers from 1 to n. Int, counting number of phones in ito n, int count equal to 0, I equal to 0, j, 4j, I, while j equal to j, and count plus plus, return count. Time complexity, O references. Akash, programming interviews, tech-queries.blogspot.com. 2. Alfred V. Aho, J.E., Data Structures and Algorithms, Addison Wesley, Algorithms, retrieved from cs.princeton.edu/ALGs. Anderson, S.E., Bit Twiddling Hacks, retrieved 2010 from Bit Twiddling Hacks Graphics, Stanford.edu, Bentley J. TNT, Bell Laboratories, retrieved from a TNT Bell Laboratories. 46. Bondalapati, K., Interview Question Bank, retrieved 2010 from Interview Question Bank, halcyon.usc.edu/kiran/msqs.html. Chen. Algorithms Hawaii.ed/chenks. Database. P. Problem Datastructures.net database. Retrieved 2010 from Problem Database, 2007, 299. Drozdek. A. Data Structures and Algorithms in C++. Ellis Horowitz. SS Fundamentals of Data Structures. Gilles Brassard. PB. Fundamentals of Algorithmics. Hunter. J. Introduction to Data Structures and Algorithms. Retrieved 2010 from Introduction to Data Structures and Algorithms, 13. James F. Korsch. LJ. Data Structures, Algorithms, and Program Style Using. C. John Mongan. NS. Programming Interviews Exposed. Wiley, India. 15. Judges. Comments on Problems and Solutions. ulm.de/acm/locals/2003/html/judge. HTML. http 90.informatic.uni. 99 klid. PNP and NP complete. Retrieved from PNP and NP complete. cs.princeton.edu/kazad. Knuth. D. Fundamental Algorithms, Volume 1 of the Art of Computer Programming. Addison Wesley. 18. Leon, JS Computer Algorithms. Retrieved 2010 from Computer Algorithms, math.uic.edu/Leon. Leon, JS Computer Algorithms, math.uic.edu/Leon/cs-MCS. OCF, Algorithms. Retrieved 2010 from Algorithms, ocf.berkeley.edu. Parlante, N, Binary Trees. Retrieved 2010, cslibrary.stanford.edu from cslibrary.stanford.edu. Patil, Fifth Fundamentals of Data Structures. Nirali Prakashan, 23, Poundstone, W. How would you move Mount Fuji? New York, Boston, Little Brown and Company. Prior, M-Tech Interview. Retrieved 2010 from Tech Interview, techinterview.org, questions, AC, a collection of technical interview questions. Retrieved 2010 from a collection of technical interview questions. Estes Gupta, CP Algorithms, cs.berkeley.edu/Vazirani. Sedgwick, R, Algorithms. Addison Wesley, 28, Cells, C, Interviewing at Microsoft. Retrieved 2010 from Interviewing at Microsoft. Sheen, CK. Linked lists merge sort implementation. Sinha, P Linux Journal. Retrieved 2010 from linuxjournal.com/article/6828. Structures, dd, cs.gordon.edu, www.math-cs.gordon.edu. Retrieved 2010 from www.math. T.H. Corman, CE. Introduction to Algorithms. Cambridge, the MIT Press. Sion Vikas, J. Pointers explained, nuclear.sdf-au.org, Warren, H. S. Hackers Delight. Addison Wesley, 35, Weiss, M.A. Data Structures and Algorithm Analysis in C. Sandrasi.
Hope you have loved this video. Yeah, it's ended now. The chapter is ended now. Let me activate myself. Hope you have enjoyed. I have completed the whole book today. Thank you so much for watching. Don't forget to subscribe my video, like this video. I will bring more books audio as well. Thank you so much.